In this video, model performances. But with respect to each and every data points, if you really need to focus. In this video, we are going to discuss about mean square error, mean absolute error, and root mean square error. Already in our previous video, we have seen about R square and adjusted R square. Now, you know that we use R square and adjusted R square to check how the model performance is. But with respect to each and every data points, if you really need to focus more on the error, we can definitely use mean square error, mean absolute error, and root mean square error. But again, I will be talking the advantages by using mean square error, mean absolute error, and root mean square error. Remember, advantages and disadvantages, both I'm going to cover. Remember, in the intuition that we have actually explained, right? So let's consider that I have a data set, and this particular data set is basically, let's say in the x-axis, I have years of experience, and in the y-axis, I basically have salary, right? Now, in this specific data set, let's say I have some of the data points over here, and let's say here I create my best fit line, right? And as you remember, in the linear regression, I've also intuitively explained you about a concept of gradient descent. And this gradient descent, the main aim is, and this was my cost function, theta 0, theta 1, and this was my theta 0 or coefficients in short. Our main aim was to basically come to this particular global minima. So this is basically my global minima, and I have to come over here, right? And how I have to come, I have to continuously change this theta value, find out the derivative, and try to come over here, right? Now, let's go ahead and see that if I have this specific use case over here, you know that, let's say this is my data set, experience and salary, right? I will obviously be having some values right now over here. Now, this salary is nothing but my y variable, that is my truth variable, which is denoted by this white color. And this best fit line, which is basically created, this will actually help us to find out the predicted data points, right? So here, with respect to this particular data point, this is my predicted data point. With respect to this is my predicted data point. This is my predicted data point, and this is my predicted data point. So what we do, we basically calculate the error like this. And our main aim is to reduce the specific error. And in order to reduce the specific error, we use different cost functions. The first cost function that we use is basically called as mean squared error. Now let me go ahead and write this formula. Mean squared error is nothing but summation of I is equal to 1 to n y minus y hat. Y hat is the predicted output whole square divided by n, right? N is the total number of data points. And this is the same cost function that we used to basically create this gradient descent. Now what is so important about this cost function? And our main aim is to reduce this cost function because this is specifically talking about the error, and our best fit line should be created in such a way that our cost function should keep on reducing. Okay, so we can also use this as a parameter to check how our model is basically performing. Okay, now in mean squared error, here we are just trying to calculate the error, right? So y minus y hat. So we are going to add up this particular error. Let's say I'm mentioning it as e1, e2, e3, e4, right? I'll add up all this particular error. Now let's talk about the advantages of using MSE and disadvantages of using MSE. Now, first of all, from our previous intuition, we have already seen that this y minus y hat whole square, it is basically a quadratic equation. So if you don't know what is a quadratic equation, I would suggest just open a browser. Let me just show you a quadratic equation, how it looks like. So let's say over here, I'm just writing it out. Plot quadratic equation. Okay. So when I plot this quadratic equation, if I probably go and see the images, here you'll be able to see we will be getting this kind of image, right? And if you're getting this kind of image, you obviously know that this is basically a gradient descent. That basically means we will be able to reach our global minima with the help of this quadratic equation. Now, why I say this as a quadratic equation? Because understand, this is in the format of ax plus by plus c, right? Because if I take this and if I write a minus b whole square, it is nothing but a square minus 2ab plus b square, right? So here it is basically a quadratic equation. And whenever you have a quadratic equation and if you plot this quadratic equation, in short, you will be getting a gradient descent. And remember, one important point in gradient descent that you will be having a global minima. And our aim is basically to come to this global minima or near to this global minima because here the error will be less, right? So this is the major advantage. So let me go ahead and write the advantages of using mean squared error. So first advantage is that if I probably write this as advantage, let's go ahead. So advantage and disadvantage. The first and the foremost advantage is that, and whenever we have this kind of gradient descent, one thing you need to know that it is differentiable at all point. And we also saw this, right? It is differentiable at all point. So first advantage is that it is differentiable. Why it is differentiable? Because it forms this kind of gradient descent curve. So at every point we will be able to calculate the slope, and based on that we can reduce the coefficient and probably reach the global minima. So most and major advantage is that it is differentiable. Coming to the next advantage is that over here, this kind of curve, it has one local and one global minima. This is a super important point which everybody needs to focus on, right? Let's say this particular gradient descent that I see is basically a convex function. Okay. If you see some of the curves, let's say that I have one curve like this, and this gradient descent curve looks something like this. Okay. Now over here, you can see that this is not a convex function. Obviously, here you have one global minima, and you'll also be seeing that you'll be having some more minimas, and this minima is basically called as local minima. If we use different types of equation, in those equations you'll be seeing that you'll be able to get, or if you plot these equations, there'll be chances that you'll be getting both global minima and local minima. But since you're using this quadratic equation, you're plotting it, you will just be having one local or one global minima, right? Not multiple. Because what will happen if you have some local minima, then your convergence will get stuck over here, right? Your convergence will get stuck over here. Because why? Here the slope is actually equal to 0. This is a super important point to understand what is the differences between local minima and global minima. Okay, if you have a local minima, that basically means your convergence. Let's say your convergence is happening like this, it will go ahead and it will stop over here because here your slope is 0, right? But in the real, you really need to reach to the global minima, right? So if you use any different kind of equation, specifically not quadratic equation, there are also some equations which is basically called as non-convex equations or non-convex functions. In this particular case, you will be seeing that they will be having both local minima and global minima. But currently we are using this quadratic equation, that is y minus y hat whole square. In this particular case, since it is differentiable, it will just be having one local minima or one global minima. Now coming to the third point, which is super important, this equation or this curve, let's say if I use this particular equation, it converges faster, right? And we have already seen how the convergence will basically happen, right? So these are the three main advantages with respect to by using this mean squared error, right? Now coming to the disadvantage, which is super important again, okay? Now in disadvantage, you'll be seeing that the first and the foremost disadvantage of using this is that this equation is not robust. It is not robust to outliers. Now why I'm saying like this, it is not robust to outliers. Let's say I have an outlier like this, right? Now what will happen if I am an outlier? Obviously here, the error that you're trying to compute, later on you'll be squaring it, right? Because y minus y hat whole square, right? So here you're penalizing this process is basically called as penalizing the outlier. Penalizing the outlier. Now, because of this, what will happen? Error will increase. Now, let's consider that I have some data points which looks like this. Initially, my data points was like this, let's say. So based on this, I created a best fit line. But later on, let's say that I included a new data point, which is a kind of outlier like this. Now, what will happen? This line, right? As soon as it sees an outlier, obviously it will go and compute the error. Now, because of this particular error, obviously this error will lead to the increase in the MSE, right? The MSE will get increased. Now, when MSE is getting increased, we really need to optimize this MSE. Then what will happen is that because of this error, this line will move towards that particular outlier like this. But this is absolutely wrong, right? Because most of the data points are over here. And because of this outlier, you can see that there's a huge shift of the best fit line from here to there, right? So this is what is an impact of an outlier. So this is not robust. There is definitely, because of the outlier, the line is moving from here to there by a huge difference, right? Because obviously we need to reduce the MSE. But currently the MSE is increasing in this particular case, right? So we definitely say that it is not robust to outliers, okay? So this is the major disadvantage with respect to using MSE. Now coming to the next point with respect to MSE, okay? Here, when I try to find out the difference between y of I and y hat whole square, you'll be able to see that whatever MSE that I get, right? This is basically 1 by n summation, or let me just use this particular equation again. You know that what is MSE? MSE is nothing but 1 by n summation of I is equal to 1 to n y of I minus y of I hat whole square, right? So this is the equation over here, right? Now in this specific equation, what is happening is that you're trying to find out the differences between the truth and the predicted value, right? Over here, just focus on this one, okay? Here, you'll be able to see that y of I minus y of hat whole square, when you're doing whole square, just focus on the units. Let's say my y of I, which is the salary variable, okay? Let's say my x-axis is basically experience, y-axis is salary. And if I do y of I minus y of I hat whole square, the salary will be in some units. Let's say this is in units like lakhs. Now, right now, y of I is basically in lakhs. But if I do y of I minus y of I hat whole square, that basically I'm changing the units. Now, this is basically becoming lakhs whole square. So at the end of the day, what is happening with respect to MSE is that the y of I and y of I hat, whenever we are trying to compute the MSE, the units is changing when compared to the output variable. So this is also a major disadvantage. So it is no longer in the same unit. Now, why I'm putting up this point? Because it basically becomes very difficult in terms of understanding that specific information. Because let's say if my error is coming as, let's say it is coming as 2.5 lakhs. Right? Or whatever error that I'm getting with respect to y of I minus y of I hat whole square is, let's say that it is 2.5. Now here, you know that this particular units that it is specified, it is with lakhs square. So it becomes difficult in understanding when you're comparing it with the truth value. Okay. So this is a major advantage, major disadvantage. So again, let me revise with respect to advantage and disadvantage. First, the advantage is that obviously whenever you use MSE, it is going to create this kind of curve because y minus y hat whole square is nothing but it is a quadratic equation. And whenever you have a quadratic equation, at the end of the day, you're going to get this kind of curve. So the major advantage with respect to this curve, which is called as gradient descent curve, it is first of all differentiable, which I have specified. It has one local and one global minima. It does not have multiple local or more than one global minima, like this kind of situation. So obviously we know that where we really need to reach, that is over here, and when we reach near this, the error will be less. The third thing is that it converges faster because we don't have any local minima over here. The disadvantage is that it is not robust to outliers, and it is not longer in the same unit. That basically means it is not in the same unit. Okay, I'm just going to mention this again. It is not in the same unit. Okay, so this is about MSE. Now let's go ahead and discuss about mean squared error. Mean absolute error. So here I discussed about MSE. The second one that I'm going to discuss is about mean absolute error. Now, mean absolute error, what happens if we take this cost function or loss function when we are creating our gradient descent, right? So mean absolute error is basically given by the formula 1 by n summation of I is equal to 1 to n, and this is y minus y hat not whole square. It will be the absolute value of y minus y hat. Now here, let's talk about the advantages and disadvantages. First of all, let's go ahead towards the advantage, and let's go towards the disadvantage. Now I think just by seeing the equation, you'll be able to understand the advantage. First of all, this will definitely be robust to outliers. Now why it is robust to outliers? Because let's consider these are my data points, and let's say I have some of the data points like this, and let's say I have created a best fit line. Let's say again, while training my data points, I get an outlier, which is over here. Now, what will happen is that since my formula is not squaring or not penalizing this specific error, you know that MAE will get increased, but it will not get increased like how MSE used to get increased, right? Error, we are trying to square it over there. But here, the error, what it is coming, will just increase MAE by some amount, okay? So because of this, what will happen, my best fit line will not divert that much, but it will just divert in a simpler way like this, okay? So this movement is just this much. Whereas in the case of MSE, you could see there's a huge movement in the best fit line, okay? And obviously, we need to reduce this MSE also. That is also the major thing, okay? The second advantage is that when I'm trying to calculate y minus y hat, it will be in the same unit, right? It will be in the same unit. So, same unit. So understanding the data over here will be simpler because your y hat and y minus y hat will be in the same units. That is like lakhs. If I compare with respect to salary, it is not becoming lakh square, right? So this is the second advantage, and obviously because of this only, this thing is getting there, right? But coming to the disadvantage, which is super important point, okay? Obviously, mean absolute error is used to, basically because of the outlier that is present in mean squared error, because of the impact of the outlier that is present in the mean squared error, we're trying to solve it with the help of mean absolute error. But here, if I talk about differentiability, right? In the case of mean absolute error, if I use this equation, usually what happens, I will get this kind of curve. Now, this curve, you'll be thinking, it looks like gradient descent. No. Understand this, here you're passing through 0. Here at this point, we cannot differentiate any value at 0. We cannot differentiate any value at 0, right? So what we do is that we create something called as subgradients. Okay, subgradients. Now subgradient basically means what? I'll be taking a part of this, and then probably finding out the slope and then trying to compute and trying to come to a global minimum point. Okay, so this is a major disadvantage with respect to this. The major disadvantage is that convergence usually take more time. Usually takes more time. Take more time because why the convergence will take more time? Because understand the optimization. The optimization is a complex task. Now, what is optimization over here? That we really need to come to a global minima. But right now, here you basically have this kind of gradient descent, and you know that at this point of time, if you probably go at this particular point, that basically means it is not at all differentiable at 0, and that is what derivative will not happen at the point of 0, right? You cannot differentiate anything that is at 0. Okay. So what you do is that you try to divide that into subgradient, and then you try to calculate the slope. Okay. Then only you'll be able to calculate the slope. Now, optimization is a complex task over here. Definitely, optimization is not that specific easy. But one very important thing that you'll be able to see that in this, it is definitely robust to outliers, right? This is the major task. Now here, it will definitely be time consuming. Okay. So these are some of the advantages and disadvantages with respect to ME, that is mean absolute error. Now let's go ahead with respect to third one, which is called as error. So here I'm just going to write it as root mean squared error. Now here we can definitely write RMSE as root of MSE. So if I say root of MSE, what it is nothing but root of 1 by n, summation of I is equal to 1 to n, y of I minus y of I hat whole square. Okay, so this is the entire formula with respect to RMSE. Again, in this, what will be the benefit? One benefit that I can definitely compare, since I'm doing the square root, right? So initially in MSE, it was not in the same unit, right? So first advantage that I would like to call about is that first advantage here, the values that you're getting is in the same unit. Second thing, this is obviously differentiable. Okay, since here also you'll be anyhow getting a gradient descent. But the major disadvantage if I like to talk about is that since we are again doing squaring here, it is not robust to outliers. Okay, not robust to outliers. Now, you have learned about this all three techniques. At the end of the day, you may be considering, which one should we use? Should we use MAE, MSE, or RMSE? My answer will be that, guys, as a starter, we should try to look on all three of them, right? RMSE, all three of them. So whenever you'll also be seeing that in further, whenever I try to create a linear regression model, I will also be showing you the errors that is going to come, because see, once we probably create a best fit line, obviously, let's say there are some data points. First of all, I will try to create a best fit line. Then what I'll do, I will try to calculate the MSE, the mean squared error, the mean absolute error, and RMSE. And after this, I will also try to check the performance of this model with the help of R square and adjusted R square. So as a starter, you should try to focus on all these things and try to see the performance metrics that you're able to get. But all this in combined totally will basically become my performance metrics that I'm specifically going to use. Okay. Similarly, in classification problem, you have different performance metrics, but as mentioned over here, you have to focus on all the metrics like performance, mean squared error, mean absolute error, RMSE, R square, and adjusted R square. But if someone asks you in an interview question, why should you use MSE when compared to MAE, then you know that you have to tell the answer that it is very differentiable because the curve that you're going to get because of this quadratic equation, it has one local and one global minima, it converges faster. Suppose if they say that what about MAE, then you should say that MAE most advantage thing is that it is robust to outliers, right? And the convergence usually take more time. This is the disadvantage, right? And then why should we use RMSE? So this is the specific question. So the question that may come is that when should you use MSE versus when should you use MAE versus when should you use RMSE? And the other question is that when should you use R square versus adjusted R square? So these are the two important questions that may come up in the interview, right? So I hope you have understood all the performance metrics till now. In this video, we have covered MSE, MAE, R, and MSE. So yes, I will see you all in the next video.
In this video, we are going to understand about some of the terminologies that are basically used when you are training your model practically, right, with the help of Python and scalar, which we are going to use probably after a couple of sessions. There you'll be seeing this kind of words like training data set, what is test data set, what is validation data set, when do you say when your model is overfitting or underfitting, and with respect to that, what is bias and variance. So in this video, I'm going to cover all the specific topics. Okay, let's consider I have a data set. Okay, let's say that I basically am starting my training. So what I'm going to do is that I will probably have my data set, right? Let's say in this particular data set, I have somewhere around 1,000 data points. Okay. 1,000 data points, irrespective of how many number of features are there, right? And initially, let's say this is my entire data set that I have, and I really need to train some model in this, okay? Train some model, and this model will be able to predict something. Let's say this is house pricing data set, so I will be having features like size of house, okay? Size of house, number of bedrooms, okay? And one more feature will be price of the house. Let's say I have this many data points, 1,000 data points with respect to our data, right? Now, this specific data points, initially, whenever you start training your model, the first thing that you really need to do is that try to split this data into two important parts. One is the training data set, one is the something called as training data set, and the other one is something called as test data set. Okay, so what we do over here is that we are trying to split this entire data points between two parts. One is training data set and one is test data set. And let's say that I've taken some ratio like 70 to 30% ratio, 70% to 30% ratio. That basically means my 700 records are over here and my 300 records are over here. Now, why we are specifically doing this specific step? Why we are dividing our data into the training data set and test data set. And from this also we will be able to understand whether our model is overfitting or not. Okay, so this training data set, I will probably use this data for my model to train. Okay, and this test data set, what I will be doing, I'll be using this to test my model. Okay, so for testing the model, I will use this specific data. And this data, once I do the splitting, I'm never going to show this data to my model. Okay, while training, my model will never know about this specific data points. Okay, now let's take up this training data set. And what is the next step that we do? In our training data set, we do further splitting of this. What kind of splitting we do? We basically divide this into again two parts. Okay, the first part is something called as train, and the second part is something called as validation. Now there is a minute difference between train and validation. Okay, train part is basically used to train the model. Okay, train the model, and in the future, whatever practical session we'll be doing, we'll be following the same steps, so that this will give you an idea that how we can identify whether our model is overfitted or not. Similarly, with respect to the validation, why do we use this validation data? We use this for hyperparameter tuning our model. Okay, hyperparameter tuning your model. So if I really want to tune my model, I will basically be using this validation data set. So in short, I will combine train and validation data in order to make our model performance better. Now, when do we face overfitting? When do we face underfitting? That I'm trying to discuss over here. Okay, now let me go away and let me give some of the scenarios. Obviously, you have seen that I have my train data and my test data. Let's say my model gives very good accuracy to the training data. Okay, let's say this is my model that I'm trying to create. It gives a very good accuracy with respect to the training data and very good accuracy with respect to the test data. Because later on, when we take this test data and predict it, we can basically compare whether it is giving us very good accuracy or not. And this is the model that I specifically want. And this model is basically called a generalized model because it is working well with both train and test data. So this is the generalized model that I specifically want. But let's say that I have a scenario wherein with respect to the training data, I get a very good accuracy. But with respect to the test data, the new test data, I get a bad accuracy over here. Let's say that the very good accuracy I get somewhere around 90%. But in case of bad accuracy, let's say I'm getting somewhere around 50%. Now in this particular scenario, since our model is giving a very good accuracy on the trained data and bad accuracy with respect to the new on the test data, we say this condition as our model is overfitting. Our model is overfitting. So when do we say our model is overfitting? When my model has been trained well with the training data set, but with respect to the new data points, it is not able to predict. So because of that, I'm getting a bad accuracy. Okay. So this is a scenario of model is overfitting. Now, whenever I get a good accuracy, we basically say or use a term which is called as low bias. Okay. And since I get a bad accuracy with respect to my test data, I usually use this term which is called as high variance. Okay. high variance. So this is one terminology that we specifically use. Now, let's consider one more scenario. Okay. Now in this scenario, let's say with respect to my training data and with respect to my test data. Okay. Let's say here my model accuracy is low. With respect to the training data, my model accuracy is low. And obviously, if my training accuracy is also low, then this model accuracy for the test data will also be low. Right? Now, in this scenario, this particular problem statement, I can definitely say my model is overfitting. Sorry, my model is underfitting. Underfitting. So in this basically, we are just trying to convey that my model is not even trained well with the training data. So if it is not well trained with the training data, obviously it is not going to perform with respect to the test data. So this scenario, we say that my model is underfitting. So in this scenario, I basically use this as high bias and high variance. Okay. We usually use this notation. Okay. And come to the first situation where I get very good accuracy with respect to the training data and very good accuracy with respect to the test data. I usually say this as with a simple name, low bias and low variance. And always our aim should be that we should try to always find out this specific generalized model where my training and test accuracy should be good. Let's say if I get my training accuracy as 90% and if I get my test accuracy as 85%, then I can definitely say that, okay, I'm getting almost similar kind of accuracy with respect to my training and test data itself, right? So this is the basic difference between overfitting and underfitting. And this entire thing, when I'm using bias and variance, here I'm specifically saying that, okay, this is also generally called as bias variance trade-off. Okay. Now, if I talk with respect to regression, right? If I try to just draw these points, okay, let's say this is my this all points that you probably see are my training data points. Okay. Now, if I try to find out a best fit line, okay, now with respect to this particular best fit line, let's say my new test data is somewhere here. Then obviously you can see that I will be getting almost similar accuracy. So this best fit line will serve or will provide you this specific condition. It will provide you a kind of generalized model. Okay, so this best fit line that I've actually found, this will basically be giving me good accuracy for the training data also and for the test data also. So this is the generalized model that I specifically want. But if I have some other scenario wherein, let's say this is my model, okay, and let's say I have the new test data which looks something like this. Let's say over here, and suppose I probably try to create a best fit line. So this is my best fit line, and let's say my new data points is somewhere here. Right? So in this particular case, I know that, see, with respect to this, obviously for the training data set, the accuracy will be high because it has properly fitted this specific model, right? But with respect to the test data, it is not being able to provide a good solution because obviously the error is very, very high with respect to the test data. Now in this particular case, this will actually lead to overfitting. Okay. So one assignment that I really want to give you is that just try to find out how underfitting it will be, right? Obviously for the train and the test, the error will be quite high. So whenever I have a generalized model, I can definitely say this as low bias and low variance. And with respect to the overfitting, I can definitely say this is low bias and high variance. Okay. So this is the scenario with respect to overfitting and generalized model. And obviously, you can guess about the underfitting part. So this specific thing you really need to understand because as we go ahead, all the practical part will be implemented in this specific way. And we'll try to use the R square and adjusted R square in order to find out whether it is overfitting or underfitting. So yes, I hope you liked it. We'll continue the practical part in the next session. Thank you.
Hello guys, in this video we are going to see how we can implement linear regression using OLS, that is ordinary least square. Okay. Now in our previous video we have already seen how to implement linear regression using gradient descent, but now let's go ahead and try to see with the help of OLS. Now the major aim is that, guys, over here you knew that like in a gradient descent, right? Whenever I have some kind of data points, my main aim using linear regression using gradient descent is that I need to find out this best fit line. And finding out this best fit line was done using an optimized algorithm, right? Some optimization was actually done, right? And this optimization usually happened with the help of loss function we have basically used. And for that, if you remember, we use something called as a gradient descent, right? And at every point, we try to calculate the derivative. And based on that, we try to come near to the global minimum. So this particular point was something like global minimum. Now, what does OLS technique basically say? OLS technique basically say that suppose if I have a specific data points, can I apply some formula and calculate my beta 0, that is my intercept, and my coefficient, that is beta 1. So that is what ordinary least square basically tells us. Okay. Now we will try to see with the help of some formula how we can basically calculate beta 0 and beta 1. But before I go ahead and directly tell you the formula, first of all, we'll try to understand or we'll try to derive this formula also by understanding the aim of OLS. Again, as usual, the aim of ordinary least square is that we should try to reduce this error, right? We should try to reduce this error that is between the predicted and the truth point, right? So this is basically the error with respect to any best fit line that we create, right? So here, what you can do is that, again, let's say that if I have another line, if I have some line like this, so for this, the intercept will be different, the coefficient will be different. For this, the intercept will be different, the coefficient will be different. But we should try to select that line which gives us a less error. So now let's go ahead and let's try to derive the formula for OLS. And again, guys, OLS, here I'm just going to give a notation. Let's say this is my ordinary least square. Okay. You know what is the aim of ordinary least square? I'm going to give you a notation with S. Let's say this is beta 0 and beta 1. Let's consider that this best fit line is given by h theta of x is equal to beta 0 plus beta 1 into x1. I'm just considering this as a simple linear regression. And as said, in the ordinary least square, I'm not going to use any loss function like mean square error, but I'm just trying to say that, okay, I have a scenario wherein I need to reduce my difference between y of I and h theta of x. What is h theta of x? H theta of x is nothing but beta 0 plus beta 1 multiplied by x1. And this is nothing but my predicted value y hat. So I'm just going to use this particular equation like this and probably write over here. This minus will get subtracted to this. Okay. So it will come minus beta 0 plus, and it will be minus beta 1 into x1. And this should be whole square. So here what I'm doing is that I'm just trying to reduce the error. Okay. My aim is that this difference that I'm actually getting, this is basically the error. Okay. And I'm just going to reduce this specific error. And obviously this basically looks like a mean squared error formula itself, right? So OLS by default, I think it uses mean squared error. Okay. And if I try to find out the average, it will be divided by n. Okay. So 1 by n multiplied by this. So here let me write it by white pen only, otherwise you'll get confused. So this will be 1 by n y of I minus beta 0 plus beta 1 into x1. Now in ordinary least square, the aim is we need to calculate beta 0 and beta 1. And obviously we'll try to derive the formula through which beta 0 and beta 1 can be calculated. So before I go ahead and talk about this, in gradient descent also we try to find out derivative, right, with respect to every coefficient, and we try to come to the global minimum. Okay. Now what we are trying to do is that we are trying to find out what should be the formula of beta 0 and beta 1. In order to find it, first of all, what I'll do is that I will try to calculate the derivative. So derivative of ds of d beta 0, and let's say beta 0 comma beta 1 is over here. Here I can specifically write this as, okay. Now if I try to find out the derivative of this value, what will happen? See, guys, if I have an x square value, and if I have y is equal to x square, and if I write derivative of y with respect to derivative of x, then this what will happen? It will say 2x 2 minus 1 multiplied by x, right? Sorry, multiplied by derivative of x, right? This is what exactly happens, right? And then finally I get 2x because derivative of x with respect to x is 1, right? So if I have equation y is equal to x square, and if I try to find out the derivative of y with respect to x, I'm going to get 2x. Now similarly over here, you'll be able to see that if I try to find out the derivative, what will happen? This will be 2 by n, okay? Summation of 1 to n, and then I will write this entire equation, y of I minus beta 0 minus beta 1 x1. Now here it will be 2 minus 1, right? 2 minus 1, so I'm not going to write 1 separately over here. And in the next one, I'm just going to find out the derivative of this entire value, right, with respect to beta 0. This becomes a constant, so obviously this will be 0. Minus beta 0 is there, then this will become minus 1. Sorry, 1, because derivative of beta 0 with respect to beta 0 is 1. And then here you can see that this will again be a constant, so I'm going to write minus 0. So at all, if I try to find out derivative of s with respect to derivative of beta 0, with respect to beta 0 comma beta 1, I'm going to get 2 by n minus 2 by n, summation of I is equal to 1 to n, y of I minus beta 0 minus beta 1 x1. Right? This is what I'm actually going to get. So this, I'll be assigning it to 0. So this will become my first equation, let's say. Okay? This will become my first equation because I need to derive beta 0 and beta 1. Similarly, if I write derivative of s with respect to derivative of beta 1 with beta 0 comma beta 1, here, the equation that I'm actually going to use again, what I'm going to do, I'm going to find out the derivative with respect to beta 1, right? Then again it will be what? 2 by n, okay? And this will be summation of I is equal to 1 to n. And here I will write y of I minus beta 0 minus beta 1 x1. Now this entire thing I have to find out the derivative. Now this will become a constant, this will become a constant. And finally I'll be getting minus beta 1. Sorry. Minus x1, right? Why x1? Because derivative of this value with respect to beta 1, this beta 1 will become 1 and x1 will get remained, right? So now I will assign this to 0. So this will basically become my second equation, okay? And this equation again, I can basically write it over here because I'm just trying to prove you what is the formula, okay? I is equal to 1 to n, beta 0, beta 1 x1 multiplied by x1, which is equal to 0, okay? So this is my entire equation and this becomes my second equation. Now with the help of this two equation, what I'm actually going to do, I'm going to basically simplify this equation and try to find out what is beta 0 and beta 1 and we'll try to calculate. Now let's go ahead and take the equation 1, okay? Now equation 1 is what? 2 by n, right? Or minus 2 by n, summation of I is equal to 1 to n, y of I minus beta 0 minus beta 1 x1, right? So here I'm going to take minus 2 by n, summation of I is equal to 1 to n. This is y of I minus beta 0 minus beta 1 into x of I is equal to 0, okay? Now let's consider this 2. I'm just taking this equation. This is my equation 1 and we'll try to calculate what beta 0 beta 1 will be, okay? Now in this equation, when I take this 2 below and if I put it to the denominator, this will be 0 by 2, then obviously I'm going to get 0. And if I take it up, it is obviously going to be 0. So here in this equation, I can also write something like this. I will now write summation of I is equal to 1 to n, and this will be minus over here. Y of I minus beta 0 minus beta 1 x of I, which will be equal to 0. Now let's go ahead and multiply the summation of I is equal to 1 to n along with y of I, right? So now here you'll be able to see I will be getting minus summation of I is equal to 1 to n, y of I. This will be plus, since I don't have any variable that is ranging between 1 to n, so here I can directly multiply n multiplied by beta 0 minus, and again this minus into minus will be plus, and here you know that I can write beta 1 summation of I is equal to 1 to n, x of I is equal to 0, okay? So this is what we have actually done over here. Now all I have to do is that I can basically consider n multiplied by beta 0 plus beta 1 multiplied by summation of I is equal to 1 to n, x of I is equal to, I'll move this entire equation over here. So this will become summation of I is equal to 1 to n, y of I, okay? Now again, my aim is basically to calculate beta 0. Let's say from this, I'll be writing beta 0 is equal to, now here you have summation of I is equal to 1 to n, y of I, minus if I take this value over here, that will be beta 1, summation of I is equal to 1 to n, x of I, okay? And here you already know that I have n. Now n, what I'm actually going to do over here, I'm going to move it in the below denominator. So let's say this is also divided by n and this is also divided by n, okay? So finally, I can prove that my beta 0 is nothing but, if what is happening over here, see, this is nothing but this is the summation of y of I divided by n. So this, can I say this is the average? So definitely I can write this as y of y hat, right? So this becomes an average. And similarly over here, x of I, summation of I is equal to 1 to n, x of I divided by n, this is nothing but beta 1 multiplied by x bar. So beta 0 in this entire equation can be calculated by using this particular equation, right? So my intercept, if I really want to calculate my intercept can be calculated by using this formula, okay? So just imagine we have taken the first equation from here after doing the derivative and we have computed how to calculate beta 0. Now let's take the second equation and let's do the same thing, right? Now in the second equation, you know that it is minus 2 by n. So here what I'm going to do, let's consider equation 2. Let's consider equation 2. Now since we have got beta 0 here, obviously now it will become easy to get the beta 1, right? And beta 0 is nothing but it is the intercept. Now equation 2, I'm just going to write minus 2 by n. So let's go ahead and write over here minus 2 by n. And here I'm just going to write it down from my notes. I is equal to 1 to n. Y of I minus beta 0 minus beta 1 x of I multiplied by x of I, right, is equal to 0, right? So this is the equation that I actually have. Now this 2 will go to the denominator, n will go to the numerator, so everything will become 0. So now I can write this equation as, again, same thing. Here I'm just going to write summation of I is equal to 1 to n. Y of I minus beta 0, beta 1 x of I multiplied by x of I, which is equal to 0, okay? And the next thing that we are probably going to do over here is that let's multiply x of I and summation of I is equal to 1 to n inside this, okay? So after we multiply this, here you'll be able to see I'll be getting summation of I is equal to 1 to n, x of I multiplied by y of I, so this will be xi yi, and then I will get minus beta 0, summation of I is equal to 1 to n, and this x of I will get multiplied over here, and minus, here you'll be seeing I'll be getting beta 1, summation of I is equal to 1 to n, and this will be x of I whole square, right? So this is the equation that will happen after doing all these things. Now one common thing that you see is summation of I is equal to 1 to n. So what I can do, I can take it as summation of I is equal to 1 to n, then this will become x of I y of I, and this will be beta 0 of x of I, and this will be beta 1 into x of I whole square, right? And this will be, let me write like this, beta 1 x of I whole square, and this will be basically equal to 0, right? Now you know that beta 0 value you already know. It is y hat minus beta 1 into x bar. So what I'm going to do, I'm going to replace beta 0 with y hat minus beta 1 into x. So if I replace this into this beta 1 into x bar, right, then what will now happen? Now let me go ahead and write in different color. So this will be summation of I is equal to 1 to n, x of I y of I minus beta 0 is nothing but y hat minus beta 1 into x bar, and then you have x of I minus beta 1 x1 x of I whole square, and this is basically equal to 0. So guys, now once we replace beta 0 by y bar minus beta 1 into x bar, here you'll be able to see this. Now in the next step, what I will do, I will just write summation of I is equal to 1 to n, and I will be multiplying x of I inside this, okay? So this will be x of I y of I minus x of I y bar, then this minus into minus will be plus, then here I can write beta 1 x bar x of I minus beta 1 x of I whole square. Now you'll be knowing why we are doing all these things, because at the end of the day we'll be getting an equation to find out beta 1. Okay. Now the next step after this, what we basically do is that here in all this equation, the most common thing that you'll be finding is x of I. So let me remove x of I outside. So here we'll basically have y of I minus y bar plus beta 1 into x bar minus beta 1 into x of I, and this x of I will come outside. Okay. Now what we do, we can remove this x of I by just putting this in the denominator. So obviously this will be entirely 0 only this side, and this x of I can also be lost. Now the next thing that we are going to do, I will write summation of I is equal to 1 to n, and here I will write y of I minus y bar. Okay. So this is my first equation, and then I will also say beta 1, and what I'll do here, I'll write x bar minus x of I is equal to 0. Okay. Finally. Now the next step that we are going to do, and obviously I can also take this as a separate group, y of I minus y bar together, right? We can also take this like this together, right? Because understand, I'm just grouping this and I'm taking a common of beta 1, and I'm basically writing beta 1 x bar minus x. Now what I'm going to do here, I'll write beta 1. Let's say that this is there outside in my complete bracket. Now if I try to multiply the summation of I1, then it will be summation of I is equal to 1 y of I minus y bar, okay, plus summation of I is equal to 1 to n beta 1 x bar minus x of I. Okay, so this is what I'm actually going to get with respect to 0. Okay, so I've just made it into two groups. Okay, now after this I can definitely write something like this: summation of I is equal to 1 to n beta 1 x bar minus x of I, and here I'm just going to take this as minus, and this will be summation of I is equal to 1 to n y of I minus y bar. I'm just taking this particular equation at this side. Then finally I will be getting beta 1, which will nothing be, it will be minus summation of I is equal to 1 to n, okay, y of I minus y bar, okay, y of I minus y bar divided by summation of I is equal to 1 to n, and this will be x bar minus x of I. Now see over here, if I try to bring this x of I forward, then I have to probably take a negative value. So here finally you'll be seeing that beta 1 I can write it as minus I is equal to 1 to n y of I minus y bar, and if I take a minus value outside, then I can also write this as I is equal to 1 to n and x of I minus x bar, right? This minus and minus will get cancelled, and finally my equation of beta 1 will be summation of I is equal to 1 to n y of I minus y hat divided by summation of I is equal to 1 to n x of I minus x bar, right? So this is my entire equation of calculating beta 1, and if you remember, beta 1 is nothing but it is the intercept. So sorry, it is the coefficient. So finally I've actually proved you that with the help of OLS, if you really want to calculate the beta 0, then your formula is basically given over here, which I've actually proved it: y hat minus beta 1 into x bar. So here you'll be seeing y hat minus beta 1, I think beta 1, right? Or let me write it, beta 1 into x bar, right? X bar. This equation is basically to calculate the intercept. This equation is basically to calculate the intercept. And in order to calculate the coefficient, we use this specific equation, that is y of I minus y bar divided by x of I minus x bar. So let's say I have some data points x comma y, and here you'll be having some values. Okay. From this, obviously you'll be able to calculate x bar and y bar, and all you have to do in order to calculate beta 0, you just have to equate this particular equation, y bar minus beta 1 into x. First of all, if you really want to calculate beta 1, first of all, you go ahead and calculate beta 1 over here, and beta 1 you know y of I, y hat, so you'll go and compute this component, you'll go and compute this component, and you'll divide this both, you'll get beta 1. Once you get beta 1, you can equate this over here, right? So first thing, let's see over here, you'll calculate y of I minus y bar, right? With respect to every point, whatever y bar is there, you'll get all these values, right? And then you'll calculate xi minus x bar. Here you'll be getting all the values. Then you divide in both of them. Once you divide in both of them, you'll basically be getting beta 1. And after that, you can equate in this particular equation, beta is equal to y hat minus beta 1 into x bar. Then you'll be able to get your intercept. So this is basically your coefficient, and this is basically your intercept. Now this is with respect to simple linear regression. In multiple linear regression, again this equation will change, but at the end of the day, here you'll be having more other components. Okay, but just to give you an idea like how ordinary least square is basically calculating, here I have derived you some kind of formulas. Okay, so I hope you have understood this. And in the upcoming videos, we'll try to do both practical implementation using linear regression using a scalar and the OLS method, and we'll try to compare the results. If you compare the results, the OLS method will approximately be giving the same value when compared to a normal linear regression using a scalar. Okay, this is for sure. So I will show you an example as we go ahead by doing some practical implementation. So yes, I will see you all in the next video. Hello guys, so I'm quite excited that after so much of theoretical intuition, understanding both linear regression using gradient descent and linear regression using OLS, now we are going to implement it practically. And this is what we are going to do. We are going to cover both scalar implementation and OLS implementation in this specific video. We will start with a simple project, and for this particular project, we're just going to take a data set which has two features. One is weight and height. And here you can see based on some weight, there is some different heights, right? And this is my entire data. And I've just taken 24 records. In short, I've just created this data set by my own. And what we are going to do is that on top of this particular data set, we'll try to apply a simple linear regression, right? And why do I say simple linear regression? Because I just have one independent feature and one dependent feature. So here weight is basically my independent feature. And since I need to predict height, this is my dependent feature. Now what I'm actually going to do over here is that I'm going to take up this specific data set and we will try to implement it with using scalar. So let's go ahead without wasting any time. So here it is. I'll just open my file. So the first thing is that we will go and implement or import some of the libraries, right? So first of all, I'm going to import pandas as PD. Pandas is the library which will actually help you to read the data set from different data sources like Excel, CSV sheet, or right. And then I'm also going to import matplotlib .pyplot as PLT. This is for visualization purpose. Apart from this, I'm also going to import numpy as NP. Okay. And guys, please remember one thing, that if I probably make any mistakes, right, I will not remove that part of the video. The reason is that I really want to keep all the things in this particular video should look like raw, because whatever issues you are going to face, it is better that we fix it in front of you, because tomorrow you may be also facing that particular issue. So just a reminder. Okay. So next thing, what I'll do matplotlib, and then I will also say inline, so that I can display all my visualization graph within this Jupyter notebook. So let me just go ahead and execute. So here it says first error, no module named matplotlib inline, right? So here if you see, what did I import? Import matplotlib.pyplot as PLT, right? So let's see why this thing is not executing. Okay. Import matplotlib.pyplot as PLT. Because here you can see clearly I have made one spelling mistake. So that is the reason why I'm saying you, even though I face any kind of issue, I'm not going to remove any part of it. So I'll make it matplotlib. So this is the spelling mistake was there in the slide, so you may also face it. So I'm just going to execute it now. Now the next thing is that what I'm actually going to do here is that I will be reading the data set. So now to read the data set, what I will do, I will write df dot, and let me just open the data set over here. And here you can see the data set name is height dash weight.csv, and this is present in the same folder location where I'm actually working. Okay, so let's go ahead and read this data set. So I'm going to write pd.read_csv, and here I will be reading my data set, and my data set is nothing but height-weight.csv. So if it is already present in this folder location, if I probably go and click on file and open it, right, you'll be able to see this particular file. Let me just show you. So right now, these are all the files that are created inside this, and here you have height-weight.csv. Okay, so if you're starting this project, after you download the file, please make sure that you keep that particular files on that same location. Okay, now once I execute this, here now I'm going to get something called as df.head. If I see df.head, here you'll be able to see one inputs and one output, that is weight and height. So these are my two features that I'm going to use, and I'm going to probably create a simple linear regression. Now, first of all, one thing that you really need to understand, what is the relationship between weight and height? Whenever you are probably creating a simple linear regression, it is very much important to actually check how your independent and your dependent features are related, whether they are correlated properly or not. Okay, so one way is that I can use some scatter plots. Okay, and here I've taken a simple data set, guys. You may be thinking, Krish, why you're not doing feature engineering? Is there any NaN values you have to check or not? Yes, obviously you need to check, but I know in my data set I don't have any other problem, and this is the first simple project, so I really want to go ahead and show you most of the important steps. So first of all, I will go ahead with scatter plot. In scatter plot, I will be using pltc.c scatter. So scatter is a function which will actually help you to project your data points with respect to x and y axis. That is your weight and height. So I just want to see what kind of relationship is there when you scatter the data points. So here I'm going to use df of weight, and then I'm also going to use df of height, right? So height, I think it is capital, so it's height. Now when I display this, you can see that over here, right? In this, if you see the specific plot, here you can see on the x-axis I've taken df of height, right? On the y-axis I've taken df of, in the x-axis I've actually taken df of weight, in the y-axis I've actually taken df of height. Now let me just put some axes also, so I'll write plt.x label, okay? And here I'm basically going to put it as weight. Well, I'm just labeling the x and y label so that it'll look better for you. plt.y label, and here is specifically my height, okay? Let's go ahead and plot it. Now here you can see that in the x-axis you're able to see height, weight, and here you're able to see height. Okay. Now this is perfect. Now from this particular data point, you can obviously see that as the weight is increasing, right, your height is also increasing. So this is a kind of linear relationship, right? And if you really want to find out whether this relationship is positive or negative, you can also use correlation, right? So what I will do, I will just write over here of finding correlation, right? So if I write df.corr, right, this basically means it will show you the correlation between your x and y coordinates. That is your weight and height. Now here you can see within weight to weight, right, there will hardly be any variance, right, if you try to compare. So this is 1.0. But if you see with respect to the relationship between weight and height, it is 0.93. That basically means that it is highly positively correlated, because inside this correlation, if I go and press shift tab, the method that is used is something called as Pearson correlation. Okay, Pearson correlation, and this Pearson correlation basically finds out the relationship between your x and y coordinates. Okay, now this is perfectly fine. You can also use one library which is called as cbond for visualization. So let me just show you that. First of all, what I'll do, I will import cbond as SNS, right? And here you can write snh.pairplot. Okay. Now this pair plot, what it will do is that in a diagrammatically way, it will try to show you, it will try to display the specific coordinates. Okay. So here I'm just going to write df and just execute it. So here you'll be able to see the same correlation is basically displayed over here, right? And obviously height and weight is positively correlated. It is in a linear correlation, and this is also in a linear correlation. Now suppose if you have something in linear correlation, you get a strong feeling that yes, linear regression is going to work well. Yes, there may be other problems with respect to the independent feature. Like usually when we do multiple linear regression, right, we also check this relationship between the independent feature, right? But right now I just have one independent feature. We'll get to know that how to check multicollinearity and all. Multicollinearity is a scenario wherein if you have 2 to 3 independent feature and the correlation between those independent features are high, then we can neglect those features which are highly correlated. Either of the feature we can basically take. Okay. So here let's go ahead with this one right now, because since in my independent feature I just have one, in the output feature I have one. So this is perfectly fine. And here you can see that okay, it is linearly correlated. So you get a good feeling that simple linear regression will work well, because at the end of the day I have to create a best fit line through it. Okay. Now the first step that we probably start in simple linear regression. Here I'm just going to divide my features into independent and dependent feature. Super important whenever we basically starts, right? Features. Now, if I probably go ahead and display df.head, here you know that how many features I have. Now see, this error has come, so don't worry, because I know what is the error I made. So here you have something like weight and height. Okay. Now this weight is the independent feature and height is your dependent feature. So in order to create your independent feature, I will just name it as x. Just a naming convention. It is a good practice that we should use this kind of naming conventions. Okay. So x is equal to df of. Now suppose if I want all my weight feature in the x-axis, so I can first of all write like this, right? If I probably write like this, right, then the x that is basically getting created is a series, right? So obviously I get my weight value over here, right? But understand, if I probably try to see the type of x, here you'll be able to see that it will be a series, not a data frames, right? Data series. Now, but if I probably try to see type of df, it basically shows me that it is data frame. Now series basically means just a single record. You have to take care of one important thing, guys. Whenever you probably try to create independent feature, right? And if I use one additional bracket, then what will happen is that just see this, okay? If I go and execute this like this, and if I write type of x, now you know that we will try to get a data frame, right? And probably if I try to here you'll be able to see that I'm getting a data frame with column name. Always make sure that your independent feature, right, should be in the form of data frame or two-dimensional array. Okay, independent. Yeah, I'm writing it over here because this will be super important when you're training a model. So your independent feature should be data frame, or it can also be two-dimensional array. When I say two-dimensional array, what does this basically mean? This basically means I can have something like this. See, suppose if I write like this, okay, and now probably let's say I'm going to write np.array. Okay, and I'll probably write x. Okay, now if I write like this, here you can see that it is a two-dimensional array. Okay, two-dimensional array, and this basically indicates that how many rows I have. I have 1, 2, 3. Let's just see how many rows I have. For seeing how many rows, I can basically go and execute shape. So if I write dot shape, here you can see that it basically has 23 rows and 1 column. Okay, but in data frame, what was happening? Let's see. In data frame, what used to happen? Suppose if I go and execute like this, and I remove this one bracket. Okay, and probably if I write np.array, right, and probably just go and see x, and then write dot shape. So here you'll be seeing that this will be a one-dimensional array. Here, no information regarding the column is given, but here importance should be given to the column, right? So always make sure that at the end of the day, either it should be a data frame which has one column, or it can be a two-dimensional array also with number of rows and some specific columns, right? Now in multilinear regression, what will happen? This columns will increase. Okay, never keep in this particular format, because what will happen? I'll tell you. Okay, let me just say that I am just writing this as x underscore series. I will try to train with this, and also I'll try to train with that also, and let's see where we get an error. Okay, so over here now, this is my x. Obviously, I've taken this as a two-dimensional data frame which has one column, and then if I probably go and write x dot head, you'll be able to see I will be getting this specific value. Okay, so this is my x. Perfect. Now till here we have executed, and let's go ahead and execute this also. And you know that probably if I also see okay, df of weight. What happened? NP.array. Oh, I have to check it x underscore series. Okay. Now here you can see it is one dimension. Perfect. This is done. Now the next thing is that after creating an independent feature, I have to create dependent feature. Now in the case of dependent feature, I can have it as a series. Okay, because dependent feature will only be one column values, right? We don't have to worry much about that. We do not have to make it two dimension. Okay, one dimension is properly fine in this, because we will have only one dependent feature in a specific problem statement, and this is a regression problem statement. Why do we say this is a regression problem statement? Because here my output value is continuous. Okay, super important point. Now here I'm going to basically write df of height. Now this is my y and this is my x. Let's go and execute. Now if you want to see your y, here is my output feature, right? With respect to this. And always remember, this needs to be in series or it can be in one dimension. Okay, so here I'm going to write it down over here. This variable can be in series form or 1D array. Okay, 1D array basically means if I probably write np.array of y, okay, dot shape, here you'll be able to see only one array. So obviously 23. Since you have 23 inputs, you have 23 outputs, right? So this is super important. So, and this is very much important, guys. Otherwise, at the last you'll face some issues. Okay, so here I've actually done my independent dependent feature. The next step, we specifically have to do something called as train test split, and I have already explained why you need to do train test split. This is for the overfitting underfitting condition. The train data only will be using for training purpose, and the test data will just be used for checking how the model is predicting for the new data point. So for this, we will be using a library from sklearn.action. So I'm going to import train test split, and here I'm going to use xtrain or xtest, ytrain, ytest. That basically means I'm creating a train data, and with respect to that particular train data, see, train and test. So training data will use the model for training that specific data. For testing that model or for seeing that how the model is performing for the new data, we'll only use test data. So that is the reason we are creating these four components. Initially we just had two components, one is x and y, but obviously I need to create xtrain, xtest, ytrain, ytest. With respect to the output of xtrain, it will be present in ytrain. Okay, so this four parameters will get called when we use this train test split, and internally we'll give x, comma y. Let's say I'm giving my test size as 25%. Okay, so in order to give test size as 25%, I will write 0.25. Now, how do you think I've got to know all these things? Just go and press shift tab. Okay, so here this, then only you'll be able to see it. Okay, so here you'll be able to see I have just imported this, and now if I press shift tab, here you'll be able to see, or the arrays over here, you can see test size I've given. The arrays basically means x and y array. Train size also you can give, and there's also something called as random state. But before this, let me make some cells. Just a second, I pressed F1. That should not happen. Now let me just go and make more cells. So I'll just copy this entire thing and I'll put it over here. Okay, perfect. Now understand one thing over here, guys. There is something called as random state. Now see, usually when we basically take this random state, let's say I'm going to take 42. The type of train test split, if you don't put this random state, right, for everybody it will be a different kind of train test split. We can randomly pick up the record, 75% of the record, and put that in the training data set, and we can randomly pick up the 25% of the record and put in the test data set, right? So that is what usually basically happens in this case. So if you write a random state as 42, so whatever way it is basically taking me, like taking my data and putting in the training data set. Similarly for you also, that training data set will get selected. So once I execute it, so here you can see now I will be able to see my X train, and I will just print the shape also. And obviously remember the shape should be two dimension. Okay, two dimension. Okay, extrain dot shape. Sorry, I don't have to use this. And since here you can see this is two dimension, right? That basically means this one is because of I have one feature and these are 17 rows, right? So 17 rows and one feature. Similarly, if you have five features, then this will become five features. Okay, like that it will happen. Okay, but at the end of the day, you will be getting a two dimension. Perfect. Now let's go ahead and let's discuss what we have to do after this. Okay, now we have to perform a very important step which is called as standardization. Standardization, why it is basically required. Now just understand this. I'm also going to write in front of you. Let's say I have two features, x and y. Let's say x is calculated based on kg units, y is calculated based on some other units. Let's say over here in this particular case, since this is height, I'm going to use centimeter. Okay. Now understand one thing. Whatever values you get over here, right? These are of different units, and you know that in linear regression, when we use scalar, we use something called as gradient descent. So obviously, based on this unit, if this value is higher, to come to the global minima, right? It is going to take time, right? Because I have a bigger value, and all the math equation that is getting applied, it will get applied to a big value, right? Which is again not a suitable solution. Okay. And obviously, for the optimization problem, will take long time to reach the global minimum. Okay. So what we do is that a very good approach is that we take up each feature, not the output feature, we take up each independent feature, and we apply a simple formula, which is called as z-score. And this formula will basically be converting all your values with mean is equal to 0 and standard deviation equal to 1. Okay. That basically means if I take up all these data points, I will write x of I minus mu divided by standard deviation. Only this formula gets applied to all data points. So at the end of the day, what will happen is that my mean, all these data points will get converted with mean is equal to 0 and standard deviation equal to 1. Super, super important. Okay. So please make sure that you remember this. And this is a very good step with respect to standardization. In the upcoming future, I will also talk about which all algorithm you not apply feature, you will not apply standardization. Okay. That part also I will try to discuss. Okay. Now what I'm actually going to do, I'm rub this and let's apply standardization. Now for standardization, again, we will be using an scalar library. See guys, every library that we are going to use, you will be able to get it in scalar. Okay. So if I probably show you one case, right? Let's say I have used train test split. So if you go and probably search for sklearn train test split, here you will be able to see that this is the algorithm that is specifically used. So here you can see all the parameters, what parameter, what it returns, and you can also see some of the examples, right? So all the time, suppose if you don't understand where this library exists, all you can do is that search the Google for that specific library. So that is the reason I'm able to write from sklearn.model selection input train test split. Similarly, here you'll be able to see sklearn standardization is there, which we call it as standard scalar. Okay. Now if I probably search this and if I probably see this, here you'll be able to see that you're getting all the values over here, right? So perfect. We are very much in sync and we're able to understand. Okay. Now the next thing that we're going to do over here is perform standardization. So from standardization, what is the library from sklearn.preprocessing? Okay. So here I'm basically going to write from sklearn.preprocessing. Okay. Import standard scalar. Okay, so once we do this, let me just execute it. And here now we are going to standardize my input feature, not the output feature. We do not have to standardize the output feature because our gradient descent gets applied into the independent features, right? So what I'm going to do over here is that I'll just say I'll initialize standardize. So let's say I'm using standard scalar. So this will initialize with that formula that I've written, z is equal to x of I minus mu divided by standard deviation. Okay, then after this it is just going to write scalar dot fit underscore transform. So let me give this formula again, scalar dot fit underscore transform. And here I'm just going to give my x train. Okay, now what will happen for all my x train, this transformation will get applied. Now here you can see all the data points. Over here mean will be 0 and standard deviation will equal to 1. Then that means all the data points will be transformed in this scale. And this I will assign it to x train. Now the same thing I need to do for test data also, right? But always remember, in test data, we do not apply fit underscore transform. See, the difference between fit underscore transform and transform is that initially whatever data that I have, let's say whatever data I have in train, I'm going to use the same mean. Let's say the formula is like this, x of I minus mu divided by standard deviation. I'm going to use this mean and standard deviation only of this training data set, and I'll apply the same formula in the test data set, right? In the test data set. So for this particular case, what I do in training, I say fit underscore transform. And in the test, I just say transform. When I say transform, that basically means I'm going to use the training data set mean and standard deviation and use it over here, okay? And apply the same formula, like x of y minus mu divided by standard deviation. For all these data points, I'll be using this mean and standard deviation only if I use transform. If I use fit transform, then again mean or standard deviation will get calculated for this data. I don't want that. And why do we do this? Because there's an important concept which is called as data leakage. I don't want my training data to know any info about test data, okay? I don't want that thing to happen. You know, my model that is created, this should be the truth value, okay? This should be the information that should only be known, right? And when my model sees this, it should always see this as a new data, so that then only we'll be able to understand whether our model is performing well or not, okay? Super important, data leakage, fit underscore transform and transform. So this is a very important interview question, okay? Why do we use fit underscore transform? And this we will also be doing in PCA, that is principal component analysis. Okay, now let's go ahead and let's continue. So here, what I'm actually going to do here for the test data, I'm writing scalar dot transform, okay? Scalar dot transform. Okay, and then I will basically write this on my x test data. Let's see whether we get any error. So here again, this is perfectly done. Now if you probably go and see your x test, you're going to get this. So this is my test data, and this is how it has got transformed. This is perfect till here. Now the next step that we are probably going to do is that apply machine learning algorithm, that is linear regression. Apply linear regression. Okay, and this is super important. I will again be using this particular scalar value. Okay, this will be again used for the new data also. Any specific new data that has come will again transform them. Okay, now I will apply simple linear regression. Now in order to apply, we'll again scalar, and in this scalar I will search for simple linear regression. So here you'll be able to see something called as linear regression. So this is the model that we're going to apply. So let's go ahead and let's write form sklearn dot linear model import linear regression. Okay, now here you'll be able to see the first thing that I will do again, initialize object. Whenever we are using any libraries from sklearn, first of all we need to initialize that object. Okay, so here I'm going to initialize linear regression. By default, the parameters, what all things are there. So there is a first parameter which is called as fit underscore intercept. Now this fit underscore intercept is nothing but it will say that whether to calculate the intercept for this model or not. Obviously I want to calculate this, so by default whatever true it is, I'm going to keep it as true. Now this normalize function is there. This parameter is ignored when fit underscore intercept is set to false. If true, the regressor s will be normalized, and this process we have already done this, right? We have normalized it, we have standardized this by using standard scalar. We have already done that. So whatever be the default value will, if you have not done that step normally, you could have kept this as true. Okay. Then you have n underscore jobs. This n underscore jobs is a very important parameter because if you set this as -1, it is going to use all the processors that are there in your system. With the help of them, it will try to converge and it will try to do the training. Okay. And positive basically says that when set to true, forces the coefficient to be positive. So I don't want this specific thing to happen because some of my coefficients can be negative. Then in return, what all things you'll be getting if you apply this algorithm? Here you'll be getting coefficients, rank of matrix, singular value of x, intercept. But out of all these things, right, the most important thing is coefficient and intercept. And we'll try to see that what is the coefficient and intercept and what is the relationship with respect to the final output. We'll see that. There's also a feature that will get returned that is called as feature underscore names underscore in. Name of feature seen during fit. That also it will show. We'll try to see this. Okay. So here I've applied linear regression. Let me just go and execute with all the default parameters. And I'll say regression dot fit. Now I want to fit this regression model to our training data, right? So all we will do is that we will go ahead and assign this and we'll assign it to x underscore train. Now understand guys, let's say before giving this x underscore train, let's say I created one more variable, right? And that specific variable was called as x underscore series, right? And you know that this is one dimensional. Now instead of x underscore train, if I give this, what will happen? See, let's say if I'm giving this and I'm giving y because this had all the data. Now see what will happen. It will give us an error. Why? Because it is saying that accepted 2D array, right, got 1D array instead, right? And this was a 1D array, right? So always remember any algorithm that you'll be seeing in the fit and whatever training data I am giving, it should always have a 2D array. In the output, if you have 1D array, that is fine, not a problem. But here you need to give it as a 2D array. Okay. So here what I'm going to give now, x train, comma, y train. Now we will go and do the fit. Now once we go and do the fit, now let's see over here. If I press shift tab, over here, if I press shift tab, here you'll be able to see one parameter which is called as n underscore jobs. Let's say it is none right now, right? I'm just going to keep it as -1. So what it will do, how many processors are there in my, so how many processors are there, it will try to run it on them. So once I execute, here you can see that n underscore jobs is equal to -1. Yes, you cannot see that because it is happening within the system, right? Now, if I probably go and see my regression now, it is basically showing linear regression. Now all I have to do is that in order to predict my test data, how do I do it? So there will be a function which is called as predict. But before this, I already told you that how many different types of parameters it is running. Coefficient basically means slope, intercept and n underscore features. Rank and singular will not focus much into it. So let's go ahead and write regression dot, here I will say coefficient. Now, if I go and execute this, here I'm going to get the coefficient. Now, this coefficient is the slope, and why only one? Because I just have one independent feature. Now, if you remember the entire equation, if I have one independent feature, so my equation will become y is equal to, or y hat is equal to beta 0 plus beta 1 into x1, right? This beta 1 is nothing but this specific value, okay? And now I can actually also get this value because I've already calculated the intercept, and these are my data points. In this particular case, these data points are nothing but weight, right? So this data points are weight. This we have calculated beta 1. Intercept we will be able to get when we are writing regression dot intercept underscore, okay? So here, let me remove this quickly. And let me show it to you. The reason why I'm using this so that I write anything in front of you, so you'll be able to understand, okay? So here, now this is my coefficient. So let me print my coefficient. So here I'm just going to say coefficients or slope is nothing but is this specific value, comma, regression coefficient. Okay. So here I've just printed it. Okay. Similarly, I can also print intercept. So I'm just going to copy this and write print over here. Intercept. And I'll talk about this. What is the meaning of this also? Intercept is equal to, so this will nothing be, I will just write intercept underscore. So this is my intercept and this is my slope. Now what does this basically? with respect to this. Okay, now super important. That basically means 1 unit movement in the weight value, let's say 1 unit movement in the weight value, that leads to 17.29 unit movements in the height value. That is what it basically says, this coefficient. I can understand, guys. 1 unit movement. Okay, let me just draw it again in front of you. Suppose this is my x and y, this is my weight, and this is my height, right? This is my height. It basically says that 1 unit movement with respect to the y axis, it leads to 17.29 unit movement. So from here to here, basically this is 17.29 unit movement, okay, with respect to the y axis. So this is what this probably will look like my slope. Okay, so this is what we are doing. And the next point is that what is this 156? 156 says that when your weight value is 0, when at what point your line is meeting the y axis. So this particular point is nothing but 156.47. So I hope you have got an idea about it. Okay, the importance of coefficient and slope. Okay, and let me do one thing. Apart from this, now you have got your coefficient and intercept. Now you may be thinking, Krish, okay, fine, we have created this. Can we see some kind of line? So suppose if these are my data points, can we see some kind of line which I can say it as a best fit? Answer is yes, and I'll show you that. So let's go ahead and plot this particular points, right? So here I'm going to plot the training with respect to training data. I'm going to plot best fit line. Okay. So here let's go ahead and plot it. So first of all, I will say plt.scatter, and here I'm going to scatter my x train and y train data. Okay. So what will happen if I plot this? Here you'll be able to see this kind of plot. Okay. Let me make some more fields. Okay, so here you can definitely see some plotting happen, right? On top of it, now you want to see how our best fit line is created. Then what do? I will go and write plt.erot plot. This plot is also used, and here I will be taking x train, and we know that how to find out a predicted value, right? Now in order to find out the predicted value, all I will be doing is that I'll take this model. Okay, this model is regression. So here I'll write regression dot predict. Okay, and here I'm specifically giving what value over here. See, if I write regression dot predict, here I'm going to predict for x train. So this will basically give my predicted value along with the straight line. Now if I go ahead and execute this, now see, this is the best fit line that has got created in the specific data set, right? And this best fit line will have an coefficient of 17.29 and intercept of 156. Because see, if I probably try to make sure that extend this when my value is 0, then you are actually going to get an intercept of 156. Okay, so this is what it basically says with respect to this. Okay, so now here you can see I've got my best fit line, and with respect to this particular best fit line, we are able to see that okay, the error also looks very less, right? Here, you can definitely see the error is also very less. Now let's go ahead and let's go to the next step. Now we need to do the prediction for the test data. Now in order to do the prediction for the test data, how do I do for the prediction for test data? So here you'll be able to see I will be using plot.scatter, or I'm going to use plot.scatter also. So my model is something called as regression dot predict on my x test. Now here when I do the prediction, this is my predicted value. So this will basically become my y underscore predict. Okay, so let me just execute it. Perfect. Now in order to see how the result is, we will try to now check with some of the performance metrics. But before that, if whenever I do prediction for test data, right, I will just go and copy this thing. Okay, just let's see. I hope everybody will understand it. Let's say I'm typing a markdown over here. Here you can see the predicted height output will be intercept plus coefficient multiplied by weights, right? So right now, what is my intercept? My intercept is nothing but 156. Okay, let's say this is my value. Okay, so I'm just going to copy it over here, and my coefficient is nothing but 17.29. So I'm just going to copy this and paste it over here. Okay, so this is what is basically happening in order to find out all my y prime. Okay, so here I'm just going to execute it, so that will give you an idea. Okay, so I hope everybody is able to understand this already. Understand x test data is already transformed also. Okay, if you don't know. Now let's go ahead and do some more things in this. Fine, we have done the prediction. Now we'll focus more on the performance. Now, which all performance metrics we have already discussed that we're going to see. So in this, I'm just going to write the performance metrics that I have actually discussed. I'll write from sklearn dot metrics. I'm going to import the library that I'm going to import is something called as mean squared error. So here you have mean absolute error, mean squared error. Okay, and there are also many other performance metrics which can also use, right? For right now, I'll just use this because we have learned about this. Okay, and then what I'll do, I will basically calculate my MSE, mean squared error. So here I'm going to write mean squared error, and here I'm going to give my y underscore test, comma y underscore print. So this will basically give my MSE. Similarly, MAE is nothing but mean absolute error, and this will basically give my y underscore test, comma y underscore print. And finally, root mean squared error, which is nothing but np dot square root, right, of MSE. Then I'm just going to print MSE, print MAE, and then print RMSE. As I said that, we really need to check all the parameters over here. Now here you can definitely see that 114.84 is your mean squared error. Definitely it has penalized a lot of outliers, whereas in this case here you can see it's almost nearby by using mean absolute error and all. Okay, so here this is what we have actually got with respect to our performance error metrics. Now the next thing that we are going to use is something called as R square also. So R square, if you remember the formula for R square, how we are going to use the R square. So here I'm just going to copy and paste the entire formula for you. We have already discussed about this. It is nothing but 1 minus sum of square residual divided by sum of square total, right? So here this is the formula that we'll apply. In order to apply also, we can also use this from my library. So I'll write from sklearn dot metrics import R2 score, right? So it should be metrics. Okay, so this also will look good because now overall we'll be able to get how our model is performing. So finally my score will be equal to R2 underscore score is nothing but y underscore test, comma y underscore pred, right? And if I probably print my score, this will be my R2 score, and here I'm getting 73%. And obviously you cannot get a perfect just by linear line. We'll be seeing how we can improve this by using some of the algorithms like polynomial linear regression, decision trees, and all. Many algorithms are going to come up in the further stages, which will try to improve this particular accuracy. But right now I'm getting 0.73. And obviously, let's go and find out one more that is called adjusted R square. And as you know, adjusted R square formula is this, which again I have discussed in my theory part, right? It is nothing but 1 minus R square multiplied by n minus 1 divided by n minus k minus 1, right? R2 is nothing but R2 score of the model, number of observation, n, number of predictor variables, right? Right now I just have one predictor variable, so I don't think so it will be such a big issue or big change in my score. So if I probably go and see, it is like somewhere around 0.50. Okay, so I just applied this formula where I've written 1 minus 4, length of y test minus 1. Y test is basically giving you the number of observation and all, and this is the x test, and this is your other thing, right? So yes, I think I've covered most of the things over here. We have also seen that we have got 0.73, which is good. I've also seen all the performance metrics like mean squared error, mean absolute error, root mean squared error. This is absolutely fine. We have done some kind of visualization, analysis, and all. Now let's try to see one thing. Okay, let's try to do the same thing with OLS technique of linear regression. So can we get the same, because that formula that I derived, right? Can we get the same output that we are looking for? In order to implement OLS linear regression, I'll say import stats models dot API as SN. Okay, and I'm going to execute it. And now I'll just use my model is equal to this model will this API that I'm actually using, right? This library that I'm using, this has a library which is called as OLS. And in OLS, all we need to give is with respect to your training data. So if you probably go and see over here, OLS, here you have something called as endog and exog, right? Endog basically means 1D indigenous response variable, that is my output variable. Exog basically means my true input variable, right? So here I'm basically going to give my xtrain, and then I'm just going to do dot fit on this, like how we did for linear regression. Once I do this, I will get my model, and all I have to do for prediction, I will do model.predict or x underscore test, and this will basically give my prediction value, right? This will give my prediction value. So if I probably execute this print prediction, you'll be able to see the prediction also. Perfect. So these are my predictions. Now let's do one thing. Okay, I'm just going to print my model summary over here. Okay, in OLS and see whether I'm getting the same thing what I did with the help of linear regression using gradient descent. So again, I'm printing this. Now here, I'll just zoom out. Here you can see that there is one feature x1 and it is having coefficient of 7.29. Now, is this matching with this or not? We'll try to see. So if you go over here also I'm getting coefficient as 7.298, which is quite amazing. Now you can see the proof that with the help of OLS also, I'm getting the same coefficient. And yes, there are some more parameters over here, right? They are like R squared value, adjusted R squared value, right? Statistics value, and this is specifically for uncentered. Centered data is not there, right? So all these things here you can basically see that, but at the end of the day we are getting a coefficient which is 17.29, right, which is approximately equal to this particular coefficient that we got with linear regression. Okay, so this is the most important point with respect to this, that basically means with the help of OLS also we are able to get some good values, right? Good because almost all OLS and this scalar works in the same strategy. Okay, now till here we have discussed about so many things, right? Now how to do the prediction for the new data. So this is super important. Prediction for new data, right? Now let's say that I get a new weight. Okay, let's say my weight value over here, and in order to do the prediction I'll write regression dot predict and my new weight value. My new weight value, always make sure this you are providing in 2 dimension again, right? So it should be, let's say I want to predict it for 72 weight, what should be my output? So here you'll be able to see the output. Now guys, here you can see that after prediction it is showing 1401. Oh my god, this basically means that the person who is having a weight of 72 is getting a height of 1401 centimeters. So what mistake did we do? Why it is basically giving this kind of output? The answer is very simple, guys. We missed a very important step, which is called as standardization. See, we did this standardization, right? And right now my data points are not, standardized down or normalized in this particular range, right? So what do? We will again use scalar.transform. So here I will just copy this and I will write over here, simple, scalar.transform, and I will give this value inside this. Now, once I give this value inside, then you will be able to see I will be getting a good value. So now this is the correct output with respect to this particular data, right? Now just imagine if you did not remember that scaling part, you would have worried, right? Oh, Krish, what happened? Why I'm getting such a high value, right? So always make sure that whenever you are doing some kind of predictions, okay, you have to make sure that this problem, this scaling transformation needs to be always done, okay? So this is super important, right? Now this was all about this, the entire linear regression model, simple linear regression model, where we took a simple data set and we tried to see much more information and we tried to do the prediction. So I hope you have understood this. In our next video, we are going to see a problem statement where we have multiple features and we try to implement multiple linear regression, and we also try to see with this OLS whether we will be able to get the same output or not. So yes, I hope you like this video. I'll see you all in the next video. Hello guys. So this is our second project, and in this project we are going to solve a use case using multiple linear regression. Now whenever I say multiple linear regression, that basically means I will have at least more than one independent features. Okay. So for this, I will just increase the complexity more when compared to the previous one. And the data set that we are going to use is something called as economic_index.csv. And again, this particular data set I have actually prepared by seeing some of the stats information. I'm not taking the complete data set, but at least 25 records from there. And we'll understand how we can implement multiple linear regression on this particular data set. Let me talk more about this particular data set. This data set is all about index price. Now, first of all, we'll try to understand what is index price. Okay. So what is index price? Now here you'll be able to see index price is a measure of relative price changes consisting of a series of number arranged so that a comparison between the value for any two periods. So to calculate this index price, and government uses this specific index price, over here we require two important things, that is interest rate of the bank and the unemployment rate. And based on this, by applying some formula, we basically calculate the index price. Now I have all these details based on month, right? All 12 months, you can see 2 years data is there. That is the reason you can actually find out 24 records. So 12 years data is there. Now we need to create a model which will be taking these two important features, that is interest rate and unemployment rate, and it should be able to give us the predicted output index underscore price, and that is what we're going to do. Why we say this as a multiple linear regression? Because here I specifically have two features. Okay. In the previous example, we just had one independent feature and one output feature, but here we have two independent features and one output feature. Okay, so let's go ahead and let's try to solve this problem. Now, first of all, as usual, what I'm actually going to do over here is that import pandas as pd, so same step, import matplotlib.pyplot as plt, then import numpy as np, because this all things has been already done. So I'm just going to quickly complete this so that I hope everybody knows how to do this. Now we will try to read the data set. So here I'm just taking this specific data set and I'll say df underscore index. Okay, and I'm just going to read this data set. Let's say I'm going to write read underscore csv, and here I'm basically going to take pd dot read underscore csv, and here I'm going to basically take economic index.csv, right? Now, if I write df underscore index dot head, so I basically have my 2 years data. Very simple. Now, over here, the first thing that you will be able to see, right? You have this extra column that is getting created. So first of all, I will just drop this column in order to drop this unnecessary column. Let's drop unnecessary column. And here, unnecessary column basically means I can also consider year and month, because I don't require this, right? Based on interest rate and employment rate, I need to be able to predict the index price. And whatever year or whatever month, if these values are given, we should be able to predict the index underscore price. Okay. So let's drop unnecessary columns. So here, first of all, I'll use df.drop, and always make sure that whenever you're trying to drop a column, you have to use one important parameter. Okay. So let me just go ahead and write df underscore index dot drop, and let me press shift tab. Here you just need to provide the labels and your axis value. You can also provide index or columns. Okay. So here, first of all, let me columns. So columns here, I can definitely provide something like, let's say in the list, it will be unnamed, or I'll just copy the same thing. Okay. And here I will add axis is equal to 1. So if I execute this here, you can see that this unnamed column will get dropped, right? And this will be the remaining data that I'll have. But I also have to drop year and month. So what I'll do in this list, I will add year, and I will also add my month column. So once I do this, here you'll be able to see that it is getting deleted. It's working perfectly fine. Now, when you're sure about this, then there'll be one more feature inside this, one more that will be in place is equal to, right? So here, when you do in place, in place is equal to true, that basically means you are actually dropping the column now, right? So, and once you drop the column, it will get updated in df underscore index. That is the main importance of in place underscore true. That basically means within this particular data set, you're dropping it and you're updating it. So now if I go ahead and execute this will be my df underscore index dot head. Now, here you can see I have two features, independent features and one dependent feature. Perfect. Now, first of all, let's go and see whether we have any null value. So in order to check the null value, I will write df.isNull.sum. This is the common code to basically find out check null values. Okay. And right now I'm not taking it, but as we go ahead, we'll have some amazing problem statements. So let me go ahead and write it as df underscore index because that is the habit, right? Most of the time we will try to write df. Now, after checking the null value here, you can see you don't have any null values. So obviously, this particular data set, what I'm actually first going to do is that let's do some visualization, okay? And this visualization that I specifically do, I use a library which is called as import cbon as SNS, and then here I'm just going to write SNS dot for that specific library function that I'm going to use is something called a pair plot. And if I give my df value here, automatically, sorry, it should be df underscore index again. I'm making this mistake again and again. Not a problem. Now, if I probably go and see this df underscore index, here is what things you're actually getting. You can basically see with respect to index price and interest rate, you can see some linear relationship is there. With respect to index rate, you can see inverse relationship is there, right? So again, if you check employment rate and interest rate, again, here you are getting an inverse relationship. So if I probably go ahead and write df underscore index dot corr. So here what we are going to get is that we're going to get some negative values also, because this interest rate and employment rate here you're having a negative correlation. Similarly, with respect to this index price and unemployment rate here you're having a negative correlation. But if I see with respect to interest rate and index price, you have a positive correlation. So that basically means as the interest rate is increasing, your index price will keep on increasing. If your unemployment rate is increasing, your index price will be decreasing. Now we are going to use this two specific feature and try to implement some amazing, we'll basically create a machine learning algorithm using multiple linear regression. Okay. Now let's go ahead and let me first of all make some cells. I'd also like to make sure that I visualize these data points, right? Unemployment rate, interest rate properly, right? So let's go ahead and visualize this more closely. Visualize the data points more closely. Okay. So here I'm going to just take df underscore index, or I can also use plt.scatter plot. And here I will be using df of, let's say I will go from interest underscore rate, along with, I really also want to see the correlation between, okay, here one more thing that we saw, right? What is the correlation between unemployment and interest rate? So obviously here you can see that it is an inverse one. And with respect to index price also it is inverse one. So obviously both these features will play an important role in predicting the output. Okay. So now if I go ahead and probably see the scatter plot, df of interest rate and df of unemployment rate. Okay. So let's say unemployment underscore rate. Okay. And here I will probably use a color. Let's say color is equal to red points. Okay. So here it will be R. Now if I probably execute it, so here you can see df underscore index. Again, same mistake, but I don't want to edit this part now because it can happen with you. Okay. So here obviously you can see that it is having an inverse relationship. Okay. So obviously here I can also do plt dot x label, and here I'm just going to write it as interest rate, plt dot y label. Here I'm going to basically have unemployment rate. Okay. And once I execute it, here you'll be able to see it. Obviously, inverse relationship, the same diagram we have got it in a bigger one. Okay. Now we'll do it for the next one, that is interest rate and index price. Obviously, you'll get a positive correlation. Fine. This is perfectly fine. Now let's go ahead and implement. First of all, what I'm going to do is that get my independent and dependent feature, right? And when I get my independent and dependent features, first of all, I'll write x is equal to df underscore index. I know what all column I basically want. So I'm just going to write my column name. So first one is interest rate. Let's see. This will be my interest rate. And this, the next column will basically be my unemployment rate. Okay. I can also do in this particular way. Let me show you and another way how you can basically do it. Okay. So df underscore index, I can also use iloc. Okay. And here iloc first parameter says take all the rows, comma, from all the rows just remove the minus last row, and here you'll be able to get your x value. That basically means from all the features, just from all these features that you have, just remove the last feature, because index underscore price is your output feature, and this is obviously a continuous value. So regression problem we're trying to solve. Okay. Similarly for the y variable, here you can write df underscore index dot iloc, and here colon, comma, colon, or -1. I'm just saying that take the last column and put it in the y value. Okay. So this two way also you can basically do it. Okay. So once I execute it, here you'll be able to see x. So let's go and see x dot head. Here you see your interest rate and unemployment rate. And similarly, if you probably go and see y, here you'll be also able to see. Anyhow, this will give you a tuple. So I'll not suggest you to go and display your data like that. Here, perfect. Now the next step is very simple. We will do the train test split as already explained. Train test split. Okay. From sklearn dot model selection, I'm just going to import train test split. Okay. And then you have x train, comma, x test, comma, y train, comma, y underscore test. Okay. And then here I'm just going to use my train test split. I'm just getting bored a little bit. So let me go ahead and copy some of the code from here. So this is my train test split. Let's say I'm doing 25%. So I'm just going to paste it over here. Okay. So here I've given xy test size 0.25 and random state underscore 42. So once I execute it, here you will be able to see your x train, y train, and all, right? Now guys, I'm also going to introduce you all to a new kind of plot in Cbon, which will basically be very, very helpful when you are actually working with this kind of data. Now, let me go ahead and show it to you. First of all, let me import Cbon, okay, as SNS. Now in Cbon, you have something called as reg plot. Okay, and if you probably want to see this plot, I'll just execute this. Okay, and let me copy this one over here, and let me just write shift tab. Now here in this particular plot, this plot is all about this plot. It plots data in a linear regression model fit. Okay, so let's say if I'm using df of let's say in my x-axis, I'm just going to put one of the features which is like interest rate, and my another feature over here will be df of the index price. Okay, so if I just try to plot this, okay, so it should be df underscore index. Okay, my mistake again, not a problem. You should do mistakes. Okay, df underscore index. So once you plot this here, you'll be able to see with respect to this kind of data points, this is the regression line that will get created. So this gives you an amazing idea that yes, the errors that probably are going to get is quite less. Okay. Similarly, let's say that I'm going to copy the same thing, and I'm just going to plot this along with the interest rate. Let's say the interest rate and the unemployment rate. So if I probably write unemployment rate, and if I plot it here, also you'll be able to see that you're able to get an amazing regression line within this particular points. Okay, and this way, and this shaded region basically shows that yes, you can hyperparameter tune this particular line to some level. Okay, so and similarly, if I probably try to plot this with index underscore price, here also you'll be seeing an inverse manner, and from with respect to that, here also you'll be able to see this kind of line. Okay, so this was just an idea to give you. Every video I'll try to teach you something new, so I wanted to include this regression plot also, which will actually give you an idea. But again, you cannot do this for more than 2 features. You cannot basically create a 3D plot. It asks for only 2 features over X and Y. So with respect to that, you can definitely check it out. Okay. Now, since you have done our train test split, the next thing that we're going to do is that obviously standard scaling, right? So I'm going to write from sklearn dot. Now see, I'm not remembering where the standard scalar fall, so I can go and search for it. Sklearn standard scalar. I'm actually you do not remember everything, guys. So it is present in processing. Okay. Right from sklearn dot pre-processing, I'm going to import standard scalar. Okay. Standard scalar. I think that is only the spelling. Okay, standard scalar. Okay, perfect. So let me just go ahead and import processing. This usually happens when you are doing the coding because I'm not seeing any materials as such right now because whatever comes in my mind, I'm basically following the best methodologies as a developer, you know. So this will also help me to learn things better. So now what I'm actually going to do over here is that I'm going to create a scalar and I'm going to basically say standard scalar. Standard scalar. I'm going to initialize it. Okay, then what we do, we write scalar dot fit underscore transform on my x underscore train data. Similarly, this will go in my x underscore train data. And similarly, here you'll be able to see x underscore test is equal to scalar dot fit underscore transform on our x test data. Okay, so this is my x train and x test. Perfect. We have got our x train now. Let's see. We don't have to do it for the y value. Now see here you have got 2 values, right? And when we do fit underscore transform, it converts this into a 2-dimensional array. So initially I had a data frame, it gets converted into a 2-dimensional. So this becomes my input, right? Now the next step, what I'm actually going to do, I'm just going to write from sklearn dot linear model. Okay, I'm going to import something called as linear regression. Okay, and this will basically be my regression where I'm specifically writing linear regression, and this I've got executed. Okay, then what I'm actually going to do, regression dot fit on my x train comma y train data. Okay, this is done. Now let me introduce you to something called as cross val score also. Okay, now this cross val score will also give you some good results. Okay, so let me just search for sklearn cross val score. Okay, now as I said, every video I will try to teach you something new. Okay, now cross val score is basically a cross validation method. Okay, and this is where I really want to talk about cross validation. And here all you have to do is that give your model, give your x train y train, and this in turn will basically create a cross validation. Now what does this basically mean? Let's say I'm going to write over here. Okay, this is my regression, right? It has fitted to the x train and y train. Let's say I import cross validation. So if I say sklearn dot, let's see whether cross validation is falling. It falls in model selection, and I'm going to import cross val score. Okay. Now inside this cross val score, what I'm going to say is that okay, fine, this will be my cross val or let me say that this is my validation score. Okay. This in turn, first of all, we will give this cross val score over here. The data set that we're going to give, obviously, when I press shift tab, I have to give my estimator. Estimator basically means my model. Okay. So here I have got my model. And then in the next parameter, if I probably go and see, I have to give my x and y value. Okay. So here, obviously, I will give my x train, comma, y underscore train. Perfect. The next parameter that I will probably give over here, if I see, there is something called a scoring. Okay, scoring parameter. Now in this particular case, let's see what should be the scoring parameter. Okay. So if you probably go and see over here, similar to cross validate, but only a single metric is used. So if I probably see a scoring parameter in that, let's say I'm just going to search for sklearn scoring metrics. Okay. Now inside this, if I go and check it out, how many different types of scoring parameters are there? So for classification, you have this many. For clustering, you have this many. For regression, you have this many. So let's say that I'm just going to consider negative mean square error. Okay, negative mean square error basically means I'm just going to get the mean square error, but in a negative manner. Okay, so I'm just going to copy this and put it over here. Okay, this will be my scoring parameter. Okay, so here I'm just going to paste it. Perfect. Now this is done. Now my next parameter, what I'm actually going to do, if you go over here, the next parameter that is present, right, with respect to cross val score is cross validation. Now this is super important. If I say my CV is 5, okay, what does this basically mean? Or let's say I'm just going to make CV is equal to 3. Let's say if I have 1,000 records, total records. Okay. Now initially, let's say I made this as train test split. Okay, let's say in train I have 900 records, in test I have 100 records. This data I'm never going to use it, right? I will just be using this data. Now this data will only be used when we need to test our model with the new data. But further, to hyperparameter tune my model or to make my model better, I can split this train data into train and validation. Now when I split this data into train and validation, what will happen is that, let's say I will split this based on some mechanism. What mechanism? I will say let's go ahead and take cross validation as 5. Now what will happen if I divide 900 by 5? This basically indicates that what is the value that I'm going to get? 5 ones are 5 8s are 180, right? So this basically means in my first experiment, when I am taking my entire data set, the first 180 records will be my test data, and remaining all will be my train data. Then in the second experiment, that is cross validation is equal to 2, the next 180 record will be my test data, and remaining all will be the training data. Similarly, I'll go with respect to cross validation 5. The next, let me just do control Z. The next 180 record will be my test, and remaining all will be the train. Similarly, I'll go like this, and at the end of the day, we'll be able to see at cross validation 5, the last 180 records will be my train test, and remaining all will be my train data. Okay. Now, as you know that with this cross validation score, for every cross validation, we will be getting a MSE. From where did this MSE come? This came from this particular scoring parameter. Okay. So here we are going to use negative mean square error. That basically means whatever MSE I'm getting, it will be a negative value. Okay. Negative value. So this is what we're going to do. And again, our target is that it should be, the more this value comes towards 0, the more better the specific model is. So here, with the help of cross validation, I will be getting 5 different accuracies. This will be my MSE1, MSE2, MSE3, MSE4, MSE5. And then I can probably take the average of all this and probably print it over here. Okay, so this is what we are going to do over here. So let me just go and show it to you. Right now I've just taken cross validation is equal to 5. That basically means I'm going to get 3 validation scores. Okay, so let me just execute it, and this is what executed. If I go and probably see my validation underscore score, here I'm getting 3 MSE values, mean squared error values. And now if I probably do the average of this, how do I find out the average of this? You can basically do np.mean, right? np.mean. So by this way you'll be able to get the mean MSE. Okay, so this is basically my mean validation score by performing all my basically cross validation on this particular data set. Okay, but again this is just to check or to do additional step of cross validation. So here this is how you have to basically do the cross validation. Okay, with the model that we have created. But now let's go and do the prediction. So now I will do the prediction. Okay. Now, before we do have a prediction, guys, I also want to make some assumptions. Okay. And this assumption is super important. But before that, let me do the prediction. So here I will be using regression dot predict. And here I'm just going to give my x underscore test data. And this will basically be my y predict, right? So y underscore predict. Perfect. Now, after this, all the things that are common, right? So first thing, I'm just going to go ahead with this entire code, that is performance metrics. And I'm just going to copy it over here. And similarly, I will go ahead and copy this, where I'll be finding the mean squared error and all. And here, this is where I've actually printed. So this is my mean squared error with respect to the prediction data. And this is my mean absolute error with respect to the prediction data and RMSE. This is fine, right? Now, let's start with some assumptions. But before this, let me also print the r square and adjusted r square, right? So here is my code. See guys, I'm just doing along with you. Please make sure that you also do it and you also practice. So this is my r square. And similarly, I will go and copy this, my print r square. And after that, I will also go ahead and print this specific value, right? So this is my adjusted r square, right? So here, this part also I'm going to print it. Now let's execute. Here you can see 75% I'm actually getting it as r square and 59% I'm getting it as adjusted r square. Okay, and obviously adjusted r square will be little less when compared to this. Okay, and but this is with respect to the test data to just see that how my model is performing well or not. Okay, but again I just have small number of data points, so I'm able to get this. If you have more data points, if you have more dimensions, at that point of time, we also have to check how the data is performing well or not. Now let's go ahead and let's learn something new. These are the assumptions. Like finally, I should be able to find out whether my model is performing well or not. And by seeing these assumptions, we can definitely come to a conclusion that my model will definitely perform well. So the first assumptions after we do the prediction, right? The first assumption is that I will just go ahead and plot my scatter plot. And I will say here I'm just going to give my y test, y prime. Now if I execute this, here you'll be able to see that they will be following some relationship here between the y test and y prime. If there is a linear relationship, that basically means your model has performed well. Okay. Now the next thing that I'm going to do is that with respect to residuals, let's go ahead and calculate the residuals or the errors between y test and y prime. If I take up this residuals, okay, residuals, here you'll be able to see I will be getting these errors, right? These are my errors that I'm actually getting. Now if I plot this residuals, if I plot this residuals with the help of this plot, let's say how do you write this plot? SNS.displot. It is basically present in C1. And if I probably write residuals over here, and the kind of plot that I'm going to take is something called as KDE plot, that is kernel density estimating. And if I execute it here, you'll be able to get something called as a linear normal distribution. So if this kind of curve is basically coming, that basically means yes, the model that you have created is good. Okay. And one final thing that we have to probably take with respect to assumptions is that let's create a scatter plot with respect to predictions and residuals. So if I probably create this plot with residuals and predictions, you'll also be able to see some observation. Okay, so what I'll write, I'll say plt.scatter with y underscore pred, comma, residuals. Here you'll be able to see that follow any pattern. See, this data is uniformly distributed. Okay. Now you may be thinking, oh, the data is very less. No, why you are saying it is uniformly distributed? First of all, let me remove this. Okay, everything will make sense. Uniformly distributed basically means data is distributed everywhere. It does not follow any patterns as such. Here also you cannot see any patterns. When we'll be taking huge data set, in going forward, we'll be doing some projects which will be having many data points. You'll be seeing that this data sets points will be something like this. So this is uniformly distributed. It does not follow some patterns. If I say some patterns, it may follow something like this. Okay, it may follow this kind of pattern. If it follows this kind of pattern, that basically means something is wrong. Okay, something. But if it follows this uniform distribution, we can definitely come to a conclusion that there is no such problem as such. Okay, so yes, most of the things we have covered in this. Now, final thing is that obviously we need to compute the OLS, that is ordinary least square. So again, I'm going to copy this entire thing, copy the y train and x train part, and do the fit. And once I execute it, and if I see model.summary, now our main thing is basically to check whether are we getting the coefficients almost similar. So coefficient over here is 88.2728 and 116.2572. So are we getting that similar kind of coefficients? Finger crossed. Right, so let's go ahead and print it. Where did I print it? So where's the code? Oh, I did not even print it. Amazing. Okay, so let's print the coefficient for my model. So here also, if I probably print regression dot coefficient, here you'll be able to see perfect 88.272 and 116.257. So yes, we've done a fabulous job, and with this formula also we are able to get this. Okay, now in the next video, what we'll do is that we'll take up a problem statement, and let's say that if I have many features, and all of these features have a concept of multicollinearity. Multicollinearity basically means that suppose if I have some input features, okay, I have feature 1, feature 2, feature 3, feature 4. Okay, and with respect to if these two are correlated, 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 then it is fine. Okay, but what happens if these two features are correlated by 95% or 96%? Then what we can do is that since both this feature, if both the features are correlated by this much percent, we can definitely say that almost both the features are almost same. So we can remove one of the feature. But how to do this kind of elimination? We'll try to have a look onto the next project that we're going to do. Okay, so yes, this was it from my side. I hope you like this particular session, and yes, I will see you all in the next session. Thank you. In this video, we are going to discuss about a new machine learning algorithm which is called as polynomial regression. Now guys, already we have covered simple linear regression, multiple linear regression, and I hope everybody knows about the equation. Let's consider an example over here. suppose if I have some kind of a single independent feature, that is x, and single dependent feature, that is y. And let's say if I have some kind of data points, the main aim in simple linear regression was to create a best fit line, right? So our main aim was to basically create a best fit line. And this was specifically to one input feature and one output feature. But if you have more than one input feature, so we basically have to select a plane, right? A 3D plane. Let's say if there is a 3-dimensional points, with respect to x, y, and z, at that point of time, if z is my output feature, then I have to probably create a 3D plane. And if there is more than 3 dimensions, then we probably have to create a hyperplane, right? So that was our aim in this, right? In regression. And obviously the simple linear regression, why do we say it as simple? Because we just have one independent feature. If you say multiple linear regression, that basically means the independent features are more than one. Okay. Now what if my data set is something like this, which is not linear, which does not have a linear relationship? Let's say over here, x is my input feature, y is my dependent feature, right? And if I plot my points here, you can see some kind of curve, right? So this is basically my curve, right? And here there is no linear relationship. So this is a non-linear relationship. I really want to put this point, okay? Non-linear relationship, okay? Now what happens if we try to create a best fit line? Let's say if this is the best fit line over here, then obviously what will happen if we just try to use this best fit line? The error will be quite high, right? The loss value that you're probably going to compute, that is the value between the truth value and the difference between the truth value and the predicted value, that specific error is going to be quite high, right? So obviously we cannot just use this linear regression over here or multiple linear regression in the case of if you have more than one feature. We cannot use this. So we need to find out a way wherein we should be able to catch all this particular non-linear relationship. Or when I say catch, I should be able to identify it. So at the end of the day, let's say I want a line which should be able to capture like this, right? Now, if you're able to capture like this, that basically means for any input point, I will be able to do the prediction. And this will definitely have error less, right? Error will be less. And how do we do this? For this, we will be using something called as polynomial regression. Okay. Now, polynomial regression concept is very much simple. If you already know simple linear regression and multiple linear regression, you will definitely be able to understand polynomial regression. So here, one thing that you really need to focus on is something called as polynomial degrees. Okay, degrees. So if I probably write a simple polynomial equation, just have a look how it will look like. Suppose if I say my polynomial equation with degree is where the degree is 0. Now, when I write degree 0, that basically my equation will look something like this. See, over here, let's say I will start with simple polynomial regression. Okay, so here I'm just going to write it down as simple polynomial regression. I'm just going to write down the equation. Now let's consider and write our simple polynomial regression with degree is equal to 0. So here I'm just going to write degree is equal to 0. So my equation will look like h theta of x is equal to nothing but beta 0 plus, first of all, I'll just write the equation like this, beta 1 x, right? Now, when I say x is equal to 0, that basically means we are not coming at this particular stage yet. Okay, so here, when I say my polynomial degree is 0, understand one important thing. Okay, as we know that our simple linear regression is given by this particular equation. Okay, so if I write beta 0 plus beta 1 into x, here definitely we'll be having a number 1, right? And for this one, we can also write this in this particular format, that is multiplied by x to the power of 0, right? So whenever we write a simple polynomial regression with polynomial degree as 0, we get this specific equation. And I even do not write this because here we are taking this degree as 0. Okay, degree as 0. So if degree is 0, obviously the next term that we are going to get with respect to any input feature, it will not count. Okay, so usually this particular value, whenever we say we are trying to create a polynomial regression with degree as 0, this will be a constant value. Okay, super important. Now see, everything will make sense when I keep on increasing the degree value. Okay, so let's say now my polynomial degree is 1. When it is 1, I will go ahead and write my h theta of x. Now my h theta of x is nothing but this will be beta 0 multiplied by x of 0. Now since my polynomial degree is 1, now I'll go ahead and write beta 1 into x to the power of 1, right? Now this is nothing but this is my simple linear regression, right? Obviously this matches my simple linear regression, very simple, right? Beta 0 plus beta 1 into x, right? So this is nothing but what is simple linear regression, right? So you can basically say simple linear regression with only one independent feature. Here you can say that it is nothing but it is with polynomial degree is equal to 1. Now what happens when polynomial degree becomes 2? Now what will be the changes in this specific equation? Now when the polynomial degree is equal to 2, at this point of time, my equation will basically change into h theta of x beta 0 to the power of 0, beta 1 multiplied by h to the power of 1 plus beta 2 multiplied by h to the power of 2, right? So here you can basically see that now, since my polynomial degree is 2, now the same input feature I took h to the power of 1 and then I use beta 2 multiplied by h to the power of 2, right? And this is with respect to simple polynomial regression. When I say simple polynomial, I just have one input feature and one output feature, right? This is super important, okay? So I hope you're able to understand. So if I have finally a polynomial degree with respect to n, then you'll be seeing my h theta of x will be beta 0 multiplied by h to the power of 0 plus beta 1 multiplied by h to the power of 1, then beta 2 multiplied by h to the power of 3, and then I can still write beta 3 multiplied by h to the power of 3, and finally like this I'll go to beta n multiplied by h to the power of n, right? So this is what is the final equation with respect to simple polynomial regression. And why we are doing this? Why we are doing this? Because as we keep on taking the polynomial values, so let's say if I plot this 2D plots, right? And then say this is my x and y axis, and here you'll be able to see some data points, right? Now what will happen is that, suppose let's say with degree is equal to 1, I know what is the kind of line that I may be getting. I will be getting something like this, right? So this is nothing but simple linear regression. But when I keep on increasing the degree, then what will happen is that, let's say the next line will get created something like this. Okay, let's say this is with degree 1. Okay, since we are increasing the polynomial, now what will happen is that this specific h theta of x or best fit line that we create, as we keep on increasing the degree value, you'll be able to see that it will be able to fit very much properly. Okay, then it will finally be able to fit very much properly. Okay, now what will happen? Let's say if I take degree is equal to some 15, some higher value, then what will happen? My best fit line will start overfitting all these points like this, right? So it is our task, and this becomes an overfitting condition. Okay, it is our task that when we are creating a best fit line, we always need to go ahead and play with this degree values, and we have to select a degree value which will be able to, probably it should not overfit the model, it should not underfit the model, but it should generalize the specific model. Now in this case, the white line that I've actually drawn, I feel that it is generalized the model, right? This is super important, right? So at the end of the day, with the help of polynomial degrees, you're trying to create a model for a non-linear relationship. Here, specifically, you're solving this non-linear relationship. Now this was with respect to only one independent feature. Suppose if I have multiple independent features, then how do I write with degree is equal to 1? So here I have h theta of x, it is nothing but beta 0 plus beta 1 x1 plus beta 2 x2. Let's say I'm just taking two independent features, and this will be with degree is equal to 1. Right? If I said degree is equal to 2, then how my polynomial degree, whenever I say degree, that basically means polynomial degree. Now my h theta x will become beta 0 plus beta 1 x to the power of 1, then beta 2 is already there. So I will keep on writing this one, beta 2 x2, then I will write beta 3 x to the power of 1 whole square, then beta 4 x to the power of 2, x2 whole square, right? So this will basically be my equation, right? Now here I have taken with respect to this, for every input feature, right, I have to also do the squaring of that. Basically, since my degree is 2, so I have to basically do the squaring part of both x1 and x2. And similarly, when degree is equal to 3, forward, I will keep on writing beta 5 multiplied by x to the power of, x1 whole cube plus beta 6 x2 whole cube, something like that. Right? And here you can see that we have two independent features. We have more independent features. We keep on basically using this kind of technique, right? So I hope you got an idea about all these things, and I hope you're able to understand about polynomial regression. Now we'll go ahead and solve a problem with respect to this, and we'll try to see practically also try to implement and show you how we can solve this kind of problem. But again, polynomial regression, main thing is that we are trying to solve non-linear relationship data points with respect to our independent and dependent feature. So yes, I'll see you all in the next video. Thank you. in this video, I'm going to implement a simple machine learning project with the help of polynomial regression machine learning algorithm. What we'll do is that we'll try to create our small data set and we'll make sure that that specific data set will have a nonlinear relationship. And with the help of polynomial regression, we'll try to solve that particular model. Basically, we'll create a model and we'll try to create some kind of best fit line so that it gives us good accuracy when compared to a simple linear regression model or a multiple linear regression model. So first of all, let's go ahead and let's do one thing over here. The first thing that I am actually going to do is that import some of the libraries. Okay, so let's go ahead and import some of the libraries. And obviously, first step is importing libraries, right? And everybody's familiar with that because from now onwards, like whatever thing what are libraries we basically install or import. So here, import NumPy as MP, import pandas as PD, and import matplotlib.pypod as PLT, right? So this is there. And then what I'm actually going to do is that I see the type of data set that I really want to create. Let's imagine that I want to create a data set. Now, whenever I say my data is non-linear, like if I probably create this kind of data with X and Y, so here I can say, okay, it has some kind of linear relationship, right? But if I have some data points which are in this shape, let's say it is in this specific shape. So here you can see that some type of curves are there, right, in this data set. And what exactly this is nothing but this kind of curve in a data set we get basically from quadratic equations. And what is the form of quadratic equation in this shape? Ax square plus bx plus y is equal to 0. So this is a quadratic equation, right? And that is the reason why we use gradient descent in a specific, this gradient descent is also like whatever loss function we use, right? Like MSE. This is also coming from this quadratic equation. So that is the reason we get this. Now what I'll do is that we'll try to create this data point. Okay, like let's say this is my X and Y. And for this, we'll try to see what happens when we create a best fit line like this. And after that, obviously here, the error that we're going to see over here will be quite high, right? Once we create a best fit line. So we really need to create something like this as a best fit line. And this will only be possible with the help of polynomial regression, right? So with the help of polynomial regression, we'll try to see how we can create this kind of best fit line for this specific data set. So let's go ahead and let's quickly try to see, and anything that I probably have to write, I will be writing in front of you so that you will be able to understand. And definitely make sure that you can practice all these things, that you can also consider any kind of other data set which follows this specific pattern. So to begin with, what I'll do is that I'm just going to copy 2 lines of code from NumPy, which will actually help me to create my data set. So here what I've done is that in the X, which is my independent features, here you can see I'm using nt.random.rand. That basically randomly we're going to pick up 100 numbers, okay, in this specific shape, 100, 1, and -3. That basically I just want to add some kind of outliers to this x-axis or x value by by just subtracting with -3. And this you can see this is a quadratic equation, right? Ax square plus bx plus c, right? Plus nt.random is again an outlier. We are specifically trying to add some kind of outlier, okay? So here I can definitely write this is my quadratic equation used, and here you have something like y is equal to 2x to the power of, sorry, it's 0.5 x to the power of 2, right? And then plus there's nothing but 1.5x plus 2 plus outliers, right? So this is the format that we have specifically used in this, okay? And then let's go ahead and plot it. So I've already made sure that let's plot the matplotlib percentile matplotlib inline so that we'll be able to display these images in this Jupyter notebook, okay? So quickly done, right? Matplot, see the spelling, okay? See the spelling over here, your spelling should be absolutely fine. So done. Now if I say plt.plot on my x-axis, y-axis, and let's say I'm going to use some green points just to plot it, okay? And along with this, I will say this will basically be my x labels. I'm just preparing my data set, guys. Nothing so amazing in this because we should definitely try to know how to create our data set just for testing purpose for any algorithm, okay? That will actually help us to see something. So here it says plt.plot. Again, plot is not actually working. So what I'll do is that you can see the data points over here. Not going to use plot, we'll use scatter. Let's see, okay, scatter. In scatter, we don't give like this. We have to assign something like a color. And let's say here I'm giving red. Now here, let's consider green one, okay? Red is too dark. Now the data points that you see over here, obviously it does not have a complete linear relationship, right? Non-linear relationship is also there. You can see this kind of curve, okay? Now we'll consider this particular data set and we will try to probably implement a polynomial linear regression, and we try to see first of all with the help of simple linear regression if we try to implement what is going to happen, and with the help of polynomial how the accuracy is basically going to get improved, okay? So after this, what I'm actually going to do, I'm going to do a train test split. So I write from sklearn dot model selection because I really need to do a train test split. So from sklearn dot model selection import train test split, okay? Then here you have x train comma x test y train comma y test is equal to train test split x comma y comma, here I'm going to specify my test size. Let's say I'm just saying 0.2, and I will be considering some random state. Let's see, random underscore state is equal to 42. Okay, perfect. So let's see what is the error. I think somewhere some error may be there. A random state, perfect. Not a problem. If you are getting an error, don't worry. You just have to fix it by seeing the description. Okay. Then now let's implement a simple linear regression, right? So here from again sklearn dot linear models, whatever we have actually done in the previous class, import linear regression, and here I'm just going to say regression underscore 1. This is my linear regression, so I will just say linear regression, and here I'll be initializing. Perfect. Then finally we will do regression dot fit on my x underscore train comma y underscore train data, okay? And we'll try to execute. Oh yes, you can also do scaling, but already the values that you'll be seeing, right, of x train and y train, it is almost in the basic scale. But if you really want to do, you can definitely do it. See, -2, 1, 0. So whatever initialization is basically done over there, right? It is based on normal distribution itself. Okay. So dot fit on x train and y train, and once we do this, here you'll be able to see this thing. Now what I'll do from sklearn dot metrics, I'm going to import the R2 score, right? And finally, I'll say score is equal to, okay. Now we're going to use the R2 score just to calculate what is the score of the model. And here I'll say y underscore test, comma, and then we can use the regression 1 dot predict, and I will try to predict my x test data, right? So that becomes my y predict, and finally I'm just trying to print the score. And obviously you will be seeing that you'll be getting some error. So sorry, you'll be getting some less accuracy. Why less accuracy? Obviously because your data point is like this. We try to create a best fit line. So obviously you're going to get a bad error, right? So let's visualize this image. Okay, let's visualize this model and how it is created a best fit line. Okay, so in order to do this, what I will be using is that I'll be using a simple plot function to just see that how the plotting is basically happened. So I can basically write dot plot on x train, comma. For the x train, I really need to use my regression model dot predict on my x train data because I'm just trying to see how the best fit line will come for the training data, right? And here I can definitely use some color. Let's say the color is red. Now we can use a dark color. That'll be good. You can actually see it. And along with that, I'll also try to scatter all my x train and y train data, right? So now I'll just scatter this X train and Y train data. Any default color can be used. And apart from that, we'll also be writing plt.x label. So this will basically my X data set. And finally, I'll just say plt.label. And here, this I'm just going to put it as Y. Okay. And finally, I'll just import it. Now, see, matplotlib.pyplot has no attribute label. Y label. I have to use Y label. Now, obviously, when you get this kind of split line, you're going to get a good amount of error, right? Now, let's see how do we solve this problem with the help of polynomial regression. The first thing in polynomial regression is that what we do whenever we have a polynomial regression, right? Let's say I have some data, right? Let's say this is my x data and y data, right? Now, x data is in degree 1, right? So I can probably take something like this. My h theta of x will be beta 0 plus beta 1 into x1. Right now, this is what my model is all about, right? And obviously, with this best fit line, we're not able to get a good accuracy. So what I'll do, I'll say h theta of x, and I'll increase this polynomial degree, and it will become something like this: beta 2 multiplied by x2 whole square. Sorry, it should be x1 only, not x2, because I just have one input features. So we will first of all try with this. If it does not work with respect to this, later on we'll try to create a generic formula wherein we just keep on increasing the degree of this x1 feature, right? Let's say I want to increase this again. This will be beta 2, then this will be beta 3, x1 of 3, right? So here, if I probably just show you, right? If I probably show you, right, over here, see. Okay, so here we will be using, or we'll be increasing the polynomial degree. Okay, so that is what we are going to do it now with respect to all my features. I really need to increase the degree of the features and try to see whether my line will fit or not. Later on, we'll try to create a common function which will do all this specific task. Okay, now how do I do this? How do I probably create a degree for 2, 3, 4, right? So for that in scalar, we have something called as, so here I'm just going to say, let's apply. So here, let's apply polynomial transformation. Okay, and here what we are going to do is that we are just going to write from scalar dot preprocessing import polynomial features, right? And finally, I will execute this. And here you'll be also be seeing that I'll write poly. Now here this polynomial features is used for the transformation, like to increase the degree. Suppose if I have just x1 variable, if I say I want to use a degree of 2, that basically means x1 square will also be created as a new feature, right? So here I will be writing polynomial features. And finally, I will be using degree is equal to 2. And here, let me also say there is a parameter which is called as include bias. I'm also going to include the bias so that 1 will also get created, first variable, right? So what do I mean by 1? Let's say I'm just going to write this equation. Let's say this is my first equation. I'm going to use this. I'm going to wrap this. Okay. Let's say my h theta of x is nothing but it is beta 0 plus beta 1 into x1, then beta 2 into x1 whole square. So if I say degree is equal to 2, that is meaning x square is created. Include bias basically means here it will be multiplied by 1. Okay. So we're going to take this 1, we're going to take x1, and we're going to take x1 square for our model training purpose. All these things we'll try to show it to you. Okay. So as soon as I probably transform this, you'll also be able to see that. Okay. Now the next thing is that what I will do after doing this, I will say x underscore train underscore poly, and here I'll be saying poly underscore fit underscore transform, and here I will be saying x underscore train. Okay. And similarly, x underscore test underscore poly will be nothing but poly underscore fit underscore transform. Okay. On my x test data. Why do I write only fit underscore? Sorry, this should be not fit underscore transform. It should be poly dot fit underscore transform, and this should just be dot transform. Okay. So probably I just written underscore. That should not happen. But again, I've already discussed why do the difference. The difference between fit underscore transform and transform. I just want to apply this techniques in my test data. Okay. I do not want to make sure that again I create all the features again. So that is the basic difference over here. Why this is done? Because I don't want to know the information with respect to my test data. My test data should be completely new. So whatever technique is getting applied over here, that same technique with that same value of x train will get applied to the x test. So in short, what will happen if I just transform this automatically for this particular feature? Degree 2 will also get created like x1 square. For this, in the same mechanism for this also it will get created. But there's a minute difference between fit underscore transform and transform. Fit underscore transform makes sure that the main data validation part from where we are actually trying to transform is my training data. No reference of the test data is basically taken. Okay. So this is super important for everyone. You really need to understand this. So let's go ahead and execute this. Now here you can see, now if I probably try to execute my x underscore train underscore poly, here is your data. So this became my 1, this became my x1, and this became my x1 square, right? If you don't believe me, open up the calculator. Let's see what I get from the calculator, right? Suppose if I say minus 2.7488, okay, whole square. So it is nothing but 7.5559, right? Which is approximately equal to this if I probably take up all the data points. So this is my bias, this is my x1 feature, this is my x1 square, right? So degree polynomial degree is 2. Okay. So this is what I've done, and similarly you can also check it for x underscore test or underscore poly. Now once you have this particular data set, all you have to do is that try to apply the same linear regression whatever we did, right? So I'm just going to copy this because it is almost the same thing, and then we're going to probably see it. Now here you can see that since the batch parameter is already included, we've taken linear regression, I've used x underscore train underscore poly, y train, and then we did a prediction. And right now, before the score was what? The score was 0.62, right? Now you see the score. Whether the score will improve or not? Yes, I think it will improve. Now you're getting 0.9393, which is quite amazing. Now you may be excited, Krish. How's the graph getting created? You can obviously see from this model, right? If you probably see one more thing, if I write regression dot coefficient, here you'll be able to see 3 coefficients. One is 0, one is 1.5, one is 0.5090. Why? Because I have 3 features now, right? Before I just had 1 feature, right? This is super important to understand. But with respect to intercept, I will just be having 1 feature. So here I'm just going to write intercept, I will just be having 1 feature. Perfect. So this is quite amazing, guys. We are able to get it. Now comes the main part. You can obviously do the prediction. You also seen that with the help of prediction. Also when I'm seeing it is coming at 93%. Now let's take some new data and let's try to plot this. Or just before this, let's plot this one. So I'll say plt.scatter and let's plot my x train. Okay, x train, comma the prediction that I did for, or I can basically write something like this: regression. This regression is basically my polynomial regression. Okay, dot predict. Okay, and I am going to predict my x underscore train underscore poly. Okay, and once I execute this, here you can see this, right? See this curve. So this is my best fit line that is coming for all these data points. And if you also want to see the other data points, all you have to do is just write plt.scatter. Okay, and here you can probably take, x underscore train, y underscore train. Okay. Now once you plot this, now see, for all these data points, this is how your best fit line comes. So that's the reason why you're getting such an amazing accuracy. Okay, such an amazing accuracy. But now the question arises, Krish, what if I make this degree value as 3? Just let's consider. Okay, so let's see if I make this degree value as 3, then what will happen? We also need to think about that, right? So if I make this degree 3, will my accuracy keep on increasing? Again, I'll copy this. I made it as 3, and then I will probably just try to see x train first of all, right? So if I write x train underscore poly, what do you think we'll be having? And now I have 4 features, right? 4 features. Now this is nothing but, it is just imagine that here you're just trying to find out the cube of that, right? This to the power of 3, right? So same thing, here you're able to create. Now what I'll do, I will apply the same thing and let's see whether the accuracy will increase or not. So here, for degree polynomial, I'm getting 0.9343. Before I used to get how much? Okay, just a second for this x train poly. So here x train poly, y train, this is my x train. Yeah, I'm getting almost same accuracy, somewhere around 0.9343, right? So before that, what was the accuracy that I was getting over here? After applying this, see the accuracy is downwards here, 0.9393. So just a minor difference, right? But yes, I can definitely say that the previous one was working well. So I may probably just consider degree is equal to 2. But sometimes you may be having a data set that will be having too much different type of non-linear relationship. Now let's go ahead and try to see the prediction for the new data. Okay, and this is super important, guys. Prediction of new data. Okay, new data set. Now, first of all, what I'm actually going to do, I'm going to probably take a data. Okay, take a data. So as soon as I get a new data, let's say I'm getting this new data with lens space this, and I'm reshaping to 200, 1. Let's say this many data points I'm actually coming as a new data point. First step I'll do poly dot transform on this new data. So here I will be getting a new polynomial feature. So in short, if my degree is 2, okay, I will be getting 2 features, that is 1 x1 square. If I probably take 3 when I was actually creating my polynomial features, then it would have been how many degree of polynomial would be 3, right? Now in this particular case, if I probably go and execute my x underscore new underscore poly, here obviously what you'll be able to see, you'll be able to see 4 features, right? Because the degree of polynomial is 3. 1 is the bias, right? And remaining all you're able to see over here, right? Very simple. Now what we're going to do, we're going to just use regression.predict. Now this is super easy, super important. So I'm just going to copy and paste the code. Plot x new, y new, x train, y train, x test, y test. Y new is the predicted for the new data points. And when I'm predicting this, I'm also plotting x train, y train, and x test, y test. Once I see this, guys, see this curve, amazing, right? I'm actually getting this entire predictions along with the green points here and there and blue points here and there, right? So this is how we are able to see this. So here I'm just going to write new. This is my training points, yeah, obviously, and new predictions right over here. Right? So this is how we are actually able to see. Right? This is for the new data set. Now see how my model has got trained for this kind of similar data. Okay, so this is so super important with respect to this. Again, you can try with different polynomial degrees, whichever gives you the best performance. You can basically take it out. Right? So I hope you like this particular video. And yes, this was it. In this video, we have focused on implementing polynomial regression. Yes, I will see you all in the next video. Thank you. So guys, in our previous video, we have already implemented the polynomial regression, and here you could see that we could have assigned different degrees, polynomial degrees over here, and we tested that for which model it is being able to give a better result. Now in this video, what I'm actually going to do is that I'm going to introduce to something called as pipelining concept. Now in pipelining concept, all we have to do is that I will create a generic function in which whatever degree you assign, you'll be able to see that what kind of curve it will be fitting to for a new data set. Okay, so for using the pipelining concept, and probably this is the first video with respect to pipelining concept. In the upcoming videos, we're going to use a lot of pipelining concepts as we go ahead. So here, first of all, what we're going to do is that I'm going to create a poly regression function. Here we initially take the data set. I will not be using transforming over here. Okay, then whatever in this particular function we are creating a degree, right? But this degree is passed by the front end, right? So whatever degree you really want to play with the polynomial degree itself, you can actually pass it. So inside this polynomial features, I'm going to use that specific degree and say include bias is equal to true. So automatically what it will do, it will be able to transform our features with respect to that. And then I'm also initializing linear regression. So every time, whatever degree I'm actually providing, it will be trying to create a new features, and for that it will try to apply the linear regression. Now both this needs to be added in the form of pipeline, one after the other. So first will happen poly underscore features, and the second will basically we are going to apply a linear regression model, and we're going to fit with respect to this particular data. So in order to do that, whatever pipeline we have imported, right, we're going to combine this inside this pipeline. So here you can see the first thing is poly features. You can give this whatever name you want, but make sure that you provide this in form of key value pairs. So over here should be the objects, whatever objects you're initializing. So in this particular case, poly underscore features is initialized over here, and linear underscore regression is initialized over here, right? And then we combine this. All we have to do this dot fit. So once we do a fit on x train and y train, what it will do, whatever degree it is basically done internally, it will transform this particular values based on this degree, right? And then finally, I can use this particular model to do the prediction for our new data. So whenever I pass my new data, what it will do, the first step of this poly regression will be that it will be creating this particular features by using a specific degree, right? Now in this particular case, the degree, whatever degree you're assigning it over here, with respect to that specific degree, it will get created, right? And then finally, you can do the prediction on the new data with the help of linear regression, which is the next model in the pipeline. And finally, here you can see I'm plotting the data based on my x new and y train new and x train and y train, x test and y test. Okay. Now let's go ahead and execute this, and overall you'll be getting an idea. First, let's say I'm going to try with degree 1. So with degree 1, you can see that I'm getting a best fit line. Obviously, the error will be high. Now if I do with degree 2, here you'll be able to see that yes, it looks good. The curve is becoming better, and the error will also get reduced. Okay, now let's go ahead and execute this, and overall you'll be getting an idea. First, let's say I'm going to try with degree 1. So with degree 1, you can see that I'm getting a best fit line. Obviously, the error will be high. Now if I do with degree 2, here you'll be able to see that yes, it looks good. The curve is becoming better, and the error will also get reduced. Then if I try with degree is equal to 3, here you'll be able to see that okay, I'm able to get a better one now. And similarly with degree is equal to 4, here you'll be able to see this. Now as you increase the degree, let's say if I'm using degree 10, it will start overfitting. Now here you can see that it is trying to overfit each of the data points. These green points are basically the green points are my test data points. The blue points are my training data points. Now as you go ahead in increasing the polynomial degree, it will try to overfit each and every data points. So it is our responsibility to make sure that whatever degree we are selecting, it does not overfit. Now in this particular case, someone asked me, should we use 15 or should we use 7 or 6? So here I will just again suggest that we should try to use 6 because it is not trying to overfit the model. Okay. So this was about the pipelining concept. So here in short, what we have done is that we have combined two models, that is polynomial features and linear regression in a pipeline, right? And initially, whenever we take a data, first of all, with the help of this poly features, we'll be getting all our features over here. So as soon as I write this polynomial regression, this entire pipeline dot fit on x train and y train. In short, what it is going to do is that first step, it is going to create all the features by using this, and the second step is that it is going to do the linear regression fit with respect to the model. So finally, here you can see when we do predict also, with the help of predict also, first of all, it will try to create this polynomial features. That is all my features, and then it will try to do the prediction. Okay. So this here you can basically say it is basically doing. One thing is that it is the first step, it is basically creating your polynomial features and then fit of linear regression. Okay. So this is super important. We will probably be using this a lot as we go ahead. Okay. So yes, try it with different parameters and degrees, and then try to see that which model is actually performing well. Fine. I will see you all in the next video with some more amazing examples. In our previous video, we have understood the in-depth maths intuition behind linear regression, and we found out that okay, we really need to find out the best fit line. Along with that, we also saw what is the equation of the best fit line. S theta of x is equal to theta 0 plus theta 1 multiplied by x. This x is just my single independent feature. Suppose if I have many independent features, it becomes a multiple linear regression. And with respect to this was the cost function that we used, right? The cost function was 1 by 2m summation of I is equal to 1 to m s theta of x of I minus y of I whole square. This s theta of x of I is basically my predicted point, and this is basically called as mean squared error. This is what is the cost function, mean squared error. And we also found out that whenever we try to plot our coefficient with j of theta, we are able to see something called as gradient descent. Our main aim is basically to come to this global minima. Okay. Now,
Now we are going to understand some series of algorithms, which is called as ridge regression, lasso regression, and elastic net regression. And we'll try to understand why do we use ridge regression, lasso regression, and elastic regression. In this video, we're going to discuss just about ridge regression. In the upcoming videos, we'll cover all the other algorithms. Now let's start with something called as ridge regression. So here I'm just going to write it down, which is called as ridge regression. Now let's say, guys, I have a single independent feature. Let's say I have something like x and y. Okay, and if I consider that I just have two specific data points in my training data set. Now in this particular scenario, obviously if I apply linear regression, this is going to pass through the best fit line. So when it is passing through, when I'm actually creating this best fit line, it passes through both these particular points, right? So this is my best fit line. Now when this is my best fit line, obviously you can see that the error is 0, right? Because there is no such difference, right, between the predicted and the real point. So in this particular scenario, I can definitely say this model is overfitting. Now what does model overfit basically mean? Okay, now with respect to this training data, you can see that the accuracy is very high, the error is very, very less, right? Or error is almost 0, right? But if I try to add some more new test data, let's say these are my new test data that I'm just going to add over here. Now when this new test data is basically getting added, you can see that now the error basically increases, right? The error with respect to this new test data is basically increasing. So this is basically a problem of overfitting. So here, what is actually happening? Here, overfitting is actually happening. Now, what does overfitting basically mean? Because I've already covered this. Let's say with respect to our trained data, my accuracy is very, very high. Let's say my accuracy is 99% or 100%. Okay. And whenever I talk about trained data, at that point of time, we use something called as bias. In this scenario, I will be saying low bias. Okay. Similarly, with respect to the test data, when my accuracy is actually low, see, for the trained data, the accuracy is high. But for the test data, over here, the accuracy is low. And in this scenario, whenever we use test data, here I'm actually going to use something called as variance. And in this scenario, it will be high variance. Okay. So this is the problem that is basically happening, right? It is overfitting in this scenario, right? Now, how do I reduce this overfitting? I should definitely find out a way to reduce this overfitting. And for that specific scenario, we use called as ridge regression. Because in this scenario, I know my best fit line is passing through both the points. Okay. And always remember, guys, if you get an accuracy of 100%, right? Definitely consider it that the model is overfitting. You should never get the training accuracy as 100%. Just imagine this. That basically means the model has been trained very well on the training data, right? Now let's understand what exactly ridge regression is all about. Okay. Ridge regression is also called as something called as L2 regularization. L2 regularization. And this is used to reduce overfitting. Suppose my linear regression creates some overfitting, then in order to reduce that overfitting in the linear regression, we use ridge regression. Okay, so we can just consider ridge regression as a new algorithm which will actually help us to hyperparameter tune the linear regression. Okay, now let's go ahead and let's understand how does the cost function with respect to ridge regression look like. So here I'm just going to write down the cost function. Initially, if I consider the cost function of linear regression, I hope everybody knows 1 by 2m summation of I is equal to 1 to m h theta of x of I minus y of I whole square. Right? So this is the cost function of the linear regression. Now in this particular case, see, when I create this best fit line, it automatically passes through both the points in my training data. Now when this is the scenario, obviously my entire cost function, this will become 0, right? Now when it is becoming 0, that basically means my model is overfitted because it is passing through all the points perfectly. Now in order to remove or add some parameters, that we have to make sure that this never becomes 0. So what we do is that in ridge regression we add two parameters. One is lambda, and the second one that we try to add is summation of I is equal to 1 to m slope square. Okay, so this lambda that you see is a kind of hyperparameter. Okay, and I'll try to show you the relationship between lambda and slope and how this is basically reducing the overfitting. That also we'll try to understand. Okay, now see over here, if I'm trying to add lambda and slope square, let's say lambda value is 1. Okay, now when this value becomes 0, I have to make sure that this never becomes 0, because if this becomes 0, that basically means this best fit line perfectly passes through all the points, and this should not happen. So my cost function should definitely know that this is not 0 at this point of time. So what we penalize this value by multiplying one lambda value. Lambda value I've just initialized as 1. Okay, and then I'll try to show you the relationship between lambda and slope. So after this one, let's say my slope, in this particular case, my h theta of x is nothing but theta 0 plus theta 1 x1. Okay, let's say I just have one input features. So summation of I is equal to 1 to m basically means how many number of coefficients or slopes are there. We're just going to do the summation of whole square like that. So here I'm just going to do theta 1 whole square. Now let's consider theta 1 any positive or negative value. Okay, so that basically means we are never going to get 0. We will be getting greater than 0, right? In this particular scenario, what will happen is that my model training, the best fit line will just not stop over here. Then it will try to find out another best fit line like this, or it will try to find out another best fit line like this, such that my cost function is minimal. Okay, so in this specific way, when I am specifically adding these two parameters, that is lambda and slope square, the situation is going to be in such a way that we are never going to get a best fit line that passes exactly through all the training data points. Okay, so this is how ridge regression is making sure that the overfitting will not happen. But one very important interview question that may come: what is the relationship between lambda and slope square? Okay, and for this, let's draw that same curve that we discussed, with respect to the simple linear regression. And this specific curve is with respect to theta, that is my slope, and cost function j of theta. Now in this particular case, if you know that we will be getting this kind of gradient descent, right? Let's say I'm just going to put some points over here, like point. Let's say this is 0, this is 0.2. This is 0.4, this is 0.6, this is 0.8, this is 1.0, and this is minus 0.2. Okay, let's say this I have just plotted with respect to theta and the cost function. Okay, with respect to this gradient descent. Now just understand, when lambda is equal to 0, see, when lambda is equal to 0, that basically means what? I will just have the same linear regression cost function. Okay, if lambda is equal to 0, this entire value will be 0. So that basically means I'm not applying ridge regression over here. Whenever I apply ridge regression, I'm basically using this equation at the end, right? So when lambda is equal to 0, I'm just having this linear regression over here, the same cost function of the linear regression. This is fine. So this is basically my global minima, right? I hope this is my global minima. So let me say that, okay, this is my global minima. Okay, and this is when your lambda is equal to 0. Now let's say I increase my lambda to 10. Now what will happen is that I will get a new line which will look something like this. Okay, if you probably try to plot theta, I'm just trying to show you how the plotting, how the graph will look like when we increase our lambda. You can definitely check out by playing with different values. But once you increase the lambda value with respect to this theta, right, what will happen is that now this lambda value is basically getting assigned some value over here, that is 10, and when we multiply with the slope square, I will getting a new gradient descent, and now you'll be able to see that my global minima has changed. When my global minima has changed, so let me just draw this line properly so that you will be able to understand. So let's say my lambda is equal to 10. So what will happen is that when the lambda value increases, I will be getting another line which looks like this. So during when lambda is equal to 10, I'll be getting a different gradient descent. And now, what is the difference between this gradient descent and this gradient descent? Here you can definitely see that my global minimum has shifted. It has shifted from here to here, right? Similarly, my theta value has got reduced. Okay, it has basically shifted from here to here, right? This particular is with respect to this theta value. Now, similarly, if I keep on increasing my lambda value, let's say I increase my lambda value again. So with respect to lambda is equal to let's say 30, then I'll be getting another line which will look something like this. And now this will again get shifted. This global minimum will get again shifted somewhere here. So in short, what is happening? Theta value is again getting reduced. And like this, it will keep on happening. But always remember, in this particular scenario, it will never be zero. Okay, it will never be zero as I keep on increasing the lambda value. So lambda over here can be considered as a hyperparameter. Okay, so lambda can be basically considered as a hyperparameter. And if you really want to know the relationship between lambda and slope, you can definitely say when lambda is increasing, your slope is decreasing. How slope is decreasing? Because we are going on this left hand side, right? You can see from 0.6 to 0.4, 0.2, like this, it is going on the left hand side. So this is the exact relationship between lambda and slope. But why we are trying to understand this particular relation? Let's say I have a multilinear regression. Okay, let's say I have a multilinear regression which is like this: theta 0 plus theta 1, x1 plus theta 2, x2 plus theta 3, x3. Let's say I have 3 coefficients and 3 independent features. Let's consider that theta 0 is equal to 0. If I say theta 0 is equal to 0, then what does this basically indicate? This basically indicates that it is passing through the origin, right? The specific line. This line is basically meeting the y-axis in the origin. This I have already discussed. Now let's consider that my theta 1 value, I'm assuming, okay, I got somewhere around 0.52 x1. I'm just assuming theta 1, theta 2, theta 3. Let's say over here I got probably 0.48, and here I got probably 0.24 x3, right? Suppose I got these values, and obviously I have theta 0 as 0. If I don't want to even take this, let's consider some different theta 0 value. So let's say this is 0.34. My intercept is 0.34. Now in this particular scenario, what will happen is that if I apply ridge regression on this cost function, then this value will get reduced. This coefficient will get reduced, but it will never be 0. See, what does this value basically indicate? 0.52 of x1. This basically indicates that with the unit movement in x1, right? With the unit movement in x1, what is the movement with y, right? So here you can see 0.52 movement with respect to y. Similarly, with the unit movement with x2, what is the unit movement with respect to y? So here you can see that it is 0.48 unit movement with respect to y. I'll not say unit movement, but 0.48 movement with respect to y. That basically means if x1 is moving by 1, then y will move by 0.52 in this particular case. If x2 is moving by 1, then 0.48 y will basically be moving, right? So this is what it basically indicates. Now, if there is too much movement with respect to unit movement, if there is a unit movement, that basically means these features are highly correlated with the output feature, right? Highly correlated with the output feature. But here you can see that with respect to x3, we have a very small value 0.24, right? Even though we have a very small value, what will happen is that if I try to make a movement, unit movement with x3, there will be a small unit movement with respect to y, right? Somewhere around 0.24. But when I apply ridge regression to this equation, I may get something like this. See, I may get something like this, where this value will get reduced. This value will get reduced. Let's say it will get reduced to 0.40 x1. This may be 0.38 x2. But when I see this value will also get reduced, 0.14 x3. But here you can see that since this value has now a very small coefficient, this won't impact much change in the movement of the specific line. Okay, because in this particular case I have 3 coefficients, so this will then become a plane. This may become a plane entirely, right? The line that we are specifically using for division, right? So here you can see over here, since this value is very small, this won't impact the best fit line by a major movement. Only a smaller movement will basically happen. And always remember, this value will never become 0. That is what ridge regression basically does. And how it is reducing overfitting? Because it is reducing the impact by the coefficient, by reducing the coefficient of the feature that are not directly correlated with the output feature. Now here you can see x3 is hardly correlated by 0.24. And it is trying to reduce this particular value also. And when it reduces this particular value, that basically means this will not have much impact on the best fit line, right? So I hope you are able to understand. I hope you are able to understand the relationship between lambda and slope. So please just try to go through this video again. This all maths you really need to know, guys. Then only you'll be able to understand what things are actually happening. Now in the next video, we are basically going to discuss about something called as lasso regression. So right now we have completed ridge regression, and we'll try to understand what is the difference between ridge and lasso, and then finally we'll go with elastic net. Thank you. We have already understood about ridge regression, which is also called as L2 regularization. The super important interview question may come that why do you use ridge regression? You basically have to say about it is basically used to reduce overfitting. Now in this video we're going to discuss about lasso regression, and lasso regression is also called as something called as L1 regularization. And why do we specifically use? We specifically use for a very important work that is called as feature selection. Now, how do we do feature selection and all? Let's discuss about this. Now in lasso regression, we just need to focus more on the cost function. So here the cost function is nothing but it is 1 by 2m summation of I is equal to 1 to m, and here obviously you have something called as h of x of I, which is my predicted point y of I. Along with this, now we are going to add 2 more parameters. One is lambda, and the second one is something called as summation of I is equal to 1 to n, not slope square, but it should be magnitude of slope. Now, with the help of this specific equation, we will try to do some feature selection. Feature selection basically means the features that are not that important will automatically get deleted, and features that are very important will be considered. Now, if I try to show you the relationship between lambda and this slope, okay, with respect to this specific cost function. So suppose if I try to draw this cost function over here in the right hand side with respect to theta and j of theta by using this cost function, obviously the first one, if your lambda value is 0, I will be getting a normal curve, right? Normal gradient descent curve. So let's say this is my 0, or so let's say this is my, I'm just going to use this over here, 0, this is minus 0.2, and this is 0.2, 0.4, 0.6, 0.8, 1.0. Okay, so if I try to draw this kind of curve, this curve is called as gradient descent curve. With lambda is equal to 0, I'll be getting this kind of curve, right? And this is obviously my global minimum. Now what happens when my lambda value will increase? Then I will probably get my another curve which will look like this. Okay, and let me just draw this, and then everything will make sense. Okay, and then I may probably also get one more curve which may look like this, and finally I may get one more curve which will look like this. Okay. Now, what is the difference between this curve and the previous curve when my lambda value is increasing? Let's say this green line is basically when lambda is equal to 10, this is lambda is equal to 20, this is lambda is equal to 40. Let's say. Okay. Now, in this scenario, what happens is that obviously, as I increase my lambda, my theta value is decreasing. But you will be seeing that after one point of time, my theta value will become 0. Okay, so this is nothing but this is basically becoming 0. So in short, my coefficient is actually becoming 0. Now what happens if my coefficient actually becomes 0? In short, we are actually trying to remove that specific feature, right? So let's say my h theta of x is this specific equation, theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. Let's consider that I have 4 independent features. Let's say my theta 0 is 0.52. My theta 1 that I have probably computed by creating the best fit line is somewhere around 0.65 x1. This is 0.72 x2. So this is 0.34 x3, and this is 0.12 x4. Now in this particular scenario, you can see that x4 is the feature that is not much correlated with the output feature. That is with respect to h theta of x, because here we have a very small coefficient that is 0.12. So after we apply over here lasso regression, since this feature is not that important, what it will do is that it will try to reduce this coefficient to something like 0, right? So 0 multiplied by x4 will actually become 0. So this will entirely become 0, and this all value will get reduced by a smaller number, 5.1 x1, because this is directly correlated, right? So this may be x2, this may be 0.14 x3, like this. So in this way, you can see that this feature is being removed, and we have not used this particular feature, or this coefficient has become 0, because this feature is not that important, right? So this is what basically indicates once we add this specific term in the cost function, right? Once we add this specific term in the cost function, we can see that what is the relationship between lambda and slope. So here, obviously, your theta value is becoming less, but at one point of time, this will become 0. That is, your theta value will become 0. So the same thing is basically happening over here, which all features are not that much correlated. And if it is not correlated, then obviously it will be having a small coefficient value. So after we apply lasso regression, this will actually become 0. And by this entire feature is getting removed. And remaining all features is basically used to find out the best fit line, right? So this is the importance of lasso regression, right? And when we do use this, suppose if I have hundreds and hundreds of features, right, I should definitely go ahead and use lasso regression, because automatically it will be able to find out features that are not that highly correlated. It will just try to remove it because it is going to make the coefficient to 0, right? Similarly, when should we use ridge regression? It is very simple. Whenever overfitting condition basically happens, when your training data accuracy is very, very high and your test data accuracy is very, very low, this basically is an overfitting condition. So we should basically try to apply ridge regression in this particular case, right? Now coming to the next one, which is super, super important. What is elastic net, right? Elastic net is nothing, guys. It is the combination of both. So let me write this. With respect to elastic net, it is a combination of both ridge and lasso. So here, with the help of elastic net, what all things we do? First of all, we try to reduce overfitting. And the second one is that we try to, along with overfitting, what we do, we also do feature selection. So if I combine both ridge and lasso together, that actually becomes a elastic net. So what will be the cost function that may look like over here now? So I may basically write my cost function, which will look like this: 1 by 2n summation of I is equal to 1 to n, and this will be y of I minus y of, I'll not say y of I, but I'll say h theta of x of I, okay, minus y of I whole square, plus, and we can basically use, for reducing overfitting, what do we use? We use lambda 1, and this lambda 1 we can basically multiply with summation of I is equal to 1 to n, and this will be my slope square, okay, and plus lambda 2, summation of I is equal to 1 to, I should not write n, instead I can also write m, okay, because m basically indicates all the slope points, okay, so this will be slope. So what is basically happening? This reduces overfitting, okay, and this reduces, this actually helps us to perform feature selection. So this is for reducing overfitting, and this is for feature selection, right? So by this, we are trying to solve both the problems. Suppose if I have a model that is overfitting and it also have a lot of features, then I can directly use elastic net regression. Now, why do we learn all the series like ridge, lasso, and elastic? In short, we are hyperparameter tuning the linear regression, okay? So hyperparameter tuning the linear regression, right? So we are basically hyperparameter tuning it. So that is the main reason why we are specifically using it. Okay. So yes, this was a series with respect to the regression. Linear, whenever you're using linear regression, you also need to think that when you should use ridge regression, lasso regression, elastic regression. And I've seen many people asking different kind of interesting questions with respect to this. Most important is what is the relationship between alpha and slope with respect to ridge and lasso. That both I've actually shown it to you, and how it performs feature selection and how it performs, how it reduces overfitting. Both have been discussed. So yes, let's continue. And in the next video, we're going to learn many more algorithms going ahead. Thank you. In this video, we are going to discuss about different types of cross-validation, and we'll also understand why cross-validation is actually used. Now, as you know that, guys, you obviously have some data set. Let's consider that you have some data set over here. And this specific data set, initially, whenever we train a machine learning model, first of all, we divide this data set into two parts, okay? The first part is something called as training data set, right? And the second part, which we normally use, or which we normally call, is something called as test data set. Now, 2 points I'm going to note it down over here. With the help of training data set, we will be training our model, right? So for training our model, we will basically be using this training data set. Along with this, the second point that I really want to mention is that for hyperparameter tuning also, we specifically use our training data set, right? Now, when I say how do I do hyperparameter tuning, there are various ways like grid search CV, randomized search CV and all. And you may be considering, Krish, how training our model with the help of training data set and even hyperparameter tuning. Over here, what we do is that we further divide this data into 2 more parts. And this is basically called as train and validation, right? So we split this data set more into train and validation, okay? And with the help of this validation data set, we basically, try to hyperparameter tune the model. So here I'm going to write it as validation data set, okay? So till here, I hope everybody's clear. But once we divide from this training data set into train and validation, in short, we're splitting this data set. So while splitting this, here specifically this training data set, my model will get trained and it will be validated with the help of this validation data set. And when we are validating it, in short, we are also hyperparameter tuning it. That basically means we'll play with multiple parameters. Now let's say initially I just have 1,000 records, okay? And let's consider that I'm using the 70% split and 30% split as my train and test split. This data that is present will only be used by my model to check the performance. So to check the performance of my model based on new data. Okay, based on new data, I will be using this test data. This test data will never be shown to the model at any point of time. Only after the model is trained completely, validated completely, then only this new test data will be shown, and then we'll check the performance by seeing a lot of performance metrics, let's say accuracy, precision, recall, R square, in case of R2 score, in the case of regression problem statement, mean absolute error, mean square error, many different performance metrics which I have already discussed. Now let's go ahead and focus on this part where we split our data set from this training into train and validation. And for doing the split, we can apply something called as cross-validation. And why do we do this? Because understand, if I try to do a split of training into this 2 part, that is train and validation, there is an important parameter which is called as random state. And as we change this random state value, you'll be seeing that we will always be getting a separate training data and separate validation data. So let's say on one of the split, I got 85% as my accuracy. In the other split, I may be getting 92% accuracy. Or in the other split, I may also get my accuracy getting reduced, like somewhere around 78 or 75. So this kind of scenario will always happen. And as a data scientist, we should be able to say that my model is probably giving an average accuracy of this much or of some specific value. And for that specific thing, we'll be using cross-validation. Now, there are different types of cross-validation which we usually use. Let's discuss about the first cross-validation. The first cross-validation that I would like to discuss about is something called as leave one out cross-validation, which we specifically say CV. And the short form is, like, if I really want to use it, we will basically be writing it as LOOCV. Okay, leave one out cross-validation. Now let's understand this. In this cross-validation, what happens? Okay, you have to understand this word, leave one out cross-validation. So let's say currently in your training data. Now when I say training data, I'm basically talking about this specific data, right? This part. Because this split is obviously required. We're never going to use the test data. From this data, so if I go down this training data, let's say the number of records are 500. Okay. Now further, I really need to split this data into training and validation data. So with the help of leave one out cross validation, what will happen is that we will be taking this 500 records, and out of all these 500 records for the experiment one, when I say experiment one, that basically means, let's say my cross validation, right now I'll not write cross validation. Let's say for my experiment one, the first record, one record, this will be put in my validation part. Okay. And remaining will be my training data. Right. And my model will get trained on this training data, and it will be validated by this validation data. So it is basically going to get some accuracy based on this particular validation data. Now, similarly, in experiment two, what will happen is that the next record that you will be having will be taken as your only one record, right? Only one record. This record will be your validation. Okay. And remaining all will be your training data. Right. This will also be your train. This will also be your train. Right. And then again, you may get some different accuracy. Now, similarly, based on the data size, you will be seeing that we have to perform that many number of experiments, because at the end of the day, my validation data size is only one. Right. Now, in this particular case, this will basically be my training, and this will basically be my validation data. And again, this will be my accuracy 500, right? Now, obviously, what are the disadvantages with respect to this? This will be my experiment 500 because I have 500 records. Now, obviously, what is the disadvantage of this? If you're just taking one out cross-validation at every experiment that we perform, we will be taking only one record as a validation data, and remaining all will be a training data. And obviously, for performing this much, as the data set size increases, the complexity of training the model also increases, right? Complexity of training the model also increases, because if I have 5,000 records, let's say, then I have to probably perform 1,000 experiments and to make sure that each and every record is passed, and I'll be able to then calculate the average of all this accuracy. So obviously, this is not very good technique, and you know that this technique is nowhere used right now. In some of the cases, we may use it. Okay. Now, the second major disadvantage over here is that this model obviously leads to overfitting. Now, what does overfitting mean? Overfitting basically means, with respect to our training data, since we are taking the entire training data, my accuracy is very high, right? Here, the accuracy is very high. Now, since my test data is very small, well, I'll not say test data here, I'll say validation data, right? Since the validation data is very small, right, then obviously the accuracy will keep on decreasing, right? And when we test the same model with our new test data, then my model performance will go down, right? Model will not perform well, so the accuracy here will go down. So this is a major disadvantage. Usually we say overfitting, wherein your training accuracy is high and your validation accuracy is less. That basically means it is perfectly fitted training data, and obviously because the training data size is quite huge. Okay. Now, similarly, the second type I can name it over here as leave P out cross validation. Okay. So here, instead of 1, you set some p value. Your p value can be 10, your p value can be 20, your p value can be 30, and this can be selected as a hyperparameter. Okay. The same process, everything is same. Okay. Now let's go ahead and understand the third important type of cross validation. And this cross validation is basically called as k-fold cross validation. So I will go ahead and basically write k-fold cross validation. Okay. Now let's say if your data set is size is 500. Okay. Let's say the total data set that you are present in the training is 500. Now from this training, I need to split this into train and validation. And I will say let my k value be 5. Okay. The total size of the data set, which is mentioned as n, is 500. Now what will happen is that we will try to first of all find out cross validation. How many different experiments we need to perform. Now in order to calculate, I will just divide 500 by 5, and here you'll be able to see 100. Okay. So this should not be cross validation, but this should be your test size. Okay. And when you calculate the test size, how I'm calculating the test size, the total number of records divided by 5. Let me write it again, so that this will be a super important point for you all. This, I'm trying to calculate my test size, and this is nothing but 500 divided by 5. And here you'll be seeing 100 records. So this will be 100 records. So what will happen is that in the experiment 1, which we also say cross validation equal to 1, in the first experiment, the first 100 records, let's say this is my 100 records, first 100 records, this will basically become my validation data, and this will actually be my training data. Okay. And similarly, with respect to experiment 2, what will happen? The next 500 records that you'll be seeing, this will basically become your validation data, and remaining all over here will basically become your training data. So again, here you'll be getting an accuracy 1. Similarly, here also you'll be getting an accuracy 2. Now just imagine how many number of experiments I have to do in order to traverse all 500 records. Obviously, it is very simple. We will go ahead with experimental experiment. How many? See, 5 experiments, because 5 into 100 will cover all the data points, right? So experiment 5, you will be able to see the last 100 records will basically be your validation data point, and this data will basically be your training data points. Okay, perfect. And finally, here you'll be having your accuracy 5. And then I can probably calculate the average of all the accuracies. And as a data scientist, I can say that the max accuracy that I can get is the maximum one out of it, the minimum out of it, and what is the average accuracy I can basically say with the help of cross-validation dataset. Okay. Very, very simple. We have discussed till k-fold cross validation. Here you can see leave one out cross validation, leave p out cross validation. Now let's go ahead and discuss about one more technique, which we specifically say it as stratified k-fold cross validation. Now before understanding why do we use stratified k-fold cross validation, let's go to the fourth one. Here I'm just going to write stratified k-fold cross validation. See, at the end of the day, cross validation is used for hyperparameter tuning along with to check how my model performs with respect to the validation data set also. Now in stratified k-fold cross validation, first of all, we'll try to understand what is the problem with k-fold. Let's say if we are solving a classification problem, there may be scenario in my test data or validation data, since I'm selecting part by part, one by one, trying to cover every data set, there may be high possibility that only one type of categories may come over here. Let's say if it is a binary classification problem, then in my test data, the scenario may be, or sorry, my validation data, the scenario may be that all the outputs are ones or zeros, right? We may not get the right combination of ones or zeros as my output. So that may be a problem because my data set is only giving one type of data, and obviously model will not be able to understand, or it will not be able to train itself properly. Stratified k-fold cross validation makes sure that whatever validation we are doing with respect to different k values, let's say if this is my k value is equal to 5, obviously test size will be 100, okay, because my 500 divided by 5 will be 100 over here, it's test size, right? Test data. Whenever it is taking the validation part, whenever I say test data, I'm basically mentioning it as validation data. Okay, guys, don't get confused with respect to this, right? So this is nothing but validation data. Now, when this validation data is selected, okay, it will always make sure that the number of outputs will be evenly distributed. Over here, let's say 60-40 ratio, the number of outputs will be distributed, right? If I have 60 ones as my output or 40 zeros as my output. So this is also a balanced data set, right? So in my validation data, always it will make sure that equal amount of zeros and ones will be present. In our training data set, we can have somewhat little bit in a different way, but it will always make sure that in our validation data set, it will probably provide you almost equal proportion. So let's say if this is my CV1, this is my experiment 1, then in the experiment 2, it will try to select the next 100 records, and it will again make sure that my validation data set is proportional with respect to the number of outputs. Now this is an example with respect to binary classification. So again, this will be my validation data set, this will be my training data set. This is the only difference between k-fold and stratified k-fold cross validation. Okay. At the end of the day, it is always making sure that the number of outputs in the validation data set is almost equal, so that my model will be able to perform. Remaining all, whatever things are there in k-fold, the same thing actually happens over here. Now coming to the fifth one, which is again super important, and the fifth one is something related to time series data. So here I'm going to basically write time series cross validation. Now here, what we're going to do, I think you've seen a lot of use cases where, let's say, there is something called as product sentiment analysis or product comment sentiment analysis. Like people usually write product reviews, right? I can basically write reviews. Okay, sentiment analysis. Now let's say initially a product is created, and later on company adds some more features in that specific product. So initially, let's say when your reviews are bad, later on it can become good, right? So all those reviews that are coming, those are based on time, right? And you can say as we go from January to December, right? Initially in the first quarter, we got bad comments for this product reviews, or we got bad reviews for this product. Later on, when we went to July, September, October, the reviews become better. So in this scenario, what happens in that in time series? The cross validation will happen based on days or based on some time. Let's say day 1, day 2, day 3, day 4, right? And like this up to day n. Now in this, we divide our data set based on days. Let's say this from day 1 to day 4 is the part of my training data set. Day 4 to day n is part of my validation data set. We cannot randomly pick up days and put it in the training data set or validation data set. We always have to make sure that whenever we are doing the split, it happens based on days, right? The initial number of days, it can be any number of days, right? And this should only be the sequence. We cannot randomly pick up some part from here and put it over here. No, that will not be possible. And where do we apply all the scenarios? Usually in time series application. You'll be seeing we'll be doing a lot of projects with respect to time series. So in time series application, we will be using this kind of time series cross validation. Okay. And this is the reason because reviews, something that is some outcome that is related to time will always change. And that is the reason we always try to make this kind of split, right? So this was the basic differences. And yes, as we go ahead, we are going to understand all these types of cross validation and we're going to implement with the help of Python and a scalar, and we'll see that how we can actually solve it. So yes, this was it from my side. I will see you all in the next video. Thank you.
Hello guys, so I'm quite excited to start a new project, and this project will be quite huge because here we are going to do extensive EDA feature engineering. Along with that, we are going to train this entire data set with 3 different models, that is linear regression, that is simple multiple linear regression. Then you will also be having the ridge, lasso, and elastic net regression. So for this problem statement, the data set that we are going to take is something called as Algerian forest fires data set. So the data set looks something like this, and here you have this data set for 2 regions. One, we have it for Bijaya regions data set. So, and the second one that we specifically have for this is CD Bell Abyss region data set. Now we're going to combine this particular data set. For classification problem, you can take classes as the output feature, but for the regression problem, we are going to take FWI as my dependent feature, and remaining all will be my independent features, right? So let's go ahead and let's see what all this information will be there in the data set. Again, the steps that I'm going to repeat: first, we're going to do EDA, then we'll do feature engineering, then we'll clean the data, and then finally we'll be applying our model. We'll also be doing, or we'll train our new models, and then we'll also do hyperparameter tuning for all these particular data sets. Okay. So here is the basic information about the data set. Algerian forest fire data set. So this data set includes 244 instances that regroups the data of 2 regions of Algeria, namely the Bajai region located in the northeast of Algeria and Sidi Bel Abyss region located in the northwest. The period is from June 2012 to September 2012. The data set includes 11 attributes and 1 attribute as class, output attribute as class, but we can also take other attributes as our dependent feature. The 244 instances has been classified into fire and non-fire classes also. So you can use also this particular data set for the classification problem. Now these are all the data set information. I have date, temperature, okay, in Celsius degree, RH means relative humidity, WS basically means wind speed, rain, that is total day in mm 0 to 16.8. So here you can also see ranges are also given, right? FFMC basically means fine fuel moisture code. That is indexed from the FWI system. You also have DUF moisture code indexed from the FWI system, drought code. Okay, again some parameters, some values will literally ranging. So these all things will be able to identify what exactly should be your fire weather index or the classes, whether fire is going to happen or not fire. So all these features are basically there. These are the attributes. Okay. Now the first thing that we'll do is that once we read this data set, right, we obviously have 2 regions, right, and this is in the form of CSV file. Let's see after reading this particular data set how it looks like. Okay. So first of all, as usual, first we'll focus on doing EDA. So obviously we really need to import a lot of libraries, including pandas, numpy, and matplotlib. Okay. So first of all, I'm creating some cells, and let's go ahead and let's start the process. Okay. So first of all, as usual, I will say import pandas as pd. Okay, import numpy as np, import matplotlib.pyplot as plt, and then we're also going to use cbon. So cbon is basically used for plotting the data sets, and then here you can see matplotlib inline, right? And finally let's go ahead and execute this quickly. So these are all the libraries that I'm actually going to use. Now the first step is basically to read the entire data set. Let's go ahead and use pandas for this. So here I'm going to use pd.read_csv, and here the dataset is in the same folder location. So if you search for Algerian forest fire dataset underscore update.csv, here you'll be able to see it. Now if I execute it, this is how your dataset looks like, right? And here you can find out Bijay region dataset. I know there are two regions. One is Bijay region, and the other one also you'll be able to find it over here. So this will be the CDBell Abyss region dataset. So what we are going to do, we are going to merge both the dataset. Now in order to merge, I'll first of all use header is equal to 1, so that the first one it will get ignored. So here you'll be able to see all the features it will be taking up, right? If I don't use this, what it is going to do, whatever dataset that you have over here, right? Whatever is there in the header over here, it will be considering this particular features as your attributes, right? So I'm going to remove this, that is header, and take my first header as the first row of the dataset. So definitely with the help of this, whatever information I have over here, it will be our dataset. But again, we have some of the features over here, and I have to remove this and this features also, and probably combine both this particular dataset together. Okay, so fine. Let's go ahead and store this in our dataset. Okay, so this is our dataset. If you probably want to see the head of this dataset, here you'll be able to see the head also. Okay, so till here it is very simple, very clear. I hope you're able to understand whatever information that we have done. It's very simple. Okay, now let's do one important thing before we go ahead. Let's see some of the basic information, right? Like initially, you really need to see some of the information regarding the dataset, what the dataset looks like, and all. Okay, and as usual, here you can basically write dataset dot info, right? If you just write info, here you'll be able to see, okay, all of them are objects, right? So you have to make sure that they should not only be in objects. If there is any numerical values, floating values, you have to convert into integers or floats. Okay, so I'll start the data cleaning process now. So here I'm just going to write data cleaning, make it as markdown, and start the process. Now, first of all, in the data cleaning, we have to check our missing values if there are any specific missing values. Now, obviously, over here you'll be able to see some missing values. So if I write dot is null, dot sum, right? Here you'll be able to see, okay, one rows data set is missing. In classes also 2 rows are specifically missing. Not a problem. What I'm actually going to do, if I also, instead of writing is sum, if I write dot is any or dot any also, and make sure that if I write axis is equal to 1, so that basically means I'm just trying to find out in any columns, right, if there is any null values, right? So obviously here you'll be seeing that false, 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 or true. Wherever there is a missing value, it will be true. But obviously I cannot see all the records. So what I'm actually going to do, I'm going to only retrieve those records which are true. So all I have to do is just write data set like this, and use this braces over here, and here you'll be able to see it. So definitely it shows that, okay, this 2 rows are there which is having specifically null values, and obviously this, I think you have identified it already from where it is coming. It is basically coming from here, right? So it is basically null values, and somewhere not fire is actually mentioned, so that can be a null value. Okay, so guys, now let's go ahead and make a quick observation from this specific data set. Now, as you've seen already in this dataset, the dataset is actually divided into 2 regions. One is Bijay region, and the other region is CDBell Abyss region dataset. Now, here you can actually see the index till 122. All the dataset that is present, it is from the Bijay region, right? From this specific region that you can see, Bijay region, right? And then after that, whatever dataset is actually present, it is for the CDBell Abyss region dataset. So we are going to quickly make some observation, and we are going to divide this dataset into 2 groups. So the dataset is converted into 2 sets based on region from 122 index. We can make a new column based on the region, that is Bijay region dataset and CDBell Abyss region dataset. So what we are going to do is that add a new column and try to represent this particular dataset over there, right? What we can do is that we can create a new column, and there we can assign labels. We can say that Bijay region dataset will have a label as 0, CDBell Abyss region dataset will have a label as 1. Okay, so let's go ahead and execute it. And what I'm actually going to do, as I already know the index 122, all I have to do is that I'll be using df.lock lock operation, and here till 122 index I'm going to create a column that is called as region, and for that, wherever region, so for all the records before 122, all I have to do is that assign a label 0, and here you'll be able to see that if I write df.loc, and here I will say from 122 onwards, any records that is actually present, use a region as 1, right? And once I execute this, let's see, okay, the df is dataset. It's a practice, right? We try to use df a lot, so what I'll do is I'll just make sure that I will just say df is equal to dataset, just assign it over here, guys, so that later on I don't make a mistake. Okay, so here it is, perfect, right? So now if I probably see df.info and try to execute it, here one value of region will be float, right? So I don't want to save much memory for float values, so all I'll do is that I'll write df of region, okay, and I'll try to convert this into entire int type, so that it looks good, because 1 and 0s I don't need to save it as floating value. So as type I'm just going to say int. Okay, int, okay, perfect. And now if I probably write df.head, you'll be able to see all the values, and here region will be 0s and 1s. Okay, now let's go ahead and quickly execute the same thing and try to find out what is the null values or not, where it is basically present, and we'll try to remove that null. Okay, dot sum. I'm also making sure that I write all these comments wherever I need to provide you some kind of observation of what we are actually doing. Okay, and right now here you can see obviously there will be 2 nulls. So what I'm actually going to do is that and already we know that what are index null are there, 122 and 167. Okay, so I'm going to directly remove this 122 row because I don't require it. So let's quickly go and drop it. So now here, if one record is there, I think not a problem. Remove the null values. And all I have to do in order to remove the null values or nan values is that I can just directly use df.drop na, right? Something like that. So here I'm actually going to say df.drop na, okay? And see, if once I just drop it, here you'll be able to see all the records will get dropped. But along with this, right, along with this, what I have to actually do is that I have to also make sure that I reset the index. Because one important thing from this particular data set is that whenever you see the specific indexes, right, once you reset, right, that will actually create a gap. And we have to make sure that all this index also get reset. So after dropping the index, I will just update this in df and probably see df.head. And if I also want, I can also print. I'll just let me execute it here. So now if I probably see df.head, you'll be able to see all the values, and obviously we have done the reset. Along with this, if I really want to check if there is any null values, I can also do that. So dot sum, I think now we will be getting all the values as 0 because we don't obviously have any null values. Okay, and here we can also check out from those specific things like whether that 1 or 2 has got updated from which all index. So if I write 122 index, here you'll be able to see that my value is basically 1. And before all these things, and again this particular column, right, here you can also see from where it came, right, and we have to also remove this because this is the column that is basically coming, right. So I'm going to also make sure that we drop this particular row, right, this row, because that row is again a repeated row because it is the same column name over here, right. Only the region values specifically then. So what I'm actually going to do, we're going to just drop it again, df.drop, and we're going to drop the 120th row, and again I have to go to do the reset index, and then again right drop is equal to same thing that what we did to remove one index over there also, and this I'm going to save it as df. So here, what is the observation? I'm going to just remove the 122nd row, right, and here done. Now if I probably go and see df of dot ilock, of 1/22, you'll be able to see this entire values. Right now, it is perfect. Perfect. So we have done this. We have done it in an amazing way. We have made sure that all the updates are actually happened, and this is good. We are in the right stage of feature engineering, and we are cleaning some values over here also. Okay. Now let me do one thing. Okay. One super important thing is that if I probably write df.columns, right? Here you'll be able to see some names of the columns, right? Has some extra spaces. This is all why I'm showing you all these things, because additional thing you really need to know, right? When we say EDA, it may be that you really need to rename the column. You need to do something. You need to make sure that you write the column name in a proper way, something, right? And that is the reason why I'm saying it's not necessarily that, okay, for this you have to do something. But here I'm just trying to show you, because tomorrow if you get a situation, if somebody says, okay, make sure that you don't have any spaces in the column name, then how do you do that? Okay. So let's go ahead and let's fix the spaces in the column name. So here I'm going to write fix spaces and column names, right? And all these comments, whatever I'm writing, it is just to make sure that you learn it in a better way. Okay, that's it. So here, first of all, if I write df.columns, here you'll be able to see this. Now all I have to do is write df.columns. Okay, dot str dot strip. When I write dot strip, that basically is just going to find out the white spaces and it is going to update. Now if I probably see df.columns, here you can see that classes white space is gone, everything white space is also gone. Okay. Now when I just search for df.info, here you'll be able to see that I'm seeing all object type. But obviously it is very much clear if you probably see the data set, right? From temperature to all the values till fwi, right? And region is already numerical values. This should be numerical or float values, right? So what we're going to do is that we're going to change the data type. First of all, we're going to take up which all values need to be integer, and then we're going to see which all values are going to be float. Okay. So first of all, let's go ahead and say, write down a comment which will be like change the required columns as integer data type, right? Data type. Perfect. I'm just going to make it this as a markdown and make sure that use some more. Okay. So that looks good. All I have to do is that I will be considering which all columns: month, year, temperature, RH, WS, rain, as integer, right? So till rain, I think not rain, rain is also floating, but till WS, I can consider all these are integer values. Okay. So in order to do that, all I have to do is that use df and start writing my column names, right? Start writing my column names. So first is month, okay, month. Second is day. Third is year, right? Fourth is temperature, which is in capital letter, and RH. If you don't want to do this, just go over here, write df.columns and copy paste. You can also do that. I'm just trying to show you by writing multiple columns. It's just not to make things bigger for you, right? So till WS, I can just directly copy it, and here will basically be my WS, right? So all these things, I'm just going to write equal to with respect to all these columns dot as type. If you write as type, and then if you probably write integer, that's it. It has got executed. Now all I have to do is that write df.info. You'll be able to see the updates. So here you can see all are becoming integer type. That is in 32. It can also be in 64. It depends on the system that you're using, the processor that you're having, how it basically assigns an integer value. Then comes the other feature, that is rain, the FFMC, DMC, DC, ISI, BUI, FWI. Right? These all should be floating. But now what we are going to do is that we're just going to write something like this. I'll write a generic thing, right? So I'll say changing the other columns to float data type, right? Now here, I will just write a common way, right? And the common way will be something like this. And again, this way, you should always try to find out a generic way to write the code. Otherwise, you'll definitely have many features when you're working in a real world problem statement. So here I will say features I'll say features in df dot columns. Okay. If df of features, I'm saying that if this data types is equal to O basically means object. Okay. So here, if I probably execute this, okay, this is an invalid syntax. I'll probably put this into list comprehension. For feature in features, let's see, for features, okay, I have to use features. So here you can see for features in df.columns, and I'm actually referring this feature over here. It is showing over here, and this shows that which all data types have basically O as an object class. O basically means object class. Okay. Other than that, here you can see region is having an integer, so it did not pick up, right? So for all these objects, what I'm actually going to do, which is these features are all in object type, right? So I'm going to just execute this, and let's say I will write for I in objects. Okay. If I say, see, if I does not belong to classes, okay, then all I have to do is that I have to say that df of I. I will convert this df of I dot as type as float, right? So in short, what it will do, because once I execute this, right? Now, if I probably just write df.info, now see one very amazing thing you'll be able to see. All have got converted into in 32, 32, 32, float. Now here you can see classes did not get changed. Why classes did not get changed? Because when I was iterating through this object, so what is this objects now? Let's see. What is this objects? This objects is basically, this is the classes, right? So here I've given a condition where this particular feature is not there. You just skip that and convert all this particular value into float. Okay. So it has just skipped classes column, which is my output feature, let's say. And this needs to be an object because this is a categorical feature. Okay. It is not an integer feature, numerical feature, because later on we'll try to convert this by assigning labels. Region is kept as in 32. Okay. So skipping this particular column, I have made sure that I have assigned everything as float. Okay. So this is what we have actually done in this specific step. Finally, you can also use df.describe to see some more information after we do the cleaning process, right? So here you can see we've done some amount of EDA feature engineering cleaning process. So finally, you can see df.head, and this is your entire data set, right? So in short, we have done some amount of EDA feature engineering and all the other things. Now, as we go ahead, what we are actually going to do, we're going to do some more advanced EDA part, but here some basic EDA and feature engineering has completed. So yes, in the next video, we will continue and we'll do some advanced EDA and we'll do the next steps. Okay. So yes, I will see you all in the next video. Thank you. So guys, till now we have done some basic cleaning of the specific data set that we have actually taken. And then we also merged it, we saw the columns, we renamed the columns, and finally we were able to also change the data type. So this is the initial cleaning process that we will do. Now after doing this particular cleaning process, what I really want to do is that also make sure that convert this entire data set into another CSV file, so that that particular CSV file will basically be consisting our clean data set in short, right? So let's go ahead and first of all, I'm just going to write a comment. Let's save the clean data set, right? And the next step, I'm basically going to write df.to_csv. Now, in order to save this back into the CSV format, I will just use this df, which is having my entire data set to_csv. And here again, I'm going to use my same naming convention, Algerian data set. And instead of writing update, I will just say that this is my clean data set, right? So clean dataset.csv. Now, once Now this particular CSV file will get stored in the same location, and anytime if you probably want to work again, you can just upload this particular CSV file and probably start working with this. Now remember, right now when we are saving this particular data set, this index will also be saved as a separate column. Now when I'm actually saving it, first of all, I'll also say one important parameter I'll use it, which is called as index is equal to false. So once I do this, this index will not get saved in that particular data set. Okay. Now till here we have done it. Now let's start our exploratory data analysis. Okay. Now extensively we are going to do exploratory data analysis, and we are going to see different things. Now first of all, this is my df.head. Okay, now let me make sure that let me make this copy in some other data frame like df1. Okay, so I'll just say df1 or df underscore copy, and I'll just save this particular data set over here. But before saving it, right now in my data set I have day, month, and year. This is not that important because right now we're not going to consider any day, month, or year. Instead, try to focus or consider this features and try to predict our FWI. So this is the problem statement that we are solving, right? If you're probably solving a classification problem, you have to probably keep this classes as your dependent feature. But right now I'm going to use WFI. Okay, so what I can do is that I can drop this day, month, and year, which I don't require it, right? So in order to do that, I'll just use df.drop, and here again you can press shift tab to see the definition. Here I have to give the labels and the axis. Automatically that particular column will get dropped. Okay, so here I'm going to write my column name as day, comma, month, comma, year, right? So since I'm dropping this, comma, axis is equal to 1. So once I do this, my df underscore copy will have all the remaining features. So I'm just going to execute it. Now if I probably go and see df underscore copy.head, you'll be able to see my entire data set, right? Now this is the first thing that I'm actually doing. Now here we have one categorical feature which is called as not fire and fire, right? So obviously in this classes we'll have two category features. Now first of all, I'm just going to make this as zeros or ones just to provide some kind of labels. Okay, so first of all, I drop these features over here. I'll just write another comment saying that drop day, month, and year. Not required as such, right? So the second step, what we're going to do is that I'm going to do the encoding of the categories in classes, right? So in order to do this, all I have to do is that write df underscore copy is equal to, okay, oh sorry, this, and the feature name is nothing but classes. So I'm just going to write classes over here, and we can use numpy where I can say np.where, oops, just a second, okay, is equal to np.where, and here I'll be writing df underscore copy of classes wherever the classes is equal to not fire, okay, in string, okay, not fire. I'm going to replace it with 0, and else I'll be replacing it with 1. Okay, so this is my entire np.where clause that I'm actually going to use. Now if I could probably go and execute it right now, here you can see there's an error. I have to use double equal to, which is synthetically right. So I have to use double df underscore copy dot head. If I see this here, now you'll be able to see ones and zeros, right? So guys, here you can see that even I have put up the condition that wherever my class's value has not fire, it should be replaced with 0. But here I'm getting it as 1. Now there is some specific I'm going to do. I'll just go and write df underscore copy of classes, and I'm just going to say dot value underscore count. Now here, once I execute this, here you'll be able to see it says series has no attributes. Okay, value underscore count. Let me just check it out. Okay, value underscore counts. Okay. So if I execute it here, the number of ones are 241 and zeros are 2. But here you could see that initially we also had many number of not fires. This should have come as 0. Now there is some problem in this. Now what exactly is the problem that we are going to find out over here? Okay, and over here when I execute one line df underscore copy of classes dot value underscore counts, here you can see different types of categories are here. Initially we thought there's only two categories, fire and not fire. But when they were recording this entire data, here you could see that there is fire, there is not fire. Again, there can be fire with some spaces, there can be not fire with some spaces, and these all are considered as a separate value. So obviously 131 is fire, 101 is not fire, but this fire, 4 fires will be there as my categories over here in classes, but it can have some spaces. Similarly, here you can see different categories are there, and these categories are different because there may be some additional spaces that may be present in this classes, right? Now how to fix this specific problem? Now we need to see that, guys, wherever in the classes not fire is present, right, we have to make sure that we have to make it 0. But over here you can see not fire is present here also, here also, here also. So what we can basically do, so I'm going to just make some changes over here. So I'm going to say dot str dot, there's something called as contains, right? So if I write dot str dot contains and probably use a braces over here, so in short what it does is that wherever in the classes it contains not fire, it's just going to replace it by 0. Okay, so that is what we are going to do. I think this will definitely give up the solution, guys. See guys, we got some errors, but I'm not definitely going to remove those specific errors. I want to really make sure that whatever errors I face, you should also be facing, and you should also be solving along with me. So now here you can see that my classes have become 0, right? Before it was not coming, and probably if I go and see tail, here also you can see I'm getting it as 1 and 0s all. Now if I probably go ahead and execute it again, this df underscore copy of classes dot value counts, here now you'll be able to see I'm having 137. So this is how we have fixed this specific issue. Please make sure that you always see the output categories what it is, right? So this is basically my categories in classes, right? So please make sure that you always make sure you check all these things before you go ahead. Okay, now let's go ahead and solve more things, and now we'll try to do some kind of visualization. And the first visualization that we are going to do is that since we have many features as numerical features of floating point variables, right, what we are going to do, we are going to use some kind of visualization. So let's see, I'm just going to write plot density plot for all features, right? So for all features. Now, first thing first, I'll say plot dot style. I'll apply some kind of styling, and again, this you can probably check it from any kind of documentation. And I'm going to say use cbon styling, okay, cbon, and then I'm also going to see that df underscore copy dot hist. If I use dot hist, it is basically going to provide us some kind of, and I'm also going to select bin size as 50. My figure size I can probably select any value that I want, like 20, 15, let's say, and I'll just write plt dot show. Again, you can play with most of the features, most of the parameters that are present over here. And once I do this, you can see this amazing diagram with respect to every features. So this is nothing with respect to temperature, rain, ffmc, dwm, dmc, bui, isi, fwi. So all these features, most of the features over here, you can see that it is left skewed or right skewed. This follows bit of normal distribution. This is also left skewed. Classes also you can see number of zeros and ones, and similarly region also you can see zeros and ones. They are approximately equal number of regions also, right? So this a small diagram with respect to just understanding how our histograms basically look like. Now I'm just going to put one more observation. So let's say percentage for pie chart. I'm also going to construct a pie chart and probably show you the percentage with respect to fires and not fire. Like what is the specific count? What percentage of the count is basically having the data points with fire and not fire also, right? So let's go ahead and let's quickly write this. So I'm going to say df underscore copy of classes, okay, and I'm going to basically say dot value underscore counts, and if I probably this right now, and let's say in this value underscore concept, if I press shift tab, there'll be a parameter which is called as normalize. Okay, so let's say what happens if I probably use normalize. So if I probably use normalize and write true, here you can see that I'm getting in the form of percentage. And if I really want to get the correct percent, I can just multiply by 100. So 56.37 is basically having ones. Ones are nothing but fire. Zeros are nothing but not fire, right? That is what we basically divided it and probably got it right. Now let's plot the pie chart. So plotting pie chart, and for plotting pie chart, it's very simple. First of all, I'm just going to assign some class labels, and let's say here I'm going to basically write fire. See guys, right now what we are actually doing is basically a simple EDA, by creating some diagrams and probably submitting it to stakeholders. And let's say I'm just going to define some plot figure, and this will basically be my fixed size is equal to some values, let's say 10, 5, 12, 7, whatever you want. And then I'll be using the spy function. And the first I will be giving you the percentage. So let's do one thing. Let's save this over here in the percentage variable. And here I'm just going to assign some percentage. After assigning the percentage, I'm also going to make sure that I assign the labels. So labels is nothing but this will be my class labels, comma. I can also define some auto percentage over here. Let's say I am just defining at percentile 1.1 f everything that is given in the documentation. I'm just using it, and probably while writing the code also I'm referring to the documentation of how to create a pie chart. One more thing, you don't need to remember all these things, whatever. Make sure that you keep on seeing pie chart. All the documentation is freely completely available. You can check it out, and you can, based on that, you can do whatever things you want. Okay, you do not remember, you're not a storage device. Okay, now here you can see that I'm just writing plot show, and here you get it. Fire is somewhere around 56.4 and not fire is somewhere around 43.6 percentage, right? So guys, now let's go ahead and try to do more EDA, that is exploratory data analysis. Now we're going to focus towards correlation and multicollinearity, just to find out that whether there is some kind of correlation, extensive high positive correlation between the independent features or not. So to begin with, what we are going to do, if you really want to simply create a simple correlation, just write c df dot or df underscore copy, since we're using that dot corr. So by this, you will basically be able to get a simple correlation between all the independent and dependent feature. Right now, if I consider FWI as my dependent feature, I'm not worried about this specific correlation. But here you can see all the diagonal elements will have a correlation as 1. This example is RH with temperature. Here the correlation is minus 0.65. That basically means this both are inversely proportional to each other. That basically when the RH value increases, the temperature will decrease. If you see rain and temperature, right? If rain is heavy, temperature is going to decrease. So this is also having a negative correlation. Right here you have positive correlation with respect to FFMC. Right here you can see with respect to temperature, when this is 0.67, it is just saying that FFMC and temperature has a positive correlation of 0.67. That basically means when FFMC value will increase, then there is chances that the temperature will increase. Similarly, you can check out all the other things. Now here, obviously, how to do the feature selection that I'll be showing you during the model training phase, but here you can definitely see some kind of idea you get that how the correlation is basically happening. Now, probably if you really also want to display this in the form of a graph, you can also use Seaborn, and probably there is something called as heat map. Inside this heat map, all you have to do is that just provide your data of the correlation, automatically it will be able to plot it by using all the specific parameters. So it shows that it plots a rectangular data as color encoded matrix. Okay, so if I probably write this as df.corr, that is giving my correlation. Here is a graph that you can basically see, right? So the more lighter side, towards the lighter side, that basically means higher correlated it is. So in short, over here you can see FWI, and FWI obviously is very highly correlated, but if you see with BUI also it is highly correlated, more than at least 80%. Now here you can see FWI and BUI, right? So this is my FWI and BUI. This is the correlation color that I specifically have, see over here. And if I probably see FWI and BUI is somewhere at this point, right? BUI over here. So here you can see 85% correlated. So this color marking will just give you an idea that how much correlated a specific feature is. But right now FWI is my dependent feature, so definitely I see good amount of correlation with respect to all the other values. Here you can see this is 92% correlated with ISI, right? Similarly, if I probably see 85%, 71%, 87%, this has many features that are very, very completely nicely correlated or positively correlated. Here you can see some examples of negatively correlated. Here also you can see some examples of negatively correlated. So with the help of heat map, you can definitely do it. The other thing is that you can also change this figure size to a little bigger one so that you can also see to it. Okay. Now let's go to the next one. Since FWI I'm actually going to consider as my dependent feature, I'm just going to draw some box plots. Okay. So here is my box plots just to check out how the outliers look like. So I'm just going to create an axis, and probably I can also use like this snx.boxplot since I've used Seaborn, and here I can use df of FWI, right? And just execute this. Here you can basically see some amount of outliers are there, not maximum, but this will basically give you a 0 percentile, 25 percentile, 50th percentile, that is median value, 75 percentile, and this is basically 100 percentile, and these are all of the outliers. So this is the data that you can see. You can also use some other color. Let's say if I say color is equal to green, so here you can also see color is equal to green with the specific things, right? Now one important thing that I really want to do, right? Now here, if I probably show you my df underscore copy, right? Or let's say df.head, since copy is basically we have removed month and year. So here you can see for every day for a specific month, data will be there. If you probably see this entire data set, you have data from June, July, August, right? And what I'm actually going to do, we are going to basically do the monthly fire analysis. This is super important for this. And obviously from seeing this data in the summer season, only more fire will happen, right? And that specific graph, this graph that I'm actually created, will provide you that specific information itself. Okay. Now the first thing that I'm actually going to do is that I will just use df underscore coffee. So let's say first of all, and I'll try to plot it region by region. We'll try to do the monthly analysis for Vijay region and then for the other region also, right? Two regions we have. So first of all, I'll just write df of temperature, and here I'll say df underscore copy dot. Let's do it for the entire df itself, because there I have the monthly data information. From df underscore copy, I've already removed it. Okay. So here I'll write df loc of df of region. And the condition that I'm actually going to put over here is that my region, let's see where it is getting closed. This is getting closed over here. I don't require this. So let me just close this. And if I probably write equal to 1, right? And then try to probably use this entire data like this by closing it, then I will be getting all the information with respect to that. Let me just write plt.subplots. And here I'm going to just use some figure size is equal to, let's say 13,6. Okay. Then sns.set underscore style. And here I'm just going to use my white grid style. And guys, these all are there in the Seaborn. Amazing stylings, right? And I can use count plot, right? snh.count plot. And in the count plot also I have to give my x-axis and y-axis, right? So x and y is there. So here the x-axis will basically be my month, whether it is 6th month, 7th month, or 8th month. There's also a parameter which is called as hui, which will basically help us to categorize our data based on classes. Then I have my entire data is equal to df. Okay, the entire data I'm actually going to div. And let's execute this. Now here you can basically see on the 6th month, right? And I have so many categories right now over here. So let's do one thing, okay? Directly applying on df, right? Instead of applying in df, I will just try to make a copy of this. See the conditions that I've actually written, right, while using df underscore this one, right? This basically happened in df underscore copy. I can do the same thing in df, right? The entire data frame. Then probably I'll be getting a good example of this. So here I'm going to write df of classes wherever this is there, remove it, not fire 0 and 1, okay? And probably 0 and 1, instead of writing 0 and 1 here, I will specifically write not fire so that my conditions look good, right? Fire. This just to show you that how my diagrams will look like. Now here you can see on 6th month, right, they were maximum not fire. On 7th month, fire increased. On 8th month, fire increased more. So you can definitely say that on the month of August, the fire was quite huge, quite huge. Okay. Here you can basically give your x label and y label. X label is obviously month. On the y label, you can set like let's say by default it is count, but number of fires you can basically write it as plot y label. Right? Plot y label, and here you're basically saying that okay, number of fires, right? And here I'm going to also make sure that I write a weight parameter, and this will basically be my bold parameter. Okay, and I'll also provide my x label saying that number of this will be months. By using this weight is equal to bold, you'll be able to see that the x-axis value will be a little bit bold. Okay, so here I'm basically going to use bold. Let's see how it looks like. Yeah, months and number of fires is coming up well. This is the fire analysis for the region that is Bijai region. So I would also suggest you to write a title over here. So here let's go ahead and write a title. So I'll say tlt.title, and this here you can basically say fire analysis of Bijai. Bijai. I hope I'm pronouncing it right, right? Bijai region. And again here, here also you can basically specify your weight. And here I'm going to just specify it with bold. Now this may look better. This looks better. Now I'm getting this particular graph. You can save this graph and also give it to us. But at the end of the day, you have to make sure that you have to give proper observation. In this case, you have to write an observation saying that the maximum number of fires occurred in the month of August. Similarly, let's say for the other region, when I say is equal to 1, that is basically, no, this is for the other region, not the Jaya region, but for the region that I have seen over here. Let's go and open it. Let's go and see this, which region it was. Again, I don't remember the name. It is a very complex name altogether. Okay, City Belt region, right? So finally I saw this. So this is basically the analysis of fire analysis of City Belt. PD Belt region, right? Perfect. Now let's go and execute. The same thing I can do it for the other region over here. And here I will basically write Bijai region. Okay. Bijai region, right? And just execute it. Now here also you can see the maximum number. Okay, it was 1. Sorry. So I'll make it 0. So here also you can see maximum number of fires were occurred in 8th month only. Now, quick observation that we can actually make out of both this diagram is that I'm just going to paste it over here, which is super important for everyone. And this observation is super important. Let me create a markdown and just it is observed that had the most number of forest fire for both the regions. And from the above both plots, you can understand a few things. Most of the fire happened in August, and very high fires happened in only 3 months, June, July, and August. Less fire was in September. Obviously, September was less fire when compared to not fire, right? So yes, this was the basic EDA that we have actually done. One important thing that we can also do is that we can also check on temperature. We can check on different things by creating bar charts and all. But I think this is more than sufficient to talk about over here. You can also analyze temperature, use this kind of charts, whatever you want. You can definitely do that. If you really want to go ahead with each and every feature, you can definitely do that. Now, in the next video, we'll start our model training. Finally, you'll be able to see that we have done the proper EDA of all the data set over here. Now, in the next step, we'll try to do the model training. Okay. So yeah, I'll see you all in the next video. Thank you.
So guys, in our previous video, we have already completed the EDA, the feature engineering part, even the data cleaning part. We also saw a lot of visualization diagrams and all. Now, and if you remember guys, we also saved one clean data set, right, within our local folder also. And the same file, this is the file name that we cleaned it and we have saved it in our local folder. Now I'm going to use this particular file and probably do my model training. And with respect to model training also, we are going to focus on multiple things. One is, first of all, we'll be taking this data. We'll see if we can perform any kind of feature selection by using correlation. And then what we're going to do is that we're going to train with a simple model. And then finally, we'll be doing something called as hyperparameter tuning. Now, with respect to hyperparameter tuning, we'll start with grid search CV and randomized search CV. I'll also be explaining you the theory part as we go ahead. Okay, so let's go ahead. First of all, just go over here, open a new notebook file. So I've opened a new notebook file over here. So I'm just going to write model training, right? So let's go ahead and quickly import some of the basic libraries. So for that, again, I will go over here, and again, all the basic common libraries are here itself. I will not waste my time, but instead just copy and paste it over here itself, right? So perfect. This was the first step. Now let's go ahead and import our clean data set. So here I'm going to write df is equal to pd underscore read underscore csv, pd.read underscore csv, and here I'm just going to write my Algerian clean dataset.csv file, and let me just execute it. Okay, it's showing ppd, not a problem. So let's go ahead and write df.head. So this was the data that I actually had. Now let's see what other things we can do. Again, a simple cleaning is again required over here. First of all, let me make some cells. Okay. Now to begin with, first of all, let's go ahead and see my columns. So these are my columns over here. You know that in this particular dataset, I don't require date, month, and year, because based on these independent features, we'll try to calculate what is WFI. Since this is a regression problem statement, I'm just going to compute WFI based on all the independent features. Even classes, I'm also going to consider. Okay. If it was a classification problem, I could have kept classes as my dependent feature. Okay. So let's go ahead and now, first of all, I'll just write df.drop. I want to drop month, day, and year. So drop month, day, and year, right? And here I'm just going to basically write all my features name. First is day. Okay. Second feature is basically in 1. And third feature is nothing but year. Okay. When I'm doing the drop, I'll use axis equal to 1 because I really want to drop all the columns. Once I execute it, here you can see that it has got dropped. So in order to replicate this as a permanent execution in the df itself, I can also use in place is equal to true, right? So once I do it, now if I probably go and see df.head, it will get updated in the df. Okay. So till here, this is perfect. We have done it. Now one issue that we really want to fix is that over here I have classes, right? And we know that in classes, right? So suppose if I write df of classes dot value underscore counts, if I probably write value underscore counts here, okay, unique it has value underscore count. So here you'll be able to see fire, not fire. I think there are some spaces and you can see so many different things. But at the end of the day, you just have two categories: what is fire and not fire. So I'm just going to write one condition with respect to this. And first of all, I will just say that here I'll just do encoding, and this is just like a feature encoding over here. So I'll write df of classes
is equal to np.where. So I'll just put a where condition. And I'll say wherever the df of classes, okay, no df of classes, dot, okay, I think it's dot str dot contains, right? I'm just using this thing and I'm saying not fire. Wherever it basically contains this specific value, then let me close this bracket. Either you can use, if it is not fire, I'll say that it is 0. If it is fire, I'll say it as 1. So if you see over here, not fire, here all the values will become 0 and then it will become 1. Okay. So I hope this will work. df of classes dot str dot contains not fire 0, 1. Okay, perfect. Now if I probably go and see my df dot head, here you'll be able to see I'm having classes, and probably if I see dot tail, here I'm actually also having this. Now if I probably write df of classes dot value counts, here you'll be able to see all the unique one, right? So 137 is 1. That basically means fire, and not fire is 106. So perfectly here we have actually done it. Now we'll divide our features into independent and dependent features, right? So first I'll create my x. Here I'll just write df.drop. And the feature that I'm going to drop is nothing but fwi, where the axis is equal to 1. Okay. So this will basically become my x feature. And then y, I can also make sure that I can write df of wfi. Okay. Once I do it, if I probably now go and see x dot head, I can also use iloc. That is not a problem. So here are all my values. And similarly, if I probably see, these are my wfi values, right? So this will become my independent feature. Now let's go quickly and see some more. What you have to do after creating this is that do a train test split. So train test split. Now in this train test split, what we are going to do over here is that first thing from scalar dot model selection import train test split, and here I'm just going to use x train comma x test comma y train comma y test, right? And here I can basically use my train test split, take my x comma y value, set my test size value as 0.25. I'm just saying that thing, saying that okay, 25% of the data can be put into test data in some random state value so that you also get the same output. Okay, so done. This is perfectly done. X train, y train, y test, train test split. Everything is done. Now, if you probably just need to verify, I can just write x train dot shape. So this is also 182, 11, and x test dot shape is also will be coming at somewhere around 61 to 11. So 61 is basically my test data, and 182 records is my train data. Perfect. Now let's do one thing. Let's quickly go ahead and do feature selection. Okay, feature selection based on correlation. Okay. Here I can basically use xtrain.corr because these are the correlation based on our independent feature. And I need to make sure that if some of the features are very highly positively correlated or highly negatively correlated, right? Negatively correlated can be an important feature, but highly positively correlated, you should try to remove it. So we can actually set up some threshold values also. Okay. Now let's check for multicollinearity. Multicollinearity basically means your independent feature should not be that much correlated, based on some threshold values. So here I'll just say plt.figure. I'll set up a figure size. Okay. And let's say this is my fixed size of 12, 10. I really want to have a big figure altogether. So now, first of all, I'll just go ahead and find out my correlation, and I'll write CORR. Now here, what I'm actually going to do is that I'm just going to display this in a diagrammatic way by using SNS, right? So if I write SNS.heatmap, so this will be my correlation. I'm also going to set the annotation as true, and I can use this too. And finally, let's go ahead and execute it. Now here you can see one cool, amazing diagram. This is the entire figure with respect to all the features, classes, BUI. So this minus 0.46 is the relationship between classes and RH. WS and DC relationship is 0.097. That is, it is hardly positively correlated. So all these correlations you'll be able to find it. Now, in order to check for multicollinearity, what I'm actually going to do is that I'm just going to copy and paste one code, and I will be saying that in this code, I'm giving my data set and I'm giving my threshold value. Okay. Then what will happen is that if I say this threshold is 0.95, so what it is going to do is that within this all the independent feature, it is going to see that which all features are like 95% positively correlated. If it is so high correlated, we can just remove that specific feature, or we can get that specific feature over here, and based on that we can remove it. Okay. So let's see this code. So here is the correlation function. First of all, I am defining a variable which is a set because I want only the unique features to come in. Then I will take this data set and find out the correlation, and I iterate through each and every feature over here, which you can see comatrix.columns, and then along with the other columns, I'm just going to compare if that correlation is greater than that specific threshold value. Okay. If it is greater than that threshold value, I'm just going to take the column name and add it in this specific set. That is what I'm actually going to do. Now let's go ahead and see. So I'll just call correlation, and let's say over here to test it, I will give my x twin, and then I will say, okay, the threshold may be 0.90. Okay, so I'm saying that whichever features are highly positively correlated, right, around 90% or greater than 90%, not equal to, but greater than 90%, just pick up that column names and give me. So once I execute it, here you can see one column is there, BUI. So BUI, here you can see BUI. BUI with DMC, right? So here you can see it is 0.98%, with DC it is 0.94%, right? So here you are able to compare and you are able to get the column name of that, right? So with two features here, you can see with DMC it is 0.98, with DC it is 0.94, right? So I want to basically use this feature, and I can also delete it because I can use these two features, right? So unnecessarily I don't have to increase my columns, right? Now here I have set the threshold, right? I have set the threshold, but the normal threshold is set up by the domain expertise, right? So whoever is the domain expert, whoever is the product manager, he'll be actually helping you to set up this specific value. So here, suppose if I write 0.75 and execute it, you can see this many number of features can be actually removed, right? So let's say that in this particular case, I am just keeping it as 85%. Okay, so I have two features, BUI and DC. So here also you can see DC somewhere it is more than 85. So with DMC also, with BUI also, right? So two more features you can basically remove it, right? BUI and DC is actually there. Now what I'm going to do is that I'm going to drop these features, and let's say I have just selected 85% as my threshold value. Okay, so drop features when correlation is more than 0.85. I'll also show you different ways how you can drop the features as we go ahead with more and more examples. Okay, so first of all, I will just say core underscore features. Let me save this over here and let me take it. Okay, and then what I'm actually going to do, I'm just going to say xtrain.drop, and this will be my core features. But So guys, now let's go ahead and probably implement the ridge regression model. Again, for ridge, we have to again be dependent on sklearn. So if I go and search for sklearn ridge regression, this is where the sklearn library is basically present. Again, ridge by default, if you remember, what kind of equation we specifically apply, see alpha multiplied by the absolute value of w, right? W basically means this is basically my slope, right? By this format, it is basically given, okay? This is also called as L2 regularization, and we have seen this particular formula in my theory part, right? All we have to do is that use this algorithm over here. So from sklearn.linear model, we try to apply ridge. So if I go over here, so here you can see from sklearn.linear_model, we are going to import ridge, and then we are also going to import mean absolute error R2 square. You can also go ahead with mean square error and all. Then we initialize ridge, then we do fit transform on x-train scale and y-train, and then we do the prediction on the x test. Finally, you'll be able to get y-pred, and then we calculate the mean absolute error, R2 score, and all these things are there. So if I execute this here also, I'm able to get 98% accuracy with the help of ridge regression model. Now, before I go ahead, already since we know we have learned in the theory part why exactly ridge regression model is basically used, please do let me know. So this is how we can basically do the prediction with the help of ridge regression model. Now coming to the next one is with respect to the cross validation. So ridge also has a cross validation. Again, you have understood the concept of cross validation. We will basically convert our data set into training and validation data set so that we can perform hyperparameter tuning on this ridge CV. We'll get 5 different accuracies. We'll merge all those accuracies. Okay, we'll basically find out the average. So over here from sklearn linear model, again I'm going to import ridge CV. Then we are going to initialize this with cross validation is equal to 5. Whatever cross validation you want to use. If you want to use 10, go ahead and use 10. If you have a bigger data set, you can go ahead and use 10. Then I did ridge CV.fit on x-train scale to y-train, and then finally we did predict on x-test scale. I got my prediction data. Then we plotted it. We calculated a mean absolute error and all. And finally, I'll also be able to see. So here also I'm able to get 98% accuracy with respect to the mean absolute error is this much. And this is how the prediction looks like. And finally, if you probably go and see what all parameters has got selected. So here you can see alpha per target value is false. Alpha's value that is basically getting selected is this much. CV value is 5. So these are coming from all these things, all these values that has got selected with respect to that particular algorithm. So if I probably go and search for sklearn ridge CV. Okay. If you want to know more about it, you can probably see it from this particular library itself. Okay. So here you can see different alpha values is there. Again, initialized. You can understand what exactly this is, right? And you will completely get an idea because I've covered all these things in the theory part itself. Okay. So quickly, let's go and see this with respect to ridge. I've also got this, right? Now, similarly, elastic net, it is a combination of both ridge and lasso. So again, from sklearn.linear model, I've imported elastic net, and just go ahead and see this. Here I'm getting 87%, but it has combined both ridge and lasso based on the equation that we have. So if you want to again go and see this, just go and search for elastic net. Okay, sklearn elastic net. And here also I will be using by default some alpha value, L1 value and all. This is the formula with respect to the minimization function. So here I will be having one alpha value, two alpha values, alpha and lambda 1 in the same. Okay, lambda 1, lambda 2 that we have written in the equation. Over here they have given as alpha value. Okay, so don't get confused with that because mathematically most of the research paper is written in that specific way. So this is what we have done it over here. We have basically computed our error rate, and then we have this alpha 1, our L1 ratio. Okay, then our L2 ratio with respect to this. So this is the formula for ridge. This is the formula for lasso. Okay, and if you probably see in that way, it is just one and the same thing. Okay, don't get confused by this mathematical equation. So yes, here it is, and yes, again you can also try with basically elastic net CV. Okay, so here you are basically able to get 98%. So in this video, we have basically seen that how to probably calculate the ridge and get the accuracy. And obviously after this, what we do, whichever is giving you the best accuracy, go and convert that into the pickle file and use that specific model for doing the prediction. Okay, so yes, this was it from my side. I hope you are able to understand, guys. I know many people may get confused with respect to reading this documentation. Don't worry about this because whatever theory part we have covered, right, try to apply with respect to that. See, in elastic net, this is the formula. The same formula I've written it. If you probably see my PDF sheet that is given in the resource, you'll be able to understand. In lasso CV, in lasso, you'll all be able to see different equations, and this is how we have basically applied over there. Okay, so yes, this was it from my side. I hope you like this particular video. I will see you all in the next video. So guys, till now we have trained multiple models like elastic net, ridge regression, CV, and all, right? So out of all this particular model, I will probably take the best model, and from here, what I see, ridge regression is basically having somewhere around 98.4% accuracy, right? So considering this, what I'm going to do, I'm going to first now probably pickle our files, right? So we want to basically pickle the machine learning models, Along with this, we will also pickle the pre-processing model, right? So pre-processing model, that is for the standard scalar, and this two model, right? What we are going to do, we are going to use it when we are doing to deployment. Okay. So over here, with respect to two things that you will be able to see, if I go ahead and write scalar, right? So this is my standard scalar, and obviously the ridge part, right? So if I probably just go and see my ridge, so this is my two models that I'm going to specifically use. Now, in order to use this, what I'm actually going to do, I'm going to basically pickle the files. Now for pickling, we have already discussed what I will do for, I'll just write import pickle, and then we will go ahead and write pickle.dump, okay, and I'm just going to write scalar, comma, and I'm going to open a file which is called as scalar.pickle. Remember, why did I select probably scalar? Sorry, probably ridge, because this may have currently this is having the better accuracy, right? You can also select other if you want, but right now let's go with this ridge one. And again, if you want to make different pickle file, it's up to you. Okay. Now I'm going to make the scalar.pickle, and here I'm going to basically write in my write mode. And similarly, I will go ahead and write pickle.dump, and this time with respect to pickle.dump, I'm going to use the model that we are having, and here the model will be nothing but ridge, and this will be nothing but ridge.pickle. Okay, ridge.pickle. So these are the two pickle files that I'm going to use. Now see what will happen is that in the next video, right, we will implement the end-to-end project solution. Now here we have probably done the EDA, we have done the model training, we have created a pickle file, we know how to do the prediction. So for doing the prediction, all I have to what I can do is that I can load this pickle, scalar.pickle and ridge.pickle. For doing the standard scaling, I can use this. For predicting it, I can basically use this particular model, right? So in end-to-end project, we'll focus on probably implementing this from this pickle particular file. We'll take an input, we'll get the output, and then we'll try to see how we can deploy that in AWS and all. I think we have done this entirely when we have discussed about the web scrapping project, which was done by Sudhanshu, right? Now in my next video, I'm going to consider this pickle file. I'm going to take it in. Probably we'll be using another lab template like like Flask. A lab template will implement in VS Code, and then we'll try to see that how things are getting implemented, right? So in the next video, we'll try to implement this end-to-end project implementation. So yes, this was it from my side. I will see you in the next video. Now what we are going to do is that we want to probably create an end-to-end project. So I will now try to convert this entire project of the Algerian forest fire dataset into an end-to-end project wherein we will be getting a web application wherein we'll be doing the deployment in the AWS cloud, right? Now to begin with, first of all, you need to get some basic idea about the machine learning project's life cycle, right? Initially, whenever we start any machine learning project, we start with the concept of data collection. Now data collection is something like where you are specifically reading a data from some specific source. Right now, the data that was present was already available in the form of CSV file, right? But in the companies, when you go, right, you will be reading from the data set from some databases like MongoDB, MySQL, or from big data Hadoop. It can be different sources, right? In a team, when you're working, right, you'll be having the cloud team separate, you'll be having the big data team separate. And as we go ahead, there will also be a lot of topics related to big data and how we can probably create this, or how we can come up with this data collection strategy. So this is the first step. Then in the second step, we performed EDA, right? So much of EDA, exploratory data analysis, where we try to understand about the data of the Algerian forest fire data set, right? And then after that, we perform feature engineering. In feature engineering, we focused on understanding how to handle missing values, how to clean the data, and many more steps as such, right? And then after that, we perform feature selection, that is FS, feature selection. Now, not all the important features are there available, should be used in a data set. Only the most important features. We also need to check multi-collinearity. That is the concept that we discussed in our previous video. And after that, we went ahead and trained our model, right? From this model, we had selected this best model, that is ridge regression, right? So that is the reason we created this pickle file, and this pickle file was saved in the hard disk, right? And in the feature engineering, there was a technique called as feature scaling. At that point of time, we created the scalar.pickle, which was for the standardization process, which is nothing but feature scaling, and this was specifically model. Now, what we need to do after our model is basically created, now we web app will have some kind of form which will take all the inputs that is required to do the prediction from this particular model, right? Once we take all these inputs, all we have to do is that just submit all those inputs. It will go ahead and interact with my ridge regression model, and this input it will take and it will give me some output which will be my prediction, right? So after we develop this particular web app, and this web app we are going to develop it with the help of Flask, and finally we have to go ahead and do the deployment, and here we are going to use AWS Cloud Beanstalk, right? So this is the step. Now we are going to focus on this web app and the deployment part. So probably my videos will be divided into two parts. One is creating web app. Again, I'll be writing all the code from scratch, and then we will go ahead and do the deployment. Okay. Now let's go ahead. First of all, to start with, what I have done is that I've already downloaded all this pickle files. See, rich pickle, scalar pickle, and I've kept it inside a folder over here. See, rich pickle, scalar pickle. Then here I have my feature engineering files and all, model training file. Now what I'm going to do over here is that I'm going to go to my lab template, and first of all, we will go and open a Flask app, right? So once I click on this, right? So this lab, I will open it and it will be a VS Code lab. Okay. Now this will basically be a VS Code lab. Now in this VS Code lab, we are going to do the coding. Okay. I'll just move my face a little bit on the left side. Now here, as soon as you open this lab, you will be getting some important things over here. First of all, it will tell you to install all the recommended extension for the repository. So I will go ahead and click on install. So once we click on install, this is going to probably take some amount of time. So the installation process will take place. And here is the installation that is happening. So whatever is the default extension we are going to use, we are just going to do the installation for that. Okay. So now I'm going to move my face this side so that you'll be able to see it. Okay. Now I'll press enter. Now let me go ahead and close each and everything over here, okay? And then we will start our code from scratch. So this is what is the by default code I will be getting, okay? And this is basically my readme file. Now let's go to the folder, and I will tell you that what all things I'm going to take from this folder. First of all, I will go ahead and take this EDA and model training file. I will upload it over here. So just do drag and drop, and I will be able to see it, okay? So here is my model training and EDA, and here I'm going to create one notebooks folder, okay? So that all my notebooks will be inside this folder for my reference purpose. So I'm going to move it, okay? Done, so that I can refer it whenever I want. The next folder that I'm going to probably create is something called as models, okay? And it will be created outside. So let me just go ahead and write over here folder models, okay? Now inside this models, what I'm actually going to do is that I'm going to probably go ahead and upload this ridge.pickle and scalar.pickle, because these are the pickle files that I'm going to use. So I'll just go ahead and upload in the pickles, okay? Now in the models folder, okay? Now everything is ready. Now all things are there. Now this is my app.py. Here I will be writing my code, okay? If you want a data set also, you can upload the data set over here inside this notebook, okay? So I will go over here and probably go and update this data set over here, okay? So I have uploaded the data set, so that data set will also be available so that you can refer it whenever you require. Now we'll go and start creating our web application with the help of Flask. And here I'm just going to write all the line by line code in front of you, okay? So you can also practice along with me. First of all, instead of writing app.py, I'll just rename it to application.py. And there is a reason why I'm doing this, and I will just tell you in some time, okay? Why I'm specifically doing this, okay? So this becomes my application.py over here, okay? Now what I'm actually going to do over here is that by default, some code is there. Definitely I'll keep this code over here. Now instead of writing app is equal to Flask underscore name, I will write application is equal to, and there's a reason. At the end, while deployment, I'll tell you, and I'll assign this to app, okay? So I've just made 2 lines of change over here. I'm saying application with Flask underscore name, and then this is basically assigned to the app variable, and this app variable will be used here just to start our execution, okay? Okay guys, so now what we are going to do over here is that let's go ahead and import some of the libraries, and now we'll start creating our Flask app. So from Flask import Flask, and along with this I will be importing request JSONify so that I return my result in the form of JSON, and then one more important thing that is called as render template. Now render template will be super important because this render template will be responsible in probably finding out the URL of the HTML file. I'll just show you, just wait till now till I execute the code, okay? Along with this I'm going to import pickle, okay? So pickle will be there, and along with this I'm also going to import the basic library as NumPy, import pandas as PD, okay? Along with this I'm also going to import from sklearn.pre-processing. I'm going to import the standard scalar, okay? Standard scalar, okay? Now here you can see that in this environment right now, NumPy pandas has not been installed, right? So how I'm saying, because in requirement.txt I just have Flask, okay? So I'm just going to add NumPy. I'll tell you why we are specifically writing all these libraries over here, because it is for our installation purpose, right? We will not every time write pip install. Instead, in one file, that is requirement.txt, I will go ahead and write all my libraries which I'm going to use, okay? So here I have all my libraries. Now if I probably want to install it, open the terminal. So this will basically be my terminal over here, and all I have to write in order to install this libraries that is probably present in this requirement.txt, that is pip install minus our requirement.txt, and just execute it. So here you'll be able to see Flask is already satisfied, but NumPy, pandas, scikit-learn, everything is getting installed, right? So this will probably take time, hardly 1 minute, but understand everybody will get the same speed because this is running in some PW skill lab, so there is some different server, different machine where it is specifically running. Now every time, if you probably want to just install a library, update that library name, it is a very good practice. You have to just update in requirement.txt and start the process. Now here you can see the libraries has been installed, so I'll close this. Now I will go to my application.py, okay? Now the first step is that obviously I have created my Flask name. I hope you have learned this in the Flask session. Okay, we start in creating our application, like our app application, okay? So Flask application, okay? And remember, here is where my entire execution will basically start. Now the first step, as I said, my web application should be able to interact with the ridge.pickle and standard.pickle, right? And why we are doing that? Because it will be able to interact and it will be able to do the transformation function, and also transformation, when I say it is nothing but feature scaling. In case of ridge, it will be able to do the prediction, okay? So here I'm going to just write import ridge regressor and standard scalar pickle, right? So for doing this, I've already imported pickle file and I've already shown you in the previous video how to load from the pickle file, right? So here I will create a variable which is called as rich model, and this will basically load my rich.pickle, and for that I have to basically use open function, and here I will just write models and I will give my path, right? Because inside the models everything is present, right? So models, everything is present inside that. So models slash rich.pickle, okay, rich.pickle, and this will probably get opened in the read byte mode. So this will be read byte mode. Okay, so done. Over here I've basically opened the rich.pickle in the read byte mode, and then I'm going to create standard underscore scalar, and here I'm going to basically write pickle dot load, and here also I will just write open and then again models slash scalar dot pickle, okay, because that is my pickle name, right? Models slash scalar dot pickle, and again this will basically be in the read byte mode. Okay, now all this has been loaded. Now we are going to just use this while we have to do the prediction. Now perfect, this is here. Now the next one that we are probably going to create is my homepage, right? Now in homepage my route will be app.route slash, okay, and here let me just go ahead and update this function like index, and here I'm going to return render template and give something like index.html. Now you will be able to understand what is the importance of this render template which we have imported. This, as soon as we write render template, this will what it will do, it will just go and find index.html where it is over here, and it will always make sure that it will find inside a folder which is called as templates folder. So render._template basically means it will just look for a template folder over there, and inside that whether that index.html file is present or not. If it is not present, then when we are executing this code, it will not work. So here I will just create a file which is called as index.html, and inside this HTML I will just write h1 tag, and I'll say I will allow this. So I will just say h1 tag, and I will say welcome to the home page. I'll just try to execute and show it to you how it will look like, okay, and this will basically be my h1 tag. Done. So I've done this, a simple application.py I've executed over here, and I created the home page, I've created a route for the home page. Now let's go ahead and execute this and see how my execution will happen. Okay, so if I probably open the terminal, okay, now one thing that you really need to note over here when we are running, right, we have given the host as 0.0.0. Now see this, okay, once I run this python app.py, okay, so oh sorry, it is not app.py, it is application.py, okay, application.py. I will just remove this, and once I execute it, now see what is happening. From skykit sklearn preprocessing import standard scalar. Now there is a problem over here. What is the problem with respect to this sklearn.preprocessing import standard scalar? I did not write the correct spelling, okay, so please make sure that you write the correct spelling. Now I will go ahead and clear the screen, because now I will just go and write python application.py just to test everything is working or not. Now see, when we are given by default 0.0.0 as my host address, right, this is basically mapped to the local IP address of any machine that you're working. So let's say if you're running this entire application in a local machine, then also if you give 0.0.0, in short this is getting mapped to your local IP address, and obviously local IP address will not be publicly available, right? Now that is simple. Now the system address where this code is exactly running is having this IP address, okay, and if you want to access this, you have to use the URL over here, okay. So this is the URL we will specifically be using, and here what I will do, I will write a port number 5000, because by default any Flask app will run the application in default port number of 5000. If you want to change the port number, then probably you can just write your own port number, whatever is available with respect to your system, like port is equal to 8080 or 8000, whatever you want, you can basically write, okay. So right now I will not write it, I'll keep it like that, and I want to run it in default 5000. Now once I execute it over here and write 5000 and slash, now see what will happen. This, as soon as I execute, it is displaying welcome to the home page. So in short, what has happened is that once we wrote slash, right, in short, this has basically triggered this function. Now this render template, what it is doing, it is searching inside the templates folder, and it found out one index.html, and it is basically displaying this particular message over here saying that welcome to the home page, right? Now this is a basic idea about how the template is basically visible. Now similarly, what I am going to do for the prediction with respect to my model, right, I'm going to create similar app.route like this, okay. So here again I will go ahead and write app.route, and this time let me go ahead and use another URL like predict data, okay. So this will specifically predict data. Now one important parameter I'm going to write methods, right. Method is equal to, and this will include both get and post method. Okay, so get and post method we are going to specifically use over here, and this get and post method, why? What is the difference between get and post method? Now see, if I go to my URL and search for google.com, so by default when I'm just searching for google.com, I will get one static page, right, like this. So this becomes a get request, right? By default, whatever the information page has, I'm getting that particular information. Now probably if I go ahead and search for PW skills, right, and execute it, now here you'll be able to see I'm posting something. I'm posting some information over here, right? Now when I post some information, that basically means I'm sending some query, right? And based on the query, I'm retrieving this kind of results, right? So I hope you're able to understand what is the difference between get and post. In the get, we're just retrieving. In post, we're sending some information into the net to our server, and based on that, we'll get some kind of response. Now similarly, our plan is what? In our web application, right? We will be creating all the input fields through which, based on that input fields, we'll be doing the prediction of FWI, right? So FWI was the parameter that we were doing the prediction. We had already seen over here, right? In the model training purpose which we saw, right? We were basically predicting. We were doing this prediction for specifically this particular data. It was nothing but it was all the input data, and I was getting the output of FWI, right? FWI is nothing but, I'll just go and show you that specific feature. It is nothing but fire weather index, right? So this was the information that I was doing. Now similarly, what we'll do, we'll create this web application, we'll create this page. Inside this, all the fields will be there. Once we enter this field, once we press the submit button, it should interact in the backend with our model and give the prediction. That is what we want to do. Okay. So quickly, let's go ahead and do that. Right now we are able to get the home page. So I'm just going to close this so that we will continue the execution. Now here you'll be able to see I'm getting get and post method. Now I will go ahead and create my definition. So definition predict underscore data point, and here I'm going to basically use if request dot method. Now see, whether it is get or post, if we really need to find out, then we really need to write this particular condition. If the request dot method is double equal to post, okay, then I will do some execution. So I'll keep pass over here, okay, and I'm not writing what I'm going to do, because whenever it is a post, I need to interact with my rich model. I need to do the prediction, get the output. This I will write the code later on. In the else block, this is basically saying that if my request dot method is get, right, if it is not post, either it will be get, right. So in that scenario, I will just say return render template. So by default, whatever HTML file I want to display, I will display. So I will write home.html. So this is the HTML that I'm going to display. Now I'm using render template. So in render template, inside my templates, I don't have home.html. So I will go ahead and create my home.html. So here I have home.html. Done. So this is my home.html that is basically created. Now what HTML I will specifically have, okay? And one thing that you need to understand, guys, in HTML, right, you don't have to worry about how you design the HTML page. This is done by the front-end engineer. But in short, my web application should have fields of the 9 input fields that I want to give. So for that, I'll be creating this form. So I'm copying some code over here. This is my HTML, this is my body, and this is the most important thing, which is my form. Now through this form, I will submit my data, right? So just to give you a good basic info about form will have some action, and that that action you write in this way about the function that you need to call, and for that you need to use URL underscore for. Okay, so once you write URL underscore for predict underscore data point. Now when this predict underscore data point is what we are basically calling this particular function, right? So in this function only we will basically do the post and then we'll get the output, right? And here is my home.html and then this method is post, right? So because of this method is equal to post, my application when we write request.method, it will be able to retrieve whether it is a post or a get. Okay, so here you have, and then these are all the 9 input fields that I'm giving: temperature, RH, WS, rain, FFMC, DMC, ISI, classes, and region. And finally I'll be having a submit button which will be doing the prediction of this entire form, right? So this will be my entire form, and finally the FWI prediction is some result. This we will discuss. Okay, what exactly this result is. This is the prediction that we'll be doing from the model. Okay, now let's go ahead and execute it. And right now nothing is there in the post. I've just written pass. Okay, so I'll just save this and go ahead and open my terminal again, and let's run this. Here again I will write Python application.py. So once I execute it, now here you can see it is running, everything is running. Now if I want to call this URL /predict data, so I will just go and call. Now what will happen once I call by default, this becomes a get method. In get method, what is happening? See, if the request method is post, but right now it is not post, we'll go into this else block. It has to show this home.html which has this particular form. So I will go ahead and execute it and just press enter, and this is what you are specifically getting, right? These are all my fields, and right now the result is empty because we did not do any post, right? Now main thing is that we'll put values over here, and once we click this predict button, what will happen once we click this predict button? It will just go and hit this predict underscore data point, which is this function. Now it will say that if this particular post, then we have to write our code over here. Okay. Now this is the thing that we are going to handle. The first thing over here that we are going to do is that read all the inputs of all these particular values, like temperature, RH, WS, rain, FFMC, DMC, ISI, classes, and region. Okay. So for that I will just remove this pass. Okay, and I will just copy one code for you so that you get all the input files, so you get all the values with respect to this all things, right? So here I require all my input values, right? Like temperature I want. Now if you want to get temperature, all you have to do use this request object and just write request.form.get temperature. This temperature should be matching with the name that is present over here. These are like input text box, right? Everything is an input text box. So this value if I want to get, I have to probably read with this specific name. So here I have written request.form.get and this particular temperature. Similarly RH, WS, rain, FFMC, DMC, ISI, classes, region. So here I get all my input parameters. Okay. Now once I get my input parameters, I will probably use this standard scalar for doing the transformation, because that is the first step. It is required. Never do fit underscore transform. You have to do transform for the new data point, right? So here we will go ahead and write standard scalar dot transform. It is standard scalar only. Standard scalar dot transform. Okay. Now inside this transform, I will be giving all my input values. Okay. So what all input values are there? Temperature, this, the region, this all things, comma by comma separated. I will give. Okay. So once I give this, I will be getting my. You can basically say I'll get my new scale data, right? So new data, new underscore data underscore scale. Done. Okay. So standard scalar, you know what exactly standard scalar is. You have basically loaded standard.pickle in the write byte mode, right? Now finally you have this. Now the next step is that I will try to predict my result, and for this I will be using ridge underscore model dot predict with respect to your new data scale, right? And once you get the result, after that you're going to show your result in the home.html only, right? So again I will write return render template, and here I'm going to basically write home.html, but I need to show this result, right? And this result will be a list of value which will have just one value, and it will be in the form of list. Okay. So here I will just create a variable which will be like results. Okay, something like results, and here this will get assigned to my result of 0. Okay, as I said, this will be in the form of a list, right? So done. We have done this. Now this result variable, when I go to home.html, we should be able to retrieve it over here. Okay, and this is basically written in double curly braces so that you can get the value from the backend, that is application.py. Okay, so yes, done. We are very much good to go with respect to this. Now the next thing that I'm probably going to do is that I'm going to just run my terminal. Okay, so quickly let's go ahead and close this. Here I'll just write Control C. I'll close all these terminals. Okay, no worries. So this will basically be my clear screen. Now let's go ahead and write Python application.py. Okay, done. So this has got executed perfectly. Now here you can see this. Now I'll go and reload this page again. So we have reloaded it. Now what I will do, see the magic. Okay, I will put some values 29, 57, 18, 0.0, 65.69. I'm putting some values based on some test data. And once I do one and I do the prediction, now this is the output that I'm specifically getting. See, that result is now getting displayed, right? So this is nothing but 0.77540. And this is how you have basically created or converted your regression of the problem statement that you did, right? Algerian forest fire into an end-to-end project, right? Now all you have to do is that do the deployment in the GitHub repository. So for that, quickly let me show you how to do the deployment. So first of all, just go ahead and write ls -a. So here you'll be able to see some .git file. Okay, so by default, whenever you open a Flask app, you will be able to see one GitHub repository will be there by default. So if you write git remote -v, so here you can basically see that I'm having this pw skills GitHub URL. So what I will do, I want to put all my code this into my personal GitHub repository so that I will be able to do the deployment. So for that, I will write git remote remove this specific origin, right? This entire thing, I'm going to remove it. So this is the command that is used. So this is now removed. Now if I write git remote v, now you'll be able to see nothing you're able to get. Okay. Now what I will do, I will open my GitHub repository. I will go and search for my repository or create a new repository. So let's go ahead and create it. So I'm just go ahead and create it. So I will write test forest fires. Okay, test forest fires. This will be public or private. It is up to you. I will not select anything. I'll just create the repository. Now once you create the repository, these are the steps we need to follow. Okay, I already have a readme file, so I will start with git init. So I will go and execute this. I will write git init and execute. Okay, so now it is reinitializing some existing GitHub repository over here, and I'm ready for the next step. The next step is very simple. I will go ahead and add all my files. So here I will go ahead and write git add dot. So now if I probably see git status, you'll be able to see all the files which has been added and deleted. Everything will be available over here, right? Perfect. So here you'll be able to see application.py. This is available. Okay. Now the next step that we are probably going to do over here is that I will go ahead and write git commit -m first commit. So for that I will go and paste it over here. Now it is basically asking me how you're doing the GitHub commit. You know, you're not given your which email ID your GitHub repository is or what is the user.name. Everything is given over here. So I will go ahead and set my git email ID. So here in the email ID, whatever is the GitHub repository email ID, you have to put it over here. So I will go ahead and write krishna06@gmail.com. Okay, and I'll go ahead and execute it. And then I will go ahead and copy this over here and write my user.name, that is Krish. I'll just write my username, that is Krish Nayak. Okay. Now once this is done, that basically means my global config email and name has been set up. So I will go ahead and clear the screen. Okay. Now what I'm actually going to do quickly over here is that I'll just say git commit first commit. So now all the file is ready for the committing purpose, and all I have to push before pushing, I have to set up my git branch also. So git branch will be set to -m main, okay, and then after that the next step is that we're going to add this specific origin over here so that it will know where to commit, in which GitHub repository to commit. So once I have done this, perfect, and here the next step what we'll do, we'll just do git push -u origin to main. Okay, so I hope this all steps, I'm just repeating it again, I hope this has been taught earlier in the project itself. Now the extension GitHub wants to sign you using GitHub, so just allow this, you'll be getting a code, copy this code and open it, and here authenticate each and everything. So just paste the code over here and click on continue. So it'll ask for the authorization, give the authorization, use your password or your mobile, whatever is required, and just confirm it. So this authorization is set and your code will get pushed with respect to all the things that is there. Now if I go and reload this, you'll be able to see that my GitHub code is available over here, right? So I hope you're able to understand how to develop a web application, and we have also done the GitHub repository. Now in the next session, what we're going to do is that we're going to use AWS console, and we're going to use elastic beanstalk, and we're going to use code pipeline, and we're going to deploy the code, right? So yes, this was it. Now in the next video, we're going to focus on the deployment part, right? So yes, this was it from my side. I will see you all in the next. Hello guys, so in this video, now we are going to focus on deploying our end-to-end project into AWS Cloud, and specifically we are going to use Elastic Beanstalk. Now, how the deployment is going to happen, what are things you specifically require, I will go ahead and step by step show you. Please make sure that you follow this particular video till the end so that you'll be able to do the specific deployment. Just to give you an idea what exactly we are doing, right now our code base, the entire code base is basically in our GitHub repository, right? Now we need to do the deployment in AWS, and specifically here we are going to use Elastic Beanstalk. Now what exactly Elastic Beanstalk is, it's just like one kind of Linux machine, you know, where you'll be able to create the environment, where you'll be able to run the code, where you'll be able to run your application in short, okay? So we are going to deploy our code base entirely from here to Elastic Beanstalk. Now before doing the deployment, there will be some configuration that will be required, right, inside this, right? Now some configuration we need to create in our code base repository, okay? So here you require some configuration, right? The configuration will be something related to the initial starting point and all, okay? We'll talk about that. Now, from this particular repository, okay, if I really want to do the deployment to this Elastic Beanstalk, so I should be able to create a mechanism from where we should be able to push the code, right? And this code will basically be created, will be pushed in the form of pipelines, okay? So this pipeline is just like a medium wherein I will be able to connect my GitHub repository to my deployment environment over here. And whenever I make any changes to this environment, I will be able to automatically deploy just by a click of button, okay? Automatically deploy just by a click of button, okay? So this pipeline will basically be created by using code pipelines, which is available in AWS, okay? So this code pipeline is just like a connecting medium between the GitHub repository to the Elastic Beanstalk, okay? Now let's go ahead and let's try to see how this deployment is done, okay? So first of all, as I said, some configuration is required in our code base repository. Now what are the specific configuration that is required? Here we will be creating one folder, okay? And this folder name will be .eb extension. Okay, so .eb extensions. Okay, so this is the folder structure that we really need to create. .eb extensions. Now inside this, I will be creating my one python.config file. See, whenever you are in that Linux, right, we'll be selecting a Python environment. So for that, we require this specific config file. And in this config file, we will be able to just put this configuration. And this configuration is nothing but it is just written as AWS Elastic Beanstalk container Python. This is just like a container that we are giving in the form of Python. This is fixed. And over here, WSGI path from where my application is going to start. This application is nothing but indicating to my application.py file. And inside that, this application is basically getting called over here, right? So that is the reason why I have specifically written application over here, and I have renamed my the file name to application. And this is what the AWS Beanstalk will basically be looking at with respect to the configuration. So just consider this as one kind of configuration that we already need to do the setting with. Okay. Now this is done. What we are going to do again, I'm just going to go to my terminal and quickly commit all this code. So here I'll write git add dot, okay, and then probably I'll write git commit, and I will say -m, and I will say beanstalk configuration, okay, configuration. Now I will just enter it. So here you can see what are changes I have done, 3 insertion with respect to 3 lines of code, and then I will write git push -u origin to main, okay. So once I write this, here you'll be able to see all the push will go. Now if I reload this page, so here you can see .eb extension, right? Again, let me see the name .eb extension, and inside this I have my python.config with all respect to all my configuration file, application.py is over here, and we are ready to go, okay. So now let's go to my AWS console, and here I will go ahead and select Elastic Beanstalk. Now in the Elastic Beanstalk, in the left hand side, go to the application and create a new application. So here I'm going to create a new application. I will go ahead and write the same thing. So I will write test forest fire. So this will be my application name, test forest fire, okay? And by default, I will not select any keys as such, okay? These keys need not be selected, and we can just go ahead and probably click on create tag, right? So yeah, I don't require this. Let me do one thing, okay? Let me just go to the Beanstalk. From here, we'll try to create it, okay? So first of all, we'll create the application over here, and now let's go ahead and write my application name, test forest fires. Don't select anything that is related to application tag. Now you need to select the platform. Now see, as soon as you select Python, this is giving you an Amazon Linux machine, right? And it has Python 3.8 running on it, okay? So this is what is the environment that you're specifically having. Now, if you go to the third part over here, you can either upload your code in the form of zip file, or you can first of all create a sample application and then probably connect it to your GitHub repository using the code pipelines, okay? So as I said, this code pipeline. Right now we are just setting up this, okay? Later on we'll set up this part, okay? First we'll set up this, then we'll set up this. As I set up this is nothing but a Linux machine. We'll create an environment, okay? So let me go ahead and create the application. So here my application will get created with a new environment name, okay? It will start creating a new environment name, and now you can see that new environment is getting created. Now this is going to take some amount of time. Till then, I will just go ahead and open my AWS console. Now once we open this AWS console, now I will go over here, and this pipeline we need to create, the code pipeline through which we will try to integrate with the GitHub repository, okay? That is what we're going to do. And for this, I will go and search for code pipeline. Now see, what is this code pipeline? It is releasing software using continuous delivery. So if I say over here, with respect to my code, over here continuous delivery is happening to my machine where my code is basically running, okay? So I will just go and click on this, okay? Then again here, the first thing is that just go to the code pipeline over here, and we will start creating our first pipeline. So to create the pipeline, I will just go ahead and write my same pipeline name. So I will say test forest fire pipeline. So I will say pipe, okay? And then No need to select any advanced settings, new service role, just click on this and click on next. Now the source provider is super important. What source provider you're taking your GitHub repository, your code from. It can be Bitbucket, it can be S3, it can be Amazon ECR. Right now I'm going and selecting GitHub version 1, right? So GitHub version 1 basically means from the GitHub repository, specifically this particular repository, I want to take up my code and then deploy it into my Elastic Beanstalk, right? Elastic Beanstalk. So for this, I need to connect to my GitHub. So I will go ahead and connect it. So it will ask me for the authentication request. I will go ahead and confirm it. Okay. Once I confirm it, I will go and search for my repository name. So it is nothing but test for fires, test forest fires. I've selected it. The branch I need to select, that is main. And now this GitHub webhooks is just triggering that particular GitHub repository to my Beanstalk environment, right? So for that, I will go ahead and click on next. Now I don't have to build my code right now because I'm not doing any kind of integration. I'm just trying to deliver my entire code to the environment and to the application where I need to deploy it and run it, right? So I can skip this build stage, but later on when we see some of the projects, we'll also be using this. So I will go ahead and skip it. Now if I go to the deploy provider, here you have multiple deploy provider, right? What deployment provider you want to use is nothing but AWS Elastic Beanstalk, right? Because here is where you really need to deploy your solution. You can use EC2 instance, and there are multiple other options. See, you have ECS, you have AWS, Amazon S3, but right now I'm going to use Beanstalk. Okay. Now let's go ahead and see whether my environment has got created or not. This is probably taking some amount of time. And now if I probably go and see on my environments and just execute this, here you'll be able to see that test forest fire environment has got created, right? So this is what we are basically going to use. Now we are good with that. So what I'm going to do, go to my pipeline and search for my application name. So test forest fires is there with respect to my application name. The environment name will be test forest fires /env, which I had actually created. Now once I go ahead and click on next, so this is my entire setting. See the pipeline setting. This is the pipeline setting. Then this is my action provider from which source I'm getting my entire code. That is the GitHub, right? So from GitHub I'm getting it. So we have done this setup. See this entire setup. It knows from where I'm getting the particular code where I need to deploy, right? So that deployment part will be in the last stage. That is over here, right? And this is getting deployed in the Elastic Beanstalk. Now what I will do, I will just go ahead and create my pipeline. So once I create the pipeline, it is going to take some amount of time. And this execution will happen. The pipeline will get created. It will probably take some amount of time. Now here you can see two main part. One is the source part, and then from that source we are just going to deploy it in the AWS Elastic Beanstalk, right? So this process will be going on. It will probably take some amount of time. Now you can see that after some time this has got succeeded, so it is able to connect to the source. Now the deployment will take some amount of time because the code will get deployed. So we'll wait till that time till the deployment happens. Okay. So guys, now here you can see that my deployment has been done. Now green signal is given just like that. Let's open and see over here. So as soon as I open, okay. Now if the health is okay, that basically means you've not got any error. If you're probably getting red color, then obviously you've got any error. So please make sure that you download my code repository and follow the same steps again. Now in order to see whether everything is working fine or not, I'll just click on this URL. Now here I'm going to get welcome to homepage, right? Now let's go ahead and see with respect to my /predict_data. Data. So here you can see my this page is coming. I will just select some values. Let's say I go ahead and select 36. I am going to select some other values over here. Rain this. Okay. It is up to you, whatever values you select. And if I do the prediction, here you'll be able to see that I'm able to get the output, right? So quite good, quite amazing. We have done this with respect to the values that we are specifically getting. This is super amazing. We are able to do the predictions and all. Yes, this was all about the deployment part. I hope you like this particular video. Yes, this was it from my side. I'll see you all in the next video. Have a great day. Thank you and all. Take care. Bye. So in this video, we are going to discuss about a new machine learning algorithm which is called as logistic regression. In our previous video, already we have completed linear regression algorithm. Now let's go ahead and understand the in-depth maths intuition behind logistic regression. But remember, this logistic regression is actually used for solving a binary classification problem. We'll try to understand the entire maths, how logistic regression basically works, and we'll try to discuss some use cases, and we'll try to understand what is the cost function that is used and other things. So without wasting any time, let's go ahead and let's try to solve this. Now, first of all, whenever I say binary classification problem, what does binary classification problem actually mean? Let's say I have a specific data set. Now in this particular data set, as I said already, right, my output feature will be a categorical feature, right? Over here, specifically, we'll be having binary categories. Okay, the output feature or the dependent feature. Let's say I'm just going to consider with one feature as an example so that I will make you understand with this, and then we'll try to understand the other examples also. So let's say in my feature 1, I have something called as study hours. Okay, and the output feature is that whether the person is going to pass or fail. Okay, so this two specific feature I have, and let's say I have a data points like 2 hours. If the person studies for 2 hours, probably he's going to fail. Okay, if the person probably studies for 3 hours, he is going to fail. Let's say if the person is going to study for 4 hours, I'm just saying that okay, the person may fail. Okay, you may be thinking, why are you writing all the persons are actually failing? I'm just taking it as an example. Okay, so let's say if the person is studying for 5 hours for a particular exam, at that point of time the person is actually passing. Similarly, 6, 7, I have a lot of data points like this. Okay, and this data points also will consider it as pass and pass. Okay, now how can we basically create a machine learning algorithm which will, first of all, whenever they take this study of hours, so suppose if my machine learning algorithm takes study of hours as an input, it should be able to predict the output whether the person is actually passing or failing. And why we say this as a classification problem? Because in our output we have two categories, so binary categories. So that is the reason why we use logistic regression to solve a binary classification problem. Now let's think over this and probably let's plot this in one kind of diagram. Okay. Now the first question that may rise, Krish, why the name is logistic regression, even though it is a classification problem, right? Why do we say regression? Okay. And if I consider this data set, can we solve this particular problem statement with the help of linear regression that we have learned in the past? Okay. So let me do one thing. Let me take this as an example. So suppose if I start plotting, okay. So let's say in my x-axis I actually have study hours, okay. And let's say with respect to my y-axis, I will be having two categories. Either this will be pass or this will be fail, right? So this specific point will be fail. I will indicate pass by 1. Okay, I'm just assigning a label, right? So let's say pass is 1 and fail is 0. Okay, and I have study hours. So let's say this is 2, 4, 2, 3, 4, 5, 6, 7, 8. Right now, if I try to train this model, then let's say we are trying to solve this particular problem statement with the help of linear regression. So over here you can see for 2 hours the person is going to fail. So over here, let me
make a point over here. So if the person studies for 2 hours, the person is going to fail. If the person is going to study for 3 hours, 4 hours, and 5 hours, the person is going to fail. And that is what my specific data set says. Let's say this 5 hours is fine because 5 hours, if the person studies for 5 hours, the person is going to pass. So I'm just plotting this particular data points. When it is 2 hours, the person is going to fail. That is 0. If the person is studying for 3 hours, he's going to fail. He or she is going to fail. And if the person is studying for 4 hours, he or she is going to fail. Similarly, when the person is actually studying for 5 hours, the person is going to pass. So let me just make some points like this so that this will indicate my one line. So I'm just going to make this specific line, or let me put some dotted points so that it will indicate you. Okay. So when the person is actually studying for 5 hours, I'm basically going to make a tick over here. Okay. That basically means the person is going to pass. Similarly, when the person is basically going to study for 6 hours, he's going to pass. He or she is going to pass. And if the person is basically studying for 7 hours, he or she is going to pass. Okay. Now, whenever I have this kind of data points, if I really want to solve this with linear regression, then how can I solve? Understand the main aim of linear regression. We try to find out the best fit line. Right now, with respect to this, I will try to create a best fit line. Let's say this is my best fit line. Okay, this is my best fit line. Now, this specific best fit line, what does it indicate? Because obviously, right, whichever will be the minimal error, if you combine it, we'll try to create the best fit line that we have already seen in linear regression. This midpoint is basically 0.5. Now, with respect to this particular best fit line, we are trying to just understand, can we solve this problem statement with the help of linear regression first of all? Okay, so with the help of linear regression, definitely we created this. Now, what I'm saying is that anything, right, with respect to any value, suppose with respect to this particular experience, what should be your output? So I will try to predict it like this, right? So from this particular point, let's say this is my new test data, I will try to predict it over here, and this will in turn get predicted over here. And if I say that, okay, if my value is less than or equal to 0.5, I'm going to say my output is 0. And with respect to any study hours, suppose at this particular study hours, if I try to plot it, I'm also getting somewhere here, and this is above 0.5, right? This is above 0.5. So anything that is greater than 0.5, we are going to consider it as 1. So this is how I'm trying to solve this binary classification problem. Okay, so this is perfectly fine, right? So definitely you can see over here with the help of linear regression also we are able to solve by putting this particular condition that with respect to any new data points, if it is coming less than 0.5, then we are going to basically consider it as 0. And with respect to any new data point, suppose if it is coming greater than 0.5, this is 0.5, right? This is 0.5, right? If it is coming greater than 0.5, then I'm going to basically consider this as the person is going to pass. Okay, so this is what we have basically considered. Now, what is the problem with this? Okay, now you may be thinking this is fine, right? We are able to solve this with the linear regression. Now, why we have to actually learn logistic regression? Now, let me say that I'm introducing one outlier. Let's say if the person is studying for somewhere around 12 hours, so this will be the new point over here. So obviously, when the person is studying for 12 hours, obviously he has to pass. But now, let's say in my training data set, I have added an outlier. So one outlier I've added. If the person is studying for 12 hours, so he's also going to pass. Now, because of this outlier, if I now again retrain my linear regression model, now you'll be seeing that my line will basically get slanted towards this, right? So my best fit line will completely change because of the outlier, right? Now, just see the scenario. Now you can consider that if I try to plot 5, okay, and here you can see that I'm plotting from here and it's coming less than 0.5, right? So this basically means even though the person is studying for 5 hours, he or she is actually failing. But in our training data set, it shows clearly that if the person is studying for 5 hours, he or she is actually passing. So this is the biggest blunder, right? With the help of linear regression, because as soon as a new data point came, because of the outlier, now you can see that I'm getting a new best fit line. So this is my new best fit line, right? Because of the new point, best fit line, right? Now here you can clearly understand what is actually happening is that because of an outlier, my entire line was changed, and now because of this, most of my data points, that were initially with respect to that many number of hours, which was giving 1, now it is basically giving 0 as an output. So this is the biggest blunder. So this is one of the issue with linear regression. The second issue is that now see, let's consider this. This white line, okay? Now with respect to the 8 hours, right? Obviously, if I try to plot this over here, and with respect to this, if I try to plot it, now in this scenario, you can see that my output is coming greater than 1, right? Greater than 1. And similarly, let's consider one more point, which is somewhere here, right? Let's consider this. And now if I try to plot it over here, I'm getting a negative value, right? So I'm also getting a value that is greater than 1, and I'm also getting a value that is less than 0, right? See, this 2 scenarios is also there. But with respect to binary classification, we should always think of getting the value between 0 to 1, right? This condition should always keep on matching, right? This condition should be fulfilled. If it is less than or equal to 0.5, it should be 0. If it is greater than 0.5, it should be 1. But here, you can see that it is either going greater than 1 also, it is going less than 0 also. So we are also getting a negative. So this is again a problem with linear regression. So we should try to find out a way wherein we should try to not extend this line from here. Instead, we should try to squash this line from here. So if we squash this line from here, that basically means I'm not extending the best fit line. I'm also squashing it from here, and I'm also squashing it over here. So if I squash it from here and here, you will be able to see I will always get my answer between 0 to 1. And this squashing is only possible with the help of logistic regression. Okay? So I'm just going to make 2 important points why we cannot use linear regression for classification. Okay? Linear regression for classification. So just pause the video and think over it. Okay?
New to Fiverr.
First is if I have an outlier, then there is a biggest issue, right? Entirely my best fit line changes, right? The best fit line completely changes. Best fit line changes. This is one of the issue, right? Let's talk about the second one. Apart from the outlier, what is the other issue that you saw? I'm actually getting greater than 1. My output is also coming as greater than 1, and it can also come less than 0. So what we should do, we should basically squash that line. And squashing that line is not possible by linear regression, right? How squashing? You're saying like I'm restricting the output that it should be between 0 to 1. So this is only possible through this squashing. So how this squashing will happen, we'll try to understand in logistic regression. But I think through this video, I've understood why we cannot use linear regression to solve a classification problem, right? So I hope you have understood this. In the next video, we'll try to understand about logistic regression, and we'll try to see how this squashing will also happen. So yes, I'll see you in the next video. Thank you. Now we'll try to understand how logistic regression solves a classification problem. Already from our previous video, we understood why linear regression cannot solve a classification problem over here because we have 2 issues. Because of the outliers, this line, the best fit line may move abruptly here and there. Okay. And the second thing is that we were trying to get an output that is greater than 1 or less than 0. Okay. So these 2 conditions were there. Now let's go ahead and let's try to understand. Now, as I told you that if we really want to prevent from getting an output that is greater than 1, we have to basically squash this result. Similarly, we need to squash the result over here, right? So this 2 squashing needs to be done. Already we know that this best fit line can be created with the equation s theta of x is equal to theta 0 plus theta 1 multiplied by x1, right? So this we have already learned in the linear regression, right? But and this is nothing but it actually gives us the best fit line. So this yellow line that you basically see, right? This is basically given for this particular equation. But we don't want this specific equation, right? Because from here we really need to squash it. And how this squashing is basically possible, that is what we are going to see. So guys, today I'm going to introduce you to a new activation function. We also say this as an activation function, which is called as sigmoid activation. Okay, sigmoid activation. Now sigmoid activation, what is the so important thing about sigmoid activation is that this sigmoid activation is basically given by the equation 1 plus 1 1 divided by 1 plus e to the power of minus z. Okay. Now, whatever the z value is, whatever the z value is, and if I try to plot this sigmoid activation function, it looks something like this. Okay. So always remember the sigmoid activation function. If you probably try to play with any z value, okay, the sigmoid activation function that you are probably going to get, and I will probably give this denotation as sigmoid of z, right? So with respect to any z value, always remember your sigmoid outputs between 0 to 1. Okay, 0 to 1. So this is one condition, and your sigmoid activation will have a curve which will look something like this. Okay, which will look something like this. Let me just again draw it a little bit properly. So this is how a sigmoid activation function will look like. That basically means your value will always be between 0 to 1. And this mid one is basically your 0.5. That basically means whenever your z value is greater than 0, understand from this, whenever your z value is greater than 0, then your sigmoid of z, right, is always greater than 0.5. Okay, so greater than or equal to 0.5. If I say greater than or equal to 0, okay, so at any instance, whatever z value you select, and you write out, you probably go and Google over there and you just say that, draw me the curve of this specific equation, which is called a sigmoid curve, right? So this sigmoid curve will always give this, and whatever z value, irrespective of any z value, let it be a negative or positive z value, your values will always be ranging between 0 to 1. Now, because of this equation, what we are going to do on this best fit line, we're just going to apply the sigmoid activation function. Okay, so that is what we are actually going to do in order to achieve this. Okay, so in order to achieve this, now what will happen is that both the problems will actually get solved since we are squashing it over there, right? So any outliers that also comes in the future over here will also be giving the output as 1. Okay, so this is how we are going to do it. Now let's go ahead and write out our all the equation that is required. Okay, now first step is that in logistic regression we also create a best fit line, and then on top of it we apply a sigmoid activation function. So let me go ahead and write our new function, right? So I will write h theta of x. Now always remember, when I'm writing h theta of x, I'm basically going to use the notation sigmoid because I'm going to apply sigmoid activation function on this specific equation if I have just one independent feature, right? If I have multiple independent features, then it becomes theta 1 x1 plus theta 2 x2 plus theta 3 x3. But let me just show you with respect to this, and you'll be able to understand that. Okay. Now what we are going to do over here is that we're just trying to apply this activation function, which is basically given in the sigmoid, and here this sigma I'm going to denote it by 1 plus e to the power of minus z. Okay, and let's consider that this specific value is z now. Theta 0 plus theta 1 into x1. Okay, so let's consider this value is z. So in short, I can basically write sigma by z. Okay, which in short I can basically write h theta of x, which is the usually whenever we even in linear regression, right, we took theta 0 plus theta 1 multiplied by x. That is the equation. Now h theta of x, the hypothesis that we're going to apply will be basically 1 to the power of e to the power of minus z, where z is nothing but this specific value, which is nothing but theta 0 plus theta 1 into x1. Okay, x1 or x, anything, right? So what we are doing, first of all, a best fit line is getting created. On top of it, we are applying a sigmoid activation function. So always our output will be between 0 to 1, right? So this is the entire hypothesis that we are going to use. Let me again highlight it. So this is the entire hypothesis that we are going to use. So I'll just mark it like this. So this is my logistic regression hypothesis. Okay. So this is my logistic regression hypothesis. Logistic regression hypothesis. Okay. And here you know that z is nothing but z is theta 0 plus theta 1 into x1. Okay. So guys, I hope you have understood the logistic regression hypothesis as I discussed. So this is basically the equation of the hypothesis. Now what I'm actually going to do is that let's go ahead and consider the linear regression cost function, and then we'll try to modify the logistic regression cost function. Okay. So I'm just going to write over here linear regression cost function. I hope everybody remembers what linear regression cost function is. Okay. Because we have spent a lot amount of time in understanding the theory of that. So this is basically j theta 0 comma theta 1 is nothing but 1 by 2m summation of I is equal to 1 to m. Okay. And this will be h theta of x of I. Okay. Minus y of I whole square. Right. So obviously you know what h theta of x is in the case of linear regression. It is nothing but theta 0 plus theta 1 into x. If you just have one single independent feature. So similarly, what I'm actually going to do, I'm going to write it for the logistic regression also. So logistic regression cost function, since we are using regression somewhere, right? And later on we are applying an activation function which is called a sigmoid. So logistic regression, if I really want to write, I can basically give the same notation over here also, something like this. So this will be j theta 0 comma theta 1, which is nothing but 1 by 2m summation of I is equal to 1 to m. Here also we'll try to use the same notation. Just a second. But what is the thing that is basically changing? It is nothing but your h theta of x. So here I can definitely write my h theta of x is nothing but 1 plus e to the power of minus z, and z is basically given by theta 0 plus theta 1 into x1. Okay, so this is how we have probably learned it from here, right? Because z is nothing but theta 0 plus theta 1 into x1. So now if I use this notation, understand what will happen. If I directly use this cost function, and inside this cost function, what is h theta of x? It is nothing but this sigmoid activation function, right? In short, this is basically sigmoid activation function. Now can we get the gradient descent curve with the help of this particular cost function? The answer is no, guys. Why? Because this cost function, if I try to plot it with respect to theta and cost, this is going to give me a non-convex function. Okay, non-convex function. And this equation that we probably saw, this will give me a convex function. Now the gradient descent. Now for this, what is the gradient descent that is usually created when you try to create a plot with respect to theta and j of theta? You will be seeing you'll be getting this kind of gradient descent, right? And over here, this will basically be your global minima, right? Global minima. So this is specifically your convex function. So I really want to call this as my convex function. So gradient descent is actually a convex function, right? Gradient descent is actually a convex function. Now if I try to use this equation that is there and try to plot it, then what kind of curve will I get? So if I try to plot it over here with respect to theta and j of theta, here you'll be seeing that we will be getting this kind of curve, something like this. Okay. And what is the problem with respect to this particular curve? It is, first of all, it is non-convex. Okay. So it is non-convex. Whenever it is non-convex, that basically means obviously this is my global minima. Okay. But here you have some more points, and these points will basically create something called as local minima. Now, what is the importance? What is the disadvantage with respect to local minima? Because whenever I come at this particular point, and if I try to find the slope will always be 0. And if the slope is always 0, the theta will be remaining stagnant at this place. It won't be able to increase or reduce, right, to come to the global minima. So it will be very, very difficult to come over here. So this is basically my global minima. So if I probably use this equation, right, and if I try to create my relation between theta and j theta, I'm going to get this kind of non-convex function. So it is proven also, guys. I don't want to do the proof entirely and probably just try to plot with respect to each and every point. But if we try to use this, we are going to get a non-convex function. Now, in order to prevent this, what we can do is that let me again write the cost function of logistic regression. So let's say this is my cost function. Here I'm basically writing 1 by 2m summation of I is equal to 1 to m, and here I am writing h theta of x of I minus y of I whole square, right? And obviously everybody knows what is h theta of x. It is nothing but h theta of x of I is nothing but 1 plus e to the power of minus z, where z is nothing but theta 0 plus theta 1 into x1, right? So this we are basically discussing from that much time, right? This is very, very simple. Now let's consider this is my cost function. Now instead of using this as my cost function, let's consider this. I'm going to indicate this as cost h theta of x of I, comma y of I. Let's say I'm denoting it. Let's denote this value as this. Okay. So what we can do in order to get a convex function, we can basically write cos theta of h theta of x of I comma y of I. I can use this equation, and yes, we can also prove this, but I'm just going to write down this equation over here because the proof is not that important. If I say minus log of h theta of x, okay, and if my y value is 1, okay, so if my y value, in this particular case my y is 1, I'm going to use this as my cost function, which is basically going to get replaced over here. Okay, and one more condition is that if my y is equal to 0, I may probably use something called as minus log 1 minus h theta of x. And why you are using this? Because this two specific thing, this two log, we basically say this as log loss. Okay, log loss. And if you're using this log loss, this will be able to create a convex function that is basically required in terms to get the global minima. Okay, so we are going to use these two conditions over here, right? Over here, when my y value is 1, I'm going to use this equation. When my y value is 0, I'm going to use this equation. And these two equations, when we are using with respect to different y value, we basically get a convex function. Okay, so that is what we get it mathematically. Again, I don't want to prove this as a formula. You just need to remember it. So in short, if I try to combine this, my cost, this specific value can be replaced by something like this. So I'll go and replace it something like this, where I'll write cost. Sorry, cost, not cost, it is cost. Did I write cost? Cost over here. Fine. If I try to write cost, it will be cosine, right? So here I'm going to write cost h theta of x of I, comma y of I. If I try to use this log loss, we can definitely create an equation which is like y log of h theta of x of I, y log of h theta of x. Just a second. Okay. So I'm just going to write minus y log of h theta of x minus 1 minus y of 1 minus h theta of x. Now here you can definitely see that if my y value is 1, if I replace y value as 1, I'm going to get this specific equation. Okay. If I replace y value with 0, then what will happen? This will entirely become 0. This into this will become 0. So I'm actually going to get something called as 1 minus 0. This will be 1. So I'm actually going to get, okay, I missed one thing over here. Just a second. This equation will be changing a little bit too. After this minus, I'll be using 1 minus y log of 1 minus h theta of x. Okay. So in short, if I replace y with 1, then I'm going to remain with only this specific equation because 1 minus 1 will be entirely 0. This entire term will be 0. If I replace y with 0, at that point of time, this will become entirely 0, and I'll be remaining with this specific equation. So with the help of this, what we will be able to do is that we'll be able to get a cool convex function as a gradient descent. Okay. So that is the reason why we specifically use it. Now what I'm actually going to do, this entire cost function that I've actually written over here, I'm going to replace it with this specific value. So finally, my final conclusion with respect to j theta 0 comma theta 1 is nothing but minus 1 by 2m. Okay. Summation of I is equal to 1 to m. Why I'm taking minus? Because here both are minus, right? So I'm going to take out this minus outside. So finally, I'll be able to write y of I, okay, log h theta of x of I minus 1 minus y of I log 1 minus h theta of x of I. So this will be my entire cost function in short. Okay. So this will be my cost function. Now what do we do with the help of cost function? And always remember, this cost function will actually give us a convex function. Okay. This cost function will be actually giving us a convex function, or I can also probably call it as gradient descent. Okay. So this is my cost function. Again, the lines are not getting created properly. Let me try it out once again. Sorry for the inconvenience. So here is my cost function. Now our major aim is always to minimize cost function by changing value. So here my cost function j theta 0 comma theta 1 by changing theta 0 and theta 1, right? So in short, if you remember, again, we have to write the convergence algorithm, and in this convergence algorithm, we repeat. So here I'm just going to say convergence algorithm. We are going to just repeat one important step. That is nothing but we are just going to change theta j value, which is nothing but theta j minus learning rate derivative of theta j with respect to j theta 0 comma theta 1. So in short, we're going to find out the slope to find out the best fit line, and here your j value is 0 and 1. And obviously that derivative part, whatever we have written in the simple linear regression, that same thing will be writing it over here, right? So this is what we have done. You need to really understand why we did not use this specific cost function, because this was giving us a non-convex function. In order to replace this non-convex function, we use something called as log loss, and this is basically my log loss, wherein I'm using two specific things with respect to this cost theta of xi minus y of I. Whenever y is equal to 1, I'm going to use this. If y is equal to 0, I'm going to use this. Okay. So h theta of x is nothing but this is where I'll do the predictions, right? Predictions with respect to any value. So finally, I write my cost theta of x as this specific equation. This will definitely create a convex function or gradient descent. So finally, you'll be able to see that I'll be writing my cost function as j theta 0 comma 1, and this is the entire equation. And our main aim is to minimize the cost function by changing theta 0 and theta 1, and we'll try to repeat the convergence algorithm where we'll keep on updating theta j value, and where j is equal to 0 and 1. And similarly, if I have multiple features, the j will keep on increasing, like 0, 1, 2, 3, 4, 5, 6. So I hope you have got an idea about the entire mathematical intuition and how we are using logistic regression to solve the classification problem, right? So yes, in the upcoming videos, we're also going to discuss about performance metrics. This was it from my side. I'll see you in the next video. So guys, in this video, we are going to discuss about performance metrics, which are specifically used in binary classification, multi-class classification. We're going to cover topics like confusion metrics, accuracy, precision, recall, and F-beta score. Now guys, let's say I have created a model using logistic regression. So I'm just going to run this. So here, let's say I'm using a logistic regression, and in this logistic regression, we are able to classify what is the main aim in logistic regression. This is basically a classification problem, and we try to split this by creating a linear line. Okay. And already we have discussed about the cost function and all. Now suppose if I probably get a new point over here, this basically means it belongs to this category. Or suppose if I get a new point over here, it basically means it belongs to this particular category because it is below the line. Okay. Now, if I really want to understand how my model is actually performing, see, in linear regression we discussed about something called as R squared, right? R squared and adjusted R squared. Now these were the performance metrics that were used in the case of regression problem statement, right? Now in the case of classification, what all things we can actually use? So we use specifically called as confusion metrics, accuracy, precision, recall, and F-beta score. And in this video, we'll understand how through this particular topics we can understand whether our model is performing well or not. Okay. Now let's consider this simple data set I have. Okay. Now in this particular data set, I have all these data points x1, x2, and this is my output feature. This is my output feature. This is my input feature, right? And this is my predicted feature. Predicted feature basically means this is basically predicted by model. Okay, this y hat. Okay, so this basically shows that when my true output was 0, my model predicted it as 1, and similarly over here when my true output was 1, my model predicted as 1. Here it was 0, 0, 1, 1, 1, 1, 0, 1, 1, 0. Okay, so this is a simple data set, and I probably trained my model, and I'm getting this kind of predictions. Now the first thing that you really need to understand is something called as confusion matrix. Okay, whenever you get this kind of outputs, okay, basically once you find out a prediction, the first thing is that you create a confusion matrix. Now what is a confusion matrix? Confusion matrix in the case of binary classification is a 2 cross 2 matrix. Okay, so I'm just going to draw this 2 cross 2 matrix. On the top, I'm basically going to draw. I'm just going to write 1, 0. 1, 0 basically means this is with respect to the output. Ones and zeros are my output. Similarly, on the left hand side, we are going to write 1, 0. Now you really need to understand what the top 1, 0 basically indicate. This indicates my actual values. Okay, everything will make sense. Just focus on this actual values. And what this 1, 0 indicates, it indicates something called as predicted values. Okay, now let's try to, now suppose if I have this real output and the predicted output, how can I fill the confusion matrix with this data? Okay, now let's say my real output was 0, but my model predicted it as 1. So over here, how do I map it over here? So my real output is 0, my model predicted it as 1. Because I told you that this is the predicted part, right? So if it is 0 and my model is predicted 1, that basically means I've got this particular scenario, so I'm going to increase the count by 1. So here, let me write it down as 1. Okay, so I've got this particular count and this belongs to this particular box. Okay, similarly in the next field, you can see when my model, when my real output is 1, my model predicted it as 1. So this is fine, right? This is incorrect, this is fine, right? Our prediction should also happen like this. So where does this 1, 1 actually fall? So 1, 1 will actually fall over here, right? So we have something over here and I'm basically writing it. Okay, perfect. Then I have 0, 0, so I have 0, 0, it will be coming over here, so I'm going to increase the count by 1 over here. Then I have 1, 1. Again, 1, 1 is there, so what I'm actually going to do, I'm going to rub this and I'm going to make this as 2. I'm going to increase the count. Then again, I have 1, 1, then I'm going to increase the count by 1 more. Then 1, 2, 3, then again I have 0, 1. 0, 1 basically means this is 0 and this is 1. So I'm going to increase the count to 2. Okay. So let's say before it was 1, now I'm going to make it as 2. Perfect. And then I have 1, 0. 1, 0 is nothing but this specific field, so I'm going to write over here. Now over here, you know that if I consider 1, 1 value, this basically means my model has predicted correctly, right? Because this scenario is that my model have done the prediction correctly because my real output was 1 and my prediction was also 1. And in this particular scenario, when my actual value was 0, my model is predicting 0. So this is also correct, right? So out of this all results, this diagonal elements are the actual correct results, right? And this diagonal elements are actually the wrong results because when it was 0, my model is predicting 1, and when it was 1, my model is predicting 0. So these are my wrong results. Now this confusion matrix, I'm again going to draw over here, and I'm going to give you some notations over here, okay? So let me draw it over here and let me provide you some notations. Now notation 1 is over here, I'm using 1, 0, 1, 0. Whenever I have in the actual as 1 and predicted as 1, so we usually say this is the correct scenario, so I'll be writing it as true positive. When the actual value is 0 and probably my model has predicted 0, I'm going to basically write this as true negative. And when my actual output is 0, but my predicted is 1, that basically means this is false positive. Okay? And similarly, if my actual output is 1 and if my predicted is 0, I'm going to basically call it as false negative. Now this is super important in respect to deriving all this formula of accuracy, precision, recall and beta score. Okay, how we're going to discuss about it. Now out of this, if I talk about true positive and true negative, these are my correct results. And remaining F false positive and false negative, these are my wrong results. So if I really want to calculate my accuracy, so this formula will be true positive plus true negative divided by true positive plus false positive plus false negative plus true negative, right? So this is the specific formula with respect to this. Now what is true positive? Over here from this we can actually see this particular field. We'll just try to populate it. So it is nothing but 3 plus 1 because 1 is over here, 3 is over here, and then I'm going to add with 3 plus what is false positive, obviously it is 2, then false negative is 1 and this is 1. So finally I'll be able to see that I'm getting 4 by 7. So this whatever value I'm getting is basically my accuracy for this particular model output with respect to this, right? For with respect to this particular confusion matrix. So guys, now we have understood about accuracy. Okay, now let's go ahead and understand about the next performance metric which is called as precision and recall. And we'll try to understand when should we use precision and when should we use recall. Now let's consider that I have a data set. Okay, so I'm just going to consider, let's say I have a data set. Now in this particular data set, let's say that I have 1000 data points. Okay, so my entire training data set has basically 1000 data points. That basically means 1000 rows. And from this, I have 900 output categories as 1. So let's say this is a binary classification. Binary classification. Okay. Now one important thing that I really want to talk about is that suppose if we have a multi-classification, then the confusion matrix will not become 2 cross 2. Let's say if I have the number of output categories is 3, then this will basically become 3 cross 3 matrix. If the number of output categories are 4, then this becomes a 4 cross 4 confusion matrix. Okay. So let's consider that in my binary classification, I have 900 as 1 and I have 100 as, let's say 100 number of categories are basically saying it as 0. Okay. So in this particular scenario, you can see the ratio of the output categories with respect to ones and zeros are 9:1, right? So this basically becomes an imbalanced data set, right? Now in the case of imbalanced data set, I cannot directly use accuracy. See, I cannot directly use accuracy. If I directly try to use accuracy, let's say if I just create a blunt model, which is just saying that for all the input data points I'm going to get 1, then if you try to calculate, right, we'll be getting 90% accuracy. But in the real, it is not true, right? In an imbalanced data set, it can give you a completely biased result. So in order to fix this, we will try to use something called as precision and recall. Now we'll try to understand what exactly is precision and recall and what is the exact formula with respect to precision and recall. Okay. So first of all, let's go ahead and let's talk about the formula with respect to precision. Okay. So first topic that I'm going to cover over here is precision. Now I hope you have understood when we should not use accuracy. Let's say if you have an imbalanced data set at that point of time, I cannot use it because I'm getting this high accuracy for that, even though my model is bluntly saying 1 to every data point as an output. So precision is basically given by the formula true positive divided by true positive plus false positive. Now over here, the most priority is basically given on the false positive. Now let me make you understand what this formula basically says. So I'm just going to draw the confusion matrix again. Okay. And let's say this is my ones and zeros of the actual point, and this is ones and zeros of the predicted point. So this is my true positive, this is my false positive, this is my false negative, this is my true negative. Now, this precision basically says that out of all the, see, when I say with respect to true positive and false positive, right? So we are basically focusing on this two, right? So what does this particular formula say, right? And we know that this is basically predicted, and this is my actual result, right? So with respect to this, I can definitely say one very important statement, okay, from this particular formula. Out of all the predicted result, how many of them are correctly predicted? Okay, this formula basically says this, right? Again, let me write it down. Out of all the predicted results. Because if we are referring to this, right, or if I'm just referring to this, right, I can definitely say, okay, let me just make a little bit change over here again, okay. Let me make a simple change because again I miss, there is always a confusion with respect to precision and recall. So let me just make this statement again, okay. Out of all the actual values, okay, because when I'm referring to this two, right, so in short I'm referring to both the actual values, ones and zeros, okay. Out of all the actual values, how many are correctly predicted. That is what we are basically going to find out with the help of precisions. Okay. So out of all the actual values, how many are correctly predicted? That is what this precision basically talks about. Okay. So again, I'm going to repeat it. Out of all the correct results or actual values, okay, out of all the actual values or true values, we are going to find out that how many of them are correctly predicted. That is the reason why we are dividing true positive by true positive plus false positive. Okay. So this is the example. And again, I'll be talking about more examples as we go ahead. When should we use precision and when should we use recall? Now the second thing, if I talk about the recall formula, okay, my recall formula is something like true positive divided by true positive plus false negative. So now in the case of recall, I am considering this specific part, that is true positive and false negative. Now you can basically guess, and I can easily write out of all the predicted values, how many are correctly predicted, right? Correctly predicted. This is what we are trying to find out with the help of recall. And always remember, with respect to precision and recall, we should try to reduce this false positive and we should try to reduce the false negative. Now you may be thinking, okay, Krish, this is the formula, fine. But tell me, when should we use precision and when should we use recall? Okay. Now let me give you some of the use cases. Okay. Let's say my first use case is I want to create a model which will basically do spam classification. Okay. Spam classification. Now in spam classification, let's say my model, if my truth value is, right, if I get a mail and this is spam, right, this is spam. And if my model predicts this is a spam, then this is quite amazing, right? So this is the true positive result. So in short, my model is absolutely working fine. So this is good, right? This is how my model should perform. But let's say if my mail is not spam, and if my model predicts it as spam, then what will happen? This is a huge blunder, okay? Blunder. Because even though my mail was not a spam, my model is predicting it to the spam and it is sending to the spam folder. So by that way, I may miss my most precious email, right? So in this particular case, whether we should reduce false positive or false negative, now you need to understand over here, obviously. And obviously this all knowledge comes from domain expert also. But you should start thinking whether I should use precision or recall or something else, okay? So let's say this is 1, 0, this is 1, 0. Now in this particular case, if I say 1 basically means spam, 0 basically means not spam, right? So let's say this is spam and this is not spam. This is the predicted output. Now in this particular scenario, when my mail actual value is here, right? When my mail is not spam basically means here, and it is model is predicting as spam. So this is the error it is basically calling, right? It is basically coming up with false positive error, right? This is obviously true negative, this is false negative. But in this particular case, this is a blunder, right? So in this use case, I should try to reduce false positive because we understand that this kind of situation is a major blunder. Okay, major blunder, because when the mail is not a spam, my model is predicting it as a spam. So when my mail is not a spam, 0, my model is predicting as 1. So this is basically false positive. So we should try to reduce false positive over here. And for this particular case, here I will be using precision because precision formula is nothing but true positive divided by true positive plus false positive, right? So this is the formula of precision. Now you may be thinking, okay, this is my use case 1. You may be thinking, then where can you tell us some use case which actually deals with false negative? Okay, let's go with the use case 2. Okay, use case 2. Let's say over here, my problem statement is to predict whether person has cancer. I'll not say cancer, that is a very big disease. So whether the person has diabetes or not. Okay, let's consider this particular problem statement. Now in this scenario, let's say if in truth, right? Let's say if I probably take as an example, let's say in the truth, the person has a diabetes. Okay, and my model predicts the person does not have a diabetes, and my model predicts the person doesn't have a diabetes. Then this is also a very big blunder, right? This is also a very big blunder because if the person is having diabetes, my model should be able to predict that the person should have diabetes. Let's say in truth, if the person is having diabetes and my model predicts it has diabetes, then this is good, right? My model is performing absolutely fine. Similarly, if I say in truth, let's say my model is not having diabetes. Sorry, in truth, the person is not suffering from diabetes, but my model predicts that the person is having diabetes. So this is also wrongly predicted. But can I say this is a blunder scenario, right? Even though the person is not having diabetes, but the model predicts as diabetes. But it's okay, right? The person will go and probably again recheck or take second opinion in the hospital, right? So this kind of error is fine. It can happen. Not a worries with that, but you need to not focus much on this because the person can go with respect to second opinion and they can actually check. Okay, they can actually check in the hospital by doing various tests, right? So in this particular scenario, we will not focus on this, but this scenario we'll try to focus. Now in this scenario, should we focus more on false positive or false negative? Let's say I am just again creating my confusion matrix, and here I'll say person has diabetes and person has no diabetes. Okay. And this is with respect to the actual value. And here also person has diabetes and person has no diabetes. Now in this particular scenario, the truth is that the person has diabetes, okay? But the model is predicting the person does not have diabetes. So what in this particular case, what is happening? We are getting false negative as a blunder, right? So this is the most important error in this use case, in the use case of medical, right? In the use case of diseases. And this gets applied to every disease, right? So we should try to reduce false negative because if the person has diabetes and if my model is saying it does not have diabetes, the person does not have diabetes, then the person may also not go even for checkup. And he may miss that. And because of that, the diabetes may be a dangerous disease going ahead, right? And if we try to treat it in the early stages, some type of fixtures, will be able to prevent it, right? In the initial days, if we are able to capture that, right? So in this particular case, I should try to reduce false negative. So in this case, I'll be using a recall formula because in my recall, the formula is true positive divided by true positive plus false negative. So in this case, we will focus more on false positive to reduce it, right? So in this use case, our main focus should be that we should try to reduce false negative, right? So now I have told you with respect to different use cases when you should use precision and when you should use recall. Okay. Let me tell you one more simple problem statement. Okay. And then you try to do it as an assignment. Okay. And probably write down in the comment section. What if I really want to, like my model wants to predict tomorrow the stock market will crash or not? Stock market will crash or not? Crash or not? Now suppose if this is my use case, what do you think we should focus on? Reducing false positive or reducing false negative? Now this should be the answer coming from you. Just try to plot that again confusion matrix and try to understand and get it. Okay. So you can definitely try to do this and let me know the answer. This will be quite amazing if you are able to talk about it. Okay. Now let's go with respect to the one more amazing performance matrix which we basically say as F beta score. Now in F beta score, the formula that is basically given is 1 plus beta square precision multiplied by recall divided by precision plus recall. Okay. So this is the formula that we basically use for this. Okay. Now let's say if, because what will be this beta value, we will be selecting it. If false positive and false negative, because for some of the use cases, both false positive and false negative can also be important. If false positive and false negative are both important and we really need to reduce both of them, then my beta value is basically selected as 1. So here now, if I talk about this will basically become F1 score. F1 score is equal to 1 plus 1 square, and this will be precision multiplied by recall divided by precision plus recall. So in short, if I probably consider this value will become 2 multiplied by this one. And this term is basically called as harmonic mean. Okay, harmonic mean. Because this is nothing but the harmonic mean. I think you have heard of geometric mean, harmonic mean, something like that. Okay, so this formula basically says about f1 square. Now, this is my first condition. My second condition is that, let's say, if fp is more important, that is false positive is more important than false negative, then what we do in this particular scenario is that we try to reduce our beta value. So now we will be selecting our beta value as 0.5. So this f 0.5 score will be, in this particular scenario, what fp is more important than fn. So here I will be getting 1 plus, the formula is beta square, which is nothing but 0.25. Okay, and this will be precision multiplied by recall divided by precision plus recall. So this is the formula with respect to this. The final condition is that if false negative is more important than false positive, at that point of time, my beta value will become 2. So f2 score is nothing but 1 plus 4, precision multiplied by recall, precision plus recall. So this is my final output with respect to all the things. So if you consider if false positive is important, if false negative is important, if both are important, you can also use f beta score. Otherwise, you can also go with precision and recall. So I hope you have understood about all the performance metrics that we have discussed. This is just the part 1. In the part 2, we are going to discuss about ROC UC curve. So yes, this was it. And in the next video, we'll be discussing about that specific thing. Thank you. I'll see you in the next video. In this video, we are going to discuss about logistic regression for multi-class classification. And in our previous video, we have already seen for binary classification, right? And in binary classification, what we have done is, and what was the main aim using logistic regression was that, let's say if I have some data points like this of binary classes, let's say I may consider 2 classes like this, okay? Our main aim in logistic regression was to basically create a best fit line so that it should be able to divide the specific points. But what if in our data set, I have 3 output categories or more than 2 output categories? Now in this particular case, this is my class A and this is my class B, right? This is my class B. Now let's say that in one of the use case, I have more than 2 output categories. Let's say in this case, let me draw it again. Suppose over here, let's say this is my independent feature X and Y, and I have 3 specific categories, my 3 output categories, which looks like this, or more than 2. It can be more than 2, okay? But we will take an example with respect to 3, okay? Just to understand multi-class classification. So let's say if we have this 3 categories as my output, then how we can solve this multi-class classification problem with the help of logistic regression, okay? That is what we're going to discuss in this particular video, with the help of logistic regression. So one important parameter in logistic regression is something called as one versus rest, okay? And in order to solve this classification problem for multi-class, we can use this version of logistic regression. And we'll try to understand how this technique will be working if we use one versus rest. Now the main aim of one versus rest, and let's consider some examples. Let's say if I have some F1, F2, F3 feature, and this is my output feature. Let's say I have some data points like this, and this is my output 1. More data points, let's say this is my output 2. More data points like this, let's say this is my output 3. Again, I can have output 1 getting repeated. Let's say this is output 3. Let's say this is output 2. Okay, so let's say these are my input features, and here you can see in the output feature I have 3 output categories, that is O1, O2, O3. So that basically means I have 3 categories, right? Output categories. And let's say these are my data points, and it looks basically like this. Now with the help of one versus rest, what we do is that we try to create, internally multiple models, and each and every model will act as a binary classification. It will try to solve a binary classification problem. So how does this basically work? Let's say I'm trying to create a model M1. Okay, and this in model M1, just imagine that this is some internal model, and this what it will do is that it will try to create a best fit line in such a way that it will make sure that all these points that are below this best fit line will be one category, and all the other points that are above this best fit line, this will be another category, right? So here both these categories can be combined into one category. So this model will be able to differentiate this class and this specific both the classes. Okay, so here what we are doing is that internally we created one M1 model, and this will basically perform binary classification. And the binary classification will be performed in such a way that we will be having 2 sets of categories. This is not going to get considered as 2 separate categories, but both categories will be combined, and this will be one data set, and this will be the other data set. Okay. So what about the next model? Like since we have 3 categories, 3 models will get created. So right now we will get again another M2 model will get created. Now this model will make sure that it will try to create this as a best fit line, where it is going to consider this as one category and combine both this as another category. So this will basically be my M2 model, and it will solve this binary classification. Okay. And similarly, internally, we'll have one more model, which is like M3. And here, what it is going to do in this M3 model, it will try to create another best fit line, which will look like this, which will consider this as one category, and this both combined as the another category. So here, again, a binary classification will get created. Okay. So at the end of the day, what we are going to do is that we're going to combine both all of these outputs, and then we're going to decide in which block it basically belongs. Okay. So that is the entire agenda of this one versus rest. Okay. So to start with, what it will do is that all this O1, O2, O3, it's just going to do something called as one hot encoding. So here I will have O1, O2, O3, and for every model, how it is going to take the input and the output, we're going to discuss. So wherever O1 is present, this will basically become 1, 0, 0. So let me just write this as wherever O1 is present, this will become 1, remaining all will become 0. Wherever O2 is present, this will become 1, and remaining all will be 0. Wherever O3 is present, the last one will become 1, and remaining all will be 0. Similarly, over here you can see that we'll be having again 1, 0, 0. 0, 0, 1, and 0, 1, 0. Now at the first instance, if I probably create my M1, right? So let's say our main model is this. Internally, we'll be having M1, M2, M3. Why 3 models? Because I specifically have 3 outputs. And finally, the averaging of all these things will give me the output model of this classification. Now in the M1, what will happen is that we will take all these as my independent features, and the output feature will be basically O1, right? So what will happen in M1? We will be taking input features, which will be F1, F2, F3, and the output feature will be O1. Right? O1 basically means this entire column. Okay. Similarly, in M2, my input feature will be F1, F2, F3, but the output feature will be O2. Okay, so the O2 will be the output feature for model 2. And similarly, here we'll be taking the input as F1, F2, F3, and finally you'll be able to see that my output will basically be my O3 model. Okay. Now let's understand how the prediction for a new test data is basically done by using this specific concept. Now, as soon as I pass my new test data, now first of all, this gets passed to M1 model. let's say M1 model is giving you some probability. Okay, so obviously M1 model over here is the output is O1, right? So based on this, let's say it is giving some probability. Let's say over here I'm getting 0.25. Now similarly, when this test data is again passed to M2 model, the same M2 model, let's say over here I'm going to get 0.20 as the output. Okay, so this is the first output, this is the second output, and then finally when this test data is again given back to M3 model, and let's say the remaining thing that we're going to get over here is 0.55. So this is the probability that I'm going to get. Now here you can see the combination is 0.25, 0.20, 0.55. Now what does this basically indicate? Here, this is the output for O1 model. This is my, or I can basically write M1, M2 like this, right? So this is my M1 model, this is my M2 model, this is my M3 model. Now you know that the probability of M3 that is going to come up is somewhere around 0.55, right? So whenever this value is more, right? From when compared to M1 and M2, obviously 0.55 is more. So this M3 model you have to see for what output it has got trained. It has got trained for O3. Then definitely we can say that since the probability is high, this 0.55 will basically give us the output of O3. O3 basically means output 3, which is nothing but this is basically my category 3. Okay, so this is the entire understanding. Whenever we get a new test data, all the three models will give you different probability, whichever will be the highest probability. Then we can understand that for which model is basically giving that specific probability and what this model has taken as the output feature while training, right? So here you can definitely see O3 has been taken by M3. So that is the reason you can basically say that for this new test data, the output is category 3. Now what we are going to do is that we're going to see some practical application with both 1 versus 1 and 1 versus rest, and here you'll be able to understand most of the things. So I will see you all in the next video. Thank you. Hello guys, so we are going to start the logistic regression implementation with the help of Python and sklearn library. And while implementing logistic regression, we're going to solve both binary classification and multi-class classification. We have already seen the theoretical intuition behind it. We have also seen that how we can actually implement or solve a multi-class classification problem using logistic regression by using 1 versus rest approach. So let's go ahead and let's complete the practical part. First, we will implement a logistic regression. Then in the upcoming videos, we'll do hyperparameter tuning. And after that, we will solve a multi-class classification. So initially, we'll start with binary classification problem. Now, as we go ahead and do various implementation projects, I really want to introduce you to some amazing ways of creating data sets also. So today, as we start, we're going to use a technique of creating a data set. So before that, I will import some libraries like import pandas as pd, import numpy as np, right? Import matplotlib.pyplot as plt. These are the common libraries that we'll be importing, and I'll also import cbon as sns. Okay, and apart from that, I'll also write matplotlib inline so that I can display my plots over here. Now let's go ahead and first of all create a data set. Now for this, I'm not taking any CSV file as such. We will first of all try to create a basic way of creating a data set. So I'm going to import one important library called as from sklearn.datasets. There is a library which is called as make classification. Okay, so when you see over here, you have a lot of options like make by clusters, make blocks, make checkerboard, make circles, make classification. So I'm going to probably show you some of the techniques when we'll be using this to create some data set also. First, for right now, we are just going to use make underscore classification. So what this is going to do is that this is going to create a data set in the classification approach. So basically, it will try to create some independent feature and it will create output feature. And the output feature I can say that how many categories we want. Okay, so it will just try to create a data set and it will create it in such a way that we don't even have to do standardization. So that particular step we are actually skipping it so that we focus on the implementation part. So this is one of the libraries that we'll be using. Now let's go ahead and create the data set, okay, for our problem statement. Now here, I'm just going to use make classification. And in the make classification, once we initialize, what all things are basically there? First of all, how many number of data points you want, you can basically specify. How many number of features you want as your independent feature, we can specify. These are some of the parameters like n underscore informative, n underscore redundant. And if you probably see the definition, you'll be able to see it. N underscore informative is nothing but the number of informative features. Each class is composed of a number of Gaussian clusters, each located around the vertices of a hypercube in the subspace of dimension. So just to say that, we get a common data points which are clustered in cluster format. Okay. N underscore redundant basically says the number of redundant features. These features are generated as random linear combination. So all these features you can basically use. We'll also be using something called as n underscore classes. Now this will basically say that how many number of classes or output categories you want in your dependent feature. So let's go ahead and let's quickly create a simple sample data set. So here I'll write n underscore sample is equal to, let's say I want to consider 1000 data points. Okay. And then the next feature is that I will say, okay, over here, I'll say n number of features. Number of features I can basically consider 10 features. I really want 10 features, let's say 10 independent features. And then I will also be able to say number of classes. Let's say since I'm solving a binary classification, I'll say 2 output categories are there. Along with that, I can also specify some random state value. And what you can also do, you can also make sure that you can use number n underscore redundant and n underscore informative also. It is up to you. Whatever you really want to do while creating the data set, you can actually create. Now this will return two variables. One is x and y. This x and y are nothing but my independent and dependent features. Okay. So here, let me just execute it. Let me see what is this. Okay, perfect. So here you can see x and y. Now once I go ahead and write x, so here you'll be able to see all your 10 independent features with respect to this. All the data points are there. And probably if I try to convert this x into data frame, I can basically write pd dot data frame. And if I write x, here you'll be able to see this is how your independent features look like. So overall, 1000 data points, right? 10 features. So that is the reason you have 10 columns. So randomly, I'm trying to create some data set so that I can actually solve a classification problem. Similarly, if you probably go and see y, here you'll be having outputs like zeros and ones since this is binary classification. Now, perfect. We have done this. Now, what I'm actually going to do over here is that quickly do train test split. So I will write from sklearn dot model selection import train test split. And here I'm just going to do the train test split for x and y. So here I'm going to write x underscore train, x underscore test, y underscore train, y underscore test. Okay. And here I'm just going to use train test split. The x and y coordinates I'm just going to give. I'm also going to give my test size. Let's say 300 records I want in the test data. So I will give a test size as 0.30 and one more variable I will define random state so that if you use the random state, you'll almost be getting the same type of data set, right? Now here I've actually done the train test split. I have my x train, x test, y train, and y test. And we have done this many number of times in our previous problem statement. Okay. Now let's go ahead and try to implement logistic regression. Okay. So I will say from, or I can just write a comment saying model training. And here I will basically say from sklearn dot linear model. This is capital letter, so I don't want capital letter over here. It's okay. This kind of warnings will come. Or linear underscore model import logistic regression. Okay. And here also you have cross validation technique. And now in hyperparameter tuning, I'll show you different cross validation technique also. So here, first of all, I'll just create my model logistic. Logistic. Okay.
This is basically your binary classification problem. So if you probably go and see over here, if you press shift tab, or let's me execute and now press shift tab, here you'll be seeing different parameters that you can apply. Now this penalty L1 and L2 norms can also be applied in logistic regression, like we did it for linear regression. Whenever we apply this L1 and L2 norms, it becomes ridge and lasso regression. Obviously, ridge is used for reducing overfitting, and lasso is basically for the feature selection purpose. So that penalty parameter also we can assign in logistic, because at the end of the day we are creating a straight line to divide the points. Okay, and there are other features like total C. What is C over here in ridge and lasso? Whenever we try to use this L1 and L2 norm, there is one parameter which is called as lambda. This C is nothing but it is inversely proportional to lambda. As the C value increases, the lambda value decreases. Okay, so that is the reason the C value is there. Here you have all the other features like class weight. I'll also be talking about class weight. This class weight will be very much useful when you're having imbalanced data set, so that you can say that on which data set you should mostly focus on. Let's say if the number of output categories are 9:1 ratio, like it is like if you have 900 output categories as 1 and 100 categories as 0, so that becomes an imbalanced data set. So you can assign class weight also. Okay, and there are multiple parameters like solver, this and this. Right now I'm not selecting any parameters. You can definitely check out all the parameters over here. I will just go and execute this. So whatever is the default parameter that will get used. Now I will write logistic.fit, logistic.fit, and here I'm just going to write it as x train, y train. Okay, and then I execute this. Okay, now once I do this, that basically means my model is trained now, and now all I have to do is the prediction for my y underscore pred, prediction for my test data point. Right, so I'll write logistic dot predict, and if I probably give my x test data, here you'll be able to see all my pred, y pred, right? I can basically see all my prediction data points. So this is what is my prediction data points for the 30% of the test data that I've actually put. Now, while we are predicting, right, in logistic we also have something called as probability, right? Predict underscore prob a. Okay, this will basically give you the probability with respect to this specific class and with respect to this specific class. Now, what do I mean by this? Let's say, let me just show you over here by rubbing this, and then you'll get an idea why probability is basically required. Suppose I have some data points. Let's say I have some data points like this, okay, and some data points like this. Now, what is the main aim with logistic regression is that we try to create a best fit line. And let's say that if you get a new data point, let's say this particular data point is somewhere here, then we need to understand what is the probability of this particular category for this point to be in this category and for this particular point to be in this category. So that is the reason we use predict underscore prob. Okay, so if I probably use predict underscore prob, let me just show you, and probably give you the x test data. Here you'll be able to see I'll be getting in probabilities. Okay, probabilities, and by default, whichever probability is the highest, that specific class will be my output. Okay, and that is what it is done over here, right? So over here you can see that logistic.predict, when I do an x test, I'm going to get that specific value. Okay, now here also you can see with respect to the specific outputs, I'm actually going to get over here. So no need to use predict probability over here. If you really want in probabilities all the values, you can basically use this. Okay, so I'm just going to remove this quickly, and no need for this particular case. Now the next thing is that we will try to see the performance metrics, and I hope I've discussed the performance metrics over here. So I'll say from scalar.metrics, I'm going to import accuracy score. Again, from has become capital. That is the reason it is not coming. So here, accuracy score. One is also I'll be using confusion matrix, which I've discussed about this, and classification report, so that we can get precision recall and all. Okay. So first thing first, let's go and print our accuracy score. And here, all I will be giving is my y underscore test, y underscore print. Okay. And this will print my score. Okay. And then confusion matrix also I will try to show you, since this is a binary classification, you'll get a 2x2 confusion matrix. So I'll write y underscore test, y underscore print. Okay. And then I can also print my confusion matrix as CM. Okay. And finally, I'll also print the classification report. And here all I have to give is y test, y print. Now this will basically give you a precision recall value and F score, whatever things you require. Okay, let's go ahead and execute it. So here I'm actually getting an 84% accuracy. These are my confusion metrics, and obviously you know that this is false positive, false negative, true positive, and true negative. This is my precision recall, and here we are also getting somewhere around 85%. Okay, along with that one score. Fine. So we have basically checked the performance metrics, we have checked all these things, and we are able to get the output. Okay. Now, one very important thing is that we've still not played with this any kind of parameters, right? These all parameters are there. How do we fix this? Can we tune this particular parameters? Can we select some other parameters? So for that particular purpose, we will be using something called as hyperparameter tuning, and that is what I'm going to cover in the next video. How to perform hyperparameter tuning, so that our model should be able to select the best attributes that are selected over here, and this particular attribute should be selected to train our model, so that we get a good accuracy and does not lead to overfitting, because we'll be using this penalty parameters, which is like nothing but L1 and L2 norms. Okay, so yes, this was about logical regression implementation in a simple, easier way, where I have actually created a data set, done the train test split, trained the model, and probably checked the confusion matrix where I'm getting good accuracy. And in the next video, you're going to basically see the hyperparameter tuning. Yes, I will see you in the next video. Thank you. So guys, in our previous video, we have already done the logistic regression. One important thing that I really want to show you, let's say if I change my random state to some other values, right, and probably if I execute it again, now what will happen, my data set that is getting created, right, it'll get changed, based on the random state. Now if I again do it and probably check out my score, here you can see that I'm getting 91%. Before I was getting 84 or 86%, right? Now this is why things are happening, because now the data set that is got created, right, it is completely different, right? And this kind of scenario usually happens with the help of random state. Probably if you also select this random state as a different value, then again you will be getting an X train and Y train data differently. Now what we're going to focus on is basically hyperparameter tuning. And hyperparameter tuning here, we're also going to add something called as cross validation. Okay, so we are going to see two different techniques with respect to hyperparameter tuning. One is grid search CV, and the other one that we are going to basically discuss is about randomizer CV. Okay, so these two are the things that we are going to discuss. Let's go ahead and let's see how we can basically implement it. Okay, now for performing hyperparameter tuning, one thing that you really need to know is that first thing over here is that when I see logistic regression, right, I have a lot of parameters like penalty, right? And in this penalty, I can either have L2, L1, or elastic net, right? So this is nothing but rich, lasso, and elastic net. I can select any one of them. Similarly, you have the C value, which is nothing but inverse of that lambda value, right? And similarly, you have class weight, whether you want balanced or you can select different values. Always make sure that you check this particular documentation, guys. Like solver is one parameter. You have Newton CG, LB, FGS, lib linear, SAG, Saga. Different values are there. And it is also saying that for small data set, lib linear is a good choice, whereas SAG and Saga are faster for larger ones. For multi-class classification, you probably have to use Newton CG, right? So all these things are there. Now, what I will do is that we really need to find out a way to select these parameters, and this can only be possible through hyperparameter tuning. So what I'm actually going to do over here is that initially, let's go ahead and create our model. So I'll say model is equal to logistic regression. And in this model, what I'm actually going to do first is that I'll be taking up each and every parameter, and I'll be using all the possible values, right? So let's say that I take penalty as my parameter. So here I will define penalty and what all values this penalty can have, right? Obviously, you have seen in penalty what all values it will be possible. You have L1, L2, elastic net, none, right? So here I'm going to select this tree, and let's say out of this tree, I really want to check which will be the better one. Okay, so I'm just going to make this as a list. Okay, always make sure that you put the proper quotes. Don't only believe on copy and paste, right?
So here you can see that I have selected all the penalty parameters. So I really want to check out of all these parameters, which is the best parameter, right? Then let's go with the next one. Let's say I want to select for the C. The C can also play a very important parameter. So let's say that I'm defining something like C values and all the possible C parameter values that can be there. Let's say I'm using 100, I'll be using 10, I'll be using 1.0, I'll be using 0.1, I'll be using 0.01. So I'm going to probably test from out of all these parameters, which will be the best C value parameter for this logistic regression. And this will change based on the data set. And then I can also use one more parameter, which is called as solvers. Let's say, and you can also try with all the other parameters what you want. But I will not take or consider this solver. And in solver, we have all these possible options, right? So I'm just going to make a key over here and basically say solver is equal to and paste it, right? So here you will be seeing that I will be having all these options, right? I'm just removing this code and I'm going to basically try with all this. And based on data, it will be able to select this, right? So perfect. I have possibly made 3 main key parameters. I really want to check with this. Now, when I take all these parameters, I have to put this into the key value pairs. Now, in order to put in the key value pairs, I'll be using a data structure which is called as dict. Now, when I write dict, this basically means it is going to convert anything that you give inside into the key value pairs. Now, first of all, I will use the first key. Remember, this key name should be absolutely right? If it is wrong, then your model will not get trained. So the first parameter is penalty. And for this, I'm just going to assign this particular penalty parameter, right? So this will be my penalty parameter. So my key will get created with penalty over here. Okay. Similarly, I will go and do it for capital C. Okay. And I'm just going to say that this C will have the C values. Okay, the C values. And the third dictionary that I'm actually going to create is for solver. So this solver will be nothing but solver. Okay, once I execute it, this is how your key value pair will get created, right? So all this key value pair, I really need to try and probably play with this, which is the best parameter that we'll be using in order to solve a problem. Now let me save this in one params variable. Okay, now for the hyperparameter tuning, we will be using first technique, which is called as grid search CV. And this is the first time we're using this. So please make sure that you understand it. With the help of grid search CV, what we will be trying to do is that we will try to find out the best parameter that will be fit for this specific data set. So if I probably search for sklearn grid search CV, here you'll be able to see from sklearn.model selection, I'll be importing grid search CV. Okay, so here from sklearn.model selection, sklearn.model selection, I'm going to import grid search CV. Okay, and then I will say grid is equal to grid search CV. I'll be initializing it. Now let's go ahead and see what are the parameters. By default, I'm just executing this so that I get some. It is coming from an error. The first parameter is basically your estimator. Estimator basically means which model you're going to use. The second parameter is all about your parameters you want to play with. So whatever parameters are defined over here, I'm going to assign this. Scoring value also will be using, because since this is a binary classification, we'll focus more on the accuracy part. And if you really want to see scoring, right? So here you can basically search sklearn scoring metrics and just go and search for it over here. All the documentation is quite precise. So for scoring classification, for binary classification, you can use accuracy, balanced accuracy, top accuracy, average precision. All these things are the possible options, right? But here you really need to understand what is important. If precision is important, then you have to focus on precision. If it is recall, then you have to focus on recall. Right now, I'll just take my accuracy. Okay. So first of all, first parameter that I'm actually going to give is my estimator. Estimator is equal to whatever model I've assigned over here, this particular specific model, comma. Then I'm just going to say param grid is equal to nothing but this will be my params, right? I'm going to assign my params over here. There's also a parameter which is basically called as scoring. I'm just going to write squaring as accuracy, as we have already seen. One more important parameter, because already we are doing hyperparameter tuning, right? There's also a parameter which is called as CV. CV basically means cross validation. How many number of times I need to do k-folds, right? So this CV, I will assign it with stratified k-fold cross validation. Now, in order to basically use stratified k-fold cross validation, I will just go and probably search for stratified k-fold. Okay. And this is basically the model that I'm actually going to do for my stratified k-fold. So I'll say from sklearn.model selection, import. Let me import it over here. From sklearn.model selection, import stratified k-fold, right? And this is what we are going to use as our CV value, right? So here I'll say stratified k-fold. And whatever parameters, how many k-fold I want to specifically use, I can definitely use it. Let me quickly do one thing. Okay. Or I will just take this as my new cell so that I can probably see to it. Okay, not a problem. So here I'll be saying stratified k-fold. So the number of splits I'm going to do 5 and shuffle will be false. Okay, so I am just using the CV. That basically means this CV is nothing but the CV we are going to assign. In short, 5 times we are going to do the cross validation. Okay, and let's see any other parameters that is left. One more parameter that I can specifically use over here is nothing but n_jobs is equal to -1. So that uses all the processors in our system. Once I execute it, so now my grid is ready. So if you probably go and see grid, this is all the parameters that we have used. Now what it is going to do is that it is going to find out the best combination and give you the best parameters that will be fitted with your model. Now, in the next step, what we're going to do is that we're going to take this entire grid search CV and just fit it with our train and test data. Sorry, train and y-train. So once we do it and once we execute it, now you'll be able to see that it will try to check for each and every parameter combination. It will try to find out the best parameter. Now, after we do the fit, the next step is that I will just go and write grid.best params. Once I do this, here you'll be able to see out of all this parameter in C, 0.01 has got selected. In penalty, L1 has got selected. In solver, saga has got selected. So, and if you also probably go and type grid.best score, here is the best accuracy that you're able to get with respect to 92%, right? And what you can do is that with the help of grid also, you can also do predict probability or predict on your X test data, right? Now, once you do this, you will be getting your y-thread, right? And then we can just copy this entire thing and probably try to calculate the accuracy score, confusion metrics, and all the other things. So now let's go ahead and see. Now here you can see that I'm getting 92%, which is a better accuracy when compared to this one that is 91.6. Your precision recall is also increased. Your F1 score is also increased. So this is how you can do hyperparameter tuning. Along with this, you also did cross validation, and here the cross validation that you applied is nothing but stratified k-fold cross validation, and the cross validation was 5, right? Now, this was the technique of the entire hyperparameter tuning. What you can also do is that you can go and select some other parameters and you can assign different values and you can play with that. At the end of the day, hyperparameter tuning is done to select the best parameters that can get applied. And with the help of grid search CV, what we do is that we try to see the combination of every parameters, right? Every parameters, like I first combination can be 100 L1 Newton CG, second combination can be 100 L1 LB FGS, like this all the combination. And out of this, the best combination is what selected is this one based on the accuracy score, right? So yes, this was it. In the next hyperparameter tuning, we'll be seeing with the help of randomized search CV. Again, this is another library which is we can say that it will take less amount of time when compared to grid search CV because it will try to take the sample of the combination and it will try to train the model. That will be seen in our next video. Thank you. In this video, we are going to perform hyperparameter tuning using one more technique, which is called as randomized search CV. Now, previous video, we have already done it with grid search CV. Now, in grid search CV, what this algorithm or whatever algorithm we are basically using and hyperparameter tuning it usually takes all the combination of all the parameters that we are using over here, right? So usually when we take all the combination, it will obviously take more time. So in order to overcome this, we basically use randomized search CV. Now, in randomized search CV, what it will do is that it will make sure that it will pick up random attributes or random parameters, and then it will try to create some, to try to find out what parameter will be suitable for a specific problem statement. Now, everything will be almost same. All I'm going to do is that you can see how we can import randomized search CV by from importing a scale on model selection. Again, the parameters are almost same like grid search CV. Here you have estimator, parameter distribution, number of iteration, cross validation value, and scoring value, right? And then we can basically do this. So let's go ahead and let's quickly import first of all from sklearn.model selection. I'm going to import a randomized search CV, and once I execute this, all I have to do is that write random CV and initialize to randomized search CV. And here again, if you press shift tab, you'll be able to find what all things are there. So first I will go and give my estimator, and before that I will just initialize my model to logistic regression. So for that I will just try to copy the same thing, and after doing this also we will be able to see some difference. Okay, so estimator over here will be my model, and then I have something called as parent distribution, and this parent distribution will be assigned to the same parameters that we have created right over here. So this will be my params that will be given over here, and I will also be using some cross validation. CV is equal to 5. Scoring parameter I will again be using as scoring is equal to for accuracy. I'm going to use the accuracy parameter over here. And after this, is there any other parameter that I have left? I think this will be more than sufficient to initialize random CV. So let's go ahead. And in the next step, what I'm actually going to do, all we have to do is random CV.fit on my X train, comma Y train. So internally, this is also doing cross validation. And once I do the fit, here you'll be some warnings. Okay, here it says that L1 ratio must be between 0 to 1 and all. So by default, L1 ratio is not given over there. So some warnings you'll be able to see over here. But at the end of the day, training will happen. Okay, now I will go and basically write random CV dot and press best score. So you can see from the best score I'm actually getting using randomized search CV, I'm getting 91.28%. And if I also write random CV dot best params, you'll be able to see what all parameters got selected. You can see solver, Saga got selected, penalty L2 got selected, and C was 100, right? And if you probably see with respect to grid search CV, here what all parameters that got selected, solver and penalty over here was L1, there got selected as L2, and C value is quite high, over here it was quite less, right? So any of the two techniques you can use, but at the end of the day, when I probably do dot predict on my X test data, right, I will be able to get ypred, and this ypred I will again try to use all my parameters that are this parameters and try to see what is the accuracy that I'm actually getting, right, for my test data. So here it is. Here you can see I'm getting 91.6. It is almost same. And again, one advantage with randomized search CV is that this entire hyperparameter tuning, when you have large number of parameters, this will take less amount of time when compared to grid search CV. Okay, but at the end of the day, we should try each and everything, to get or see how the accuracy is basically fluctuating between models. So these were the two hyperparameter techniques that I have actually taught you in the series. And as we go ahead, we'll be also learning about the other hyperparameter tuning techniques. Now, the next topic that we're going to cover is something like how do we solve multi-class classification with the help of logistic regression. And for that, we are going to use one versus rest technique. So let's see how we can basically use it. I will basically see you on in the next video. I hope you're liking the sessions. Please make sure that you revise again in order to practice more and more. And yes, please try to change your data set and again try to see to it. Okay, so I will see you all in the next video. Thank you. Hello guys, so in this video we are going to implement logistic regression for multi-class classification problem. Already we have done it for binary classification. We have also seen how to do hyperparameter tuning using grid search CV and randomized search CV. Now let's go ahead and let's continue this problem statement and try to solve multi-class classification problem. Now what I'm actually going to do, I'm just going to copy this entire code and create our new data set. And in this data set, I will not be giving binary classification, but the number of classes over here, let's say it will be greater than 2, that is 3. Okay, you can give any number, right? And we will try to create our X and Y data. Okay, so let's see what is the error that I'm getting. N number of classes must be smaller. Okay, so not a problem. So here I am also going to use N underscore informatives, and here I'm going to basically specify some value like 3. And now if I probably execute it, here you'll be able to see my X data, right? So if I probably see X, here you'll be able to see all the features. I've taken 10 features, I've taken 1000 data points, but number of classes that you'll be seeing in Y, right? Here you'll be able to see I have 0, 1, 2. So 3 categories in short I specifically have over here. Okay. Now what I'm actually going to do, first of all, I will do again the train test split. Again, I don't have to write the code again because already the code is here. But I really want to show you that how with the help of logistic regression we'll try to solve this problem, right? So this is my train test split. I've done it. Now all I have to do is that initialize my model. Now in order to initialize, I've already imported. Again, you can import it from sklearn.linear model import logistic regression. Okay. And then I will say logistic is equal to logistic regression. And here, one important parameter that you'll be seeing, yes, there are many parameters, but one parameter that you'll be able to see over here is with respect to multi-class, right? This multi-class, right now, if you give auto, let's see what all parameters are there with respect to multi-class, right? So here, if you probably see, your multi-class will have values like auto, OVR, and multinomial, right? And here you can see if the option chosen is OVR, then a binary problem is fit for each label. For multinomial, the loss minimized is the multinomial loss fit across the entire probability distribution. But anyhow, I've actually discussed about one versus rest, that is OVR, what it is going to do based on the number of categories internally, that many number of models will get created. So here, what I will do is that I will just set this particular parameter as multi-class and basically write OVR, right? Now, once I do this, all I have to do is that write logistic dot fit on my X train, comma Y train, and once I do this, all I have to do, go ahead and find my prediction, and here you can see logistic dot prediction on my X test data, right? So once I do the prediction, I will basically get my Y underscore right. Now here also I'll be seeing 0, 1, 2s because I have 3 categories. Now all I have to do is I just go and check the score, right? So I'll just go and paste this entire scoring parameters. See guys, most of the code I'm just copying and pasting it because it will be easy. Now for this particular problem statement, I've got 79% accuracy, and the confusion matrix will be now 3 cross 3. All the diagonal elements are the correct elements and the remaining elements are the wrong elements. So here you cannot just say true positive or true negative because there is not a 2 cross 2 matrix. But again, with the help of hyperparameter tuning, you can actually improve this accuracy right now to 79 probably with the help of hyperparameter tuning, and if you select the right kind of keywords, you will be able to get good accuracy. But I will keep that particular task to you. Try to do some hyperparameter tuning like how we did it for randomized search CV and the grid search CV. So just try it out from your side, and yes, this was the technique that we have actually followed in order to solve multi-class classification. All you have to do is that just add this particular attribute that is OVR, that is nothing but 1 versus rest. So I hope you have understood this video, and yes, I will see you all in the next video. Thank you. Hello guys, in this video we are going to implement logistic regression for imbalanced data set. Now, whenever we want to implement logistic regression, till now we have seen that we have taken most of the balanced data set. Now, what does balanced and imbalanced data set basically mean? Let's say that if I have total number of data points that are available in my data set as 1000, okay, and let's say we are solving a binary classification problem. Now, with respect to the dependent feature, let's say the number of categories will be 2. Now, out of that 1000 data points, the two labels that I have, zeros and ones, the number of zeros, let's say it is 900 or 9900, and number of ones are just 100. Now, here you can see the ratio is 99:1. That basically means this is completely imbalanced data set with respect to the number of output categories. Even though you solve multi-class classification, if this numbers of percentage, like based on the percentage, if the ratio is quite huge, at that point of time, we will basically say it as an imbalanced data set. Now, with the help of logistic regression, also we can solve an imbalanced data set. And there is a very important parameter in logistic regression, which is called as class weights. Class weights will actually help us to assign more importance to less number of categories that are available in the data set. So let's go ahead and let's see a practical application. Here I have imported counter, and the next class that I have imported is something called as make underscore classification. And this we have already used to create our data set. Now, this same library will be using to create imbalanced data set. Okay, so I will try to execute it over here. Now, over here you can see I've used make classification, and over here, by default, what are the parameters? N underscore sample is there, N underscore features is there. By default, N number of classes is 2, right? So number of classes means 2 basically means your output feature will have 2 classes, and that is a binary classification. So if my number of samples is 10,000 over here, number of features that I've taken is 2. Now this is also a very important parameter. Now when I'm creating this imbalanced data set, I'm making sure I'm telling them that you have to probably make 2 clusters of data. So that is the reason number of cluster per class. So for one class there will be one cluster, for the other class there will be another cluster. And then this is a very important parameter to create an imbalanced data set. So here you can see weights is equal to 0.99. When I say 0.99, this basically means that when compared to the other category, right? This, let's say there are 2 categories, zeros and ones. One of the category will be 99 times more, or it will be having more data points when compared to the other category. And then I've used random state is equal to 10. So once I execute this is my x. And now if I probably write counter of y, here you'll be able to see number of zeros are 9846 out of the 10,000 data points, and number of ones are 154. Okay. Then after that, I'm going to import cbon, and let's say I'm going to use the scatter plot, and I'm basically going to plot this x of zeros and x of ones, my 2 input feature, and then I'm providing my parameter which is called as hui over here. Now once I provide this y output will basically label like this. So if I probably go and execute it, here you'll be able to see these data points. Okay. Now this is pretty much easy, pretty much clear till here, right? Now definitely you can see this is a completely imbalanced data points. Now with the help of logistic regression, how can we solve it? Now I already have my x and y data set over here. First thing that I will do is that I will split this into train and test data. And obviously how do we do it? We'll be using a train test split. We'll be using test size of 0.25 and we'll do it. So once I execute this, you'll be able to see train test. Now this is super important, guys. In hyperparameter tuning, here I'll just try to comment hyperparameter tuning, right? Now in this hyperparameter tuning, here you can see that I'm having logistic regression. Now you know that in logistic regression you have a lot of parameters. So I've played with penalty parameters, I've played with other parameters, we can play with solver parameter. But there is one important parameter which is called as class weight. And with the help of this particular parameter, you will be able to play with the imbalanced data set. Now in class weight, if you probably go and see the information, class weight can be either a dictionary value or it can be balanced. If we basically say balanced, or if you just copy this and write class weight as balanced, then what will happen? It will basically consider equal importance for zeros and ones also. And this usually we can use during a scenario where our number of outputs are equal, right, with respect to the number of categories. But right now, since we have a complete imbalanced data set, I will try to specify dictionary. Okay. Now in our case, number of zeros are this much, number of ones are this much. So I have to give around 100 times importance to this one category, right? So what I'll do is that here I've written a code, okay, and please focus on this code. This code is super important. We're going to play with different class weight value. So probably if I go and execute this over here, and probably just write class weight. Here you'll be seeing that I'll be playing with this all parameters. Here I'm saying that give zeros and 1 equal importance. Here I'm saying give 0 importance 1, 10 times more importance than 0. Similarly over here 0, I'm giving importance as 1, I have to give 50 times importance. So all the combination I've actually taken it, and I will now create this in the form of dictionary. Okay, how to create this in the form of dictionary? I'll just use dict, and probably I'll use this penalty parameter, c parameter, solver parameter, and class underscore weight parameter. This parameter name should be same like how we have in the logistic regression. So once I execute this, so this will be my parameters that I'll be playing with. Now here you'll be seeing that in the left stage, I will probably applying grid CV stratified k-fold, and I'll just provide this parameters over here. Now, once I do this, I've already trained it, guys. You will be able to see that it takes some amount of time for doing the training, and you'll also be getting some warnings. Okay. Now you can see on all these parameters that is got trained. Now, probably if I write grid dot best params, let's see. Okay, let me just train it once again. So here you'll be seeing that it will take some amount of time. It will take some amount of time, and it will also give you some amount of warnings. You can ignore the warnings. We can also remove these warnings. So this will be an interview question. How do you remove a warning? Okay, it can be, but I'll give you the hint. You just have to import one library. All the warnings will be removed. Okay, so this will probably take some time. We'll wait till the execution will get over, and after that, when I probably write best score or best params, it will basically give us the best params that is required, that it has basically selected from this entire fine tuning, But this is the hyperparameter tuning technique, right? With the help of this, we are doing this, right? Grid dot fit. Okay. So now these are all completed. Now if I probably go and write best params, here you'll be able to see that this params has got selected. For this problem statement, 0 is given 10 importance, but 1 is given 50 times more importance, or 5 times more important than 0. And then penalty has got selected, then solver has got selected. Okay. So now more importance is given to 1 because in order to solve this problem, and because of this data points only, right? This data points, if I'm giving some importance, I can basically create a best fit line on top of it, and I can solve it with a logical regression. Now here is what we have actually done it. It's quite amazing. We've got all these parameters. Now I can probably write y is equal to grid dot predict, and here I'll basically write x underscore test and just execute it. And at the end of the day, what I will be doing is that I can basically use all the accuracy score, all the parameters over there, right? So where are all the parameters? I will copy this entirely, and before this, I also have to copy all the accuracy score and all. I have to import those parameters, right? Import those libraries. So I'll say from sklearn.metrics import accuracy score, classification report, and confusion matrix. So once I execute this, here you'll be able to see I'm able to get 99% even in an imbalanced data set. So now here you can see that, guys, we have also solved imbalanced problem statement, and we have classified these data points by assigning class weights. And here you can see that we are able to get a good accuracy of 99%. And this is how a confusion matrix looks like. But with respect to precision and recall, here you can see something very the number of data points is obviously less. The precision value is quite high. The precision with respect to 1 is quite low because obviously the number of data points are less. But 18 plus 2, right? 20 data points have been incorrectly classified. So this is how you can basically use class weights in order to classify data points using logistic regression by using class weight itself. So I hope you like this session. Yes, this was it. Just try it out again with considering different data points, and let's see whether you'll be able to solve this or not. Okay. So yes, I will see you all in the next video. Thank you. So guys, in our previous video, you have seen so many different examples with logistic regression, right? We have also seen how we can solve logistic regression with imbalanced data set. Now in this specific video, what we are going to focus on is that, let's say until now, let's say this is my model, and when I was doing prediction on
X test data, right? My output was either ones or zeros for a binary classification. And for one versus rest, we used a multi-class classification. Now over here, you can see that my output is either ones or zeros. And we also know that in logistic regression, the threshold value is 0.5. Suppose if the prediction is greater than 0.5, then it becomes 1. If it is less than 0.5, it becomes 0. That much you obviously know. And that is what we have also learned from the theory and from the practical part. Now, the threshold that is kept, which is 0.5, is the default value. And if you, and based on different problems taken, this threshold value may change. Like for a healthcare problem, we may have a discussion with the domain expertise, and they may say that no, we have to keep the threshold to 0.3 or 0.4. That basically means anything greater than 0.3 then will become 1. If it is less than 0.3, it may become 0. There may be again different kind of critical use case, so the threshold should be higher. Let's say 0.7, right? Anything greater than 0.7, then only it should be 1. Otherwise, it should be 0. Something like that. So how should we come to a conclusion for a specific threshold value? Right now, by default, whatever logistic regression we're using, it is using the threshold as 0.5. So in this video, we're going to see that with the help of ROC curve and ROC AUC score. So let's go ahead and let's see what are the steps with respect to this. Now, first of all, I'll be importing make classification data for creating my own dataset, logistic regression, train test split, ROC AUC curve, and here I'm using ROC AUC score. So this two will be specifically using for some purpose, which I will be showing you. Now, apart from this, I'll also say from matplotlib from matplotlib import pyplot. Okay, so I'm also going to use pyplot over here. So import pyplot for the plotting purpose. Okay. Now, the first thing that we have done is over here is that a simple way till now we have learned how to create our dataset. So here we have created 1000 data points and number of classes 2, right? So here we have in short created our data points. So this is very much simple. So I'm just going to skip this step by executing. Okay, and then we did train test split. I hope everybody's familiar with train test split now. Okay. Now let's do one thing, guys. Let's create a dummy model that will always give the probability of that particular output for any data, for any test data as zeros, right? So how do I create my dummy model? Here I've just set that 0 for dash in range of length of I underscore test. So how many data points in white test are there? For every data point, I'm getting the output as 0 probability. So I've just selected 0 as the output, default output for this particular dummy model. Okay. So here once I execute it, this here you'll be able to see that I'll be able to get completely 0. Now what we'll do is that we'll compare with this specific model, okay? With this specific model, with our current model that we are creating. But here, in short, we have just created, I'll just say over here, we have created a dummy model, okay, with default 0 as output, okay? That's it. This is what we are basically doing, okay? And we have just executed it. Perfect. So here, a dummy model with just basic zeros I'm able to get. Then, let's go ahead and create a basic logistic model. Here, again, I'm not doing hyperparameter tuning. You can definitely do it. But quickly to show you how to create an ROC and AUC curve, we'll try to discuss this. So here, I've written model is equal to logistic regression, model.fit on extract migrate. So this is perfect. So we have created a logistic model. And then, the next step is that we will do the prediction based on probability. Prediction based on probability. Now, when this prediction is basically given, probability, okay, prediction based on probability. Now, whatever prediction is basically happening, we'll get in terms of decimal values, right, with respect to the X test data. Now, whatever prediction I'm giving, I'm just writing as model underscore prob. So that basically means some probability values I'm getting. Okay. So once I execute this, and then I just want to focus on one outcome. Let's focus on one outcome. Let's focus on the positive outcome because I've written colon comma 1. So this will basically be my positive outcome. Okay, positive outcome. Very simple till here. So now, if you probably go and execute this, if I make a cell and right model underscore prob, here right now you'll be getting two values, right? One is the probability for 0, that is for the negative, for the positive, something like that. Okay. Now I'm just going to take all these values on, okay, and then probably set this all as different probability and try to create my ROC AUC curve. So that is the reason why I'm taking with comma 1, right? So when I do comma 1, I'm basically taking all these values. Okay, perfect. Now the next step is that we will calculate the ROC AUC score. Now in order to calculate the ROC AUC score, all I have to give is that give my white test data, which is my true point, and whatever dummy model for the probability that I've given, I'll basically calculate. So now my ROC AUC score that I'm calculating for my dummy model also and for my model that I've actually created with the help of logistic regression. So here I'll give y underscore test with the dummy model probability, and obviously these all values are zeros. Here I'm giving y test and whatever probabilities that I've got over here, model underscore prob over here, I'm going to give that. And once we compute it, you'll be able to see that we will be getting somewhere around 0.5 for a dummy model and 0.90 for the the model that is predicted, right? And obviously this needs to be 0.5, no, because at every point of time it is just giving the output as 0. Okay. Now you need to understand what does this ROC AUC curve basically give us. Okay, it gives us two important things. One is the false positive rate, that is nothing but false positive divided by false positive plus true negative, and one is the true positive rate, true positive divided by true positive plus false negative, 1 minus FNR. We also say this as. And if we plot TPR in the y-axis and false positive rate in the x-axis, right? Once we plot this two, again I'm repeating, if we plot TPR in the y-axis and false positive rate in the x-axis, we will be then able to get something called as ROC curve. Okay. Now, in order to use this ROC curve, we have already imported ROC curve over here. You can see. Okay, we have already seen ROC AUC score. Okay. Now, when I try to see this ROC curve, right, all I have to give two things. One is my test data, and one is whatever probability that I've got for my dummy model, right? Then this will basically return two things: false positive rate and true positive rate. So here you can see false positive rate and true positive rate. How it is basically returning? By using that same confusion matrix. In the confusion matrix, we have false positive, true negative, false negative. With the help of that, we'll be able to get it. So here I'm getting false positive rate. Here I'm getting true positive rate. So whatever ROC curve is basically applied, is basically applied on the real test data and the whatever the probabilities the model is given. And this right now, this is dummy model. Obviously, it will give zeros, right? And based on that, I'll get false positive rate and true positive rate. Similarly, over here you can see for the real model also I've actually done it. So here also I'll get false positive and true positive. So once I execute this and probably execute over here and see what is my model underscore FPR, you'll be seeing some values will be getting. So here you can see for all these different values, for all different probabilities, I'm getting some false positive rate, right? For different things. And similarly, if you probably go and see for model underscore TPR, here also you'll be able to see it. So here also you'll be able to see. Now, at the end of the day, to create the ROC curve, right, all you have to do is that use this false positive rate, plot in the x-axis, use the true positive rate, plot in the y-axis, and then see how your curve is basically getting created. Now, we will try to compare the curve for this dummy model and the model that we have created. And obviously, the area under the curve for this particular FPR and TPR for the specific model that we have created will be high because it has done some good predictions. Now, all I have to do is that I use pyplot.plot, I've used dummy FPR, dummy TPR, line style I've used said that this is my dummy model, and similarly model underscore FPR, TPR, marker, label with logistic, and then I probably plot X label and Y label. If I see the legend and pyplot.show, here you'll be able to see the curve. So guys, now finally here you can basically see our ROC AUC curve. Now let's go ahead and understand what information we are able to get from this curve. Now first of all, you need to note down, we are plotting two important information. One is the ROC AUC curve of the dummy model based on the FPR and TPR, and one is of the model that we have specifically created, that is logistic regression. This orange line is basically the line representing the logistic regression, okay? And whatever area it is present inside this, all this entire area. So if I probably consider this entire area, right?
if I probably consider this entire area, is the area under the curve for the logistic regression model. And from this, you can see the maximum amount of area is getting captured. So obviously, logistic regression performs well when compared to the dummy model. Now, where do you see the dummy model? Whatever this blue line that you're able to see, right? This curve is basically the curve of the dummy model. And obviously, here you can see the area, the AUC curve of the logistic is greater than the AUC curve of the dummy model. Clearly, you can see from here, right? So your model has actually performed well when compared to the dummy model. But still, the question rises, Krish, how do we select the threshold? Because you're saying that logistic by default 0.5 is the threshold. Anything that is greater than 0.5, this becomes 1, greater than or equal to 0.5, or if it is less than 0.5, it becomes 0. So how do we basically select the threshold based on this particular curve, right? That is the next question that we're going to solve. So let's go ahead and let's quickly go back to our ROC AUC function. So let me just rub this first of all, and let me close this, okay? Now here you'll be able to see when we are seeing this ROC curve, right, when we are applying this ROC curve and we give a y-test and the probability value, the third parameter that is put is blank, but this third parameter will give us the threshold values. And based on this threshold values, it will be testing our model and it will be drawing the curve, right? So whatever points that you basically see over here, these all points are based on some threshold values. So based on some threshold value, we calculate our false positive rate, true positive rate. Hello guys, in this video, we are going to implement logistic regression for imbalanced data set. Now, whenever we want to implement logistic regression, till now we have seen that we have taken most of the balanced data set. Now, what does balanced and imbalanced data set basically mean? Let's say that if I have total number of data points that are available in my data set as 1000, okay? And let's say we are solving a binary classification problem. Now, with respect to the dependent feature, let's say the number of categories will be 2. Now, out of that 1000 data points, the two labels that I have, zeros and ones, the number of zeros, let's say it is 900 or 9900. And number of ones are just 100. Now here you can see the ratio is 99:1. That basically means this is completely imbalanced data set with respect to the number of output categories. Even though you solve multi-class classification, if this numbers of percentage, like based on the percentage, if the ratio is quite huge, at that point of time, we will basically say it as an imbalanced data set. Now with the help of logistic regression also, we can solve an imbalanced data set. And there is a very important parameter in logistic regression, which is called as class weights. Class weights will actually help us to assign more importance to less number of categories that are available in the data set. So let's go ahead and let's see a practical application. Here I have imported counter. And the next class that I have imported is something called as make underscore classification. And this we have already used to create our data set. Now this same library will be using to create imbalanced data set. Okay, so I will try to execute it over here. Now over here you can see I've used make classification. And over here, you know, by default, what are the parameters? N underscore sample is there, N underscore features is there. By default, N number of classes is 2, right? So number of classes means 2 basically means your output feature will have 2 classes, and that is a binary classification. So if my number of samples is 10,000 over here, number of features that I've taken is 2. Now this is also a very important parameter. Now when I'm creating this imbalanced data set, I'm making sure I'm telling them that you have to probably make 2 clusters of data. So that is the reason number of cluster per class. So for one class there will be one cluster, for the other class there will be another cluster. And then this is a very important parameter to create an imbalanced data set. So here you can see weights is equal to 0.99. When I say 0.99, this basically means that when compared to the other category, right? This, let's say there are 2 categories, zeros and ones. One of the category will be 99 times more, or it will be having more data points when compared to the other category. And then I've used random state is equal to 10. So once I execute this is my x. And now if I probably write counter of y, here you'll be able to see number of zeros are 9846 out of the 10,000 data points, and number of ones are 154. Okay. Then after that, I'm going to import C1, and let's say I'm going to use the scatter plot, and I'm basically going to plot this x of zeros and x of ones, my 2 input feature, and then I'm providing my parameter which is called as hui over here. Now once I provide this y output will basically label like this. So if I probably go and execute it, here you'll be able to see these data points. Okay. Now this is pretty much easy, pretty much clear till here, right? Now definitely you can see this is a completely imbalanced data points. Now with the help of logistic regression, how can we solve it? Now I already have my x and y data set over here. First thing that I will do is that I will split this into train and test data. And obviously how do we do it? We'll be using a train test split. We'll be using test size of 0.25 and we'll do it. So once I execute this, you'll be able to see train test. Now this is super important, guys. In hyperparameter tuning, here I'll just try to compare comment hyperparameter tuning, right? Now in this hyperparameter tuning, here you can see that I'm having logistic regression. Now you know that in logistic regression, you have a lot of parameters. So I've played with penalty parameters, I've played with other parameters, we can play with solver parameter. But there is one important parameter which is called as class weight. And with the help of this particular parameter, you will be able to play with the imbalanced data set. Now in class weight, if you probably go and see the information, class weight can be either a dictionary value or it can be balanced. If we basically say balanced, or if you just copy this and write class weight as balanced, then what will happen? It will basically consider equal importance for zeros and ones also. And this usually we can use during a scenario where our number of outputs are equal, right, with respect to the number of categories. But right now, since we have a complete imbalanced data set, I will try to specify dictionary. Okay. Now in our case, number of zeros are this much, number of ones are this much. So I have to give around 100 times importance to this one category, right? So what I'll do is that here I've written a code, okay, and please focus on this code. This code is super important. We're going to play with different class weight value. So probably if I go and execute this over here, and probably just write class weight, here you'll be seeing that I'll be playing with this all parameters. Here I'm saying that give zeros and 1 equal importance. Here I'm saying give 0 importance 1, 10 times more importance than 0. Similarly over here 0, I'm giving importance as 1, I have to give 50 times importance. So all the combination I've actually taken it, and I will now create this in the form of dictionary. Okay, how to create this in the form of dictionary? I'll just use dict, and probably I'll use this penalty parameter, C parameter, solver parameter, and class underscore weight parameter. This parameter name should be same like how we have in the logistic regression. So once I execute this, so this will be my parameters that I'll be playing with. Now here you'll be seeing that
in the next stage, I will probably be applying grid search CV, stratified k-fold, and I'll just provide these parameters over here. Now, once I do this, I've already trained it, guys. You will be able to see that it will take some amount of time for doing the training, and you'll also be getting some warnings. Okay. Now, you can see on all these parameters that is got trained. Now, probably if I write grid dot best params, let's see. Okay, let me just train it once again. So here you'll be seeing that it will take some amount of time. It will take some amount of time, and it will also give you some amount of warnings. You can ignore the warnings. We can also remove these warnings. So this will be an interview question to you. How do you remove a warning? Okay, it can be, but I'll give you the hint. You just have to import one library. All the warnings will be removed. Okay, so this will probably take some time. We'll wait till the execution will get over, and after that, when I probably write best score or best params, it will basically give us the best params that is required. That it has basically selected from this entire fine tuning. But this is the hyperparameter tuning technique, right? With the help of this, we are doing this, right? Grid outfit. Okay. So now these are all completed. Now if I probably go and write best params, here you'll be able to see that this params has got selected. For this problem statement, 0 is given 10 importance, but 1 is given 50 times more importance, or 5 times more important than 0. And then penalty has got selected, then solver has got selected. Okay. So now more importance is given to 1 because in order to solve this problem, and because of this data points only, right? This data points, if I'm giving some importance, I can basically create a best fit line on top of it, and I can solve it with a logical regression. Now here is what we have actually done it. It's quite amazing. They've got all these parameters. Now I can probably write y is equal to grid dot predict, and here I'll basically write x underscore test and just execute it. And at the end of the day, what I will be doing is that I can basically use all the accuracy score, all the parameters over there, right? So where are all the parameters? I will copy this entirely, and before this, I also have to copy all the accuracy score and all. I have to import those parameters, right? Import those libraries. So I'll say from sklearn.metrics import accuracy score, classification report, and confusion matrix. So once I execute this, here you'll be able to see I'm able to get 99% even in an imbalanced data set. So now here you can see that, guys, we have also solved a imbalanced problem statement, and we have classified these data points by assigning class weights, and here you can see that we are able to get a good accuracy of 99%. And this is how a confusion matrix looks like. But with respect to precision and recall, here you can see something very that the number of data points is obviously less. The precision value is quite high. The precision with respect to 1 is quite low because obviously the number of data points are less. But 18 plus 2, right, 20 data points have been incorrectly classified. So this is how you can basically use class weights in order to classify data points using logistic regression by using class weight itself. So I hope you like this session. Yes, this was it. Just try it out again with considering different data points, and let's see whether you'll be able to solve this or not. Okay. So yes, I will see you all in the next video. Thank you. Rate, and that basically is pointed over here, right? So we will try to find out these thresholds, right? And our main task will be that after we plot this threshold based on this particular curve, we have to select what threshold we will be selecting for getting high true positive rate and less false positive rate. Okay. Now the next step will be that I will just go ahead and execute this, and from this I will be getting my threshold value. So if I probably go and execute it, here you'll be able to see the threshold values, and based on all this threshold value, we will compute the true positive rate and the false positive rate, and we will keep on plotting in all these points. And then wherever there is a high true positive rate and less false positive rate, we'll capture that particular point, and that threshold will be selected for our logistic regression. So quickly, let's do one thing, guys. I'm just going to remove this code. Now here I've written a very simple code. I'm plotting obviously my dummy model, my logistic model, but apart from that, I'm also plotting thresholds. Okay. Now how do I plot threshold? Here I'm specifically using something called as annotation. Now I will be using a zip function which will combine all these three values. Wherever if I write ax.annotate, ax is nothing but the axis of this particular figure of 111. Okay. Here the first parameter that I'm displaying is basically my threshold value. So whatever things it will display with respect to every point, it will basically be my threshold value. Okay. And I'm rounding it to 2 decimal points because I require that much value. And then in my xy value, the xy coordinates, right, I'm probably putting my model underscore FPR and model underscore TPR. And based on that annotation, this will get displayed. So what is going to happen in each and every point, I will be able to get what is the threshold for that specific point. So if I probably just go and execute this, and this model is all this plotting is almost the same with respect to this. Here just I've added this line with respect to annotation. Now once I execute this, here is the curve that you're able to see. Okay, big curve. And I've actually created it big because I really need to make you understand. Because from this curve, now we'll try to understand what should be the threshold we should select. Should we go with this 0.36 threshold, 0.31, 0.22, 0.54, 0.5, and some are overlapping like 0.60, 0.61, or 0.63? Okay, what should be the thing that we should? Now let's go ahead and see on the x-axis, guys. Over here in the x-axis, you see that we have false positive rate. On the y-axis, you have true positive rate. Now let's say your domain expertise person says that you really need to get a good true positive rate. That basically means your true positive rate should be high. Okay, but you have to also make sure that your false positive rate should be less. False positive rate basically means misclassified points, and these are my misclassified points, right? So if I go and see this particular line, suppose if I probably refer over here, if I consider less false positive rate, that basically means I'll be considering over here. And my true positive rate should also be high. I'll be considering over here, right? Now my domain expert basically says, what is the problem statement I'm saying? Suppose if I'm a domain expert in sales, that probably I got an ROC curve over there. I say that okay, you just need to focus on true positive rate. Then I don't have to worry about false positive rate. Then I'll be capturing this particular point which is having the highest true positive rate. But this does not usually happen. In a problem statement, we also need to focus on the false positive rate. I need to say that okay, let's say that a false positive rate is very less over here. Then I will go and select this specific point. Let's say in this specific point with respect to this point, I will try to select this, and this whatever threshold I'm getting over here, and that threshold will be my actual threshold of logistic regression. That is what we are going to do. But that is again a decision-making skills with respect to the domain expert. Here, if I want true positive rate very, very high, then I can basically select this point because my true positive rate is 1 over here. But understand, my false positive is also increasing. Right? My false positive rate is also increasing. So domain expert will say no, try to restrict your false positive rate to this range, and then try to select the threshold value considering the true positive rate is high. So what we'll do, we'll come over here, we'll consider this point, and with respect to this, whatever threshold we are getting now, let's say here threshold is 0.61. Okay, here the threshold. I'm not talking about this side. Okay, so let me remove this. Let's say with respect to this, based on our ROC curve, I got the threshold as 0.55. Then I will be using this threshold. Anything that will be greater than 0.5, I'll be saying 1. Less than 0.55, I'll be saying it as 0. And here in this diagram that you'll be seeing below, right, I have displayed this threshold entirely. You'll be able to see this. See this now. I will try to display this threshold entirely. So if I go over here, you'll be able to see all this threshold is displayed. Let's say I want less false positive rate and I want maximum true positive rate. I will select this point. Okay. Now in this particular point, if I probably zoom in, you'll be able to see this is somewhere around 0.7. This is somewhere around 0.6. This is somewhere around 0.61. Right. So you just have to zoom in and probably see it. Right. And we can definitely see or explore this graph in a better way by just projecting it in a bigger screen and try to zoom each and everything. There's some overlapping. Now in this particular case, if I select this point, it is 0.51 as the threshold. If I select this point, it is 0.49 threshold. Right. So let me zoom in more. Right. So here you'll be able to see this. right? This is the true positive rate when it is high. Now if I go down, here you can see 0.59, 0.62, 0.63, 0.77. There are 2 points less, so that is the reason it is getting overlapped, right? So I can select any of this threshold where my false positive rate is less and my true positive rate is less. Okay? So I hope you got an idea about how to select the threshold values. This is what we really want to see and check, and this is what you will be doing a discussion with the domain expert. Again, my main aim is to make you understand in a better way. See, implementing is not that important. Coming to a conclusion is super important. Okay? So yes, in this video, we have covered logistic regression with ROC curve and ROC UC score. In the upcoming videos also we'll be doing this. I hope you're liking it. Please make sure that you continuously revise and try to understand the concept. So I will see you all in the next video. Thank you. This video, we are going to discuss about a new machine learning algorithm which is called a support vector machine. Now, this particular machine learning algorithm helps us to solve both classification problem and regression problem. If we are solving a classification problem, we basically say this as support vector classifier, that is SVC. In the case of regression, we basically say support vector regression. So I'm just going to mention over here, we're going to discuss about these two algorithms. First, we'll try to finish up support vector classifier, and then we will try to go ahead and see which is called a support vector regression. Okay. Now, if I talk about support vector machine, first of all, it is very important that you really need to understand logistic regression. So if you have skipped logistic regression, if you have come over here directly, I'd again suggest you, please go through the logistic regression, math intuition and everything. So to begin with, again, let's consider that I have two axes. And here, let's see that this is a, in logistic regression, what we do, suppose if we have some two categories of point, let's say it is a binary classification. And similarly, if I have another category over here, in logistic regression, our main aim is basically to create a best fit line, that is a line between these two particular points such that this line is able to clearly separate them. And this is what we basically do with respect to a logistic regression, right? We try to create a straight line in the case of a 2D plane, straight line in the case of a 2D plane. Let's say if I have a 3D plane. So suppose if I have coordinates like x1, x2, x3, right? Let's say these are my three features. And let's say these are some of my data points, which is over here. And my other data points are somewhere here. Now, in this particular case, what we used to do with the help of logistic regression is that we used to create a plane, right? So this is basically a 3D plane. And with the help of this 3D plane, we were trying to categorize this particular data points. And whenever a new test data, suppose if it comes over here, obviously we know that it is below this particular plane. So we would use to categorize this into this category. That is what we were trying to do in logistic regression. Okay. I'm just going to write it in logistic regression. Similarly, with respect to n dimensions, we basically have to create a hyperplane. Okay. Now, with the help of support vector machine, now let's just discuss about the support vector machine. Now, in support vector machine, what we do is that specifically with respect to support vector classifier, let's consider first of all classifier. And here I'm going to take an example with respect to SVC. Now, in this, let's say that I have this two axes, that is x1 and x2. We're just trying to understand the geometric intuition, what we are planning to do with support vector machine. So let's say this is my x and y coordinate, and let's say I have some of the data points over here, and I have some more data points which is over here. Now in support vector machine, what we actually try to do is that, again, we also create a plane or a best fit line along with this super important. Suppose let's say that this is my best fit line in the case of 2 dimension, in the case of 3 dimension it becomes a plane, 3D plane, and in the case of n dimension it becomes a hyperplane. Now what we try to do over here in support vector machine, along with this best fit line, or let's say in the 3 dimension I can basically call this as 3D plane, I also try to create two more lines, and these lines are basically called as marginal plane. Okay, these are called as marginal planes. So along with the best fit line, we also create something called as marginal planes. So this is also my marginal plane. This is also my marginal plane. And this marginal plane, first of all, let's say that this distance combined is something like d. This both should be equidistant. And this marginal plane should be created in such a way that the distance between this marginal plane should be maximum. Okay, should be maximum. So let me again repeat with respect to support vector machine. If I'm just considering SVC, what we are trying to do is that we are trying to create a best fit line. And in this best fit line, in the case of 2D plane, so if I'm just creating a 2-dimensional, in the case of 2-dimensional categorization, right, I really need to create this best fit line. Along with this, I have to create a 2 marginal plane. And this marginal plane distance should be maximum. So suppose let's say the same points, if I try to populate it over here. Okay, if I try to populate it over here, let's say I have these points over here also. Okay, and I'm just going to draw the same points like this. I hope I'm drawing it right because there may be some mistakes, but approximately it will be equal. I'm just drawing the same coordinates. Okay. Now, suppose let's say now my best fit line looks something like this. And along with this, I try to create my marginal plane, which will pass through the nearest point from here. And similarly, it will pass to the nearest point from here. Right? And this is my marginal plane. Now, out of this two, right, which is the marginal plane that we should select, or which is the best fit line that we should select along with the marginal plane? Obviously, you'll be saying this. Why? Because over here, the distance between this marginal plane is less. Let's consider this is d dash and this is d. We know that from this, d is greater than d dash. So what we do is that we select this best fit line along with this marginal plane for doing the classification. Okay, classification. Now, this is the first thing. The second thing that you really need to understand over here is that the marginal plane passes through one of the nearest points from this particular plane. Let's say this is my nearest point, and similarly over here, this is my nearest point. These points are basically called as support vectors. Okay, this point are basically called as support vectors. Okay, so same with respect to this specific point. Both the points are basically called as support vectors. Now, in short, what is the aim of the support vector machine is that we really need to create a best fit line. Along with that, we need to create a marginal planes so that we'll be able to categorize the point very clearly or classify the point very clearly. What happens is that suppose if I get a new test data point, you'll be seeing that this belongs to this particular category, so this will get assigned to this particular category. Suppose if I get any new point over here, this will get assigned to this particular category. Okay. Now, this is a super important thing that you really need to understand. Now, one more thing that I really want to conclude from here is that suppose let's say if I have a 3D points, let's say I have a 3 dimension, x1, x2, x3, and let's say, and this is also used in multi-class classification also. Let's say I have this two categorization of coordinates. Okay. Now here, with respect to the 3D coordinates also, we have to create a 3D plane. Along with that, one more plane will be basically the marginal plane. It will be created like this. Another marginal plane which will be below this, it will be created like this. Okay, so this is how, what is the differences between
the 2D and the 3D plane. In this particular case, this will be my marginal plane. This will also be my marginal plane. I have to make sure that this distance should be maximum. So this is what is the problem statement that we are trying to solve. And in my next video, I'm going to explain you about what is soft margin and what is hard margin in support vector machine, a super important topic. And after that, we're going to understand the maths behind it, like how we are going to create this best fit line along with the marginal planes and try to solve this particular problem statement. So yes, I will see you all in the next video. Thank you. Now you have understood what is the main aim of the support vector machine, specifically for a classification problem when we are using support vector classifier. Along with the best fit line, we also try to find out a marginal plane in such a way that this particular distance should be maximum. Okay. Now let's discuss about this important topic which is called as soft margin and hard margin. Now usually, see, in this particular best fit line that we are using and marginal plane we are using, it's clearly separating all the points. But in the real world scenario, we will not have this much clearly separable points. There'll be a lot of overlapping. Suppose if I have some points in this two dimension, there will also be some overlapping, right? Now in this kind of overlapping case, I cannot clearly separate, just by using a best fit line and marginal plane in short. There will definitely be some amount of errors. Now when I say some errors, this points may be coming somewhere here. This points may be somewhere coming over here, right? Now, obviously, we cannot get a clearly perfectly best fit line along with the marginal plane to split the points. In this particular case, we will have some kind of errors. So this situation is basically called as soft margin. Okay. Now, whenever I say soft margin, that basically means some amount of errors will always be there because obviously in a real world scenario, we may get a lot of overlap points. Similarly, in this particular scenario here, you can see that we are clearly separating this, right? So this specific thing is basically called as here, since we are clearly separating all the points and we don't have any errors, this scenario is basically called as hard margin. In hard margin, we don't get errors. In soft margin, we definitely get some amount of errors because there is a lot of overlapping. Now, in the next video, we are going to discuss about what is the maths intuition, how do we draw this best fit line, how do we make sure that we come up with this marginal plane, or what equation is basically used for this particular line. So we will again be revising all the, the equation of a straight line, the distance from a point to the plane, all these things again we'll be revising in our next video, and then we'll try to understand the maths and depth intuition. So yes, I will see you all in the next video. Thank you. This video, we are going to understand the support vector machines in that maths intuition. In our previous video, we have already seen what is the main aim. We have to probably create the best fit line along with the marginal planes. Now let's consider I have two coordinates x and y, and obviously with respect to this 2D plane, I need to create a best fit line. Now let's consider this is my best fit line, and this is basically given by the equation w transpose x plus b is equal to 0. How this came? Earlier in my previous video, I've already explained that the equation of a straight line is given by ax plus by plus c is equal to 0. If I can also write this as w1 x1 plus w2 x2 plus c or b is equal to 0, this is in turn nothing but w plus x is equal to 0. W transpose x plus b is equal to 0. And if my line passes through origin, then b will be equal to 0. So finally, we can basically write w transpose x is equal to 0, right? But here, my b is not passing through the origin. So let's consider this is the equation of this particular straight line. Now, one more thing, what W is over here? W will be basically perpendicular to this particular line, right? So W is a vector that is perpendicular to this particular line. That basically means it has a 90-degree angle. And already we have also seen one very, very important thing is that suppose let's say that we have a specific coordinate here, and let's consider I'm going to take coordinate like -4, 0. Okay. Now in this particular coordinate, if I take this particular coordinate and if I try to find out the distance between this two coordinate, right? Now when I try to find out the distance between this two coordinate, let's say this is my d dash, and let's just consider one more coordinate. Let's say this is 4, 3, right? And this is my another coordinate. Let's say this is s, this is h dash. And if I really want to find out the distance between this to this hyperplane, what things we specifically used to do? We first of all used to calculate the angle between this particular vector, that is w, and s. Now obviously here you can see that the angle is greater than 90 degree. So we have already discussed this previously. Whenever this angle between this particular vector w and s, which is given by this coordinates -4, 0, is greater than 90, then with respect to this particular point, and the distance between this point to this hyperplane will be negative. Okay, will be negative. So any points that are there below this plane, right, below this best fit line, and if you try to calculate the distance, it is always going to be negative. Okay, this is super important to understand. Okay, similarly with respect to the coordinates that are above this particular point, right? Now in this particular coordinate, if I try to see, or if I try to plot this vectors w and x, here you'll be able to see that I'll be getting an angle that is between 0 to 90 degree, right? Whenever we have this kind of scenario, the distance between s dash to this particular coordinate or to this particular plane, or with respect to any points that are above this plane, the distance will always be positive, right? So the distance will always be negative below the plane, right? And distance is going to be positive above the plane for all the points. Right? So this is the pure understanding that you will need to find out, that every points that are below this, it is going to be negative if I try to calculate the distance between this two plane. And similarly, all the points that are above the plane, the distance between those specific point and the plane is going to be positive. So this we have already discussed in finding the distance of a point to a plane, right? So please make sure that if you're not able to understand this, check out that specific video. Okay. Now till here, I hope everybody has understood what we are actually trying to do. Okay. We are just trying to calculate the distance and we are trying to find out. Now, let's quickly go ahead and do one very important thing. Let's say I'm just going to draw the specific point again. So let's say I've clearly made you understand that suppose if this is my best fit line, wherein my y is basically perpendicular to this plane, and this is given by the equation w transpose x plus b is equal to 0. So I said that any point below this plane, and if you're trying to calculate the distance from here to probably this, it is going to be negative, right? So here what we can do is that we can create one more plane. So let's say this is my plane, and this plane is basically called as marginal plane, okay? And this plane passes through one of the coordinates over here. Similarly, on the right hand side, what we can do is that we can create another marginal plane, okay? Another marginal plane, wherein my other points that are the other coordinates, and obviously from this particular coordinate to the distance between the marginal plane, it is always going to be positive, right? Positive. So let's say if this is my nearest point from this plane, so these are my support vectors, these are my support vectors, right? And this is what we have to basically do. And obviously you have understood any points that are below this plane are going to be negative with respect to distance from this point to the marginal plane, sorry, to the hyperplane. And similarly from this particular point to the hyperplane, I'm always going to get a positive distance value, right? Positive and negative. This is super clear. Now, can we provide out some equation to this specific line? So here I'm just going to like w transpose x plus b is equal to +1. The reason why I'm writing +1, because over here you can see that from this particular plane, anytime I go up, right, it is going to be positive. It is going to be plus 1, plus 2, plus 3, plus 4, plus n, plus some values, right? We can also replace this with plus k. But in many research paper, they usually use plus k or plus 1. So here I'm going to basically write it as plus 1. Okay. Similarly, this particular line that you see below the plane, I can also mention this as w transpose x plus b is equal to minus 1. So obviously our main aim is basically to make sure that this distance is maximum. That is the distance between this marginal plane and this marginal plane. So in order to compute the distance, what I'm actually going to do is that we are just going to subtract these two values. So let's say this is probably x2 and x1, right? So in short, what I'm actually going to do, I'm just going to basically write w transpose x1 plus b, and similarly I'm going to write w transpose x2 plus b. Here I'm going to use plus 1, and here I'm going to use minus 1 because this plus and this minus is there. And now if I really need to compute the distance between them, and that distance needs to be maximum with respect to all the other best fit line or marginal plane that we are creating. So here if we try to solve this linear equation, this will be minus minus, this will get cancelled, and this will be w transpose x1 minus x2, which will be equal to plus 2, right? So which will be equal to plus 2. Now you really need to understand one very important concept which is called as unit vector. If I really want to calculate the unit vector of any vectors itself, right? Unit vector basically means where the magnitude of that vector is 1. Magnitude of the vector is 1, right? Now if I really want to show you that how this magnitude of the vector will be 1, it's very simple. We just divide w transpose with the magnitude of w. Okay, so once we do this on both the side, here we are basically going to get it as unit vector. And it is always a good idea that we need to come up with a unit vector because all the points will be normalized within that value between 0 to 1. So guys, this RHS that I have specifically got, that is 2 by magnitude of w, so this is basically going to be my cost function, right? Because if I take this 2 by magnitude of w, I really need to maximize this value. Why we need to maximize this value? Because this is basically the distance between these two marginal planes and it needs to be maximum. Now, this maximization will be doing by changing the values with respect to w comma b, okay? And on top of it, I would definitely like to write another constraint, okay? And this is nothing but distance between marginal planes. Distance between marginal planes. Along with this, I'm going to write a small constraint, and let me write that particular constraint. And this constraint is with respect to all the truth values, that is y of I, my true output. Y of I will be plus 1 when w transpose x plus b is greater than or equal to 1, right? Similarly, y of I will be minus 1 when w transpose x plus b is less than or equal to minus 1, right? These are for all correctly classified points. Okay, correctly classified points. Now, whenever I say correctly classified points, what does this basically mean? This basically means that whenever all the points that are above this, w transpose x plus b is greater than 1, I'm going to basically categorize this as plus 1. And this all points I'm going to categorize as minus 1. So this will basically say about my truth points, okay, about my true points. So whenever in our data set, whatever output feature I specifically have, that all truth points will be there. So w transpose x plus b greater than 1 will basically be talking about the positive points, and w transpose b is less than or equal to minus 1. Whenever I find out with respect to any points, we're going to label it as minus 1. Okay. Now, let me finally write one important thing. For all correct points, we know that if I multiply, so here I'm just going to add one more constraint. If I multiply w of I multiplied by w transpose x plus b, you will always be getting this as greater than or equal to 1 for all the correctly predicted points, right? Because see, if you are getting w transpose x plus b is greater than or equal to 1, if it is greater than or equal to 1, that basically means our output is plus 1. So if I multiply both these two, I'll get positive. Okay. Similarly, if my w transpose x plus b is less than or equal to 1, if I multiply with minus 1 for the correctly points, I'm also again going to get it as greater than or equal to 1. Okay. So this is my entire cost function, and I really need to maximize the specific cost function by changing w comma b. This is the constraint with respect to, like, for all the points that are above the plane, I'm mentioning it as plus 1, and all the points that are below the plane, I'm mentioning it as minus 1. Okay. And when I probably multiply plus 1 with w transpose x plus b, always I'm going to get greater than or equal to 1 for all the correct points. Now let me fine tune the cost function a little bit, and this part I will try to show you in my next video. Thank you. This is eta. Eta basically says it is the summation of, because here I'm doing the summation of, right, from I is equal to 1 to n. So here I'll say summation of the distance of the incorrect data points from the marginal plane. So here in short, what I'm doing, eta basically computes the distance between this point to this marginal plane, this white point to the above marginal plane, this yellow point. So these are two hyperparameters. One is that how many number of misclassified points I can have, and the second parameter is that, okay, this much distance is allowed. If I probably do the summation of all this distance, that much distance is basically allowed. Okay, so this is what a cost function of SVM looks like, and this is not related to hard margin, but this is the cost function that is related to soft margin. Okay. So with the help of this particular cost function, I will try to minimize this. Along with this, we will be setting a parameter with respect to C of I and eta of I, and this specific hyperparameter is called as a hinge loss. Like how we have in logistic log loss, similarly we have over here as hinge loss. Okay. So I hope you have understood about how does an SVC basically work, and with the help of this, we will be able to create our best fit line along with the marginal planes. So this was the entire in-depth maths intuition behind support vector machine, which is specifically support vector classifier. In the upcoming videos, we are going to understand about support vector regression. So yes, I will see you all in the next video. Thank you, and keep on revising this mathematical concepts. Thank you, guys. In this video, we're going to discuss about the support vector regression machine learning algorithm. In our previous video, we have already seen support vector classifier, and we have seen what is the cost function, what is the constraint, and we have also learned about a new loss function which is called as hinge loss. Now, in this specific hinge loss, you know that we have two parameters, that is C of I and eta of I, right? And our main aim is basically to reduce this cost function by changing w comma b, right? And if we discuss about the regression problem statement, the regression problem statement will also be working like this. So first of all, we really need to find out the best fit line. Along with that, we need to find out marginal plane, and we have to make sure that this distance is maximum. Now, here I'm going to take a simple problem statement. Over here, you can see the okay, let me just change this parameter a bit. So first of all, I'm going to basically write in the y-axis, this is the price of the house, and this is the size of the house. And we really need to create a SVR model, that is support vector regression model, to basically predict based on the size of the house, what is the price of the house. Okay. And over here, why this is a regression problem statement? Because all your output feature, that is your price, is a continuous value. Okay. So this is a regression problem statement. Now to begin with, whenever if I really want to construct the best fit line along with the marginal plane, I can definitely write my cost function, which looks something like this. So the cost function will be, main aim will be to minimize by changing w comma b, and this will be magnitude of w by 2. And this from where did we get? We had actually derived this. Over here, you can see it. Okay. Now, once we write this cost function, let's go towards the SVC and see along with the cost function, I had written some kind of constraint, okay? And the constraint was that y of I multiplied by w transpose b plus b should be greater than or equal to 1. This is super easy. Now, if I see in the support vector regression, see, this is super important, okay? Our main aim should be to basically create this best fit line along with the marginal plane in such a way that my distance between the predicted points and the real points, if I do the summation, it should be really less, okay? So let's consider that this particular line I am denoting as w transpose x plus b, okay? We denote this particular line with w transpose x plus b. What about this line, that is this top marginal plane? Now here, if I probably compare from the best fit line to this marginal plane, we are in short adding some value, right? This value, let me denote it as epsilon. And this below line, we are subtracting a value which is epsilon. So here I can basically write an equation which is called as plus epsilon, w transpose x plus b plus epsilon, this will be minus epsilon. So if I say what is epsilon, this is nothing but my marginal error. Marginal error basically means, marginal error or margin error basically means the distance between this point to this point. Similarly, the distance between this point to this point. And both this distance will be almost same, okay? It will not be changing over here. This distance will be almost same. So I'm using this three equation. To find out the best fit line, I'll be using w transpose x plus b. This will be w transpose x plus b plus epsilon, and this will be w transpose x plus b minus epsilon. Now, if I'm probably creating this for a regression problem statement, I have to make sure that most of my points, data points over here that are present in this problem statement are covered within our marginal plane. So the first constraint that I'm actually going to write over here, that is the distance between y of I and w of I x of I. W of I x of I is nothing but this is my points with respect to the predicted points over here. And y of I is basically my truth point, right? This truth point. So if I probably try to find out the difference, right? This should be less than or equal to epsilon. If it is less than or equal to epsilon, that basically means our model is really performing well. So most of my data points over here also you can see it is less than this particular epsilon. That basically means it is falling within the marginal plane, right? Within the marginal plane. So this should be one of my constraints whenever I am actually creating my best fit line and the marginal plane for a regression problem statement. But there is one simple catch, okay? Here you'll be seeing that, okay, most of the points are falling within the marginal plane. But what about the other points that are falling away from the marginal plane? So here we will again define some deviation. Some deviation basically means that this deviation can probably use as an hyperparameter to construct our best fit line and the marginal plane. So here I'm going to make some changes with respect to our cost function. First of all, I'm going to add a parameter which is called as c of I. So this will be summation of I is equal to 1 to n, and here I'm going to basically use as eta of I. Okay. Now the same thing I've also used over here, right? I've used over here like this is my hyperparameter. We basically say the two parameters are nothing but a hyperparameter, and we can also say this as my hinge loss. Okay. Now let me explain what is eta of I in this particular case. Okay, eta of I in this particular case. Now, as I said that most of my points will be falling within this marginal plane. If it is falling within the marginal plane, that basically means the difference between the real point and the predicted point will always be less than or equal to epsilon. Okay, but what about this specific points that are outside this marginal plane? So here you can see I have some points over here, here that are outside the marginal plane. Here also I have some points that are outside the marginal plane. So for this also, if I really want to, I should also be considering these points when we are constructing our marginal plane along with the best fit line. So what we do is that we define one more parameter which is called as eta of I. Okay, eta of I basically says that okay, this will be a deviation from our top marginal plane and from our bottom marginal plane, that okay, if we are also getting this much distance, we should also consider this as a hyperparameter to construct our marginal plane along with the best fit line. So this value is basically my eta of I, the distance. Here is also eta of I with respect to the distance. Okay, now this is super easy till here. I hope everybody is able to understand. Now whenever I try to do the summation of eta of I, now see, this is super important. If I try to do the summation of eta of I, that basically means I'm going to find out the summation, or I'm going to find out the difference. Just let me know this quickly. So I'm in short finding out the distance between this point and this particular point. So this will basically be giving my eta of I for this point. Similarly, if I try to do the summation of the distance between this point to this point, I'll be getting different eta of I. So I'm just going to do the summation of all these values, and we are going to also use the hyperparameter while probably constructing our marginal plane and our best fit line. So we are going to do the summation of all these things with respect to the eta of I. Okay, so this was it. So what I'm actually going to do after this is that I'm also going to change my constraint. So this should be epsilon plus eta of epsilon plus eta, right? So this constraint will now change like this. The reason is that now we're just not considering epsilon. Epsilon is this specific value, the distance between this to this. But when I talk about eta of I, I'm basically trying to find out all the points, all the distance between the points that are above the marginal plane and the specific predicted points on the marginal plane. So this both will be specifically used in order to fine tune our model with respect to the SVR. Okay, super easy. Now what exactly C is? Okay, C is again one kind of another hyperparameter. Okay, hyperparameter. And one more point that I missed, guys, this is obviously a kind of loss function, right? It can be any loss function because here we are trying to find out the difference between the true point and the predicted point. Okay, now with respect to C, I'll just try to create a small diagram to make you understand the relationship between C and loss. Okay, C and loss function, or let me just write this something like this. Now you know that when the C value will keep on increasing, the loss function will keep on decreasing. Okay, that is the relationship that we will be able to find it out. The relationship that we will be able to find it out, that when the C value will keep on increasing, then here you'll be able to see that my loss function will be decreasing. So just let me know how the curve will be. Take this as an assignment, but if you know this, the curve will look something like this. Okay, so as the C value keeps on decreasing, the loss basically keeps on decreasing. Okay, now let me just create it in a good way so that you will be able to find it better. Okay, so this is what is the relationship between C and the loss function. But yes, I hope you have understood with respect to a regression problem statement, and this I will show you in practical, like, how you'll be able to find out the relationship between C and loss function. But here you can definitely see that in the case of a regression problem statement, you use something like epsilon. Here epsilon is nothing but your margin error from the best fit line, margin error, and eta of I is nothing but the error above the margin, and this both the parameters can be used to basically create a best fit line along with the marginal planes, right? So these are some of the hyperparameters with respect to the support vector regression. So I hope you have understood this particular video. If you have not, please make sure that you revise. If you have any queries, you can definitely put down in the comment section of this video. So yes, this was it from my side. Thank you and all. Keep on rocking, keep on learning. Thank you.
Hello guys, in this video we are going to discuss about support vector machine kernels, right? So we also say it as SVM kernels. Already in our previous video we have seen support vector classifier, support vector regressor, we have understood about the hinge loss and many more things. But at the end of the day, what is the major aim of support vector machine is that we really need to find out the best fit line. Along with that, we need to find out marginal planes. So these are nothing but marginal planes, and it should be in such a way that we should be able to efficiently separate both these points. Suppose in this case, which is a binary classification problem, right? binary classification problem. And for this, we specifically use SVC, that is support vector classifier. And since we have to create this best fit line along with marginal plane, we basically say this variant as linear SVC. Okay, so we also say it as linear SVC. Linear SVC basically means we basically create a straight line. Along with that, we also create a marginal plane. Now, what if you have some data points and those data points looks something like this? Okay, so let me just show you some of the data points. Let's say I have two dimensions, that is x1 and x2, and let's say I have some of the features which looks like this. Okay. Now, in this particular case, here you'll be able to see my features, it may be in this way, and the other feature, which is my output category, will be in this way. Now, in this particular scenario, if I really want to use this linear SVC and try to create a best fit line, let's say this is the best fit line. Along with that, let's say I create a marginal plane, which is like this. Obviously, for this kind of scenario, linear SVC will not work, right? Why linear SVC will not work? Because all these points are overlapped. It is not clearly separable, right? So, during this scenario, my accuracy will definitely go low if I probably use a linear SVC model, right? So, in this particular case, obviously, my accuracy will be low, my error will be high, right? Just by seeing this, you can see that efficiently it will just be able to divide 50% of the points, right? Now, during this scenario, can we find out a way to solve this? And that is where, whenever we have this kind of data set or this kind of scenarios where my data points are not linearly separable, we can definitely use something called as SVM kernels. Okay, we will discuss about what are the different types of kernels later on in the upcoming video. But let's understand what this SVM kernel will do. Okay, so let me again draw these points again for you. So let's say if my data point is something like this. Okay, I have a lot of data points which is present over here like this, and obviously this is not linearly separable. This is just overlap points and distributed in this specific way. Now for this particular data points, I'm just taking as an instance, as an example. Okay, let's say this is my x coordinate and this is my y coordinate. Now with the help of SVM kernel, we are just going to apply some transformation on this data set. This is super important to understand. Some transformation. Once we apply this specific transformation, then you will be seeing that the final outcome. Now because of this transformation basically means we will be applying some mathematical formula on this specific data set. Okay, it can be, we'll discuss about it, what are the different formulas we'll be using, the different types of SVM kernels. Now what this will do is that this, whatever transformation we are applying on this data set, this will create, right now it is in 2 dimension, right? Let's say it will create a 3-dimensional data point. And right now here you can see there are white points, they are red points, right? Now this white points will look something like this. And this red points will probably look something like this. Okay. So what exactly has happened over here? I think it is very simple. Here you'll be able to see that the data points that were present in 2D, that is 2 dimensions, has been now converted into 3 dimension. And how it got converted to 3 dimension? By using a simple transformation technique. Now what is this transformation? There are many which we'll be learning. Just understand the base idea over here. Now this will be x, this will be y. Over here in this 3 dimension, they'll try to create an additional axis which is z, right? In this particular axis z, right? And now you'll be able to see that this point, because of this transformation, is clearly separable, right? Now what you can do is that with the help of linear SVC, you can probably create a plane, and this is nothing but a 3D hyperplane. Along with that, you can also create a marginal plane, and then probably separate this all points. So this is what we are specifically doing with SVM kernels. We are making the data set, we are basically applying some transformation on this current data set, which is not at all linearly separable, and we're trying to convert this into some other dimension because of this transformation. And during this scenario here, you can see that data points are clearly separable. So we can then create our best fit plane along with the marginal plane and probably separate these data points. And obviously during this particular scenario, if you're able to do this, the accuracy will definitely go higher. Now what are the different transformation techniques, or what are the different SVM kernels? We'll discuss about it. Okay, but let me just make you understand how this, I definitely want to give you some basic example of some mathematical formula that we may be probably able to apply on a specific data set. Okay, so let's go ahead and see one basic example, and later on we'll try to discuss about all the types of kernels. Okay, so let's consider I have a data set, and this specific data set is just in 1 dimension. Okay, a basic example, 1 dimension. Let's say this is my data points. Here is my 0 in the x-axis, so this is my x-axis, and here I have a lot of data points. Let's say like this, I have data points, and I have another category of data points which looks like this, and then I have one more similar category of data points like this. Okay, now here also you can see that if I really want to apply a SVC in this, over here you can see that my data points is clearly separable over here also. But with the help of SVC, I can only create one separation line, right? Now, obviously, if I separate it from here, still this many number of data points will be clearly misclassified, because whatever is below this line, it will be considered as yellow points, and whatever is above this line, it will be basically considered as this orange points. So obviously, we cannot solve this particular problem statement, which is in 1 dimension. All the points are in 1 dimension. We cannot solve it with the help of linear SVC. Now let's see how we can solve this. Okay. Now what it will do is that, let's say I'm going to apply some transformation. Now this specific transformation is super important. Now what I'll do in this transformation is that I will create a new axis y, and here I'll just put y is equal to x square. Now when I apply this specific formula, what will happen? I will get a new axis y. This will be my x-axis. Okay, and let's say this is my x and this is my y. Initially my points were something like this, right? Let me draw this point again. 1, 2, 3, 4, and then I will probably draw this points. Initially my points were like this, right? Now when I apply this transformation technique, then here I'll definitely have different y values. So here you'll be seeing all these values. When we do x square, you'll be seeing we'll be getting this kind of coordinate system. Okay, and then I will probably get yellow, and then probably I will get orange. Right? Something like this. Now, as soon as I applied the transformation, here you can see that this 1D got converted into 2 dimension, right? I just use y, I created a y-axis. But what will be the advantage when we have this kind of data points now? What is the advantage when we were able to convert this 1 dimension to 2 dimension? Here you'll be seeing one very simple thing is that now you can probably create a best fit line with the help of linear SVC. Now I can basically solve this with linear SVC and probably get my accuracy quite high. Right? It's clearly separable, right? Because I was able to convert my data points from 1 dimension to a higher dimension. Now all I have to do is that just create a best fit line, along with that just to try to create a marginal planes, right? And then you'll be able to see that I'll be able to divide this particular point, that is orange and yellow, in a very easy way, right? So this is the entire idea behind the transformation, and obviously this kind of transformation in many of the scenarios we'll be using SVM kernel. Now, what are the different types of kernel we'll be discussing going forward? First of all, we'll be discussing about a kernel which is called as polynomial kernel. Then we'll also be discussing about RBF kernel. and there is also another kernel which is called as sigmoid kernel. The major thing that you really need to understand is that what is the transformation formula it is basically applying in order to create a new dimension. Similar thing, like if you have a two-dimension point, we can also convert this into three-dimension by just applying transformation formula, and probably for that I may use RBF kernel. So different techniques I'll be showing you with some different examples which will be seen. And as we go ahead, this kernels will be quite interesting because this is also asked in a lot of interviews. Okay, and it's quite powerful, guys, quite powerful. Okay, so I hope you have understood this. Yes, I will see you all in the next video where I'll be discussing about different types of kernel. Thank you. Hello guys, in this video we are going to implement a support vector classifier with the help of sklearn, and for this we'll create our own dataset. We'll see some visualization, and probably we'll also be discussing about SVM kernel as we go ahead with respect to all these videos. Okay, so first of all I'm just going to import some important libraries. First of all, let's go ahead and import pandas as pd, import numpy as np, okay, import cbon as SNS, and finally you can import matplotlib, which I am also going to use, .pyplot as plt, and I can also import cbon, right, cbon as SNS. So these are some of the basic libraries that I'm going to use it. For creating our dataset, the first step is that we will try to create some dataset, but in the upcoming videos we'll be seeing a full-fledged project also with respect to support vector classifier. So now let's create a synthetic data points, okay, data points, and here we'll try to solve both classification problem, and for multi-class also we can basically use that OVR concept in SVM. Okay, so let's create some data points, synthetic data points, and in order to create a synthetic data points, all you have to basically do is that import from sklearn.datasets, import make classification. So I hope everybody knows about this make classification. We have already used this. This make classification will be giving me x and y axis, and probably if I use make classification, here the number of samples will be 1000, and the number of features that I'm probably going to consider, let's say the number of features, I can basically say 2, just to see that whether my visualization will look good or not. And here the number of classes also I'll be trying to take it as 2, and there is also like number of cluster per class, I will go ahead and assign this value as 1. Okay, and any specific parameter, let's see whether this will work or not. So here it gives some warning, number of informatic redundant and repeated feature must be some. Okay, this is the same warning that we got earlier. So here I'm just going to make it as number of redundant features. Let's make it a shift tab over here, number of redundant features. So here I'll just make it as 0. Okay, so now this is my x coordinates with respect to my input features, and this is my y, which is with respect to my output features. Now quickly let's plot the scattered plot. So I'll be using SNS cbon dot scatter, and on this particular scatter plot, you will be seeing I'll be using my x and y coordinate. Okay, so x and y coordinate, and there will be a parameter which is called as y. Okay, and here I can definitely see the thing is that in my x I have two axes, right? X1, this is my first column. This can be my second column, right? So we will give in our x and y axis with respect to that same column. Okay, so probably I can do one thing. I can just write df pd dot data frame. I can basically convert this into data frame. And if I probably write an x here, you'll be able to see this is how we'll be getting. If I want to get the first column, I can write of 0. So this will basically give me the first column, right? So I'll go and paste it over here, and then I will go and paste over here and basically write 1, which will give me my y-axis, and this y will basically be given by my y parameter. Now once I plot it here, let's see, cbon has no attribute scattered plot. Okay, then this will be sns.scatter plot, and then we try to execute it. Now here you can definitely see that my data points are very clearly separable, and obviously I can actually create a best fit line with the help of SVC. And for this, the SVC that we will be using it is called as linear SVC, and let's see how the accuracy of our data set will basically come with respect to this. Okay, so this is how my data set looks like. Now in the next step, all I have to do is that go to sklearn and use SVC. So if I write sklearn SVC, that is SVM classifier, this is where the library is basically present from sklearn.svm. So all I'll do is that I'll say from sklearn.svm, right, import SVC, right? So once I execute this, this will be my SVC, and then I am basically writing my SVC over here. By default, there are many parameters which we can basically play with hyperparameter tuning, like kernels, degree, gamma, and all. We'll try to play with hyperparameter tuning, but right now, by default, you'll be able to see that we are having a kernel which is called as RBF kernel. But as I know that, right, because this is two-dimensional points, I definitely know I can see that okay, it's clearly separable. I can definitely use the kernel as linear. Okay, so when your data points is clearly separable, you can use the kernel as linear and start fitting the entire data set. Then I will go into svc.fit on my x train, y train. Okay, so once I do this, so okay, x train and y train is still not done. So let me do after this, right? I will just try to do my train test split for. So I'll say from sklearn dot reprocessing import. Okay, it is not reprocessing. I think it is model selection. Import train test split, and then what I'm actually going to do over here is that I'm just going to create my x train, comma x test, comma y train, comma y test. Okay, and this will basically give me my train test split. Okay, and here is my x and y coordinate, and my test underscore test size is nothing but 0.25. Okay, and I can basically use any random state as I want. Okay, so random underscore state is equal to 10. Okay, so this is got executed. Now I will go and do this. I will go and fit with my x train and y train, and now let's go ahead and do my predictions. Okay, for this I will do the prediction as y underscore pred svc dot predict, which is a linear kernel. Now obviously I know that this will give us a very good accuracy because we definitely have a good separation between these 2 points. Okay, so now what we're going to do over here is that from sklearn dot metrics, I'm going to import. I'm basically going to import some libraries like classification report and confusion metrics. I think this both will be more than sufficient. Then I can print my classification report with my y underscore test, comma y underscore pred, and then I can also print my confusion metrics with my y underscore test, comma y underscore pred. So once I execute it, here you can see absolutely 100% accuracy, and obviously because my data points looks clearly separable, right? So this is one amazing thing that we had done, and with the help of linear SVC, yes, we are able to get it. Probably if I apply logical regression also, I will be able to get a good accuracy. Okay, the reason is that my points are very clearly separable. Now let's say if I don't give the specific parameter n underscore clusters per class, what will basically happen is that you just see it. Okay, so let's say if I press shift tab and over here n underscore plus 2 plus per class is 2 by default, right? Let me just give attach 2. Now you will be seeing, if I probably plot my data set, now this has a lot of overlappings. Now if I probably use linear SVC, I will be getting a bad accuracy. You can see over here. So obviously my accuracy is decreased to 85%, right? Why? Because these data points are not that linearly separable. But usually we try to find out a data set which is trying to get, if it is linearly separable, we can definitely use this linear SVC. Now there may be a situation that we may get this kind of overlap data set also. And for this kind of data sets, we can use different kernels. Okay, the kernels like RBF kernel, there are kernels like polynomial kernel, sigmoid kernel. Let's say by default, if there is RBF, and for the same data point, I go ahead and use RBF kernel, right? So if I say RBF and probably use SVC, and here, and the kernel that I'm actually going to define is nothing but RBF. Okay, so now if I do RBF dot fit on xtrain comma ytrain, okay, xtrain comma ytrain, and here I basically get my SVC kernel. Okay, now all I have to do is that do the fit over here with RBF. Okay, now I have also done the fit. Okay, same thing, I've implemented it 2 times, no need of doing this fit. Now I can do the prediction. For doing the prediction, let's say this is white red one. Here I'm going to basically use RBF. And once I execute it, I'm probably copy and paste this entire thing and try to print it with respect to white red one, red one. Now you can see that the accuracy has improved, right? Before I was getting somewhere around 85%. Now because of the RBF kernel, what may have happened internally, some transformation of these lines has happened, this points has happened, and it's probably created a new dimension. Okay, and because of that, you'll be able to see that you are able to get better accuracy, right? Similarly, if you try with other kernels, even like polynomial. Suppose let's say if I try with a polynomial over here, I'll copy everything over here and paste it. Let's see, this will be my prediction. Okay, and this will be my classification report and confusion matrix. So let's say if this is polynomial, okay, and with the help of polynomial also, there are chances because of the mathematical equation or transformation that will basically happen, it may improve the accuracy. Okay, so here it is polynomial, white red one, white red two. This will be white red two. This will also be white red two, white red two. So once I probably plotted polynomial is not in the list. Okay, so I think it is poly. Okay, you can probably press shift tab and you'll be able to see that what are the possible options in the kernel, right? So in kernel you have poly, RBF, linear, sigmoid, and all. So suppose if I say I'll be using poly, I'm probably trying to predict it. Now I'm getting 82%. So definitely poly transformation will not work because it is giving bad accuracy when compared to the linear part also. Similarly, I can basically do it for sigmoid also, right? Sigmoid, right? And this I will just make it as sigmoid. Because these are all different kernels which we will basically be using, and each and every kernel applies a different kind of formula and transformation on your data set. Okay, so this will be my this one, and once I predict it, this will be white red 3, and let's see whether we get a better accuracy when compared to the previous one. We can also do that. So here you can see that with the help of sigmoid, again bad accuracy is coming. So out of this, if you tell me that which kernel I may be probably using, I'll be using RBF kernel for this kind of data set. Okay, because it will do some kind of transformation, create a higher dimension based on the formula of RBF, that is radial basis kernel. Okay, so this is how the kernel basically happens. Now along with the kernel, once you are able to decide the kernel that you're probably going to use, you can also perform something called as hyperparameter tuning. Now, with respect to hyperparameter tuning, what we are basically going to do is that we're going to play with different parameters. Okay, so I have probably made a list of parameters with respect to param grid. Okay, now as I know, with respect to my particular problem statement, I'm going to use RBF because it has given better accuracy with respect to RBF over here, right? With respect to this specific data set. But there are some more parameters in SVC that you'll be able to see, and these parameters are nothing but C value, kernel value, degree value, gamma value, shrinking, probability, total. All these values are there, and we can definitely play with this parameter. We can select this right kind of parameters, and it completely depends on the data set. So here I'll just show you one example how we can perform grid search CV. So once I execute this, all I have to do is that go ahead and train my grid search CV. So here you'll be able to see I'll be using grid search CV with SVC, comma, param grid is equal to, I'm just going to assign to my param grid, comma, here I can basically also use CV is equal to 5. Let's say I'm going to use CV, and then I'll also use some verbose will be 3. Okay, and once I probably implement this, I will save it in grid. Okay, there's also a parameter which is called as refit in this. Okay, so I will also say refit for every iteration. It is just going to refit each and everything for every cross validation. So now if I probably write grid dot fit on xtrain, comma ytrain. Now you'll be seeing that it'll take some amount of time for training. Now this entire training has happened with respect to different parameters, and now here you can see that I will be able to get the best parameter. So if I write probably grid dot best underscore params, you'll be able to see these are the parameters that I got selected. C value 1000, gamma 1, kernel this one. Now if I probably do the predictions, here you'll be able to see it. So this will be my predictions, and my predictions will be done with the help of grid, right? So grid dot predict, and this will be my white red 4. And finally, you'll be able to see what is the output result that I'm actually getting. So overall, a good accuracy of 93%. Now see, this is the basic difference what will happen if you try to select the right C value, gamma value. I just played with 2 parameters over here. Like that in SVC, there's so many different parameters, right? So I hope you got an idea with respect to grid search CV, and you have also understood how we can basically perform hyperparameter tuning. So I'll just make a cell over here and basically create hyperparameter tuning with SVC. Okay, super important, super easy technique to basically see the accuracy. And now you can see that the accuracy is increased to 93%. Before it was somewhere around, if you probably see it, it was somewhere around 88%, right, with the help of RBF. But still we use some different parameters like C, gamma, kernel. So here you should not stop over here. Still you should basically try out with different parameters right now. Like class weight, if you have an imbalanced data set, definitely use class weight. You can also use gamma, right? Gamma with respect to gamma, different values you can assign. With respect to coef O, you can assign different values, and you can basically play. Now this whenever you probably calculate with respect to SVC also gives you different coefficients and intercepts. So suppose if I probably see for sigmoid, if I write sigmoid dot intercept, here you'll be able to see this intercept, comma, if I probably write sigmoid dot coef, so here also you'll be able to see the coef value. Coef is only used when using a linear kernel. Okay, perfect. So for this, it will not be there. But if you probably see over here for a linear kernel, which we have actually seen in this SVC, here you'll be also able to see the coefficient. Obviously, it is because for a curvy line, you will not get coefficient. For a straight line, only you'll be getting. Okay, so SVC dot coef. And once I execute this, here you can see the coefficients that you're able to get, right? Because in my xtrain, I have 2 features, right? So yes, this was just a basic implementation of SVC. I hope you are able to understand this. Now what we'll do is that we'll try to create more complicated data set, and let's see by if I do the transformation manually, right, like polynomial kernel transformation manually, what things will happen, and are we able to change the data or clearly separate the data, once we find out a linear separable data itself by using a plane. So that all things we'll have a look onto my next video. So yes, I will see you all in the next video. Thank you with SVM kernel. Hello guys, in this video, we are going to see the power of SVM kernels, right? In our previous video, we have seen some SVM implementation, and here also I showed you that when we have this kind of data set, right? And when we use RBF, we basically get a very good accuracy, right? And along with that, if you perform hyperparameter tuning, still more better accuracy. But today, in this video, I'm going to focus more on SVM kernels. Now let's say, if we are using a linear SVC, that is support vector classifier, if my data points are linearly separable, then only it will give us good accuracy. What if I have data points which looks like this? Now here you can see my data points are completely overlapped, right? I cannot create a linear best fit line which looks like this, right? I cannot do that. I cannot create a linear best fit line, right? I cannot create something like this line. Okay, sorry for the line. I cannot create like this, right? Obviously, it will give me an error because 50% of the points are correctly classified, 50% will be incorrectly classified. So this is a big blunder. So can we use SVM kernel, probably increase the number of dimensions with respect to this particular features, and then probably see how we can easily classify this again by using linear SVC. Okay. So first of all, I have just created this data point. So here you can see these are my data points. Here I created my x-axis, y-axis. I've stacked all my values with respect to. Now see this. If I probably execute it and if I see this my x-axis, now here this will be what will be my x value. It says that it is basically present between -5 to +5, and the number of points are 100, right? So these are all the 100 points, right? Similarly, if you see y, I've just done the np.sqrt over here, and finally you'll be able to see this. Okay. Now if I go over here, this is my other coordinates. Let's say this x and y are my outer coordinates over here, right? The inner coordinates I have actually plotted over here between 5 - 5 to 500 and np sqrt with 5 square and x1 square. Okay. So once we do this plotting, then y, x and y1, x1, I will be getting this kind of data points. Now this is perfectly fine. Now what I will do is that with respect to this outer data points, I will label it as 0. Okay. So here you can see that I'm doing the vertical stacking of y, x. Vertical stacking is one after the other. Okay. Of y, x. Okay. Probably let me just show you what will happen if I probably do this and probably transpose this particular value. So if I probably make a cell above, here you'll be able to see that I have vertically stacked this and I have made a transpose like this, right? So how we do a transpose in the matrix. So here you can see this is my first feature with two features. I have these values. Then this is my second data point, third data point, fourth data point like this, right? So that, and I've specifically taken two data points over here because I can visually see this. Okay. Now here I've given my column names x1, x2, my d, f1 of y. This is my output feature. For all these outer data points, I'm saying that all my data points is basically given as 0, the output feature. And with respect to y1, x1, when I'm actually putting it in data frame 2, this is the output will basically be 1. And then I'm appending df1 with df2. That's simple, right? And this is my final df. X1, x2 I have. Then after that, this will get appended y1, x1 along with this, and this will be my y value, which will have 0 and 1, right? So if I probably see df.tail, you'll be able to see finally I'll be getting all the 1's values like this. Okay. Now after this, as usual, I will try to divide my features into independent and dependent features. So x1 and x2 will be all my independent features. Y will basically be my dependent feature. So here it is. This is my y value. Then I do train test split. This is super simple. So I'm going to go a little bit quickly. So here is my y train. Now there are different types of kernels that you can apply. See, one is something called as polynomial kernel. Okay, polynomial kernel, SVM formula. If I probably go and search for this and search in Wikipedia, right, you'll be able to see that I'll be getting a definition which is looking like this, right? So this is the transformation that I can apply on the feature 1 and feature 2. So basically on 2 points, not feature 1 and feature 2, but 2 points, x and y, right? And if I probably consider x, there will be feature 1 and feature 2. In y also there will be feature 1 and feature 2. Two separate points. If you do the transpose plus c to the dimension of t, to the dimension of t, d is nothing but the polynomial degree. So in this particular case, here I'm specifically applying polynomial kernel, and this is the transformation that I'm going to apply for any points. Okay, and we have already discussed in theory. Based on this transformation, we are going to get what are key important points, that is x1 square, x2 square, and x1 multiplied by x2. So these three key points I will try to find it out from this particular equation, and I'll try to plot it over here. When I try to plot this by considering x1 square, x2 square, and df of x1 and x2, I'll be able to see that my points will be linearly separable. Okay, so from this equation, the three key important components that we will be getting is x1 square, x2 square, and x1 multiplied by x2. Since all my values are in data frames, so I'm just going to create new features like x1 square, x2 square, and x1 multiplied by x2. So once I execute this, these are how my points will look like. Now see, let's take all my independent features from here. Independent features, these all are my independent features, right? So I'll then update my independent feature, and my y will basically have my output feature. Now again, let me go ahead and do train test split. Now see, one magical thing will happen now. Okay, so once I do the train test split, and now if I try to plot it, now see what I am doing while plotting. I will take x1, I will take x2, and then I'll take x1 multiplied by x2. Okay, and probably this is a scattered 3D plot. So in plotly.express, you have something called a scattered 3D plot. You have to give three coordinates: your entire data frame, your x coordinate, y, and your z. So x I'm taking it as x1, x2, and x1 multiplied by x2. So if I probably plot this, and you'll be able to see this. So once I plot this, see, this is the same thing I plotted, right? This is the same thing I plotted, x1, x2, x1, x2, right? So these are the three features I plotted, x1, x2, and x1 multiplied by x2. So if I plot it here, you'll be able to see that I'll be getting a data points which will be separated like this. Obviously, from this particular data point, you can see that it is not clearly linearly separable. I cannot just create a simple SVM line, right? I cannot create a SVC line, a marginal plane onto this, right? Because again, half of the points are here, half of the points are here. But now see what happens. If I try to plot this same 3D plot by using x1 square, x2 square, and x1 multiplied by x2, now see what will happen. So here I'm taking x1 square, x2 square, and x1 multiplied by x2. Once I execute it, now you see the magic guys. My data points has now got transformed into a higher dimension of 3. Now this particular points is my other points, and these are my other points. Now here you can see easily, initially my data points were something like this, right? How was my data points? My data points were like this. Now after applying this polynomial transformation, what did we do in polynomial transformation? We just created this additional feature, x1 square, x2 square, and x1 multiplied by x2. And I took these three features, I plotted it in a 3D plot. Now here you can see that I am able to get two groups of plot very much clearly with respect to different data points. Now all I have to do is that create a hyperplane within this. And how do I create a hyperplane? Because if I'm able to get this kind of transformation, all then I can do is that use an SVC kernel with linear and just try to do the prediction. Now you see what will be the accuracy. Okay, so let me import Cbon. So here I'll just going to import from sklearn.svm import SVC. Now, if I probably try to execute, okay, accuracy score is also not there. Let's say from sklearn.metrics import accuracy score. Now, if I try to execute, I'm getting 1 as my accuracy score, right? But here you can see that with respect to polynomial kernel, right? What did I do? I manually created this. I manually created these features, and then I applied a linear kernel over here with respect to SVC. But instead of that, if I could have just written like this, and over here, if I would have written my kernel as polynomial and executed this, here you'll be able to see, okay, the polynomial is not polynomial, it's poly. Okay, if I had just directly written kernel is equal to poly and executed, I could have got the same accuracy. So poly internally, what it does, polynomial kernel, it internally creates this feature x1 square, x2 square, and x1 multiplied by x2. You don't have to do it manually. If you do it manually, then you can definitely apply linear kernel, right? Because it is clearly separable. Now, similarly, you can also solve this problem with the help of RBF kernel, that is radial basis kernel. So if I probably search for RBF kernel, now see this, RBF kernel, right? This is radial basis function, right? And in this kernel, we are, okay, let me just open Wikipedia. Okay. Now over here, the transformation formula that gets applied to create more dimensions is this formula, right? X and x dash are different coordinates, and sigma is basically initialized with some values. Okay. If you apply this exponential formula in creating new transformation feature, then automatically RBF will also be applicable in solving this problem. Now see, instead of writing poly, all I have to do is that write RBF and then try to do the prediction. Here also you can see that I'm getting 1. Right? So with the help of RBF kernel, how does RBF kernel looks like? How RBF will basically make the changes? So here, if I probably change, see the images, right? So here, if I probably go and search for the images, let me see one example with respect to RBF kernel. Okay, how the RBF kernel will look like. So my RBF kernel will basically create this kind of transformation. That basically means all the points that are present below, right? It will become like this. It will have this kind of curve. So all the elements that are present in the central, right? This will become like this. It will go up. Okay, probably I can show you some more things, some more examples. Yeah, this is the right thing. Now see guys, here you can see one curve, right? This curve. Okay, yeah, this is the perfect curve. So this curve is basically created by this RBF kernel, right? So here you can see the central points is going up. Now all you have to do is that probably create a plane in between like this, probably to separate the points, because all your major classes will be going up and this will be your other set of classes, right? So this is what RBF kernel does. By using the simple transformation technique, all the points from here will go in the higher dimension, right? So this is what RBF kernel will do. And similarly over here, you can see that I have this kind of points, right? I have this kind of points over here. Now what will RBF kernel do in this particular case? It is very simple. RBF kernel will make sure that all these points, once it is converted into 3 dimension, it should look something like this. Let's say these are my points. Okay, these are my below orange points, or let's say these are my blue points. On top of it, I may create this points which may look like this. Okay, and then probably I can create my best fit line. Okay, so this is what it basically does with the help of RBF. So we can solve this kind of problem statement with both linear, polynomial, and RBF kernels, right? And similarly, there is also another kernel which is called as sigmoid. You can also try it out with sigmoid. So let's see again this particular problem statement with sigmoid also. So here I will just go and copy and paste it, and probably instead of RBF, I'll write sigmoid. Now let's see. I don't know whether we'll get or not, but sigmoid also we are able to get as 1.0, that is 100% accuracy with respect to test data. So whenever you get bad accuracy with respect to SVM, try to use SVM kernels, try to play with this kind of hyperparameter tuning with respect to linear, poly, or RBF, or sigmoid, and then you try to select what parameter is best for it. So that is what I had actually shown you in my previous example. So this was the power behind the SVM kernel. I hope you like this particular video. Please make sure that you understand things, understand what is the transformation technique that is used, some mathematical formula to create some more additional features internally. I showed you an example of polynomial. Similarly, you can assume with respect to radial basis function, that is RBF, and similarly with respect to sigmoid. Okay. So yes, I will see you all in the next video. Thank you. Hello guys, so in this video, we are going to implement the support vector regression machine learning algorithm. We'll take up a use case and we'll try to solve it. We have already seen with the example of support vector classifier, we have also seen SVM kernels, and let's go ahead and try to explore support vector regression. So for this, first of all, we will start with a dataset, and this dataset that we're going to take is about a tips dataset. And again, this dataset is available in a library called as cbon. So if you probably say that import, okay, cbon as SNS, and probably if I write sns.load underscore dataset, and if I probably write tips, right? So this is the dataset that I will be working with, So here you can see this is the dataset. I have features like total bill, tip, sex, smoker, day, time, and size. Based on this, like let's consider that in this particular data set, let me make it as a DF. And probably if I write df.head, here you'll be able to see in this data set. Now our problem statement is that we need to, the total bill that is present over here, this will be my dependent feature, and remaining all the features will be my independent feature. So with respect to this all features, we will try to predict the total bill, okay? And for this, we will be using support vector regression. Here, some more additional things that I've put over here is that you can see features like sex, smoker, and day, and time. This all are categorical features. So suppose if I probably write df.info, here you'll be able to see that you can see sex, smoker, day, time are categorical features. That basically means we have fixed number of categories. So if you probably write something like this, df of sex, okay, dot value underscore counts, and probably execute it. Here you can see that the number of male categories are 157, the number of female categories are 87, right? Similarly, if you go and see with respect to smoker, right? So how many smokers are there? You'll be able to see 93 are smoker, 151 are not smoker, right? So that information also you can see. And one more thing that you can basically check out is with respect to your day. So now if I probably see day, I think day is not there as a category. Okay, it is in small d. So if I probably go and check over here, you'll be able to see I'm having 4 days information. Saturdays are 87, Sundays are 76, Thursday are 62, Friday are 90, right? And obviously it does not have missing values also. And similarly, I can do it for time. So here I'm actually trying to find out the count of each and every categories. Now, sex, smoker, and time are binary categories. Like only 2 categories are there, like dinner and lunch, yes or no, male or female. So for this, what we do is that we'll do some kind of feature encoding. Now, this is super important to understand. Now, feature encoding. In feature encoding, we are basically going to apply 2 encodings. One is label encoding and one hot encoding. Okay. Now let's understand what exactly is label encoding. Whenever we have just 2 categories, right? We can basically we can replace this male and female by ones and zeros, right? If you have 2 categories. Similarly, over here in smoker, we have 2 categories, yes or no. So here also we can replace it with zeros and ones. And similarly with respect to time, here you have either dinner or lunch. Here also you can replace it with ones and zeros. But if I probably take the example with respect to day categories, here I have 4 different categories: Saturday, Sunday, Thursday, and Friday. So here we will not apply label encoding. Here we'll be applying one hot encoding. And if you know about one hot encoding, that basically means we'll be creating that many number of features, and wherever that specific value is, it will be 1, remaining all the values will be 0. Now our main aim is basically to do the feature encoding, but before doing the feature encoding, I have to first of all have my independent and dependent features. So let me just write it down over here: independent and dependent features. Okay, dependent features. Now here this will be my x value. So here I'm just going to write df of, and probably I will write all my features that will be independent, right? Independent. So for that I will just write df dot columns. Okay, and here you can definitely see what all are the features that will be in my column. I will take all those features and copy and paste it inside this, right? So these are all the features that will be my independent features. Let me make more cell. I'll copy this entire thing over here and paste it, right? Similarly, my dependent feature will be df of total bill, right? So total bill. So here is my independent and dependent feature, right? In the next step, I will do something called as train test split. Train test split. Now, for doing the train test split, we will be using from sklearn dot model selection import train test split, right? And here I'll be having x train, x test, y train, y test. Okay, and this will basically get here. I'm going to use my train test split with my test size is equal to 0.25, and let's say random state is nothing but is equal to 10. So here I've actually done my train test split. Now, if you probably go and see my x train, here we will be having all these things, right? So extend.head, probably I'll be having this. Now let's go ahead and do the feature encoding that we have actually done, right? With what we had actually discussed. Now with respect to feature encoding, understand we have divided this into train and test data. The reason we should definitely divide this into train and test before doing feature encoding, the reason is that there will always be a problem of data leakage if we don't divide this into train and test. Data leakage basically means the model should have no information about the test data. So whatever techniques we are using for the train data, the same technique needs to get applied for the test data. So always understand the concept of data leakage. Model should not have any information about the test data itself. Now, the best practices for performing the feature encoding, right now we will go ahead and pick up all the features that are binary. Whichever features are binary, we are just going to apply label encoding. Okay. So for applying label encoding, I will write for scalar dot pre-processing, and I'm going to basically import label encoder. Okay. Now once I execute this, now I will be creating different label encoder. LE1, because I am having 3 binary categories: sex, smoker, and probably time. So I will create 3 encoders. LE2, okay, again this will be a label encoder, and this will be LE3, which will again be a label encoder. So 3 label encoders. Now all I will do is that I will take up each and every encoder, and I will write fit underscore transform on the feature that I really want to work. Suppose xtrain, this LE1 will get in smoker. So suppose I have a feature over here, you can see smokers. Okay, first of all we'll start with sex. Okay, then similarly we will try to do it for smoker. Okay, but here please make sure that you're going to provide another label encoder. Okay, LE2. Similarly, I will go and copy this and paste it over here for my next feature. My next feature is nothing but time, because time is also binary, right? So whenever you have a binary feature, here we are basically going to do label encoding. Okay, and this thing I will try to assign it to xtrain of sex. Now wherever there are like male, it may get assigned as 1 or 0. Okay, so similarly I will write x underscore train of smoker. Okay, similarly here I'm just going to write x underscore train with respect to time. Okay, and once I execute this, time also is basically having binary categories. Okay, I'm not taking day because it is not having binary categories. Okay, so now once I execute this, you'll be getting some warnings. If you want to remove this warning, all you have to do is that import warnings, something like this. So I'll just import this warnings. Okay, and then I can basically say warning.filter warnings ignore. Okay, just to have a proper notebook file, so I'm doing this. Okay, so I will again start from here. Again, do this label encoder, and now finally you can see over here. Let me make some cells. Now all my warnings are gone. Now if I probably see xtrain.head, you'll be able to see now my sex column will have 1s and 0s, my smoker will have 1s and 0s, my time will have again 1s and 0s. Now the same transformation needs to get applied for the test data set. So here I will write xtest, and I'll copy this entire thing. Let's say I'm copying this entire thing. I'll paste it over here. Now instead of writing train, I'll be writing test. Here also I'll be writing test. Here also I will be writing test. Okay. And then here you have LE1. Instead of writing fit underscore transform, now I'll just focus on writing transform, because we don't do fit again on the test data. Okay. This is just to prevent data leakage. So x underscore test, x underscore test, x underscore test. Okay. So once I execute this, here you will be able to now see x underscore test dot head. And here is all the values in the test data also. But still we have one more column, which is day, and day we have already seen that we have 4 different categories. Now during this particular case, we will definitely apply one hot encoding for this particular scenario. Now in order to apply one hot encoding, let's see how do we apply one hot encoding. So one hot encoding. Now one hot encoding is applied along with something called as column transformer. Okay, so let's go ahead and import it. So first library that I'm going to import from sklearn.compose import column transformer. Okay, similarly from sklearn.preprocessing import one hot encoder. Okay, so we're going to use these 2 specific libraries for doing the one hot encoding, and we really need to perform one hot encoding for the column that is day. Now once I use this column transformer, I'll be initializing this. This column transformer takes some important parameters. One is what kind of transformer we are going to apply. So usually we give this transformers in the form of tuples. Okay, so here we will be defining first of all a list of tuples, and inside this first parameter will be my transforming name. So let's say I'm going to apply one hot encoding. So I've just given a name over here with the help of class which is called as one hot encoder. So here I'll just press shift tab, and in one hot encoder you also have a parameter which is called as drop is equal to. So here if you probably see this, here you'll be able to see this. Okay, so if you probably write drop is equal to first, after doing the one hot encoding, it will remove the first feature, because remaining features can represent that first feature. Okay, and after this, after applying one hot encoding, the third parameter that we will be doing is that for what index I need to apply one hot encoding. So here you can see that I have to apply for this day, right, feature. So what index it is present? 0, 1, 2, 3. So for the third index. So here I'm just going to apply for the third index. Now after this, one more parameter will go into the column transformer, and this specific parameter is basically called as if you probably see from this definition, you have something called as remainder. Okay, so if you probably press shift tab over here, and if you go down, there is something called as remainder. Now remainder can have 2 values. Okay, one is drop or one is pass through. Drop basically means that only which feature I want to do the encoding, only that will be kept, and remaining all will be dropped. But in this particular case, I don't want to drop all the features, because here I have already done the encoding. The only encoding that is left is day. So for this particular case, what I will have to do is that I will be setting the parameter remainder. Just a second. I'll be setting the parameter remainder. Okay, just a second. Okay, so let's say I'm just setting this parameter remainder is equal to, and spelling. Okay, let's see the spelling once again. Shift tab. Here is what is there. So I will just try to copy this and probably write it over here. Now instead of drop, I will just say pass through. Okay, so pass through is another keyword that we can definitely use over here, and you can see from the definition itself. If I want to just keep all the other things, right? So here I can basically use pass through. So once I execute this, here you can see some error is there with respect to the remainder. Let's see what is the error. Okay, this list should get closed over here. Okay, this list should get closed over here, and now probably if I try to execute it, it will work fine. Okay, now ct dot. Now if I really want to start the transformation, all I will be doing is something called as ct dot fit underscore transform on my xtrain data. So once I execute it, here you'll be seeing that I'll be getting some error. Let's see what is the error that we are getting. 1D data passed to transformer that accepts 2D. So guys, here the error that you see is, it is saying that the reshape your data using array.reshape minus 1, 1. Now the problem is that the index that I have given, it is not in the form of list. So what I can do, I can basically give this in the form of list. So once I execute and do fit transform, now I can see that all the transformation has happened and one hot encoding has happened. Okay. Now let me expand this entire array. Okay. Now in order to expand and show you the entire array, first of all I'll import sys, then I'll probably import numpy, and I'll say numpy dot set print options, and I will keep the threshold to this, just a setting which will actually help you to see the entire data set. Now see, initially my data set was like this, right? Now what has happened is day column has got dropped, and instead of this day column, which had around 4 different features, right? 4 different categories. Now this has basically become one hot encoded. Now when you see one hot encoded, the first 3 elements in the one hot encoded is added over here. Since we applied drop is equal to first, drop underscore first is equal to true, or drop is equal to first, the first column has dropped and remaining all the 3 features has been one hot encoded. And here you can see all the other columns are remaining in this specific way. Now I will try to save this on my xtrain data. Okay. Now same thing I will do for my xtest data. So for my xtest, I will basically write ct.transform, because I also need to transform all my xtest data with respect to that same index. So once I execute it, and probably now if I probably see my xtest, here is what is the output that you can see. Okay. So I've done all the feature encoding along with the one hot encoding. Now the time is that we should start applying our algorithm, right? So I have my xtrain, xtest, ytrain, and ytest. Now all I have to do, I will start applying support vector regression. Okay, support vector regression, right? Now here you'll be able to see from sklearn.svm import svr, right? Svr is equal to svr. Okay, and here again you have some different parameters, and you can obviously play with the hyperparameter over here with different kernel values. This is there, right? Obviously you can play with all these values, and I will also show you with the help of hyperparameter tuning. Okay, but right now I will just try to define this and then go and fit my xtrain and ytrain, xtrain comma ytrain. Okay, now once I do this fit, all I'll be doing is that we can now do the prediction. So y underscore pred with respect to svr.predict, and here I'm just going to write on my xtest data. Okay, so I've got my y pred, and now finally you'll be able to display the metrics over here with respect to R2 square and mean absolute error. These are the metrics that I've actually got. Okay, now this is very much simple. Now we can simply apply hyperparameter tuning also. Now hyperparameter tuning is pretty much simple. We'll just play with the parameters. Hyperparameter tuning using grid search CV, right? So I'm just applying all the hyperparameter tuning. Now here you'll be able to see that I will be copy and pasting this entire thing. These are the different parameters that I'm going to play with, and along with RBF is obviously there, right? So once I try this, all I will do is that again apply grid search over here by using SVR, param grid, refit is equal to true, and then we'll do the fit on xtrain and ytrain. So here you can see all the combination of xtrain and ytrain has been done. And at the end of the day, what I will do with the help of grid, I will try to find out my best params, and execute it, right? So these are the best params that I got selected. Now at the end of the day, we will just do grid underscore predictions with the help of grid search CV, and I'll write grid.predict on my xtest data, right? So here, finally, these are my predictions. Now all I will do is again to check it, I will just import all these things and paste it over here. And just instead of ypred, I will just give my grid predictions. So here you can see I'm getting 0.508 and 3.86. Okay, R square is becoming a little bit better when compared to this one, and my mean absolute error has also got reduced. You can see over here like 3.86. So again, with different parameters, you can definitely check, and you can definitely improve the performance of support vector regression. So in this video, I've implemented support vector regression implementation, and along with that, you could see many things that I did, feature encoding, which is one of the super important. Similarly, in the upcoming videos, you'll be seeing how to handle missing values and all, and with respect to that, we'll try to implement. So yes, I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to a new machine learning algorithm which is called as naive Bayes algorithm. Now naive Bayes algorithm is specifically used to solve classification problem, both binary and multi-class classification. In order to understand naive Bayes, right, you really need to have some basic idea about probability. Okay, so super important. There is some concepts in probability that you really need to understand. Okay, and after understanding these concepts, we will also try to derive an important theorem which is called as Bayes theorem. So based on this Bayes theorem, this entire naive Bayes algorithm, machine learning algorithm works. Okay, now let me just go through this probability, like what all topics we specifically need to revise. Okay, so in probability, right, with respect to various events, right, there are two types of events. Like there is one something called as independent events, and the other one is something called as dependent events. First of all, let me just talk about an example of independent events. Let's say I am rolling a specific dice. Now you know what are the outcome of a dice? It is nothing but 1, 2, 3, 4, 5, and 6, right? So these are my specific outcomes with respect to a dice whenever I roll. Now whenever you try to find out a probability, let's say that I want to find out the probability that the roll should be 1, right? Or the outcome should be 1. Then what will be the output over here? First of all, you will divide by total number of outcomes. So over here you have 1, 2, 3, 4, 5, 6. And then probability of 1 will be that how many times 1 can come in a single roll? Only one time, right? That is the maximum probability that you can get. So the overall probability of 1 is somewhere around 1 by 6. And even similarly, if I go ahead and calculate probability of 2, I'll be getting 1 by 6. So the probability of 3 will be nothing but 1 by 6, right? So this is with respect to an independent event, right? So here, why do we say this as an independent event? Because one outcome is not hampering or not changing the probability of the other outcome, right? So probability of 1 is not changing the probability of 2. The values are same. Every time when I'm rolling a dice, I will be almost getting the similar kind of probability, right? 1 by 6, 1 by 6, 1 by 6. But if I talk about the second type of events, which is called as dependent events. Now in the case of dependent events, let's say, what does a dependent event look like? Okay, let's consider that I have a bag of marbles. Okay, let's say there are 3 orange marbles and there are 2 yellow marbles. Okay, now my question is, what is the probability? What is the probability, okay, of removing a white marble, and then a yellow marble? Then a yellow marble. I'll not say white marble because I've taken an orange marble. So let's go ahead and write here it as orange marble. Okay. So my simple scenario is that what is the probability of removing first event that is happening is removing a orange marble, and then you're removing a yellow marble. So in this scenario, let's say first of all I remove a orange marble from this bag. So what is the probability of orange? Very simple. The probability of orange is nothing but 3 by 5. The total number of orange marbles are 3, and over here I have 3 marbles, and total number is divided by 5, which is my total number of marbles. So this is my first event. Okay, this is my first event. The second event. Now, after this, I definitely need to remove the yellow marble from this bag. So if I say 3 by 5, once this event occurs, right, how many number of marbles I have remaining in this bag, right? I have somewhere around 4 marbles. See, 1, 2, right? 2 red marbles are there, and along with this, 2 yellow marbles are there, right? Orange marble has been removed. So in this event, the orange marble has been removed. Okay. Now in the next event, I need to probably remove the yellow marble. Okay. So in the first event, see what has happened. I've removed the orange marble. First of all, we need to find out what is the probability of removing an orange marble and then a yellow marble. So these events are basically called as dependent event because one event is happening and the first event will definitely change the probability of the other event, right? How it is changing? See the count of the marbles. There are only 4 marbles, right? Now if we go and see what is the probability of the yellow marble after this particular event, then you will be able to find it will be nothing but 2 by 4, which is nothing but 1 by 2, right? So this is the outcome of the second event. This is the outcome of the second event, right? And this event has already been impacted by the first event. Why? Because here initially there were 5 marbles, but here it became as 4 marbles because I removed one. In the case of independent events, my outcome will be always same for any kind of events, right? In rolling a dice, this outcome, it will always be 1, 2, 3, 4, 5, 6 for any kind of events, right? So here we have specifically removed the yellow marble. Remove the yellow marble. Now, if I try to combine both these events, I can use a notation, right? What is the probability of taking out the orange marble first and then the probability of taking out the yellow marble, right? Very, very, very simple. Then over here, I can probably denote this entire equation by probability of orange multiplied by probability of yellow given orange event has taken place. Given orange features have, or orange, I'll not say feature, orange marble has been taken out, right? This is what it basically indicates. Here, what I'm doing, what is the probability of orange and then the yellow marble to take place, one after the other, dependent events, right? So here I will basically be writing the probability of orange multiplied by probability of yellow given orange has taken place. And if I really want to find out this value, then what exactly it is? Here, I can write this as also probability of orange given, probability of yellow given orange has already taken place, right? And this is my second event. This is my first event, okay? This is my first event. This is my second event. And I hope you are able to understand now, right? This scenario is nothing but you're taking out the yellow marble given the orange marble has already been taken out or the first event has already been taken place. So what do? We basically combine this. And this equation, this side equation is basically called as conditional probability. Why do we say it as conditional probability? It is very important to understand because here I'm saying probability of yellow marble to take out the yellow marble given taking out the orange marble has already been done, right? Or I can also say this that probability of a event considering a specific event has already occurred. That is nothing but conditional probability. So this entire thing is basically called as conditional probability. So I hope you are able to understand. Now if I combine this equation, what will be? Probability of orange will be 3 by 5 multiplied by 1 by 2, which is my probability of y given O has already occurred. So here I'm going to write it as 3 by 10. So this will be my probability of O and y. Again, I'm telling you O and y basically means I'm taking out the event O is occurring first and then event y is occurring after that. Okay. Now in the generic way, if I really need to write this equation, it is nothing but probability of A and B is nothing but probability of A multiplied by probability of B given A has already taken place. So this is my equation in this case of dependent event, okay? And this is super important because this is what we are going to use for deriving our Bayes theorem. Okay, super important. Now let's talk about Bayes theorem. As I said, first of all, we need to understand probability, then we'll need to understand Bayes theorem because based on this Bayes theorem, this entire Bayes algorithm works, okay? So what I'm going to do over here, first of all, let's go and write the Bayes theorem and what exactly Bayes theorem is, okay? Now just imagine guys over here, okay? You know that if I take this equation, so if I probably take this equation, probability of A and B, okay, and I'm going to derive the Bayes theorem now, is nothing but probability of B and A, right? We can write like this also, probability of event A occurring and then B occurring. Instead, we can also be, this will also be equal to probability of B and A also, right? And in my previous videos also I've discussed about Bayes theorem. Now, how do I expand this equation? In order to expand this equation, I will write probability of A multiplied by probability of B given A has already taken place, right? And trust me guys, if you do the calculation with respect to this also, right, you'll be getting the same output for both this kind of events that is occurring. Now, similarly, on the right hand side, I can also write this as probability of B multiplied by probability of A given B, right? Both these equations are almost same, right? Over here you can clearly see, right, what I'm actually writing, right? The same equation is basically coming from this, right? The same concept I've used over here. Now let me do like this. Let me take this equation and write somewhere like this. Probability of A by B is nothing but probability of A multiplied by probability of B given A divided by probability of B, right? So this entire equation, so what I did over here, I just kept probability of A by B at one side and I divided this in below. So this equation that you're probably getting, this is basically called as Bayes theorem, a super important theorem. And now we will try to understand how this equation is basically used in a machine learning problem statement. Okay, so a very simple way to derive the Bayes theorem. Okay, the Bayes theorem says that the probability of A or B is equal to probability of A multiplied by probability of B given A divided by probability of B. Now what is probability of A given B? That is nothing but probability of event A. I have to calculate probability of event A given B has occurred. Okay, given B has occurred, right? So this is probability of event A. Similarly, if I go ahead with the next one, what is probability of A? Here I can basically write this is nothing but probability of event A. Okay, of event A. And this equation will also be used to solve machine learning problem statement. Then what is probability of B? It is nothing but probability of event B, right? And finally, you have probability of B given A. And obviously, you know what this is? Probability of event B given A has occurred. Given A has occurred. This is quite amazing. Like I've understood each and every components inside this Bayes theorem. Now, I will again copy this entire equation and make you understand how this thing will now be used in with respect to machine learning. Okay, super important. Okay. Now, in machine learning problem statement, guys, you have a lot of independent features. Let's say my F1, F2, F3, F4, F5, F6 are your independent feature, right? And let's consider, I will write instead of writing F1, F2, F3, let me go ahead and write, let's say that I have 3 independent features, X1, X2, X3. And this Y is my dependent feature. So I may have some values over here. Here I may have output like yes or no. Okay. Yes or no. So here also I will be having yes. Here also I will be having no. So like this kind of independent. So these are my independent features, right? So these are my independent features. And this is basically my dependent feature, right? The output feature. Now I will try to solve this entire prediction and all by using this Bayes theorem. Okay, this is what is a Bayes theorem. Now we need to see the algorithm that specifically uses this Bayes theorem is called as Bayes algorithm, right? And it is used for binary and multi-class classification. Now how we will be using this equation to solve it, okay? Now I'll write the same representation of this equation. Here I will say, see what we need to predict, we need to predict y, right? So in short, can I write this equation as probability of y given my features x1, x2, x3, right? I can write like this, the same thing it is, right? Probability of A given B. So probability of A is nothing but probability of y. I need to find out what is the probability of y given x1, x2, x3. Then I can probably go ahead and write this equation as probability of y, okay? See this probability of y multiplied by probability of x1, x2, x3 given y. okay, given y divided by probability of x1, x2, x3. The same equation we have written in this way. And what this equation is saying, that we need to find out y given x1, x2, x3. Okay, so this equation is all about naive Bayes machine learning algorithm. So I will just copy and paste it over here because we will further use this formula for a very important purpose. Okay, but this is the entire equation. Now, if I expand this equation, how this equation will now look like? See, I will write like this only. So here I have probability of y multiplied by probability of x1 given y multiplied by, see, when we expand this, right, we have to expand with each and everything. So here then I have probability of x2 given y and then probability of x3 given y. See, how many number of independent features I have? No, that many number of times I need to expand. Okay. Now, what I will do, I will copy this, I'll divide this by probability of x1, x2, or instead of writing like this, also I can write like this. See, probability of x1 multiplied by probability of x2, probability of x3. Understand the mathematical intuition, guys. Because I will solve a problem in front of you. I'll take a data set, I'll solve this. What is probability of x1 given y? What is the probability of x2 given y? We'll solve it with the help of example, but understand the equation. Okay. Now, with respect to this particular data set, okay, if I take this data set, okay, what are the two important things that we need to find with respect to the output, right? The two most important things that we need to find out is that what is the probability, my outcome of y is either yes or no. So I will say, what is the probability of yes given x1, x2, x3? This is the first thing that we need to find out. So this one I can basically write it as probability of yes multiplied by probability of x1 given yes multiplied by probability of x2 given yes multiplied by probability of x3 given yes. So these three things I need to find out from this equation, and this will be divided by what? Probability of x1, probability of x2 multiplied by probability of x3. So these two things we need to find out. See, if my outcome is yes or no, I need to find out what is the probability with respect to yes and what is the probability with respect to no. If my probability with respect to yes is 0.60 and probability with respect to no is 0.40, again we know that the maximum probability is saying yes, so my outcome will be basically yes, right? So similarly, we need to find out what is the probability with respect to yes and what is the probability with respect to no. So here I will go ahead and write probability with respect to no also, and we'll try to find out given x1, x2, x3. Now based on the above equation, how might this equation will change? Very simple. I will write probability of no multiplied by probability of x1 given no multiplied by probability of x2 given no multiplied by probability of x3 given no, right? So once we divide this, now this time we divide this by probability of x1, probability of x2, and multiplied by probability of x3. See, I'm deriving right now, still I'm saying this. Now observe one thing, over here in the denominator, both these are constant because this is also I'm going to get a constant value, and here also for this denominator I will get a constant value, right? So what we can do, we can cut this equation, we can reject this, or we can remove this entire denominator. Now if I really want to calculate what is the probability of yes given x1, x2, x3, I will just use this equation to find out the output. Now let's say if I get the probability as 0.60, I get the probability as 0.40. Now you know that for any new test data, and this is for any new test data. So any new test data, if I'm getting probability of yes is 0.60, probability of no is 0.640, then my output will be this one, that is nothing but yes, right? Now, this was almost all about the naive Bayes machine learning algorithm. This is how it works. It uses this Bayes theorem, the simple Bayes theorem, to probably calculate everything. Like this is my simple Bayes theorem, right? And the same Bayes theorem we're trying to find out with respect to yes and no, and try to find out the output. Now, let's go ahead and solve a specific problem where we will be considering a data set, and we'll try to solve it. The data set we'll be talking about will be an amazing data set. We will take up that, okay? And obviously, we have used that data set even in decision tree, and we'll try to manually find out what is the probability of yes or no with respect to any new data point. So let's go ahead and let's talk about that. So guys, now I think we have discussed about Bayes theorem. We have understood how naive Bayes algorithm works. In short, it calculates the probabilities like yes or no if it is a multi-class classification based on the input features that we are getting, and we probably got this entire equation also. Now, what I'm going to do is that I've taken this amazing example which we have also seen in this particular decision tree. So this is the data set. We will try to find out, I'll do the manual calculation and show you what all probabilities we will be getting. Okay. Now let's go ahead and probably split this particular data set. And when I say split this data set, not using decision tree, we'll be using naive Bayes. But with respect to every feature, we'll try to find out something. Okay. And then whenever we get a new data point, we'll try to predict it. Now, first of all, the first feature that I'm going to probably take is outlook. Okay. So here you can probably see outlook is there. So here, let me go ahead and write outlook. Okay. Now based on this outlook feature, what all things we really need to find out. Okay. So in outlook, what all possible options you have? See, sunny you have, overcast you have, and rain you have. So I'll write the three categories over here: sunny, overcast, and rain. Why? Because I really need to find out the probabilities of each and everything, right? Now with respect to sunny, how many yes outputs are there? How many no output are there? And based on these two values, right, I also need to calculate two important things, okay? That is, what is the probability of this sunny event given yes, and what is the probability of this sunny event given no, right? So these two values will be using it because at the end of the day, we are going to use this kind of equations in this particular formula, right? When we are trying to calculate, okay? So when I say x1, x2, x3 over here, right? These are my x1, x2, x3. These are my x1, x2, x3, x4 like that. So in this case, what we're going to do is that we're going to solve this classification problem based on this input features: outlook, temperature, humidity, and wind. Now let's go ahead and find out what is the probability, how many times like sunny, whenever sunny input is there, how many times yes are there. So if you probably go and see with respect to sunny, there are around 1 yes here and one more maybe here, right? So 2 yes are there, 1 yes this side, 1 yes this side. So the total number of yes in the case of sunny is nothing but 2. Now similarly with the case of overcast, how many yes and no's are there? Just go ahead and calculate. You'll be able to get 4. And with respect to rain, there will be 3, right? And in case of sunny, again, no, how many no's are there? 3. Just go and count it. And we have done this in decision tree by using the same example. Then in case of overcast, it will be 0. In the case of rain, it will be 2. Now in order to find out this important thing, what is the probability of sunny given yes, right? What is the probability of sunny given yes? So total number of yes, if you try to find out, count over here: 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So total number of yes are 9. And when I say probability of sunny event is how many times? 2 given yes, right? So here I'll be writing 2 by 9, right? Similarly, if I go ahead and calculate with respect to overcast, it is 4 by 9. So I have this 4 number and divide by 9, and this will be 3 by 9. All these values are there. Now similarly, we'll go ahead and calculate what is the probability of event given no. Now we are really need to focus on this divided by 9. So in this case, I will go ahead and write this will be 3 by 9, 0 by 9, and sorry, not 9, it will be 5, right? The total number of no's are how much? 1, 2, 3, 4, 5. So total number of no's are 5. So here I'm going to write 3 by 5, and then here you'll be writing 0 by 5, and here you'll be writing 2 by 5, right? That many number of no's are there. Now similarly, for every feature, we'll go and see what is the probabilities, right? And then we will try to find out what is the output, and we'll use the same formula. Now this side, I'm going to probably go with temperature. So let me go ahead and see with respect to the next feature, that is temperature. Now with respect to temperature, how many different values are there? Obviously, you know over here, one is hot, one is mild. See, hot, mild, and cool. One is cool, right? Now, if I see with respect to outputs, I'll be getting yes or no, and what is the probability of the event given yes, and what is the probability of event given no. If I had more classes, I would have write probability of event given the third category, fourth category, fifth category, right? Now, with respect to hot, how many number of yeses are there? Just try to find out how many number. Here I can see 1, and the other one I can probably see here 2 yes. Okay, so I will go ahead and write this value 2 yes, 4 in the case of mild, when the value is mild inside the temperature, 4 yes I'm able to get. When it is cool, I'll be able to get 1 yes. Okay. Now, similarly with respect to no, sorry, not 1, so 2, 4. And with respect to cool also, if I see, right, there are 3. 1 yes, 2 yes, and 3 yes. Okay, so just try to calculate it, guys. Just try to find out how many numbers are there. In case of no, it will be 2, 2, 1. Okay, so do the calculation. Automatically be able to understand how many yes and no's are there. Now, what is the probability with respect to this event that is hot given yes? So obviously here you have to. So here I will be writing 2 by 9. Here I will be writing 4 by 9. Here I will be writing 3 by 9. Similarly, the probability of event given no. So I have to consider this. So it will be nothing but when given no basically means what? Given no basically means what is the probability of hot given no, like that. So if I probably see this will be nothing but again 2 by 9, 2 by 9, and this will be 1 by 9. Okay. So these are my values that I'm able to get with respect to all the values over here. And sorry, this will not be 9, guys. Again, I'm forgetting it because the total number of no's are 5, right? So total number of no's. So probability of event, when I say probability of hot, given total number of no's. Okay. So here I will go ahead and write probability of event that is hot event to take no. So over here I will write 2 by 5, 4 by 5, and 3 by 5. Right. The total number of no's in this are 5. Now let's go and take only these two features. I will not take the other two features. Let's consider only these two features just to give you an idea. Now finally, the output feature is play, right? And play has values either yes or no. Okay. So here also we'll go ahead and calculate the probability. So total number of yes and no are nothing but 9 and 5. So if I really want to find out the probability of yes, right, it will be 9 by 14, right? Total number of events are 14. So here 9 by 14. Total number of yes and no's are 14. So probability of yes will be 9 by 14, and probability of no will be 5 by 14. Now we have calculated almost everything, right? Now our main aim is that whenever we get a new test data, and let's say the test data in case of outlook is sunny, and in case of temperature is hot, we really need to predict what is the output. Okay. So for this feature, we have taken the first feature as sunny, and the second feature as hot. We need to predict what is the output. Now, how do I write this? I will write in a simple equation. What is the probability of yes? I need to calculate, right? Given I have sunny, comma, hot, x1 and x2 feature, right? When I have these two features, so how do I write this? It will be probability of yes, right? Multiplied by probability of sunny given yes, multiplied by probability of hot given yes, right? Very simple. I don't have to take the denominator because I told you, right? With respect to yes and no, the denominator is a constant value. So this is what is my values, right? This is my entire equation to calculate according to the name bias, right? But if I really want to go ahead and write the denominator part, this will be probability of sunny multiplied by probability of hot. And you know that this will be a constant value for yes and no both, right? So I will remove this. Okay. Now let's go and see what is the probability of yes. Probability of yes is nothing but 9 by 14, right? So now I will equate it. See, 9 by 14 multiplied by what is the probability of sunny given yes? What is the probability of sunny given yes? 2 by 9, right? I can see over here. See, this is nothing but 2 by 9. Probability of sunny given yes, right? So this in short I can also write this as probability of sunny given yes. So it is nothing but 2 by 9. And the last term is what is the probability of hot given yes? Hot given yes, 2 by 9 again. So here I will go ahead and calculate it 2 by 9. So in short, if I probably calculate this, if I cut all these things like this, right? So over here you can basically see that I'm going to get so 9 and 9 got deducted, and I have 2 1s are 2 7s are 7 9s is 63. This will be nothing but 2 by 63. And here you have 0.031. Okay. So this is the output that we are specifically getting with respect to the probability of yes with respect to sunny and hot. Now in order to get the next one, and we'll keep this value, I will just show you everything. Now the next one will be that I need to compute what is the probability of no given sunny, comma, hot. Okay. So here I have probability of no multiplied by probability. So the PRP, that's one and the same thing. Okay, I'm just trying to mention in this way. So what will be the probability of sunny given no multiplied by what is the probability of hot given no? See, there's a reason why I'm doing this. Denominator we are not considering, so I'm not going to write. So what is probability of no? It is nothing but 5 by 14. So here I'm going to write 5 by 14. See, this is quite amazing, guys. So clearly, so precisely you are able to understand. What is the probability of sunny given no? See, what is the probability of sunny given no? What is the probability of sunny given no? 3 by 5. So here I will be having 3 by 5. And what is the probability given hot with respect to no? So here I have 2 by 5. So once I take this and do the computation, so this will be 2 1s are 7s are 5 and 5 gone, so it will be nothing but 3 by 35. I hope so I'm doing the calculation right. If there is a small mistake, you can let me know. Okay, but at the end of the day, you're smart enough, you should be able to understand. So this is the output for probability of no, and this is the output with respect to probability of yes, right? Now this output is just a probability, but we should try to make this in the form of 100%, right? So first of all, I will go ahead and compute what is the probability of yes given sunny, comma, hot. Now see the final conclusion. So here I can basically write what is the probability of this. I got 0.031, right? So 0.031, and since I want to make into 100%, so I will divide by 0.031 plus 0.085. So here you'll be able to see that I'll be getting 0.27, and this will be nothing but 27%. This step is just done to make sure that we get it a 100% probability. Okay. Now the next one, similarly, if I go ahead and compute probability of no given sunny, comma, hot. Now here you have what? 0.085 divided by 0.085. Sorry, this will not be 0.085. It will be 0.031, right? So this will be 0.031 plus 0.085. So if I do the total calculation over here with respect to probability of no, I'm going to get somewhere around 0.73. So this is nothing but 73%. Okay. Now see this. Okay. You can obviously say if you get a test data where your outlook feature is sunny, and the next feature, right? If I probably talk about the next feature, which was the next feature over here, temperature, and your temperature is hot, then what is the output? Your output is nothing but, it is saying 73% they will not play tennis. They will not play tennis, right? Because no is there, and 27% they will play tennis. 27% they will play, they or he or she will play tennis. Now you know that what is the highest probability? Obviously 73%. So the outcome for this particular record will be nothing but 0, which is nothing but person is not going to play the tennis, because the probability of no is high. Okay, not playing tennis or not going to play tennis, right? So this is the overall conclusion, and just see every step and why this formula is super important. The derivation of this particular formula is very important, because all this x1, x2, x3, right, it will be converted in the form of features, and this is how naive Bayes solves any kind of classification problem, let it be with respect to binary classification or multi-classification, right? So overall, we could see that whenever our new test data was this, we were able to solve this problem. So yes, I hope you got an idea, guys. That is the reason I say machine learning theory part you should really understand. Implementation, hardly 2 lines of code it is. Okay. So yes, this was it from my side. If you did not understand, please do make sure that you revise it. You will definitely be able to understand. So yes, this was it from my side. I will see you all in the next video. Hello guys, so we are going to continue discussion with respect to naive Bayes machine learning algorithm. Now, previous video we have already seen how we can probably use Bayes theorem and in the naive Bayes machine learning algorithm to solve a binary or multi-class classification problem. In this video, we are going to discuss about the 3 variants of naive Bayes. That is called as Bernoulli's naive Bayes, then you have multinomial naive Bayes, and you have Gaussian naive Bayes. Now, all these variants is super important because if you have a different kind of data set, right, then which naive Bayes algorithm you have to probably use from this particular video, you'll be able to derive that specific outcome. Okay. Now, let's go ahead and discuss about the first one, that is called as Bernoulli naive Bayes. Now, what exactly is Bernoulli naive Bayes? It is very much simple, guys. Whenever your features, when I say features, mostly the independent features, are following a Bernoulli distribution. I hope now you remember what exactly is Bernoulli distribution. You have learned that in statistics, right? Then we need to use Bernoulli naive Bayes algorithm, okay, to solve classification problem. That basically means, and you know what is Bernoulli distribution? Bernoulli distribution basically means the outcome that you specifically have in this is either 0 or 1, right? Tossing a coin, it can come out heads or tails, right? Success or failure. So there will be only 2 outcomes, pass or fail, right? So if I probably consider with respect to a data set, so in a data set, if I have some examples, let's say I have features like F1, F2, F3, and then I specifically have an output feature. So F1 feature can be like this: yes, yes, no, yes, right? And similarly, F2 feature, how it will be? It will be like pass, fail, right? Fail. So this can be your outcome is either 2. Let's see, either 0 or 1, right? So 2 outcomes are only there. Similarly, with respect to F3, it can be a gender feature, right? Male, female, right? Like this. And like this, it will be continuing. You'll be having this repeated feature again and again. And your output can be a binary classification or it can also be a multi-classification. So whenever you have this kind of features, which is just like kind of a Bernoulli distribution, then you will be able to apply, or you should apply Bernoulli naive Bayes to solve this classification problem, right? That is the reason it is given a name called as Bernoulli. See, at the end of the day, it's all about simple things. Now, all the statistics that we have used, some or the other way to be coming into use, right? Now, see, the last one is called as Gaussian naive Bayes, okay? Now, keep on thinking what exactly Gaussian naive Bayes can be if it is Bernoulli naive Bayes. Oh, yeah, as first, and we'll discuss about that, right? Remaining all the techniques to calculate the probability will be almost same. Now, coming to the second one, which is called as multinomial naive Bayes. So let's go ahead and discuss about this one, which is second one. Is it nothing but multinomial naive Bayes? Now, this is also a very good algorithm, right? Because with the help of this, whenever you have your input data in the form of text, then you can probably use multinomial naive Bayes. Now, whenever I say that if your input data is in the form of text and it is a classification problem, so when we say your input data is in the form of text, what does it basically mean? Let's say in your data set, we are trying to solve a problem which is called as spam classification. So let's say that you receive an email. So this is my email body. Okay. I need to predict whether this email is spam, or not spam. So this becomes a classification problem, right? So let's say my first message is something like this. You have won $1 million lottery. Okay. So in this case, obviously the answer will be spam, right? So here, let's say that another email is like, let me give you something like this. It's like, I'll say my name, Krish. You have done good job. So let's say this is my second sentence. And obviously I know that this mail will not be a spam. So I will write it as ham. Ham basically means not a spam. Now in this scenario, this is my input feature, right? This is my input feature. And this is my output feature, right? So in this, my input feature is in the form of text, right? And when we have this kind of scenario, the first thing that we really need to focus on is that we need to convert this text into a numerical values. The reason we need to convert this into a numerical values because obviously in this scenario, the model will not be able to understand the sentence. So what we do, how do we convert this into a numerical values? We will be using NLP techniques, natural language processing techniques. Still, we have not started natural language processing, guys, but I really want to just give you an idea about it. Later on, as we go ahead with the syllabus, we will be learning about NLP. Now, in natural language processing, in order to convert the sentences into numerical values, we use a lot of techniques. The first technique is like bag of words, which we say it as bow. Second technique, we can go with something called as TF-IDF. So what does this do is that it converts these sentences into some numerical values, which we also say it as vectors. Okay, but these all techniques is required to do that, like word to vec. Like word to vec is also one more technique, word to vec. And similarly, there are a lot of techniques, even in deep learning, there are different NLP techniques. Now, in all these techniques, there will be different formulas, like how you can convert the sentences into numerical values or vectors. So, in those formulas, you basically try to find out how many total number of words are there in the sentences, how many total number of unique words are in the sentences, or how many total number of words are there in the entire paragraph, right? Something like this. So, whenever we try to ask this kind of questions, right, and then we try to convert this into vectors by using this formula, for this problem statement, whenever your output is spam or ham, we try to use multinomial naive Bayes, because multinomial naive Bayes will be very much suitable for this kind of problem statement. Internally, some changes in the formula will be there with respect to understanding this particular implementation. Again, I will not even show you the practical example right now, but as soon as we start NLP, our first project will be solving based on multinomial naive Bayes. This all will not work better whenever your input data is in the form of text, because we are trying to convert our text data into some numerical values. Now, coming to the third type, okay? So, guys, we will learn about multinomial naive Bayes. Don't worry about that. With respect to practical implementation, see in the back end, how does the naive Bayes algorithm work? It uses Bayes theorem, but for different data sets, these 3 variants are basically used, okay? So that optimization wise, the accuracy wise, it will be able to give you in a better way, right? Now, coming to the third type. The third type is specifically called as Gaussian naive Bayes. Now, obviously, I told you, just think over it. What exactly is Gaussian naive Bayes? Okay, you know about Bernoulli. So in Gaussian naive Bayes, what do we do in the Gaussian naive Bayes? If the features are following Gaussian distribution, what does Gaussian distribution mean? Bell curve. You remember that in statistics we have learned it, right? Then we use Gaussian naive Bayes. for multi-class classification or binary class. So this variant is only being used when your features are Gaussian distribution, right? And one of the example that every feature may probably have this kind of distribution, or it can be a little bit right skewed or left skewed. That will also work well, right? But even though if it is of a different distribution, you can convert this into normal distribution. That we have seen how, like log normal distribution was there. We have learned about exponential distribution, right? Exponential distribution, how we can convert a power law into a normal distribution. All those things, simple transformation formula needs to get applied. Now, some of the example, I hope everybody is now familiar with this Irish data set, because in the last problem also we solved this, right? In our previous algorithms, we used this. In Irish data set, I had that sepal length, petal width, sepal width. All these features, in short, are continuous value. So one important thing with respect to the data set is that here the features are continuous. Right? It is continuous. Now, when I say continuous, I will be having features like age, height, weight. Okay, let's say here we need to predict whether the customer, whether the person is overweight or not. Yes or no. Okay, so I'll be having some values over here like 25, 38, 22, 24. These are all continuous values, and most of the time this distribution follows this Gaussian distribution only. This will be my mean, standard deviation, right? Something like this. So here I'll be having 170, 160, 150, 150, and weight I'll be having 78, 75, 60, 35. Right? So yes or no, based on the output, we'll be able to see this. Now, whenever you have this continuous features, you specifically use Gaussian neighbors. But still, you may have a question, Krish, what happens if you have some of the features Bernoulli distribution also over here? Now you need to see that which of the maximum features, like whether the maximum features are having continuous values or whether it is having a Bernoulli distribution. If it is having max Bernoulli distribution, I would suggest always go with this technique called as Bernoulli naive bias. But if you have features that are continuous and you also have some of the features that have multiple categories inside that, not Bernoulli, then you can go with Gaussian naive bias. Right? At the end of the day, because you need to convert that feature into numerical values also. Right? So this is the basic difference, right? To just understand with respect to this particular variance. But the main important thing that you really need to know is that how the naive bias working is done, and for which kind of data set what variant you really need to apply. And that is what we are going to see in the next video with respect to the practical implementation. Hello guys, now let's go ahead and discuss about the naive bias machine learning algorithm implementation with the help of sklearn and Python. Now before I go ahead guys, one very important point that I really want to talk about. When I open this particular, in our previous session where we discussed about the variants of naive bias, initially we saw Bernoulli naive bias, right? Where my features will be either having zeros or ones, right? So let's say that I probably convert this feature into F1, F2, F3. So it will be basically having ones or zeros like this, right? Ones and zeros, something like this, okay? So let's say all the yes are 1. So here I will basically be having 1, 1, 0, 1. And here also I'll basically be having 1, 0, 1, 0, right? Wherever it is passed, wherever it is male, female, 0, 1, 0, okay? Now usually when we convert these categorical features into numerical features, right? All these kind of features, these are basically in the form of sparse metrics. Right? These are in the form of sparse metrics. Sparse metrics basically means maximum number of ones and zeros are available in your entire data set. So this technique of Bernoulli also, we will be specifically using in NLP problem statements. Why NLP problem statements? Because as I said, right, in NLP, what we do, we take up our text data and we convert that into numerical data by using this particular techniques. The conversion that is probably coming, right, the outcome will be either in this format only, ones and zeros. It can also be in decimals, right? In TF-IDF, it will probably be in some decimals. In Word2Vec also, it will be in decimals, okay? So here, and when I say decimals, it will be a smaller value only most of the time, right? So whenever we have this kind of sparse metrics, so in this particular case, we can either use Bernoulli or we can use multinomial naive bias. Now, I've already discussed, right? Multinomial naive bias we specifically use for NLP problem statements. So for NLP problem statements, you can use two techniques. One is multinomial naive bias and the other one is Bernoulli naive bias, okay? So please do remember this. I forgot to say this in my previous video, but I really want to talk about this so that you'll be able to understand as we go ahead. Later on when we discuss about NLP, right, we'll be using these two techniques. Obviously, multinomial naive bias is there, but the other technique also that you can specifically use is Bernoulli naive bias. Okay, so this is done. This was the first discussion that I wanted to do. Now we'll discuss about naive bias practical implementation. As I said, why I'm not showing you Bernoulli or multinomial, because later on we'll try to do that. Once you know the NLP technique, what exactly it is and how a text data is basically converted into a numerical data. Now in naive bias, let me go ahead and take a data set from sklearn.datasets. Import load iris dataset. Okay, so I will probably take this load iris dataset and I will go ahead and implement it. Okay, now with respect to this particular dataset, I will go and also do .model selection, import train test split. Okay, so the model selection S is missing, so that is the reason it's giving an error. But don't worry, whenever error comes, right, be strong, nothing will happen. Okay, so that is what we're going to do over here. Now after we have this, we have done the train test split. I will go ahead and load this data set, and loading the data set is quite easy. X, Y, I will do it, and I will use this load underscore iris. Okay, and with respect to this, I will just say that return. There is an important feature which is called as X and Y. Return X, Y, X underscore Y. That basically means it will just say to return your independent and dependent feature. So when I say true, so this will basically give my X, Y. So this is my X in the form of numpy array. So here you can see sepal length, sepal width, petal length, and petal width, right? So these are the four inputs that you are able to get. And similarly, if I probably go and see Y, these are my 0, 1, 2. Now here we are trying to solve a multi-class classification problem. Now what I will do, I will quickly do the train test split. In order to do the train test split, what I'm going to do over here, I'm just going to copy paste. Instead of writing 50% of test size, I'll go ahead and 30%. Okay. So here we are basically going to do the train test split. Now see this, how we apply Gaussian, because here all my distributions are numerical, right? This X is entirely numerical. See, if I probably go and see X underscore train, these values are all numerical values. So when I say numerical, these are nothing but continuous value. And whenever we have a continuous value, we have to use which kind of Gaussian distribution? Sorry, which kind of naive bias? That is Gaussian naive bias, right? So I will go ahead and search for sklearn Gaussian naive bias, right? So this is what I have with respect to this. Now see, Gaussian naive bias, where it is present? It is present in sklearn.naive bias, and I'll go ahead and import Gaussian naive bias. Okay. So here, what I will do, I will write from sklearn.naive bias, naive underscore bias. Okay. Import Gaussian naive bias, right? So here I will go ahead and write this particular thing. I'll copy and paste it over here. Okay, so once I execute it, okay, sklearn. So that is the reason it was not giving in the form of tab, So I have all these values over here. Okay, Gaussian naive bias. Now I will go and write GNB is equal to Gaussian naive bias, and I'll initialize it. Okay, once I initialize it, the next step, obviously, you know what we need to do. We need to do dot fit on X train, Y train. Now we will try to see all the probabilities. Now whenever we get those values, and we will be able to check the new data probabilities, like how we discussed in the theory part. So once I execute this is my Gaussian naive bias, and finally I will write GNB dot predict on my X test data, and this will basically be my Y predict, right? Y underscore predict. So I'll go ahead and execute it. Now finally, what we will do over here is that from sklearn dot metrics import from sklearn dot metrics import, I will be importing accuracy score. So and my classification report. Okay. So this is what I require. Now I'll go ahead and print. If you want, I can also go ahead and import the confusion matrix also. Okay. So here will all be my data and accuracy score. Here I will give my Y underscore predict, Y underscore test. Okay. So this I will just try to print it. This is the first thing that I will print it, but before this I will go ahead and print my confusion matrix also. So let me go ahead and write this confusion underscore matrix, and then finally we'll go ahead and print the classification report also. So here I will go and copy the classification report. Okay, and this is how we basically find out in classification problem. So confusion, okay. Now if I go ahead and execute it, now here you can see 100% accuracy that I'm able to get for the test data. Why? Because obviously this data set is very, very small. But just with this particular naive Bayes, and here obviously that suitable naive Bayes algorithm was which one? Gaussian NP. Similarly, you have scale on multinomial, scale on Bernoulli. See Bernoulli naive Bayes, if you go and search, this is your Bernoulli naive Bayes. But this we will try to use it in the form of when we are working with test data. Okay, I'll show you this example. Again, fit and predict will be there. But at the end of the day, everything is all about data. Whenever data changes, the data is having a different value, you have to probably use different kind of Gaussian distribution technique. Okay. Now similarly, in the previous videos, whatever data set we have probably taken, right? Just try to use that, right? And one internal assignment that I would like to definitely give. So I will go ahead and write import cborn as SNS. See guys, unless and until you will not practice, you'll not become perfect. I'm telling you. Okay. So cborn. Okay. So here I will go ahead and import this. Just go and see SNS dot load data set, and here I will write tips. Please do make sure that you consider this data set. This data set has numerical values also, right? And here you have some categorical values also. So categorical values, obviously, you try to convert this into ones and zeros, okay? And this dinner and all also you can convert into ones and zeros. Just try to predict anything, okay? Try to predict smoker, okay? This is a binary classification, or try to predict the time. Either it can be dinner, this. But here you have two numerical features. Just see how it will perform, okay? You know how to do this, how to change this into categorical into numerical. You know that. Take this as the output feature, time, okay? It can be dinner, lunch, or a breakfast, something like that. Based on this input data, you need to predict what is dinner, whether it is dinner or whether it is lunch, like that, okay? By using name. So just try it out. You have to do some amount of feature engineering. Just convert these features into one hot encoded, or you want to probably convert this into label encoded. That is up to you. But I think it should be converted into one hot encoded, okay? Yes, this was it for my side. I hope you like this particular video where we have actually discussed about naive Bayes machine learning algorithm. Here we have just tried with Gaussian naive Bayes, but as we go and learn about NLP, we'll also try about Bernoulli naive Bayes and multinomial naive Bayes. So yes, this was it from my side. I will see you all in the next. Hello guys, so we're going to continue the discussion with respect to machine learning, and in this video we're going to start a new machine learning algorithm which is called as k-nearest neighbor. So out of all the machine learning algorithm we have learned till now, k-nearest neighbor is the most easiest one because you'll be able to understand it, and with the help of both k-nearest neighbor, we can solve both the problem, that is classification and regression problem statement. Now let's go ahead and let's try to understand what exactly we are doing with respect to the k-nearest neighbor, what is the mathematical intuition behind it, and what mathematical formula is also applied or used with respect to this particular algorithm. So to start with, first of all, I'm going to discuss about classification problem, and once you understand classification, I think it will be very easy to understand about the regression problem statement. So over here in the classification with respect to the k-nearest neighbor, let's consider that I have a data set, okay? And in this particular data set, let's consider that I have feature f1, f2, and this is my y features, the output feature, okay? Now I'll be having f1 and f2 values, and y category can be a binary category to just start with, okay? It can also be a multi-class categories, okay? So binary categories, right now I'm just taking binary categories basically means zeros or ones. It can also have multi-class categories, not worries. Now with respect to f1 and f2, if I consider over here, I'll go ahead and plot some points. Let's say I'm plotting some points over here, and these points are basically of the category, let's say 0, okay? So this belongs to the category 0, okay? And similarly, I'll go ahead and plot some other points, okay? Some other points like this, and this categories actually belong to the category 1, okay? Now with the help of k-nearest neighbor, how we are going to solve this classification problem? When I probably consider this particular data set, this data set is my training data set, right? Training data set, okay? Now I have to probably use this particular data set or this particular algorithm to probably test my new data point, okay? So what are the steps we specifically use? So the first step is that we have to initialize the k value. We have to initialize the k value. Now what this k value is, because the name suggests k-nearest neighbor. K can be any number which will be greater than 0, okay? And it can probably go to infinity, not a worries, right? So if I say k is equal to 1, or k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5, that basically means 1 neighbor, or 2 neighbor, or 3 neighbors, or 4 neighbors, or 5 neighbors. Like this, we can have any value. And in order to find out the exact k value, we have, this can be considered as a hyperparameter. Hyperparameter basically means this k value can change based on various data sets, right? So I'll show you in the practical example how we select the k value, okay? We have to definitely try different k values and then come to a conclusion that which nearest neighbor, like what should be the k value, which can actually give us the highest accuracy, okay? Now let's consider that after performing the hyperparameter tuning, I have selected the k value as 5, because when k is equal to 5, my accuracy of the model is very high, okay? Now in the second step, what we do is that we find the k nearest neighbor for the test data. Now what does this basically mean? Okay, so what I'm saying is that, now see, let's consider that this is my training data. Now what I'm actually going to do is that, let's consider that this is my new test data. Now I want to predict whether this particular data point belongs to this category or this category. Now it's very simple. First step is that we have selected what our k value is. Let's consider with the help of hyperparameter tuning, we selected it. I'll show you in the practicals like how do we select this k value, okay? Now after finding out this k value, this k is equal to 5 basically means 5 nearest neighbor. Now we will go ahead and find out which is the 5 nearest neighbor to this particular point, okay? So let's say to this particular point, I say this is my first nearest neighbor, this is my second nearest neighbor, third nearest neighbor, fourth nearest neighbor, fifth nearest neighbor. Okay, so the 5 nearest point I have actually found out with respect to this particular test data, right? With respect to this particular test data point, I'm just trying to find out the distance, right? Whichever is the nearest, the top 5 nearest, right? I've selected that. Now in the third step, what we do is that we try to find out from those k values, right? From those k values, from those k is equal to 5 values, let's say, how many points, how many neighbors belong to 0 category, and how many neighbors belong to the 1 category. Now I'm just going ahead and counting it over here. How many 0 categories are there? Now with respect to zeros, you'll be able to see with respect to zeros, okay, you'll be able to see the count is 1 and 2, right? So 2 counts, 2 nearest neighbor I found from this particular point that belongs to this particular category. Similarly with respect to ones, how many points are there? 1, 2, 3. So 3 is there. Now you know that maximum number of neighbors belongs to the ones category, so your final output for this will be also 1. Right? So that basically means this particular point has been now predicted as 1 because the maximum number of neighbors are actually 1 with respect to this particular data point. This is the entire funda of that k nearest neighbor classification problem. But now the question rises, how do I find the k nearest neighbor for this particular test data point? We have to probably use some distance metrics, right? We have to probably use some distance formula. So what exactly is the distance formula with respect to this, right? So for this, we use two different types of distance formula. So the first one is something called as Manhattan distance. Okay, or I will start with something called as Euclidean distance. This distance formula is used to find out the distance between 2 points, right? And the second technique that we can probably apply is basically called as Manhattan distance. Okay, we'll understand what is Euclidean and one is Manhattan distance. So let's say that I have two data points over here, and this data point coordinate is x1, y1, and this data point coordinate is x2, y2, right? In just a two-dimensional space. Now, if I really want to calculate the distance between this point, right? And I hope you may be knowing this particular formula, okay? At the end of the day, we have probably learned this in linear algebra and 8 or 9 standard mathematics, right? The distance formula with the help of Euclidean distance is just simple. That is root of x2 minus x1 plus y2 minus y1. And this both will be having a whole square, right? So the distance between 2 points or two coordinates in a two dimension will have this particular formula. In 3 dimension, you'll be having x1, y1, z1. So another one more term that I can add over here is z2 minus z1. In 4 dimension, that many number of coordinates will increase. This is a simple formula of Euclidean distance, okay? And this kind of distance is used in various different applications. Air traffic control, right? If the flight wants to go from one place to the other place, let's say from Bangalore to New Delhi or from India to US, we specifically use this Euclidean distance concept to probably calculate the distance with respect to the air, right? There is a second type which is called as Manhattan distance. Now, in case of Manhattan distance, let's say if I have two coordinates over here, okay, and these coordinates are x1, y1, and this coordinate is x2, y2. Now, in order to calculate the distance between them, we will not calculate through the hypotenuse. No, we will be using the base and the adjacent. So we will first of all calculate this distance, and then we will calculate this distance. When we calculate this plus this, then only I will be able to get the distance between these 2 points. Now you may be thinking, Krish, where this specific distance matrix is used? Very simple, guys. Right? If you know about Iron Man movies and all, right, or if you've seen the cities in US, every cities are having basically block-wise. So it is like block. So these are buildings with respect to the blocks, and in between you have roads, right? So another distance is between another block. So there will be another block. Now if I really want to, if a person is over here, if this person wants to go over here, so he or she will book the Uber. Now Uber is going to basically take the distance, which will be like this, and it will be like this, right? It cannot be something like this from here to here, unless and until you're traveling a helicopter, right? So this way, the Manhattan distance will be used. Now you may be thinking, should we use Euclidean or should we use Manhattan? It depends on the problem statement, right? But most of the time, people go ahead and use with respect to Euclidean distance, and any one of them, you just try to check whichever is the accuracy is the high, we can probably use this. Okay, again, with respect to hyperparameter tuning, we can use either one of them. Okay, so this way, we'll be able to calculate the distance between them and find the nearest point, and then we can go ahead and tell that this particular test data or new data point belongs to which category. Very simple, very easy. Till now, I hope everybody was able to understand. Now, if you have understood about classification, the second one is regression. Now, regression will be super easy. You don't even have to do anything. So these are your data points. Okay. So these are your data points. Okay. Let's say with respect to regression, you have size and you have house price. Okay. So size of the house and price of the house. Now let's say this will be a continuous value. Now whenever, and this is your training data. Now whenever you get a new test data point, let's say for this size, right? Okay. For this size, what will be your house price? Okay. Or let's consider something like this. For a new test data over here. Okay. What will be your house price? It's very simple. You will just go ahead and see which are the 5 nearest neighbors. So let's say these are my 5 nearest neighbor. So what you are basically going to do, you are going to combine all of them, and you are basically going to find out the average of all these points to find out the output. Average of all these points to find out the output. Right? That's it in regression. All the steps are same. You have to find out the k value based on the number of neighbors. But here, you'll just try to find out the average, or if you have a lot of outliers, you can also go ahead with the median. Only this is the concept entirely in the regression problem statement. Right? Now I hope you're able to understand this. Okay. Now, in the next video, we'll also try to understand about the variance of KNN. Okay, now it is important to understand the variance of KNN. Now, see, why I'm saying is that when I have some data points, let's say I have some 2 categories of data points, which looks like this. This is my first category, and this is my second category. Okay. Now, whenever I get a new test data, what I have to do? Suppose let's say this is my new test data. I have to probably go ahead and compute the nearest neighbors, right? Nearest neighbors. Don't you think this process of calculating the nearest neighbor, I have to probably calculate the distance between all these points, right? First of all, I have to calculate distance between all these points from this particular test data, and then you have to take the top 5 nearest neighbors. Understand with respect to the time complexity. So if you have basic idea of DSA, right, the time complexity will be order of n. Now this will be a problem if you have millions of data points. Then calculating the distance between each and every point to the test data will be a very cumbersome process. The time complexity will obviously be high. So we use variants of KNN, right, like KD tree. So some of the trees that we specifically use is like KD tree, ball tree, right? So with the help of this particular tree techniques, we basically optimize this entire calculation, distance calculation. How do we optimize? Because we don't go ahead and check the distance between each and every point. Because see, understand when we said these trees, right? These trees are basically created in binary tree format, right? Now, whenever I say binary tree, then to calculate the distance between every point to the test data, right, will be reduced by half. Why? Because it will not be checking with respect to every data points. And that is the power of binary tree, right? So in the next video, we'll go ahead and understand about both these variants, and we'll get to know the idea about this KD tree and ball tree, and how we are basically optimizing this particular time complexity. Because see, at the end of the day, if you really want to find the top 5 or 10 k nearest neighbors, you need to calculate the distance between every point. Why not? We just group it in such a way that I don't have to calculate the distance between other points based on the data that I have. And that is only possible with the help of KD tree and ball tree. And that is what I'm going to show you in the next video. So I hope you're able to understand this. We have understood this, and probably this is the most simplest algorithm in the entire machine learning. I still say it because it's very simple to understand. The only thing that you really need to remember is about Euclidean distance and Manhattan distance. That's it from my side, guys. I will see you all in the next video. Hello guys, so we are going to continue discussion with respect to KNN, and in our previous video we understood about the theoretical intuition. In this video we are going to discuss about the variance of KNN. Now one problem with respect to KNN is that if I really need to find out some nearest neighbor, I need to probably check the distance between the query point and probably all the points, and then whichever will be having the less distance we will try to select them. In that the time complexity is obviously very high, that is order of n. So how can we decrease this time complexity? So for this thing we will be discussing about two variants, that is KD tree and ball tree. Now let's understand what does KD tree basically mean. Let's say that this is my data points, okay, and here I have my F1 F2 feature. Based on this particular data points I have plotted this. See, I have 7,2, 5,4, 9,6, 2,3, 4,7, 8,1. So I have plotted with respect to that. So this one is nothing but 8,1, this is nothing but 7,2, this is nothing but 2,3, this is nothing but 5,4, and this is nothing but somewhere around 4,7, and this is nothing but 9,6. Okay, so all these points are there. If you want, I can also write it down for you so that you'll be able to understand it. So this is 7,1. Sorry, this is 4,7. Okay, 4,7. This is nothing but 5,4, and this is nothing but 7,2, and this is nothing but 8,1, and this is nothing but 9,6. Okay, F1 F2 feature, and this is nothing but 2,3. Now our main aim is that we should definitely find out a way that whenever we try to find out the k nearest neighbor, right, we should not go ahead and check the distance for each and every point. So for this, we will try to create a new tree, which is called as KD tree, which is in the form of a binary tree format. Why? I'll tell you. Now how this binary tree is basically getting constructed, we'll discuss about this. Okay. So binary tree, what do I mean by binary tree? So this point should will be later converted something like this. See, I will try to convert these data points into something like this. Now because of this, what will happen is that whenever we do any search, it will be limited to this particular tree itself. Okay. Either it can go through this particular path and quickly get the elements, or either it can go through this path and quickly get the elements. Right. So in short, we are reducing the number of searches. Okay. Now let's see how we will probably construct this particular node. Now in the first case, what you need to do is that you need to find out what is the median of F1, median of F1 and median of F2, right? Now in this case, if I probably see what will be the median, so if I probably try to create this in a sorted manner, it will be 2, 4, it will be 2, 4, it will be 2, 4, 5. So this is with respect to F1 feature. See this, okay? 2, 4, 5, 7, 8, 9. So here you have around 3 elements. So what you'll do, you will take the mid of this. It will be nothing but 5 plus 7 divided by 2, which is nothing but 5 plus 7 is 12, 12 by 2, which is nothing but 6.5. Now when I say 6.5, you don't have any elements like 6.5 in the training, right? So either you can take 7 or either you can take 5, right? Or either you can take 3. 5 element is present over here with respect to the x-axis, or 7 is present. So either you can go ahead with 5 or 7. You don't have anything like 6.5. Yes, we can get the median value to 6.5, but one of them I'll actually take. Now let's say that I will be going ahead and taking this 7. Now this 7 element is with respect to the x-axis. First, we will be considering x coordinate, right? X coordinate basically is this F1 feature. Now once we get this median value, what I will do is that I will try to draw a line like this, and I will project it into this x-axis. So I'm projecting it over here in the 7 value. Okay, so let's consider this is my 7 value. Okay, so this is the first line I've created. Now because of this line, now I have two main regions. This is my region 1 and this is my region 2. Okay. Now similarly, I will go ahead and create my second region. Now in the second region, I will go ahead and take my F2. Okay, I will again go ahead and calculate my median value. So here what I will do, 2, 4, I will go ahead and write first in the sorted order. So it will be 1, 2, 3, 4, and 1, 2, 3, 4, and it will also be 6, 7. Now here also you can see there are 6 elements. So I will try to find out the median of this 2. If I try to find out, it will be 3.5. But do I have an element like 3.5? Either it can be 4 in the y-axis or it can be 3 in the y-axis. So let me consider that I'm going to consider 4 in the upper ceiling bracket. So this 4, what I will do next is that I will try to create another line, and now this time this will get projected in the y-axis. So this is my second line that is getting created. Whenever I project in the y-axis, okay, it will be in the blue line. Whenever I project in the x-axis, it will be this particular line. Okay. Now this is done, right? So now I've actually got this with respect to F1 and F2. Perfect. Now as soon as I divide this line, now how many regions I have? I have this 1 region, I have this 2 region, I have this 3 region, right? And this particular point is basically falling over there. Now similarly, what I can do, I will take these 2 points now, and I'll try to find out the mean with respect to the x-axis, right? Or median with respect to the x-axis. I have 9 and 8 over here, so I can probably consider 8 or 9, right? And if I probably consider 8, or let's say if I consider 8, what I will do, I will go ahead and create this another straight line, which will divide these 2 regions again, right? Which will divide these 2 regions, right? Now why I'm dividing these 2 regions, it will make completely sense. I'll just let me explain you in just some time, okay? Now similarly, with respect to the x-axis, I'm able to get something like this, okay, over here, right? Now similarly for this particular region, I can go ahead and do more divisions, right? I can make divisions like this or like this, right? So similarly, like once we go with x and y, continuously we'll be able to make this kind of lines, okay? By creating this, we are actually creating what? We are creating a split, right? And when we are creating a split, this split will be also considered over here. Now with respect to this particular point, the first point was 7,2, right? Then with respect to 7,2, I got 2 regions. One region was this, one region was this. So the second region that I made a split was 5,4 over here, right? Which I projected into the y-axis. Now from 5,4, I have 2 plots, right? 4,7 and 2,3. Now this 4,7 will come over here and 2,3 will come over here, right? Because 2 over here is less than 5, 7 is greater than 4, right? So this kind of split you'll be able to see over here, right? And this is nothing but KD tree. Okay. Now similarly after 7,2, I had 2 elements, 9,6 and 8,1, right? So 9,6 will come over here and 8,1 will come over here, right? So this way we are able to make the splits, right? All the elements that I had, I was able to make a simple binary tree over here, right? Binary tree, and this is nothing but this is a KD tree, right? In the first time, I projected in the x-axis. In the second time, I projected in the y-axis. In the third time, we are projected in the x-axis. And then similarly, when we project in the y-axis, okay, we can do this, right? So now let's see. Okay, I will also rub this because I don't want to show this because I did not give you a clear idea how we projected this, right? So I'll just go ahead and delete this, and this will be my 2,3. Let's consider this, okay? And this is my 4,7. Okay, 4,7. This is my 2,3. Now see this. The next line that I projected was this one, right? In the x-axis. This is fine. Okay. Now after projecting this, what happened with respect to this? I got 9,6 was one region and 8,1 in one region. So I made this particular line. Now again, if I want to do the split with respect to the y-axis, I can again take this particular point because there is only one point. Now obviously the median will be this. So I can probably go ahead and construct one line like this, right? Now this will be one group, this will be another group, right? Similarly with respect to 4,7, I can go and project this 4 over here, right? In this line. So this line will look something like this, right? And similarly, I can go ahead and continue with my x-axis coordinate and y-axis. So in short, I'm making groups. Now tomorrow, if any new query points come, and now if I want to calculate the distance, right? How many elements should I look? I know it is belonging to this region. I don't have to worry about any other region. Okay. Now this point, let's say this point is nothing but 5,7. Now where is 5,7? You know that, right? 5,7. First of all, I have to go over here, and then I have to go over here, right? 5 x-axis, 7 y-axis. Now I know what will be the nearest point from here. Either it can be 4,7, Or it can be 2, 3 is not possible, 2, 3 is very, very far. So I know what will be my nearest point. That will be nothing but 4, 7. So this becomes my first nearest point. Now if I really want to find out the second one, then what I do? Again, I will traverse back. If I traverse back, what is the element I'm getting? 5, 4. So this becomes my second nearest point. Then if I traverse back over here and come in this particular axis, then the third nearest point will become something like this. Right? Again, if I traverse back, I go back again, and then I will be able to see that then my next nearest point will be 7, 2. Now similarly, I will go ahead and calculate 9, 6. Then finally, I will go ahead and calculate like this. So this way, I will be able to get all the nearest points. So over here, backtracking is also used to find out the next nearest point. This was the idea behind KD3. Okay, just to make you understand this thing. Why we are doing this? Because we really need to decrease the time complexity. Because with time, I'm just going through one route. I'm not finding the distance with respect to every element. That we should do in the before stage, right? When we don't use KD3, or if you just do a brute search. Brute search basically means go and find out the distance between every point and the other point. Like with respect to this particular query point, if I'm finding the distance with respect to every other point, that becomes a brute search. But now here I'm able to decide my path, and then I'm able to find out my first nearest point, then the second nearest point, then the third nearest point. And obviously backtracking will also happen in this. So this was the entire idea behind the KD tree. Now similarly, second concept or second type of tree that we specifically have, and this is a better one when compared to KD tree. Why? Because in this KD tree, you also have to do backtracking. But in ball tree, which is the second variant, you don't have to do that. Now ball tree concept is very simple. Let's say I have some data points. So I can see this is my near data point. So this is my 1, 2. Okay, 2 data point over here I have. Then I have over here 3, 4. Let's consider like this. And then let's say I have one more 5, 6, 7. Okay, 8, 9. As the name suggests, ball tree. Now see, in ball tree the concept is very simple. First of all, what you do, whichever is the nearest point, right, you group them together. So here you can see 2 and 3 are together, 3 and 4 are together, 5, 6, 7 are together. So I will group them. 8 and 9 are together. Okay. So you start your element from here. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this is your element, right? 9. Now what you do, first of all, what you have combined together a group, right? So this is your group 1, right? So I will combine this 2 and create a group which is called as group 1. I will combine 3 and 4. I will create another group which is called as G2. And then I will combine 5, 6, 7. I will create a next group which is called as G3. So here you can see this, right? And similarly, I will go ahead and combine 8 and 9, and this will be my group 4. So this becomes my group 1, group 2, group 3, and group 4, right? Now the next step is that what I will do, I will try to combine the nearest group. Now the nearest group is nothing but G1, G2, let's say. So this is getting combined, right? The next nearest group that you can probably see is G3, G4. So I will go ahead and combine this group, right? Over here you can see this. I'm combining this two group. So what happens first of all? I combine G1 and G2, right? So this becomes my G5 group. I combine this 2. This becomes my G6 group, right? And finally, I combine the entire group. That will basically become my G7 group, right? So in short, what we have done, we have combined this with respect to clusters. Now, whatever new data point that comes, let's say if I'm getting a new data point over here, what this circle is G5. You know which will be the nearest neighbor point, right? The group 1 neighbor point. So you have all these elements, group 2 neighbor point. So here you directly go ahead and calculate the distance between all these points. So this becomes your top 4 nearest neighbor, right? So this way, because of the group, we are directly able to get the elements instead of searching for each and every element and calculating the distance. And this is the entire power of ball tree. Okay, so I hope you are able to understand this, guys. Ball tree concept and KD tree concept, right? At the end of the day, both are actually creating a binary tree. And always remember, with respect to binary tree, the time complexity to search or to find the distance. So first of all, to search an element over here and to calculate the distance, it reduces because here you're not trying to calculate distance with respect to each and every point, right? So this was an example with respect to KD tree and ball tree. I hope you're able to understand this. Again, just a way to optimize some kind of algorithms with respect to KD. Hello guys, so we are going to go ahead and discuss about the implementation with respect to k-nearest neighbor classifier and regressor. So here again we'll try to understand what are the important parameters with respect to k-nearest neighbor classifier, regressor, and we'll take a simple data set and we'll try to solve it. Remember one thing, all these things will again be repeated in end-to-end projects because there we also need to perform hyperparameter tuning. Okay, so initially what I will do, I'll go ahead and import all the important libraries over here, and here I'm using make classification to create a data set with 2 classes. That is my binary class over there. Where we are trying to solve a binary classification problem, and then the number of samples over here are 1000 points, and the number of features in my data set will be 3, and I'm using some random state value so that it can be created with respect to random data. So if I probably go and see X, so here you'll be having 3 features in every data points. Okay, then what we'll do after this, obviously we need to do the train test split, so we'll go ahead and do the train test split, and here also we'll do it. Then from here the next thing is that we have to import the k neighbors classifier, that is the k nearest neighbor classifier. Now in k nearest neighbor classifier, one thing that you really need to know about is all the parameters. Okay, so here you can see that sklearn.neighbors.k-neighbors classifier. Here the number of neighbors will be by default 5. So the k value by default is selected as 5. And then you have parameters like weights, algorithms, leaf, p, right? So the most important thing that you really need to understand is about these 3 parameters. That is weights, algorithms, and p value. First of all, let's go and see what is this p value. Okay, so I will go over here. By default, the p value is that it is basically int and the default value is 2. Okay, so the default value that is basically 2. What does this indicate? This indicates Euclidean distance. So if you remember, if I really want to calculate a distance from one point to the other point, if my p value is 2, by default we're using Euclidean distance. And if we set it to 1, then it is equivalent to Manhattan distance. Okay, which one to select? Whether p should be 1 and 2. You have the answer for that. You have to perform hyperparameter tuning by creating a key value pairs. Okay, and then what we will be doing is that we'll be understanding about the algorithms. Now in algorithms we have already discussed, right? Ball tree, KD tree. Why it was specifically used? Because you understand when we try to find out the k nearest neighbors, we need to first of all calculate the distance from the target from the new point to every other point, right? And then only we'll go and see that which are the top 5 nearest point like that, right? So this algorithms like ball tree and KD tree, this creates a binary tree. Now in binary tree, what happens is that the search, right, with respect to every target point, if you want to calculate the distance, that gets minimized because there will be less number of points. So because of that, the time complexity decreases and optimization happen. So you can use either ball tree, KD tree, or brute force search. This is also one brute force search algorithm, which is specifically used in DSA. If you just keep it to auto, right, so based on the data set, any one of these parameters will get selected. Okay, so what is based on the fit method, whatever data set you specifically have, it will automatically select that. Okay, now coming to the next one, that is weights, which is nothing but uniform and distance. Okay, so you can read about this. It is basically given over here. And again, which one to select? You can perform hyperparameter tuning for the same. Okay, and this is the same thing for the k neighbors regressor also. Here also you have n_neighbors, weights, algorithm, and p, right? So these are the default things. So what I'll do over here is that we'll go ahead and import k neighbors classifier. It is present inside from sklearn.neighbor. Okay, and then we are basically going to consider k neighbor classifier with n underscore neighbor is equal to 5, and the algorithm that we are basically going to use is something called as auto. Auto why? Because any one of them, and by default p is equal to 2. Okay, which I'm basically taking as Euclidean distance. Whenever you have features that are randomly distributed in feature dimensions, you should definitely take Euclidean distance. Okay, so here we have this classifier dot fit on x to n by train, then we are doing the prediction, and then it is very much simple. We'll go ahead and do the confusion matrix, accuracy score, and classification report. So here is my accuracy, that is somewhere around 90.6. Now I'm going to give you one task: perform grid search CV and try to find out what is the suitable k value. K value when I say n underscore neighbor value. Here by default I took 5. If I change it to 6, again this accuracy might change a little bit. Like over here you're getting 89%. Now see, with k is equal to 5, I got how much? With k is equal to 5, I specifically got somewhere around 90%, I guess. So let's see over here, yeah, 90%. So instead of taking k is equal to 6, I'll take k is equal to 5. So what I want, test it with different k values and let me know what is the best k value that you can probably get. Okay. So this is with respect to the k nearest classifier, and here is again with respect to the k nearest neighbor regressor. I created a regression data set with 2 features and 1000 data points. We did train test split. We use this. We use algorithms. Here also I'm using n underscore neighbor is equal to 6. Algorithm is equal to auto, and then we predict, and then we probably calculate the R square, mean absolute error, and mean square error. And finally, this is basically my entire R square. See, 91% accuracy I'm able to get. So here also perform that similar kind of task. So this in short was about k nearest neighbor and k nearest neighbor classifier and regressor. So I hope you're able to understand this. At the end of the day, tomorrow when you're doing any end-to-end project, we will be using all the classification algorithm, all the regression algorithm, and we'll try to find out which is the best one and probably predicting the model or using the model for our better use, which has the best accuracy out there. Right? So yes, this was it from my side. I hope you like this particular video. I will see you all in the next.
So till now, I hope you're able to understand all the previous algorithm in-depth maths intuition. From this particular video, I'm going to start something called as decision tree algorithm. It is a very important algorithm altogether because in the upcoming videos, you'll be seeing ensemble techniques, bagging and boosting. Over there, some of the algorithms like random forest, lazy boost, all uses decision tree internally. Okay, so let's go ahead and let's try to understand the maths intuition behind decision tree. So to begin with, guys, decision tree classifier, and right now, see, decision tree can be used for solving both the kinds of problem statement, that is classification and regression problem statement. In this video, we'll focus on how to solve a classification problem statement with the help of decision tree. And with respect to this, we're going to discuss some of the important topics like entropy and gain index, which is specifically used to check purity split. And then we'll go and understand about information gain. Information gain and all, I'll try to just explain. But let's start with some simple understanding. Usually in decision tree, there are 2 types. One is ID3 and one is CART. Currently, the sklearn library that you probably use for creating the decision tree algorithm through Python code uses this CART technique. Okay, so we are going to focus on both the techniques, but in short, see, the basic difference between ID3 and CART is that in CART, you just create, whenever you're creating a decision tree, you create only binary splits. Okay, with respect to each and every node, you basically create a binary splits. Whereas in ID3, it does not happen like that. You can also create more than a binary split. Like you may also have 3 splits from one specific root node. Okay, so this is the basic difference. And yes, some of the mathematical formulas will be changing with respect to this. Okay, but let's start and let's understand like what exactly decision tree is and why it is basically used. Now, I hope you probably may know many programming language. So let me just write a very simple programming language. Let's say I'm using Python. So let's say I'm going to write age is equal to 14, and I'm going to say if age is less than or equal to 15, I'm just going to say that print. Okay, the person is in school. Okay, so if I'm just saying that if he or she's age is basically less than 15, I'm just saying that the person is in school. Okay, so this is one condition. Okay, and let's say after that I write an elif block. So if I say the person age is greater than 15 and less than or equal to 21, I will probably say that the person may be in college. Okay, the person may be in college. Okay, I'm just giving you an example, guys. Everything will make sense why I'm writing this specific code. Okay, and finally else, I'm just saying that the person has passed. Okay, the person has passed the college. Okay, so I'm just giving this specific statement. Now understand, if I really want to compare decision tree, right? Decision tree will also be working similarly like this if condition, right? So let's say I'm going to probably take a root node, okay? And here, let's say my root node over here will be first condition, age is less than or equal to 15, okay? So obviously I will be having 2 outputs, either it can be yes or it can be no, right? Now in this particular case, if the age is less than or equal to 15, what we are going to do, we are going to basically create another root node, and here it is basically going to print the person is in school, right? So here obviously it is going to basically print where the person is in school. Right, very simple. Now, similarly, in the case of no, I may have a different root node, okay? And over here, what it will be that this no basically means we are basically going to move towards the elif block, okay? Or instead of writing yes or no in this way, I will just change this. I'll make sure that I will write yes over here and no over here, okay? So left hand side will just try to write like this. So here I can definitely say that the person, when it is yes, in this particular case, it is going to print the person is in school. Okay, so person is in school, it is going to print. In the case of no, what will happen is that you're just going to go to the elif block. Now in the elif block, I will be writing another condition. Here the condition will be age is greater than 15 and age is less than or equal to 21. So with respect to this, again, I can have 2 more divisions, and this 2 specific division will be again yes. Let's say this is yes and this is no. So this can either be true or false. If it is no, it will probably print something. Otherwise, it will come over here. And again, we can do this specific split from this particular yes, from this particular no, which will be my else block. Okay, so here you can basically see that like this, the same if else condition. I have actually constructed a simple decision tree, and this is how decision tree will get constructed from this kind of conditions itself. So suppose if I have a specific data set, our main aim is that if I have some independent and dependent features, we are going to make sure that we try to take that particular data set and we try to construct a decision tree in this specific way. But just to construct this, you really need to know some of the technical terms like entropy, gain index, and all, information gain and all. Okay, so in short, decision tree we'll try to create in this bottom to top approach. Okay, so let's go ahead and let's talk about this and how a decision tree will basically get constructed. What does entropy, gain index, information gain actually mean? So here I'm going to take a very simple example. So this I have a specific data set. Let's say this particular data set, I have already spoken about this particular data set in nearby. This data set is very simple. Here you have independent features like outlook, temperature, humidity and wind, and you really need to predict whether the person is going to play tennis or not based on this independent feature. So obviously I'll be using decision tree classifier. This is a classification problem, specifically a binary classification problem, and we'll try to solve it out. Okay, binary classification problem. Now let's start. Okay, let's start and let's see how we are going to split this all nodes and how we are going to construct a decision tree. So in the first instance, I'm just going to take outlook as my node. Okay, so let's say this is my outlook. I'm taking outlook as my first feature. Okay, or the root node. Now you might be thinking, why you did not take temperature, humidity, wind, or anything as well? Don't worry, guys. I'll explain you about that also. But right now, let's consider that I've selected outlook. Now, over here, with respect to outlook, how many unique categories are there? So if you go and see, sunny is one unique category, overcast is one unique category, and rain is one unique category. So based on the outlook, I'm going to divide this into 3 splits. Okay. So the first split over here is basically my sunny. Okay. The second is basically overcast, and the third is something called as rainy. Okay, so based on the outlook, you can definitely see that I'm getting this many number of subcategories from this particular root node. Now, with respect to outlook, first of all, try to find out how many yes and no's are there. So if I start counting 1 yes, 2 yes, 3 yes, 4 yes, 5 yes, 6 yes, 7, 8, 9. So total number of yes that I have over here is 9 yes, and total number of no's that I basically have 1, 2, 3, 4, 5. Okay, so here I have 9 yes and 5 no's. Okay, now with respect to outlook, when I split it with respect to Sunny, considering Sunny as a category, now go ahead and find out like how many number of yes and no's are with respect to Sunny. So Sunny over here 2 no's I can see, then this is 3 no, and obviously if I probably try to see 1 yes over here and the other yes over here. So definitely I can, just by seeing this, you can just go and count it ahead, and you will basically be finding I will be getting around 2 yes and 3 no's, right? Because see, this is 1 no, 2 no, and one more no is somewhere here with respect to Sunny, so somewhere here. So I have 3 no's and 2 yes. So I have 1 yes over here and the other yes over here. So you just have to count and just try to find out that with respect to Sunny how many yes and no's are there. Similarly with respect to Overcast, if you go ahead and find out with respect to Overcast, I will all be getting yes. So 1 yes, 2 yes, 3 yes, and 4 yes. So here I'm going to get 4 yes and 0 no's. Similarly with respect to Rain, we just go and calculate, I'm getting 3 yes and 2 no's. Okay, so here you can clearly see that I've been able to find out like how many number of categories are left with respect to this particular split. Now the next thing is that with respect to Sunny, you can see that I'm having 2 yes and 3 no's. So this is basically an impure split. Why impure split? Because I have both yes and no's, right? So this is going to be an impure split. So what I'm actually going to do, I'm going to further split this down into some more categories, considering considering other features. Suppose I may consider temperature, so I may again split it. Why I'm splitting it? Because this is an impure split. But if I see in this particular case, this is a complete pure split. Why I'm saying pure split? Because here either I have yes or no. So here I see that I have 4 yes, but 0 no's. So all my output over here is going to be yes itself, right? So suppose if I traverse this, suppose if my outlook is Overcast, I'm definitely going to say that I'm going to play, right? So this pure split is always good because we will be able to get the leaf node. So this node is basically called as leaf node. Okay, leaf node basically means either you have yes or no's, right? Similarly, in this particular Rain case, you are basically having an impure split, so further you really need to split this down. Okay, now this kind of split will keep on happening in decision tree unless and until we don't get a leaf node. Okay, we don't get a leaf node. Now, obviously, just by seeing, you can definitely find out whether this is a pure or impure split. But mathematically, how do we find out whether this split is pure split or impure split? So for that particular case, we will be using a technique which is called as entropy and information gain. So let's go ahead, and here I'm going to just write down 2 important points. First of all, purity, right? If I really want to check whether it is a pure or impure split. So how do I check it out? Okay, for this mathematically we have to use 2 techniques. One is entropy and the other one is something called as Gini index. Okay, Gini index or Gini impurity. Okay, so I can also say it as Gini impurity. Okay, so these are the 2 techniques that I'm specifically going to use. Let me just write it down this as Gini impurity. Okay, Gini impurity. So we'll try to understand mathematically how these specific things will happen. Now coming to the second thing is that I just asked you a question. You may probably be thinking, Krish, why did you just select outlook? So what feature you probably need to select for the splitting purpose? Okay, so second question is this: what feature you need to select for splitting? Because you can select any feature, right? So how do I understand that which is my best feature to select for the splitting purpose? Because if I select this particular feature and if I'm able to get the leaf node quickly, that basically means this particular feature should be selected and it is correct, right? But if I select a feature that may not give you a leaf node, it may take time to give you a leaf node, then that is bad, right? So for this particular case, we use something called as information gain. So now this 2 specific thing we are going to understand. First we'll start with entropy and Gini impurity and then we'll start with information gain. Okay, so this is with respect to the introduction of decision tree classifier. So in the next video, we're going to discuss about entropy and information. Let's continue discussion with respect to decision tree classifier. And in this video, we are going to discuss about these 2 important points, that is purity, how to check whether a split is pure or not. And for that, we are going to use entropy and Gini impurity. Okay, so let's quickly write down the formula and then I'll start explaining the formula itself. So the first thing on the left hand side, we'll try to understand about entropy. And the second thing that we're going to see is something about Gini impurity. Okay, so this is Gini impurity. Now with respect to entropy, if I really want to see the formula is basically given by h of s minus p plus log base 2 p plus minus p minus log base to p minus. Now what is this p plus and p minus? So let's consider that we have a binary classification problem. Now in this particular case, what will be p plus? P plus is nothing but the probability of being positive, like probability of one category, like or the positive category, or it can be a negative category. So here if I say 1 and 0, so if I really want to talk about if my outputs are basically having 1s and 0s, I may say that p plus is nothing but the probability of being 1. P minus can be the probability of being 0. So like something like that. Suppose if I have multi-class classification, then instead of writing minus p plus, I can write minus what is the probability of being category 1, what is the probability of being category 2, what is the probability of being category 3. So it'll be like it'll keep on going like minus 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 sign. So that is the basic difference between the formula. Okay. And similarly, if I really want to find out the Gini impurity, then I will probably be using 1 minus summation of I is equal to 1 to n, and this will be p square. I'll talk about what exactly is p square. It is a combination of both positive probability and negative probability. So like it's like p plus and p minus. I'll just expand this equation in some time. Okay. Now let's go ahead and understand first of all entropy, and then we really need to understand many things in entropy also. So I hope with respect to binary classification you have understood the formula. P plus basically means it is just the probability of being one category, and this p minus is the probability of being the other category. Okay. Now let's say that I have a split. Let's say with respect to this feature 1, I'm doing this particular split, and let's say initially I had 6 yes and 3 no's. So when I made the split, let's say I'm going to get 2 categories. It is nothing but this first category is C1, okay, and the second category is C2. Now with respect to this split, let's say I'm getting 3 yes and 3 no's over here, okay, and similarly I'm actually getting 3 yes and 0 no's over here. Okay, I'm just saying that after this particular split in the category 1, I can see that total number of yes and no's are 3 yes and 3 no's. Like how we did this particular split over here, the same way we are doing this particular split. Okay, now what we are going to do is that we are going to check the purity split for this, and here you can definitely see that okay, this is an impure split because I have 50% which is saying like yes and 50% as no. So this is obviously a very impure split, right? Very impure split. So and this in this particular case you can say that this is a pure split. Just by seeing it, we are able to understand. But mathematically, let's go ahead and apply it. So I'm just going to write h of s. Now here I'm just going to see h of c1, and h of c1 basically means what is the entropy of this specific node. Okay, so h of c1, the entropy will be, I'll just write the formula, minus p plus log base to p plus minus p minus log base to p minus, right? So this is the formula that we are going to use. Now what exactly is p plus? Now p plus is nothing but here you can clearly see that what is the probability of being yes, right? So obviously when you see this, the probability of being yes is 3 by 6, right? 3 by 6 because the total number of yes and no's if I combine it is 6. So here I can basically write minus 3 by 6 log base 2 3 by 6. Okay, and similarly, what is the probability of being negative over here? Again, the same thing. So here I can definitely say that, okay, this is nothing but 3 by 6 log base 2 3 by 6, right? Because the probability of no is also that many. So if I go ahead and compute this log base 2 1 by 2, and if I start computing it, and if I try to apply the log base 2 formula, here I'm going to get 1. Okay, now see guys, since this is a very impure split, because the number of yes and no's are equal, right? So obviously my maximum impure split value will have 1. So this is the reason why I say that this is a very impure split. And with the help of entropy, we are able to find out that, okay, fine, it is 1. Now, in this particular case, here you can directly see that this is a pure split, because here I have only yes and 0 no's, right? 3 yes and 0 no. So let's go ahead and apply this specific formula for that too. So here I have xc of 2, so it's nothing but, what is probability of plus over here? So it is nothing but 3 divided by 3, right? Because the total number of no's are 0. So if I combine both, it is going to be 3 only. So here I'm going to have minus 3 by 3 log base 2 3 by 3, then it will be minus, what is the probability of being no? It is 0, right? Because 0 by 3 is nothing but 0, right? So here I'm going to basically use 0 log base 2 0. So this in turn will be, if I try to just compute this, this will be 0 itself, because 0 multiplied by anything, and this will be minus 1 log base 2 1. So this in turn will be giving you a 0 value. So here, since I'm getting a 0, this is basically a pure split. And obviously, you can see over here, since I have only yes, I'm actually getting a pure split. Okay. Now with respect to this, let me create a very good graph so that you'll be able to understand entropy. So out of this, I can definitely come to a conclusion. Let's say this is my conclusion that I'm coming up with. Over here, in the x-axis, I can have probability of plus or minus, and obviously this value will be between 0 to 1. So if I say probability of plus is 0.5, that basically means probability of minus is 0.5. Now whenever I have probability of plus is 0.5, you know that, see, in this particular case, probability of yes or probability of no is 0.5. So the maximum value that we can get is 1. So in the y-axis, I will try to plot h of that specific category. It can be s. Okay. Now in this particular case, whenever my probability of plus or probability of minus is 0.5, I am always going to get my value as 1. Okay, that is a complete impure split. Okay, and with respect to 0 to 0.5, it will differ. 0.5 to 0.1, it will differ. So finally, I will be able to get this. I will be able to get this kind of curve. Okay, when we are trying to plot probability of plus with h of s. Okay, so maximum value will be 1, and when it is 0.5, I'm going to get this. So this is the curve that we usually get with respect to entropy. Your values will be always between 0 to 1. That you always need to remember. Now, if you are able to get this kind of graph, I hope you are able to understand it. Because why I'm teaching you this graph is that because in the interview, the interviewer may ask you what is the differences between entropy and your Gini impurity. Okay, so this kind of questions may be definitely there. Okay, so you will be able to say this, that your Gini, your entropy basically ranges between 0 to 1. Okay, now let's go ahead and try to see for Gini impurity. So in the case of Gini impurity, how we will be able to see, and I'm just going to repeat that same formula what I had actually written. Okay, so Gini impurity is nothing but 1 minus summation of I is equal to 1 to n. N is the number of data points, and this is p square. I had written this p square. Now let me expand this. So it is nothing but p plus whole square plus p minus whole square. Now what is this? This is probability of being yes, this is probability of being no, right? So in this particular case, whenever if I'm applying for this particular split, Gini impurity, so if I have 3 yes and 3 no's, how do I calculate what is the probability of yes over here? It is nothing but 3 by 6. So it is nothing but 1 by 2. So let's go over here. I'll write here 1 by 2 whole square plus 1 by 2 whole square, because 3 by 6 is nothing but 1 by 2. So when I try to compute this, this is nothing but 1 minus half, it is 0.5. So for an impure split, which is a complete impure split, the maximum value with respect to Gini impurity, I will be getting somewhere around 0.5. That is what from this particular formula we are able to see, right? And we will be able to see that we will be getting a graph which looks like this for Gini impurity. So in the case of Gini impurity, your value will be ranging between 0 to 0.5. In the case of entropy, it will be ranging between 0 to 1. If you don't believe me, just try to apply for this particular split. So for this particular split, let's say if I have 3 yes and 0 no's, so if I try to apply this is nothing but 1 minus 3 by 3 whole square. Okay, and this is nothing but 1 minus 1 is 0. I will not have probability of minus because it is 0, right? So 0 by anything is 0, so I'm not writing it over here. So here you can see for a pure split, I'm getting it as 0. For a very impure split, I'm getting it as 1. So this will again be ranging between 0 to 1, right? So this is the basic difference with respect to understanding about entropy and Gini impurity. Now my next question is that, Krish, why did you, suppose if you have 3 features, F1, F2, F3, why did you first of all select F1 and probably make a split to F2 and F3? Why I could not make a selection of F3 and make a split for F2 and F1? And probably in the future, I can probably make again a split with F2 and F3. How do I decide which features to basically select to make this decision tree split? Okay, decision tree split. So for this, we will try to understand about information gain, right? Information gain. So and with this help of information gain, we'll be able to understand that which features should I select and probably do the decision tree split. With the help of Gini index, Gini impurity, and entropy, you're definitely able to find out like whether this node split is pure split or not split, pure or impure split. If it is an impure split, you further do this particular split, right? In this particular case, you don't do more splits. You may take another feature and do this particular split. But now, and I hope you have understood what is the difference between entropy and Gini impurity. But now my question is that which features to select? How we should select each and every feature and start doing the splits after we understand whether it is a pure or impure split. So for that, we'll be using information gain. So in the next session, we're going to discuss about information gain. Okay, so I hope this revised particular session is super important with respect to different interview questions you may be getting, different questions, right? So yes, I'll see you in the next video. Thank you. Now let's continue the discussion with respect to decision tree. In our previous video, we have already discussed about Gini index and Gini impurity and entropy, and we understood that, okay, to check the purity split, we basically use this. But now let's discuss about information gain. Let's say in my data set, I have features like F1, F2, F3, and probably I have my output feature. I may take F1 and start splitting as a decision tree, right? Or I may take probably F2 and start splitting in terms of the decision tree, right? So how do I determine from which feature should I select in order to start the split? And for that specific case, we'll be using information gain. Now let me quickly write down the formula for information gain. So here we basically write gain S comma feature 1. That basically means that I need to start with this feature or this feature is equal to, this is basically the entropy of the root node, okay, minus summation of v belongs to value. I will explain each and every term. Don't worry about it, what exactly it is. First of all, let me just write down the formula. And this is entropy with respect to all the categories. Okay. Now, what exactly this is? This is nothing but entropy of the root node. Okay, entropy of the root node. Now, let me quickly talk about this. And obviously, you know that what is h of s. H of s for a binary classification, I can basically write the formula as probability of log, probability of plus to multiply by log base 2 plus similarly probability of minus log base 2 p minus. So this is the formula that we specifically use. Now, let's say if I am trying to do a split. Okay, let's say I'm trying to do a split over here. Okay, and we'll try to compare this to specific split. Okay, so let's say my first split is with f1. Okay. Let's say I have this F1 split, and here I'm just making into two categories, C1 and C2. Okay, and let's say initially in F1 I had 9 yes and 5 no's, and here I actually have 6 yes and 2 no's, and here I actually have 3 yes and 3 no's. Okay, so let's say that this is what is the outcome that I probably get. Okay, and similarly, let's say there will be another split which is with F2, and here I'm getting category C3 and C4. Now I really need to compare out of these two which is the best split. Should I start with F2 or should I start with F1? Now let's consider this one and try to put up and try to find out the formula what gain we are actually getting. Okay, so here you can definitely see that it is 9 yes and 5 no's, 6 yes and 2 no's, and 3 yes and 3 no's. So first of all, we'll try to calculate the entropy of the root node. So here this entropy of the root node we'll try to calculate. So here we have already minus p plus is nothing but over here in this particular case it will become 9 by 14 log base 2 9 by 14, and here I basically have probability of minus. So in short, I will be getting somewhere around with respect to this no, I will be getting 5 by 14 log base 2 5 by 14. Okay, so with respect to, in order to calculate, and this is the entropy for the root node. Okay, so if I try to calculate it, I've already done the calculation. This will approximately be equal to 0.94. So this is the first step. I have actually found out what is the entropy of the root node, and I've got somewhere around 0.94. Now let's go ahead and let's try to find out this specific thing. Now here in this category, this is my first category C1. I have 6 yes and 2 nodes. This is my second category C2. I have 3 yes and 3 nodes. Now whenever I say h of SV, in short, I'm trying to find out the entropy of both these categories. Okay, so let's quickly go ahead and calculate the entropy of both these categories. So here I'm going to write h of C1, and again I'll try to apply the same formula. In this particular case, what is the probability of plus? It is nothing but 6 by 8, right? So here I'm going to get 6 by 8 because they're total 6 yes and 2 nodes. Then here I'm going to write log base to 6 by 8. Similarly here, minus when I'm doing with respect to the probability of negative. What is negative or probability of no? In this particular case, I'll get 2 by 8 log base to 2 by 8, right? So finally, you'll be able to see that what is the output that I'm going to get. It is nothing but 0.81. So this is what the entropy of category 1. Similarly, I'll go ahead and calculate the entropy of category 2. So in this particular case, entropy of category 2 is basically having 3 yes and 3 no's. And obviously, I don't think I need to solve this because this is a complete impure split, right? So if it is an impure split, I know, and this is a very, very impure split, the worst impure split, I know with respect to this, I'm always going to get 1. So I have actually found out the entropy of category 2 as 1, and this as 0.81. Okay, now fine, I've got this information for both the categories. Now let's understand what is this S of V and S, and I will start putting up all these values. Okay, so finally, let's go ahead and write the gain. So gain with respect to S, F1, first thing is h of S. H of S is nothing but 0.94 minus. Now here it is something called a summation. Now when I say summation, that basically means I need to find out all the summation. So here I'm just going to use this bracket. What is S of V? S of V, see, whenever I write S basically means the entire sample from feature 1. Then whenever I say S of V, that basically means we are trying to check this category and this category. So S of V, we'll just try to find out that after the split, how many number of yes and no's are there. So here you can see 8 total. If I try to calculate, it is 6 yes and 2 no's. So total 8 is there, and over here total 14 was there. So here 14 is the total, here 8 is the total. Here how much? 6 is the total, right? So S of V will be 8 divided by 14. Okay, for the first case. So here I have 8 divided by 14 and multiplied by h of SV. H of C1 is how much? H of C1 is nothing but 0.81. So I'm going to multiply this with 0.81. Then here I'm going to have plus since it is summation, and here you can basically see with respect to the next category, what is S of V? It is nothing but 6 divided by 14. So 6 by 14 multiplied by 1. Okay, so here I will be probably getting a value, if I compute it, it is somewhere around 0.049. So this is my gain of S, F1. Okay, so here I'm just going to highlight it. So this is my total gain. Okay, with respect to S, F1. Now I have my next split, right? Now let's say this is my next split with respect to F2 feature. I will be having C3 and I'll be having C4. And similarly, we can go with more further splits as many as we want. And now if I go and compute the gain of S, F2, and let's say if I get a greater value than this. So in this particular case, let's say after computing all this thing, and I'm not restricting it to just one depth, guys. It can be any number of depths. So that many number of categories, automatically this formula will get extended since I'm using summation, right? Summation of this one, right? Now in this particular case, here you can see that gain of S of F2 is greater than gain of S, F1. So here this is 0.049, right? Now in this particular case, this gain is more. So this indicates that I have to start my splitting from feature F2, right? So that entire combination can be checked upon. Decision tree internal checks all this particular condition if I'm specifically using entropy or gain impurity, and it will then try to find out which feature is best for splitting. So this is how the entire information gain is basically calculated. Okay, calculated. Okay, now one very important thing that we have probably missed in our previous class is that when should we use entropy and when should we use gain index? So this is a very important question. When should we use entropy and when should we use Gini impurity? Okay, so this part I will try to complete in my next video. So I hope you have understood what exactly is information gain, okay, and you've got an idea about information gain completely and how it is basically calculated. But at the end of the day, it is just helping you to decide, or it is just helping the decision tree to decide which features we should select and we should start splitting. Okay, now in the next video we'll discuss about when to use entropy and when to use information gain. So yes, I'll see you in the next video. Thank you. Now let's understand when should we use entropy and when should we use gain impurity. And this is super important because we discussed about two different techniques to check the purity split, right? And that's entropy and gain impurity. And obviously you know the formula. H of S is nothing but probability of plus log 2 probability of plus minus this standard formula itself. Now let's say if my categories are 3 categories as an output. Okay. Now in this particular case, this equation will get expanded, and here I'm basically writing minus probability of category 1 log base 2 probability of category 1 minus probability of category 2 log base 2 probability of category 2, and similarly minus probability of category 3 log base 2 probability of category 3. So as the number of output categories will keep on increasing, this will be increasing. So this is what, so that you should not get confused with respect to this particular formula. So similarly, this gain impurity will also get expanded based on as the number of output categories get expanded. Now let's go to the question: when should we use gain impurity and when should we use entropy? Now see guys, with respect to the entropy, the formula uses log. Okay, so here a simple, easy way to talk about entropy is that whenever your data set is small, okay, you can definitely use entropy. Now people will say how small, okay? So I'm just saying that let's say if you just have 10,000 records, you can definitely go with entropy, because if you are trying to implement with the entropy, right, it will obviously take time because here there is log. Okay, with respect to small data sets, the time difference will be pretty, the difference between the time that is going to take to train the model will be almost minimal, right, for between entropy and gain impurity. So when the data set is large, definitely try to use gain impurity. Okay, so this is just the suggestion that I really want to give. But again, how much large, how much small, again, that is a question. You should try to think over it. In short, my suggestion will be that by default, whenever you use gain decision tree classifier, they use gain impurity. Okay, so this is just a suggestion to make in front of you with respect to when to use entropy versus when to use gain impurity. But by default, if you are using decision tree classifier, gain impurity is basically used. And I think for most of the scenario or problem statement, we use gain impurity. Okay, so now let's go ahead and understand in our next video is that when our features features, right? Let's say in this particular thing, the features were just categorical variables. But what if a feature is over here a continuous variable? Okay, continuous values are there. So how do we make decision tree to split the specific values? That is what we are going to see. Okay, so yes, I will see you all in the next video. Thank you. We're going to continue the discussion with respect to decision trees. In our previous, when we are discussing about decision tree classifier in our previous video, we saw this particular problem statement. And here, one thing that you could note that all the features were basically categorical features, right? And this is specifically my output feature. Now here you can basically see categorical features. You could easily divide those categories based on each and every split. What if I get a feature that is specifically continuous like this? Now in this particular scenario, how should we go ahead and probably do a decision split? So that's the reason the topic name is decision tree split for numerical features, right? So let's go ahead and understand. Now in this first step is that, first of all, we will sort the feature values. Okay, this is the first step we basically say. Feature values. Now over here by default, I've made sure that all these particular values are sorted already. So you can see this is sorted in the ascending order. Okay, specifically sort the feature value based on ascending order. Now what we do is that we create many decision trees. Okay, so in every decision tree, let's say this is my first decision tree, I'm going to pick up my threshold. Now let's say this threshold over here is my first value. So I'm going to do the first split from here, right? So I'm going to make 2.3. So here this basically means my root node will be less than or equal to 2.3. Any value that is less than or equal to 2.3, there will be one instance like this, and the other instance will go like this. So if it is less than or 2.2, less than or equal to 2.3, let's say this is yes and this is no. Now in this particular scenario, you know that I will be getting what output? I'll be getting one yes output. So in this particular case, how many yes I have? I basically have one yes and zero no's because I don't have any no's over here, whichever values are less than 2.3. Now similarly, I will go and create this specific node over here. Now in this node, how many yeses are there? 1, 2, 3. So 3 yes. And how many no's? 1, 2, 3. 3 no's, right? So here you can definitely see that initially I had 4 yes and 3 no's. After the split with respect to less than or equal to 2.3, I made a binary split. And in the left hand side, you can see how many yes I got and how many no. So this is one decision tree we initially construct. And let's say if there are many features, we further split this into many splits. That is not a problem, right? And based on the entropy and all, we can basically do the further splitting. Now let's say after this, the second decision tree will be made sure that now the threshold will be changed. Now we are going to keep the threshold as 3.6. Now what will happen is that now my threshold will get updated. It is 3.6, and now I will create a node which will basically be having less than or equal to 3.6. Now when I say less than or equal to 3.6, again there will be two splits. Okay, yes or no. Now whichever is less than 3.6, that basically means this two records are less than 3.6. So here obviously I'm going to get 2 yes and 0 no's. In this particular case, how many yes and 0 no's I'm going to get? 1, 2, 2 yes and 3 no's I'm going to get, right? Now like this, I will keep on creating multiple decision trees with different. I'll just move this to the next step, and then this will be in one side, and then this will be next side. Like that, I'll create on multiple decision tree. But now to understand whether this split is better and this split is better, how do I actually get it? It is very simple. We basically use the information gain. So whichever has the highest information gain, we will be selecting that specific split. Let's say if I have 10 different splits with different values, whichever will be the best, whichever split will be having the best information gain. From there, let's say from this particular value, if I'm doing the splitting, right, and I get the best information gain out of this specific split. So I am going to basically split my node by taking 4 as my root node. So less than or equal to 4 as my root node, I'm actually going to consider. So this is how actually it happens in case of a decision tree split for numerical feature. Now there is one major disadvantage, guys. Just understand this particular split when we are doing the comparing with so many decision tree. What happens if we have in our data set millions of records? So the time complexity is usually high. Okay, the time complexity is usually high for this particular process. Okay, so this is the disadvantage with respect to this. But again, since we are using decision tree, we really need to use this technique, or internally it uses this particular technique with respect to all the numerical features, right? So I hope you have understood this particular video. Yes, keep on. If you are not understanding anything, please revise this particular video and try to gain the momentum of understanding the in-depth math simulation. Thank you. I'll see you on the next video. Guys, in this video, we are going to discuss about a very important topic, which is called as post-pruning and pre-pruning in decision trees. Now, just by the meaning of pruning, I think you will be able to understand something at least. Okay, so let's discuss what exactly is this post-pruning and pre-pruning, and let us understand why do we do post-pruning and pre-pruning also. So guys, suppose if I have a training data set, and if I probably use a decision tree for this particular training data set, so and if I use the by default parameters that are available in decision tree, it will start splitting it, and it will make sure that it will keep on splitting unless and until we don't get the leaf node. Okay, so let's say here I'm actually getting the leaf node. Unless and until we don't get the entire leaf node, it will keep on splitting, right? So this is also a leaf node, but here we quickly got that specific leaf node. Here till this particular path when we went, here we got the leaf node. Now let's consider that at this particular instance, if I have 9 years and 2 no's as my output category that is remaining, and what did I do? I did a further split and made sure that I get 9 yes and 0 no's. And since this is an impure split, and here I probably got 0 yes and 2 no's, right? So here this also became a pure split, and this also became a pure split, and finally I was able to get a leaf nodes like this, right? So this is also a leaf node, and this is also a leaf node. Now understand something about pruning, okay? Pruning, whenever we talk about, right, you've seen gardener, whenever some plants, they grow, right, they just try to prune it so that the shape is maintained and it grows in a proper way, right? So similarly, in decision trees also, whenever I try to do this kind of split completely to its depth with respect to the training data set, usually we face a scenario which is called as overfitting. Now, many times I've discussed about overfitting. Overfitting basically means your train accuracy, it gives very high because you have done the splitting completely till the end, but with respect to the test accuracy, my accuracy will be very, very low. Okay, so this scenario we basically say it as overfitting, and with respect to overfitting, again I'm repeating it, you usually get a scenario of low bias and high variance. Bias is for training data, variance is for test data, right? Since over here the test accuracy is low, so I'm saying it as high variance. Okay, now if I'm splitting my decision tree completely to step, I usually face an overfitting scenario. Okay, now how can I prevent this overfitting scenario? Because if I'm using the default parameters, you'll be able to see that I'll get my all decision tree will get split completely to step, right? So in order to reduce the overfitting, we can use two different techniques. In order to reduce overfitting, we basically have two different techniques. One is specifically, if I talk about this overfitting, in order to reduce it, one technique is called as post-pruning, and the second one is pre-pruning. Now, what does post-pruning mean? Post-pruning basically means, first of all, I'll construct my complete decision tree, and then after that, I'll start pruning it or cutting it. Okay. Now, in this particular scenario, let's say at this particular depth, I was having 9 yes and 2 no's, and still I made this further split. Okay. But just understand over here in this scenario, the number of output categories is 9 yes and 2 no's, and obviously the ratio of yes and no in this particular case, the ratio of yes is very high, right? Over here, because you have 9 yes and 2 no's, very small number of no's and yes. So I did not have to do the further split because whenever over here, if it comes, right, whenever with respect to all this decision it comes over here, I should have selected, okay, my output is basically yes. But still, I did this particular further split. So in the post-pruning, what we can do is that we can basically cut the branch from here itself because I don't want to further do the split till here.